Buddy, welcome. Hope everybody is having a great time tonight. Thank you for coming to the Cozy Cosmic Stream. This is Tom, who is a fellow astronomer, and I'm Ryan. How is everybody doing tonight? Hope everybody is having a good time. If you are in chat now, for everybody viewing, let us know where you're from. We're expecting people from all over the world, so it would be very cool to see people as they come in and out for wherever they are, letting us know that they're tuning in.
So we are going to have a fun night tonight. We are here, Ryan and I. Well, we are. Yeah. So I think he said we're both astronomers.
Mm-hmm.
We are here at Lick Observatory from beautiful Mount Hamilton, California. And we have a chance to use their 1 meter telescope, 40-inch telescope, and also combine that with our Unistellar eVscopes. And so we will be looking at some really cool stuff. We'll start with some comets, then we'll move on to an asteroid, and then nebulae, galaxies, star clusters, maybe planets, all kinds of stuff.
Whatever we can find. If you have any suggestions for things you want to see, as long as it's visible, we can try and fit it in.
Yes, we have an agenda that we can walk through real quick. It's linked on most of the advertisements that we sent around. Let me try to share this. And so we'll just take a few minutes now to introduce the program. And then the very first thing we'll do in a little bit is look at the nickel telescope. So we'll take a tour of the 1 meter and show you inside. So let me pull this up. Just a second.
It's also, you're going to see me having to shift over little by little because this desk is actually a lot bigger on this side. And so I've set up over here, and I realize now that I'm kind of like halfway off the frame. So if you see me shuffling in, that's fine. Tom and I do like each other. We like a little bit of space too.
We do. Okay. Let's see.
What planets from Celod? What planets will be out tonight? Jupiter, right? Saturn?
Yes, they will both be up. I think Saturn's the one in the schedule, but we're flexible. We'll see exactly what we want to look at. And any second now, I will have that agenda. So this is basically the end of the scripted portion of this show.
Yeah.
Right?
They began and end with the and that's how they found the body joke at the very beginning.
Yeah.
Now we're completely off the rails.
That was it. Now we're winging it, and it's gonna be a little rough, but we're gonna soldier on. And so really the big idea is, while this comes up, we want to give you a window into what a night of astronomy looks like when you're actually observing on a real telescope, a major telescope at a professional observatory. What are the things that you have to do? What's the stuff that we plan, the stuff that we click on the computers?
Yeah.
The things that go wrong, hopefully not too many.
Well, yeah. What does it look like planning an observation or having to troubleshoot when there's a bunch of particles in the air and the telescope suddenly closes? So there are lots of little random things that you don't normally think of when you think about astronomers observing. And so a lot of it is also a night of doing an astronomical observation. While it is very fun and very cool to be using a big telescope that you would never have the chance really to use otherwise, there's a lot of downtime. So this was another good way to kind of pass the time for us, as well as giving you all an insight into kind of what it's like to be an astronomer. Because if we didn't have this, I think we would largely just be on our computers and maybe playing music or just talking to each other, which is fun, but this seems like it would be a more fun time.
Exactly. And so already I'm unable to share the agenda. So I will put the link to that in the chat instead, so you can all see it. I see people so far from, Toronto, Georgia, Oklahoma, Pennsylvania.
We have some people a little bit earlier up from Italy, France, Mexico, Michigan, and I saw Japan earlier, Osaka, Japan. Oh, Ireland as well, and Australia. Wow, we have everybody from all over. I was not kidding when I said we were going to have some worldwide viewers.
Yeah, and we'll pick up people probably from Europe, Africa later on when they wake up. And then, yeah, it's going to be an international affair.
So we have a question from Stephen Schreier that looks like it might be a super chat. Question is, does Lick have AO? AO stands for adaptive optics. So that's the kind of ability to get rid of some of the turbulence in the atmosphere that causes the light to get disrupted and distorted. One of the telescopes on Lick that I know of has adaptive optics, and that's the Shane telescope. The nickel, does it have a tip tilt, or is it, do you know, or does it just have, you're good to go?
As far as I know, there are no active or adaptive optics on the nickel.
Okay.
It is simply a fixed primary mirror that reflects to a fixed secondary mirror, and that's about it. We'll talk a little bit about the secondary will move to help focus the telescope. They do, however, we'll get into this when we talk a little bit more about Lick Observatory, but they do a lot of testing of things like adaptive optic systems on the nickel. This telescope is really good for trying out new instruments, new tech, new hardware. I actually ran into a colleague just before we started tonight who was doing just that, trying some new instruments. And you know, that kind of stuff happens all the time on telescopes. We don't just build something in the lab and immediately it works. You got to do a lot of testing.
Yep.
All right. I'm still fighting Google to sign in here and actually get this link. So Ryan, you talk for a second.
Yeah. So I think while Tom works on this, we can answer a few more questions. So Paul Hawkins over on Facebook has asked, what are some of our more notable observations recently? Have we had any shots of the Nishimura? So I know I haven't gotten any observations of Nishimura. I am largely, and we'll talk a little bit about this as well later, but I am largely focused on near-Earth asteroids in my research. So one of the main targets that we're looking at tonight is 2011 MD5. This is a near-Earth asteroid that doesn't really have any information on it besides where it is in its orbit. So one of the things that we're hoping to get tonight is a long enough observation that we can maybe get some of a light curve of it, so we can see how the light changes over time, and that is indicative of its rotation. So we can actually see by measuring how the light changes for the asteroid, we can see how long it takes for it to rotate, and from that you can usually get some other information if you have enough light curves or enough data. You can get things like the shape of the asteroid. You can get an idea of what that is. You can figure out what axis it's rotating around, and it's largely pretty cool. So I don't know if I would say that is my most notable observation recently, but that's one that I'm excited about. What about you? You have anything interesting that you've been looking at recently?
So I've been transitioning a little bit. I worked mostly on exoplanets, as the shirt would imply, most of my career. I still do that with a couple of different groups, both at UC Berkeley, also at SETI Institute and with Unistellar. Lately, though, I've been actually working more on supernovae, things that go boom in the night. That's part of our Unistellar citizen science program called Cosmic Cataclysms, and so that's been where most of my time has gone lately. I think I finally have this link. My word, Google. Okay, so we will post this in chat right now. Comments. And while that's making its way through the interweb tubes, yeah, oh, sorry, go ahead.
Oh, no. Well, there's more super chats as well, unless you had something you were going for.
Go for it.
So Jennifer Smith has asked, how did we both get interested in astronomy in the first place? I actually have a fun little story about this. I kind of liked astronomy in undergrad, or in high school. I had a passing interest. I'd always wanted to be an astronaut. I thought Mars was really cool, but it had never been really something that I was super taken with. So when I got to undergrad and I was doing the freshman orientation where they kind of let you know how the college works and let you kind of talk to different departments. I figured I didn't know what I really wanted to do. I would go talk to the astronomy department, and then I'd walk down to the theater department and I'd see what happened there. So the astronomy department was on the way, so I went there first, and I had the chattiest professor in the world. For the full 2 hours that they gave us, he talked to me about astronomy. And so I thought, I was like, really liked the passion. But by the end of it, I was like, okay, well, I like astronomy. I think it's a pretty neat science. And I've always like really liked science in general. I don't have time to talk to anyone else. So let me just see how it goes. Let me take a few classes and we'll see what happens. And that's essentially how it worked. I fell into astronomy, and I fell in love with it when I started taking the classes and really learning about how the universe worked. Not the Cinderella story, but actually I like it for that reason. Sometimes it's okay to fall into something and realize that you really like it.
Yeah, I kind of have a similar story. I was always interested in science growing up. As a kid, I loved space, like I think a lot of kids do. I don't remember, but I probably wanted to be an astronaut at some point. And then just as I got older, I stayed interested in science, and then kind of as I went through high school and then college, my interest in astronomy just was the one that didn't really fade away. And so I just kind of sort of wandered into it. And haven't left since.
Yeah.
Okay, so I think we're basically at the point where we can start looking at the nickel. I want to let's see. Yeah, for some reason I'm unable to share my screen here.
Really?
Yeah, I don't know. This worked perfectly 10 minutes ago, and now it doesn't work at all. And in fact, now I'm just showing nobody. There we go. But so I'll run through it anyway. So you have the link. You can follow along for about an hour. Oh, we're getting a phone call. Hold on. We need to answer this. Do we? I think we do.
They're worried we're going to break the telescope. They're already telling us that. Was it wrong number?
Hello? No, this is Tom in the nickel control room. Okay.
Wrong number. Amazing.
No, they were looking for someone who's not here.
I really thought for a second we were going to get in trouble for this. It's like they know we're doing this.
Right.
They're okay with it.
No, they're already pulling the plug. This is as far as we got. They're cutting the hard lines. No, when you're at the observatory, you always answer the phone because you don't know what's going on. There could be something.
I've never answered the phone.
Okay.
That's why I don't go to many observatories
anymore.
That's
right. You only go once, and then you can never go back. Okay, so yes, for about the next hour, we're going to take you through a tour of the nickel dome. We'll show you the telescope, show you the dome, how all the mechanics, the big machines and stuff in there work. It's pretty cool to look at if you haven't seen a big telescope before. And this is pretty much a medium telescope or even a small telescope these days. It's part of the reason we're allowed to do this, but we'll get into that later. So then around 6:15 p.m. Pacific time, we will start taking actual calibration data with the telescope. There's a lot of prep to do before we can actually do science with the telescope. So that will involve things like using the camera to take calibration frames of the electronic noise and the noise on the optic, the issues on the optics. Oh, there we go. Wow, my screen share finally went through, or are you doing that?
No, that's not me. That's you.
Wow. Okay. Well, this might be tiny, but you can try to follow along here.
Zoom in.
Yeah. Let's fit. So then around 7:20 p.m. here, that's sunset.
Oh my gosh.
There we go. And we will try to take a quick peek out the window to show you what sunset from Mount Hamilton looks like. But we'll have to quickly pop back into the remote control room, or into the control room here, and start taking images of the twilight sky. And that's part of the calibrations that we'll explain later. That'll take about 45 minutes or so. Oh, sorry, no, that'll take about maybe 20 minutes. Then we'll get to setting up the eVscopes. So those are the Unistellar small telescopes that we'll be using 2 of. Show you how they work and get them set up. And then we will start observing our first target around 8:15 Pacific time. We'll look at Comet E1. This is a really cool comet. It should look nice and colorful and bright. And so we'll do that with both the eVscopes and the nickel. And we'll have a special guest, Dr. Ariel Greykowski. She's part of our group at SETI and Unistellar, and she is an expert on comets. So she will tell us a lot of interesting stuff about this comet that we're looking at. Then we'll have a little bit of time for a Q&A while we keep looking at that comet. We'll show you the live views from the telescope as we get them. Brian and I will answer some questions. So leave questions in the chat. We'll try to get to as many as we can. It seems like we're already not going to be able to get to all of them, but we'll do our best. And then about 9:35-ish, the asteroid, which is our main target, will rise. And so this is named 2011 MD5. And that is part of the planetary defense program that we run for Unistellar and Citizen Science. I should say, not we, Ryan runs for Unistellar and SETI. And this is a near-Earth asteroid that we will try to measure the brightness of over at least 4, maybe 6, or even 8 hours if we're lucky, and watch the variation in its brightness to try to see how that asteroid is rotating in space. And the rotation period, how long it takes to go around one time, tells us something about the asteroid. We'll talk more about that later. And then around 10:20-ish, we'll start looking at some really pretty things with the eVscopes. You can see there's tentative targets listed on the schedule. There's Pinwheel Galaxy, the Eagle Nebula, the Ring Nebula are at the top of the list. We'll try to catch them before they set. We have an asteroid occultation we'll do at 11:20. That's really cool. It's really precise timing. About 11:35, we expect an asteroid near Mars, I think. We'll pass in front of a distant star, and we'll actually try to capture that live. Try to get through this more quickly. We have more eVscope time after that, around 12:45 a.m. If you're still with us, we'll talk about some of the citizen science results we've had from the Unistellar Network and SETI. We'll have another special guest after that, Dr. Frank Marchus, who leads that group, and he'll talk about probably asteroids because he loves asteroids. Yep. And then we'll try to get some more information out of him. More eVscope viewing this entire time. More Q&A. Around 3:45, we'll start wrapping up with our last set of targets. We'll try to maybe make it a little more fun by spinning the wheel of targets, see what comes up randomly. And then, 5:15 in the morning here, we'll have to start shutting down, closing up the telescopes for the night, taking some final calibrations. And then we will be done around 6:15 because sunrise is about 6:36 in the morning. Yep. Whew, that's a lot.
You're the one that came up with the agenda, not me. That's on you.
That is on me. All right, so I think we should move to the nickel.
Yeah, absolutely.
Okay.
So
I will stop sharing this.
Yeah, and I will bring my computer this to stage. Hello. So you now all see my little roving Ryan. Oh. So I'm going to be using my own laptop. We tested this on using the phone earlier to try and do a little tour of the Nebula. I should unmute myself. So we tested earlier using phones to try and give a tour of the nickel, and it turned out the service was really bad. So instead, we're using the laptops, and I have to just kind of carry it around like a fool. So this is the nickel telescope. So this is a 1-meter telescope. You can see here we've got it in what's called the park position. So this is when it's not in use. The way that we keep the nickel in pristine condition. This is how it always ends up, straight up, so that you don't have any pressure on the mirror. You don't have any pressure on any of the mechanics, cause anything to kind of crimp or bend over time. And then so you see it's huge. A 1-meter telescope is 1 meter in diameter, but much, much larger when you actually get all of the supports and the infrastructure around it to actually hold it up. So let's see. I think when we were talking yesterday with the support astronomer, he said that the nickel telescope is actually called, they colloquially call it the spare parts telescope. So you see these giant struts. When they were building this telescope, they had a $50,000 grant or a $50,000 donation from Anna Nickel, who was a seamstress back in the 1970s. And so $50,000 is a lot, but not necessarily to actually build a huge telescope. So you have to figure out where you're going to save some money. And these giant metal struts are actually unused water pipes that they ended up soldering together and creating the giant mount for this telescope.
Yeah, so we can point out some of the bits here. So here at the bottom of the telescope, the mirror, the primary mirror, so that's the one that's about 40 inches across, that's in here. And then underneath, we have some electronics. So this is the filter box. So this is where the different filters that allow certain wavelengths of light, different colors of light to pass through to the camera that's attached to the telescope. They live in there. The camera is down here in this box, actually in some of these boxes. This metal thing here is called a dewar, D-E-W-A-R. That is full of liquid nitrogen. So that's at about minus 110 degrees Celsius. I have no idea what that is in Fahrenheit to you.
No.
It's cold.
Yeah.
You don't want to touch it. It'll burn your hands.
You can see, if I can get the angle right here, you can see the that is basically liquid nitrogen having caused the air to condense around the top of the dewar there. So it's quite cold.
Yeah, and the reason we do that is that the electronics in the camera. So the camera has a CCD sensor. It's a little silicone chip, like a computer chip, that's sensitive to light. And so that's what actually collects the light from the telescope and shows us an image. But that sensor works best when it's cold. And that's just because of the physics of what's happening in there. And the colder it is, the less noise there is, the better your image quality. And so that gets filled every day with liquid nitrogen. We can't show it. It's pretty cool, actually. Some telescopes, you can fill it yourself. You have a big can, like a watering can, basically. You put on gloves and goggles and stuff, and you pour it in, and it smokes everywhere. That's that. So one of the things that I really like about these big telescopes is that while they are massive, they're really, really incredibly well balanced. To the point that some telescopes, when you're moving them by hand, some of the smaller ones, obviously not this one, but you can actually move a lot of these really large, like 2-ton, 3-ton telescopes by hand because they're just so well balanced. And one of the ways they get that is by just stapling bricks onto it. So I do love that. That is one of the ways that we make sure that we can move the telescope around and that it is always going to be pointed exactly where we want it. We have it very finely tuned, and we do that by stapling giant metal plates, essentially, onto the side. Yeah, it's like balancing your tires on your car.
Yeah.
It's the same, basically.
Yeah.
Okay, yeah, so let's see. Ryan pointed out the support structure before, but so this is one of the motors here that actually rotates the telescope in the azimuthal axis. So not up and down, but more like rotating from side to side. And it actually works by, there's a motor in here that turns a little wheel inside of here that just by friction pushes so hard against this round plate that it spins the plate and then spins this entire truss all at once. And this, I don't remember how much this, do you know how much this weighs? It's tons. It's many tons.
Yeah, it's several tons.
So it's a lot. But such a simple device, and it does what it needs to do. Should we talk about the dome?
Sure.
So the dome, maybe a little bit hard to see.
Yeah.
But we have all the dome lights on in here that we can. The dome is metal on the outside.
Let's see if we can find a good angle for everybody. Sorry.
Yeah.
Yoink. All right, so that's the roof.
Yeah, basically the roofs. And so that if you're not familiar, telescopes live in domes to keep them protected from the elements, keep things like rain and dirt off of your very important mirrors and optics. And a dome is just a nice stable shape. It also lets you have something large inside, and you can rotate it. So the dome, if you can sort of see, well, we'll show this off a little bit later, but around the edge of the dome, there are motors and wheels that let the whole roof basically rotate.
Yeah, we can zoom in. So yeah, basically there's tons of these wheels lined around the edge of the dome, and this is how you actually don't touch the thing.
I got it. I didn't touch it.
There's also the danger orange, that's a live voltage, and Tom keeps trying to touch it. So.
Don't touch that. We were told do not touch this high voltage, but we weren't told how high. Yes, so that's the wheels that let the dome rotate. Like I was saying before, the outside of the dome is metal, the actual shell, and then there's actually, I think these are wood, the wood spars.
The wood struts. Yeah.
Yeah, that actually are the skeleton of the dome. This dome was built in, is it 1889?
Yeah.
So this is the oldest structure on Mount Hamilton, and this observatory was basically built in 1888, 1889. So this is from the beginning. And it was meant originally to hold a much smaller telescope. It was a 12-inch refracting telescope. And so in 1979, they put in the nickel, this nickel telescope, and they really just kind of squeezed it in here. It barely fits, and we'll show you a little bit later exactly how close it is. And we won't be able to open the dome just yet because the sun's still up, but we can spin it around for you.
Mm-hmm.
Let's see, that controller's over here. So there's a little
small panel controls the entire dome.
Little box with a switch that lets you drive the dome left and right. We released it earlier in the control room, so I think if I hit this, let's see if we can see the dome spinning. That's the slit that will open that the telescope will look through, the white part, later. But if I hit the switch, so I am not rotating this. This is the dome itself rotating. You can see, here we go. Yeah. So we can stop it, and then we can
Send it back.
Swing it back the other way. It actually moves quite fast, faster than I thought it did. But you want to save time when you're looking at targets during the night.
So you can see those wheels. It's a surprisingly simple machinery for something that is so big and requires such precision. Just these giant iron wheels rolling around to move the dome itself. There is one thing while we continue. So the dome has an ability, it has to be able to know which way it is rotated at any given time. Because you want it to be able to, A, follow along with the telescope itself. But then if anything goes wrong, say at the end of the night, your telescope has gotten disconnected from where the dome is and the telescope's parked or the telescope's put away, and you're trying to get the dome back into its normal spot. Sometimes it's a real pain to have to come in here and do it yourself. Sometimes you can't even do that. One of the things that astronomers can do, a lot of observatories will allow astronomers to do, is to observe remotely. So they'll be on their computer at home or at their university and controlling the telescope from there rather than coming directly out to the university itself. So what do you do in an instance where the dome is no longer lined up with the telescope and you can't come into the room itself and manually move it? So one of the things, they tested this little technology on the nickel. So one of the nice things about the nickel is that it's a great kind of experimental telescope for testing new technology, because while it is a really big telescope, it's not the biggest on Mount Hamilton, and it's not the most expensive. So in general, they like to use this to test out new tech. And this was, I'm not going to touch it. Anyway, and so this little barcode on the edge of the dome here was one of the first attempts to kind of automate
getting the dome to recognize where it is. So what it does is these are little magnetic strips, and the dome can actually read these as it moves around. And that tells the dome, okay, I'm actually pointed in this direction. I'm trying to go home. And it will use where it is on these magnetic strips, where it reads here, until it reads to the point where it goes, oh, okay, this is where I am supposed to be when I don't know what to do. And that is like the same thing as the park position for the telescope, where you just leave it at that position when you aren't messing with it. Home is the same thing for the dome, where it is the default position for the dome. It is where it always has to go back to whenever you're done for the night. So this was one of the first attempts to get this to work, and that is how it happens. These are all magnetic strips, essentially little magnetic barcodes that computer on the other side of the dome, which I'm not able to reach, so I can't really show you that. But a computer actually reads these as the dome turns to figure out where it is. So, yeah.
All right, so let's see, I think that covers the dome. When we actually open up, we'll come back in here and I think and show you. There I am. Hi. When we actually open up, I think we'll come back in and show you what it looks like to look through the dome slit when it's open.
Yeah.
Let's see, Ryan, can you point towards the top here? I'll try to light it up a little bit. Yeah, so if you look towards the top, so this, the telescope is pointing straight up, like Ryan said. The red rust-colored metal is the support for the second mirror of the telescope, which is at the front, the very top of it. That's called the secondary mirror. It's the second one. It's the second mirror that the light from the star hits. The light first comes through the top of the telescope, hits the main primary mirror, the first mirror at the bottom, and it reflects to the secondary mirror, which is underneath that black circular baffle there at the top. So the black part is just to shield stray light from getting in, but it allows the important light to hit the mirror, and then that light bounces from that mirror straight down this bottom black tube, which is maybe hard to see, but that's another baffle that keeps out stray light, but the important science light goes through that tube down to the bottom of the telescope where the camera is that we looked at earlier. And so what I was starting to say before is at the top, you can see that metal, the red metal structure is really close to the top of the dome. And it's really close to that black rectangular plate to the left specifically. And that's part of the fact that this telescope is just squeezed in here. And not really, this dome was not designed for it in the first place. So they were reusing resources, we'll say. Let's see. Anything else on the dome, Ryan?
No, I think, so that metal plate, because in order to fit this, they did end up having to widen the slit of the dome. So the telescope that was originally in here was smaller, so the opening on the dome could be smaller. But this, the 1 meter is much bigger, and in order to actually make full use of the size of your telescope, you want to make sure that the dome can open up wide enough that all of that light can come in and hit your telescope. So they ended up having to widen that gap in the dome, and in doing so, it became a little structurally weak. So that black plate that Tom was talking about up there, that's actually a strength plate that they had to bolt in order to keep the dome structurally sound after they widened it. But yeah, no, I think that's pretty much it. But yeah, it is crazy. It's maybe like 2 inches of clearance between the telescope and the roof. So.
All right. So you want to stay here?
And you want to
move the telescope?
Yes, you'll have to open the mirror too, though.
Yeah. So I think I'll move.
Oh, okay.
I think the plan, we will point the telescope down towards Brian and you, so that we can look into it and see the primary mirror. So I have to do that from the control room. Actually, no, I can move the telescope from here, but then I'll have to go into the control room to open the mirror cover, which is you'll see it's a cover that covers the mirror so that it doesn't get dirty when not being used. So I can move the telescope from here with another.
Wondering if we should turn the dome lights off.
Lights off.
It's fine.
Is it better to see or?
Yeah, we've got two of them right there, but I think it's okay.
Okay, I can turn it off.
Sure.
1 second.
Yeah, so we're going to test since our angle here, we have two really bright dome lights. We'll see. Okay. I think that's a little bit better. Yeah. Yeah, that's okay.
All right, so we have another little paddle here that I can use to point the telescope, and towards right is due south, so I will move it now.
All right, so I'm going to angle this up so you can see a little bit. You can see the top of the telescope is moving down, slowly pointing towards us. And we can start to see, we'll turn the dome lights back on after this so that we can see, but you'll be able to see the mirror cover there a little bit. It's basically just a black mirror cover keeping the inside of the telescope pristine, like Tom said. You don't want dust. You don't want dust getting on your mirror, especially these mirrors in particular. Because they have a chemical coating on them, and so certain particles can literally etch away at your mirror and make it less usable. They kind of degrade it. So you have to be careful with what you allow to hit your mirror. You really just want light. If anything else, then it makes the mirror worse.
All right, Ryan, can you come down while I'm ready?
Sure. So yeah, just real quick, you can see here exactly the kind of clearance that we're talking about. This is a way better angle. All right. Now we're going to come down, and we're going to try not to touch the danger ring.
Yep.
That's the danger ring.
Literally says danger. Yeah, so we just don't want Ryan there while we move it the rest of the way down.
Yeah.
You can hear the motors and things make some funny, scary, terrifying noises when they move. I'm told it's normal. All right, so this is...
What kind of telescope design is this?
So I think this is just, in general, this is just a Cassegrain telescope. It has a primary mirror that reflects off a secondary, and then in this case, in most cases, it passes back through the center of the primary mirror. So that, well, you'll see in a second, but the primary mirror has a hole in it. It's shaped like a donut. All right, so let's go down a little bit, and that's probably good.
So yeah, one of the things that you have to be aware of is while we're goofing around and wanting to show this off, we also have to be very careful. This is still very heavy machinery, and you never want to take for granted the fact that these can hurt you. All of these, if you are not paying attention, can hurt you. So that's why Tom called me down. You never want to really walk in between the bottom of the telescope and the scaffolding right there, because if it ends up moving, you can get caught. So just one of those things that you always got to be very careful. We want you guys to know that while we are here having a good time, we're also still trying to do our due diligence and making sure that everybody is safe. So you can see here the mirror cover, you can see it really well, and that central baffling right there, that is the baffling that Tom was talking about, that is meant to keep out stray light. So the light that is reflected from the secondary here. Yeah, it's fine.
Black tube.
Haha.
Oh, there you go. That's
You
a
see
mirror.
yourselves. Well, you see what I see, which is this little screen. But yeah, so that is... Light comes in there. Any kind of stray light gets hopefully deflected by the baffling here. And then the light from your star ends up going down, because it's all the mirrors are very well aligned precisely down this tube to the mirror underneath in the center. Camera right up the camera. I'm good. Okay. All right, so this is so awkward doing a giant laptop. It's great.
Yeah, one day we'll have a real camera, and this will be easier. Okay, so let's see. Can we still see the mirror cover if I take the light off?
Okay. We'll see it moving if you open it.
Okay, so yeah, you'll see it moving.
Or you can leave me the light.
Yeah, you're gonna be able to hold.
Yeah.
Let me turn it back.
I got it.
Just hold it for a sec. Okay. All right.
Whoa.
Oh, no. Oh, it's a rave now. There we go.
That's.
3.
We're doing great.
Yep.
Oh, fancy. Okay.
There we go. Okay. I will go to the control room and open the mirror cover. All
right, so while Tom's not paying attention, I'm going to tell you things and not tell him that I told you, so he's going to repeat it later and he's going to look like a fool. We have these little lights here. Here we go. So this is a little lamp right there and right there. One of the things that we want to be careful of when we are taking observations is that we want our data to be as accurate as possible. And cameras aren't perfect. They are sensitive in some areas and less sensitive in others. So you want to be able to take that into account and make sure that what you're seeing is actually light from the star and not just the fact that the camera is very sensitive in that portion or very not sensitive in that portion. So we, at the beginning of the night, will turn these lamps on and illuminate the camera just like we would take a normal observation of a star or an asteroid or anything else. And the idea behind that is it's just a flat lamp. So you can get an idea of how sensitive is each pixel because theoretically every pixel should be getting roughly the same amount of light when you use those lamps. So those are called flat lamps. And another way that you can do it is by pointing the telescope at the sky, which is what we're going to try and do later. So after the sun has set, but before the sky is completely dark and stars have come out, that also works as a great way of flat fielding, is what we call it, testing the sensitivity of each of your pixels on your camera. So that's something that we couldn't do last night, so we aren't technically checked out to do that yet. One of the support astronomers on the mountain is going to come up and show us how to do it and get us checked out on that so that anytime in the future we come back, we'll be able to do it on our own. But that's something we're going to try and do tonight as well. So Tom should be looking. There it is. Whoa! All right, so that just flew open. So yeah, you can see the mirror cover itself has clicked open. You can even hear it all the way from the control room that we were in earlier. You can always hear it. It's just like this giant pop. And then, yeah, the mirror flies open. It does the exact same thing when you close it in reverse. It slams shut. That's because in case you weren't paying attention and it starts to rain or something, you want to close up the mirror as soon as you possibly can. So I'm going to hand this back to Tom and let him start discussing.
Yeah, so you can see, I mean, it's such a shiny mirror that it's kind of actually hard to see maybe that there is a mirror.
There we go.
When it's there, there's a little dust on it maybe.
Yeah, you're never going to have a perfectly clean mirror. That's probably fine. I've just got my head in between two giant metal struts.
Maybe step back for a second, and then I will just disable the vision of the telescope.
Oh yeah, that's a good idea.
Just don't be in when I do it.
Oh, what's the worst that can happen? All right, remember we goof, but take things seriously. So yeah, I'm going to step down actually while he does that, since we could hear some of the engines, the motors kind of going on the telescope. It wasn't moving or anything, but it will sometimes settle a little bit if you're not careful. So we'll just make sure that we're stepped out of the way. All right, we're good. We're going back up now. All right. And back.
Okay. So yeah, so that mirror is
Excellent.
it's glass, but it's coated with aluminum coating or something like that. Some telescopes are silver coated, some are gold coated. Depends what wavelengths of light you're looking at, and they reflect with different colors of light differently. So you got over here. To there.
I can't see us in the mirror. My eyes aren't good enough.
But you can see that it's a donut shape, so it's round, but there's a hole in the middle. So it is 40 inches across, about 1 meter. But the actual collecting area, how much glass there is less than if it were a whole circle. That's okay. We kind of give up a little bit of power and sensitivity of the telescope in order to have a more efficient design of where we can send the light.
Yep.
What else can we talk about? Does that cover the telescope?
I think so. So we can check comments in a second. Sorry, we haven't been able to really look that much at the comments, so we'll sit back down and check those out to see if you had any questions. But yeah, if you have any questions about the telescope or the dome, put them in chat, and we will try and answer those. And if there was something we really egregiously missed that a lot of people want to see, we can come back.
Yeah, and you can see there's all kinds of electronics and equipment and stuff stored around the edge of the dome, things that are being tested or occasionally used. I'm going to put that thing that I accidentally kicked off.
Yeah, that's probably a good idea.
And I'm sure this wasn't important.
Well, I mean, if it was, it's on. Now it's now recorded forever, so I'm calling the cops.
It wasn't bolted down. Yeah, and then there's a bunch of, well, on our way out, we can, we head out.
Yep.
I guess I can move the telescope back if you want to see that.
Sure. Yeah, let's see it from this angle.
I'll park it again, but before I head out, do that, you can see there's a big red button. That is the kill button, so that anything that's happening in the dome that's powered, if it's something that you don't want to happen, say the telescope were about to run into something, you would hit the big red button and it would stop and it would just bring everything to a halt. And when you're sure that everything's safe again, you can undo it and get back to what you were doing.
Yep.
And there's also some different light switches. There's this, you can have red lights if you don't want white lights.
Yeah, preserve your night vision.
Yep. And I think that's it. So let me go park the telescope.
Sure.
Close the mirror cover.
Yes. So that's, you can just park it from in there, right? And, okay. Yeah. Yeah. So that is one of the, I guess, nice things about the software is while the paddle to move the telescope itself is really cool, same thing with moving the dome itself is really cool. It's not very precise, and it can really become a pain if you have a specific portion of the sky you want to look at, and then another one that is very different shortly after. So having software built in that controls the telescope and can send it home or can send it to wherever you want it to go, like Tom is about to do, is extremely nice and really makes the night more efficient. So let's see. Can you summon the Dark Overlords from the Nexus Somnus from Howard the Duck? I don't think I can. So we've tried. We have tried summoning the Dark Overlords, but the connection's really spotty up here on Mount Hamilton. That's actually one of the problems. We're very remote. So every time we have tried, they haven't really listened, and we've kind of lost the signal before we could pull them over. So, you know, but that's fine. We can figure out other workarounds. From William T. Do you have any quirky names to anthropomorphize any of the other hardware? So I know that is probably something that the sports astronomers have that they haven't shared with us yet. So we're going to move back. I think in general, that is 100% a thing that astronomers do, especially if you, I forgot to turn off the dome lights. Especially if you use a telescope or an instrument enough, you kind of get to feel like it's part of the family. It's a friend. I had friends in graduate school who used a very particular spectrograph. Oh, you stole my seat. That's fine. A very particular spectrograph, which is just an instrument that takes light and breaks it up into its different wavelengths. It was a notoriously finicky little thing. Because it required you to lay down specific wires on where the stars were going to be when you moved the telescope, and the wires were constantly breaking and things. So they had a lot of names for it that weren't necessarily very nice. But it was called Hydra, and so that was like the snake. The Hydra was kind of what they would call it, because it had a bunch of wires that basically came out of a central body that you had to connect. Yeah.
Okay. We can also take a look around the control room here. Kind of tough. It's a little dark in here. But this is our home for the night while we're observing. So it has all the essentials. Let's see, turn around and face the computers first. So this is our control station. We've got lots of computer screens. This main one here is where we actually control the nickel telescope from. It's a little bit, we're inceptioning right now because we're watching ourselves in one window. We have 4 other control windows. They're called virtual network connections. They're virtual desktops, basically. And each one has a purpose that we will describe as we go. And let's see, we've got my laptop here is set up to help the stream, and actually also with our observations. We have another monitor there. We have a 3rd laptop over here, 2 iPads,
Jenga.
3 phones, and Jenga.
So that's in case we get bored. In case you all get bored, we will throw up a Jenga tower and you'll see us make a mess.
That's right. We got a nice bookshelf here with, let's see, the Astronomical Almanac. That seems, we got all the way from 2007 through 2022. We've got some other things. Let's see, there's the Smithsonian Astrophysical Observatory Star Catalog, parts 1 through 4. I don't know.
The Unix Programmer's Manual.
Oh, that's very handy. What else we got here? Catalog of infrared observations, catalogs. So lots of catalogs so that if you need to look up a star or some piece of information about some known object, it might be on this shelf. I don't know what some of these other ones are. I don't know. Books are boring. Yeah. All right. So, and then we got some other equipment here.
Some very old.
Yeah, some power supplies, perhaps. Tools.
A random bottle of wine that has been repurposed for something.
Oh, yeah. Celebrating some sort of first light. Neuro SETI. So this is actually SETI Institute related. Neuro, I think, is near infrared optical SETI. And so you can see somebody
that's cool.
Celebrating that. I'm sure they were not doing it on duty. And then we can see out there's a window here. We're going to have one of our eVscopes will be out the window there.
I'm trying to angle the computer by looking at the big screen and your screen.
Yeah. No, you're nailing it. So one of our eVscopes will be down on the road there later. Actually, we can leave that open so it's bright. You've got snacks. Gotta have snacks.
Nice fresh coffee grounds and nice fresh coffee because it's going to be a long night. Like that's part of how things go. We were observing last night as well. And the hardest part about back-to-back observations is staying awake before your sleep schedule has really acclimated.
Yeah, definitely. We've got more. We got chocolate, M&Ms, Reese's. The Mars company does not support or endorse the stream.
No.
In any way. They probably condone it. Or don't condone it. They condemn it. Goldfish, that's one of my favorites.
The moral of the story here is also that no one's on a diet at 4 a.m.
No.
As we can see.
We've got a fridge, a microwave.
Beautiful microwave art about covering the food up.
Oh, yeah. Don't let that happen.
Mm-hmm.
And I think that more or less covers it. This door here leads to a server room where there's computers that are helping to run all the electronics. We don't go in there.
Mm-hmm.
We've got our eVscopes here in the corner. We're going to set them up shortly. And I think that covers the room, what they call the readout room.
Yeah.
I think the term comes from the old days where the data actually were printed out on paper as they were taken by the telescope. And so you were reading out the data as it came off of the spool of paper. They keep the name. Okay.
Cool.
Good. I think that more or less covers the nickel telescope. I guess we could answer questions for a few minutes.
Yeah. All right, so let me go back through. I'm going to scroll up a little bit to see. I also will add back the Ryan and Tom, I think.
Yeah, I can do that.
Okay, cool. We'll
remove yourself. All right, here we go. We're back.
All right. So scrolling through, Gary Allen Smith had asked if the telescope was a cassegrain, which is why I asked you, because I couldn't remember. And then, let's see. We answered Jet Fusion, William T. What is the resolution of the telescope camera? How many CCD pixels? So it is a 2048 by 2048 pixel CCD. And do you remember what the pixel scale was? I've already forgotten.
Yeah, so the angular size per pixel, so it's how much of the, I'm looking at the wrong screen, how much of the sky maps to each pixel is 0.18 arc seconds of sky per pixel. So to give you an idea, the moon, the full moon is about half of a degree in angular size on the sky. That is 30 arc minutes of angle, because a degree is like 1 arc hour. And then, 30 arc minutes is the width of the full moon. And then 1 arc second is, let's see, that's like, well, 1 arc second is 1/60th of 1 arc minute.
Yeah.
So we're looking at, each pixel looks at a very tiny patch of sky is what I'm trying to get at. And that's, I'd say that's a pretty common pixel size for a telescope like this. You definitely have telescopes with smaller pixels. They will look often at smaller patches of sky in general, so that what we call the field of view is how much of the sky fits in your entire image. We'll have examples of that hopefully when we get on sky. But usually the smaller the pixels, the smaller your field of view typically. And there are reasons for this that I think we'll get into during the night while we have plenty of time to kill.
Mm-hmm. Yeah. So one of the more recent questions, and then I think we have a few as well saved from earlier. Daniel Peluso asked, how did we learn to operate large professional telescopes like this in person when we were in grad school or later? And what was that like? So large professional telescopes, I learned in grad school. I was very lucky though in undergrad. So I went to Appalachian State in North Carolina, and they have a 32-inch telescope, so reasonably large, and that's basically a telescope that is for university use. So when I was doing research there, my advisor would take me out and he taught me how to use the telescope. And then eventually it was me and another undergraduate. He would let us, basically he'd say, okay, here's the list for tonight. I'd like you guys to observe these. And we would have all those targets and we would look at them throughout the night. So that is, I think that's really where you I started to learn was in undergrad, and I kind of got comfortable with moving something that large and that expensive, but doesn't even compare, honestly, to something like a 1 meter class telescope, which I never really used until grad school. So,
yeah, I guess I had a slightly different path. So I went to undergrad college at Georgetown University. I did physics there. Didn't have an astronomy degree, so I took no astronomy courses at all in college. Decided to go to grad school anyway for astronomy, which was a leap of faith, I guess. So I went to UCLA for my PhD, University of California, Los Angeles, for the non-Americans maybe on stream. And my first year there, I guess maybe my second year, was when I actually got to use my first telescope, and it was here at Lick Observatory. It was not this telescope. It was the Shane 3-meter telescope, which is just down the road. It's the biggest dome on the mountain, I believe. Biggest telescope on the mountain for sure. That was really cool. I don't think I'd ever seen a professional telescope at all, and I walked into that dome with my advisor and was just in awe, basically. That telescope, the mirror is 3 times larger than the nickel that we just saw, but all of the support structures and the dome and everything to operate it is, I feel like, more than 3 times bigger. It takes up a lot more space. So it's a really cool machine. And so, yeah, that was back in 2010, I think. Did my first night of observing with Mike Fitzgerald, my advisor at UCLA, and we were doing spectroscopy, and I've never done spectroscopy since. It's it's about 13 years. I don't think I've ever had a night purely for spectroscopy. I've used spectrograph and spectroscopically capable instruments before, but so I went to a 3 meter. I guess I started pretty big. I was spoiled.
Yeah, okay.
I was
Must
very
be nice.
I was very fortunate. The University of California has great access to telescopes, and from there I went on to using the 10-meter Keck telescope in Hawaii. One of them. There's 2 of them. I used the 8-meter telescope at Gemini South in Chile. And we'll talk more about others. But,
so we got a question from Tonko on YouTube. What telescopes are you most interested in, and would you like to use now?
Well, I mean, I think the hot one is James Webb.
Yeah.
Right. So the James Webb Space Telescope was launched not last year, but the year before, I believe. Was it 2 years ago now? Yeah.
Well, no, it was
Christmas,
about 2 years.
Christmas-ish.
Because we were observing it when I first started at SETI.
Right.
So.
So that was 2022. Late 2021 was when it launched, I believe.
Yes.
And so it is the largest space telescope we've ever launched. Anyone has ever launched. Really high quality infrared telescope that looks at longer wavelengths of light than the eye can see to really probe faint parts of the universe, look into parts of the galaxy and the universe that are just blocked for other telescopes. So that's kind of, I think, one of the things we'd really like to use. I don't know if you have other ideas.
So honestly, a lot of my graduate school studies, while I did use some big telescopes, it was largely for courses where I was a TA. My research before this was all about data mining. So I really love the idea of using astronomical data that's already been taken and finding new uses for it. Because I think that's a lot of times we have a project in mind when we go to the telescope and we get an observation and we get the answer, we get the information we want from the data that we've collected, and then it just kind of goes into an archive and never gets used again. And I feel like that's a bit of a waste. So I've always been enamored with not necessarily using the large telescopes, but using the data that other people have gathered from the large telescopes. So I really like large telescopes. I love being at the observatory, but I've never had one that I've really been like, I really want to use it. I need to use this. But I love it when I'm here. It's genuinely, I think it's so fun to be here.
Yeah, for sure. All right, do you want to get to one more question, and then I think we can start taking some calibration data.
Yeah, so Paul Hawkins asked, what frequency ranges are we observing, and can we see the IR or the UV with our sensors? So this is all optical, right?
Yeah, so we're looking tonight, we are looking purely in what we call the optical or the visible wavelengths of light. We may, depends how the night goes and what kind of data we get, we might try one filter that stretches just kind of to the very red edge of the colors of light we can see. Towards the infrared, not really the infrared, it's like in that fuzzy middle ground. The nickel, I believe, only does optical imaging right now. The direct imaging camera, which is the instrument we'll be using, only can detect optical wavelengths, visible wavelengths of light. So if you're familiar with the electromagnetic spectrum, something like 400 to 1,000 nanometers-ish, maybe 400, 900 something nanometers in terms of the wavelength of light. In order to see longer wavelengths of light, you need different technology. So the chip, that CCD sensor that I talked about earlier, longer wavelength photons, so redder colors, just basically pass through the sensor and don't get captured. And so you need, instead of a sensor that is silicone atoms mixed with some other sort of material, you might have a sensor that's mercury cadmium telluride mix, or an indium based sensor. And so those are more for the infrared, for example.
Yeah, cool.
Okay.
So we have a few more questions, but I can save those. So we'll star those to get back to them.
Please keep leaving your questions. We will come back to them.
Mhm.
We're gonna have plenty of time.
Yeah.
We are just past hour 1, so we made it. We did it.
We did it.
We did it, everyone. We have 12 and a half more to go. So yeah, buckle up.
Oh boy.
And yeah, so let's start taking calibrations. I think, how do we want to do this? I just want to, we can briefly share, I think, the screen of this control telescope.
Should be able to.
Yeah. We're not going to do it for long because it's a lot, honestly. It's it's a lot.
Entire screen at the bottom.
Entire screen.
Mm-hmm.
Allow. All right, and we'll get rid of that so we're not. Let's see if this. Oh, I have to add it to the stage.
Yeah. There we go.
Okay.
So this is our view for the night as well. This is everything we need to run the nickel telescope. It's a lot.
So yeah, there's a lot happening here. I guess we can talk through some of it really briefly.
Mm-hmm.
The one on the top right is the easiest. This is kind of for any sort of web browsing we need to do. We're keeping an eye on the weather here. Green is good. The main thing we've been worried about has been particle counts. So particles in the air, actual dust, basically. There was, we think we were getting smoke from a wildfire that was up north in Napa. So yeah. I don't know, I forget if we described it, but Mount Hamilton is east of San Jose, California, kind of southeast of San Francisco in the San Francisco Bay. And so northwest of us is Napa Valley, where you may have had wine from. And there was a fire up there that's been contained, but was, I think, sending some smoke this way. And they don't allow you to open the telescopes when there's too many particles because they will actually scratch the coating on that mirror and degrade its performance. So yeah, this here is weather, and there's lots of graphs and plots and things showing how the weather has changed over time. We'll assume things are still going well. I don't know, Ryan, you want to describe some of these others?
Sure. So, there we go. This bottom right window here is everything that we need to control the telescope itself. So this is what lets us move the dome, and it's what lets us point the telescope. So we have a couple of little menus here. We have the easiest probably to just talk about right away is there are two webcams in the dome. One is attached directly to the telescope, and one is attached to the dome. They are not like night vision or anything. They're just a way of kind of giving you some insight into what's happening in the dome when the lights are on. So you can kind of at a glance see where everything is and make sure that the telescope's where you want it to be and the dome is where you want it to be. One of the things that we're going to have to do at the beginning of the night is point and focus the telescope. So the telescope does not start the night knowing exactly where it is and being able to perfectly point to a star that you want to point it to or an asteroid that you want to point it to. So one of the ways that we get around that is we pick a bright star, usually from a star list like this, and we say, okay, point to this, and the telescope will do its best. And the telescope is usually very close. It will be within the field, but it won't be exactly center of the image. It will probably be off in a corner somewhere. So we point the telescope first so that we get a general idea of how good the pointing is. And then when the star is in the field, we kind of nudge the telescope around until the star is in the middle. And then we tell the telescope, okay, now you are actually where you think you are. I keep looking down here at my computer screen rather than the webcam. So this is our star list where we can, ooh, that was fun. There we go. So this is our star list where we can send the coordinates, the RA-index of the star, to the actual menu that lets us move the telescope, the POCO menu, which is this here. So this is what lets us move the telescope. As you see here, it says move to target. Mark centered is how when we have centered up the star, we tell it, all right, now you are actually pointed where you said you were pointed. And then object not found, we hopefully won't ever have to use. This tells us where the RA index, the hour angle, which is HA, and the air mass gives us an idea of where the telescope is pointed. The RA index is currently where the telescope is pointed. Hour angle is similar to the right ascension. It's basically just a conversion of the right ascension. And then the air mass is how much atmosphere are we having to look through. As we point the telescope closer to the ground, that air mass is going to shoot way up because we're looking through way more air. And then we have some general kind of guidance down here letting us know what is happening in the dome. Something that tells us about our guider camera. The guider camera will help us stay focused on the target that we want to stay on, and it will keep the telescope from kind of moving when we don't want it to. The dome information lets us know if the dome is in the way of the telescope. Are we looking out the slit of the dome, or are we pointed at a wall? Because there's that giant sheet metal at the top, we can't actually look straight up out of the dome. The sheets covers a little bit of the telescope. So that's what the zenith warning means. It means that zenith is pointing straight up, and it means that we are too close to the top of the dome, pointing to the top of the dome, and that little plate is blocking our telescope. And then the 40% occulted is just a fancy way of saying that it's being blocked. So about 40% of our telescope opening is being blocked right now by that plate. So when we move the telescope around and we move it towards one of the targets, you'll see that the dome will no longer be in the way, ideally, and these two warnings will go green, saying that we're no longer pointing at the zenith and that we're no longer blocking our telescope. We have different times for keeping track of local sidereal time is how we keep track of targets in the sky. What their position is, you can see it's pretty close to this RA right now. The Pacific Standard Time, so even if we're on daylight time, Mount Hamilton itself uses Pacific Standard because the software requires it. And then GMT is the Greenwich Mean Time that has now actually been converted to Universal Time. And that basically is just a set time that you can use anywhere in the world. We say it's a placeholder essentially, rather than having to do a bunch of time zone conversions from Pacific to East Coast time, or Pacific to time in India or in Europe. You just say it's UTC. It's this time UTC, and everybody kind of goes along with that when you're an astronomer. Let's see. What are you still working on stuff right now?
I'm good.
Okay.
So I was just connecting so that we might be able to share some of this more effectively.
Okay.
I'll work on that while we describe things.
Sure.
So yeah, why don't you keep going?
Yeah. So we have dome control lights. So this little menu here lets us control. Oh man, I just realized you are not able to really see a whole lot of the screen. You can't actually zoom in.
Yeah, that's why I was going to switch. When are you going to show?
I was going to show this. Yeah.
Okay.
Okay. So the menu.
Can you do this one? Well, hold on. Yeah.
Okay.
Keep going with what you were doing.
The menu that you can't really see right here. I'm sorry. I realize now that this is way too small. But we have a menu here that lets us control whether or not the dome opens and whether or not the mirror is open. So we keep that there. It will flash green when everything is open, and if it's closed, it flashes yellow, kind of as a warning of, hey, if you're trying to take data, it's not going to work right now. We have two options underneath that are about turning on the dome flat field lamps and the telescope flat field lamps. So like I was talking about earlier, flat fields are useful for determining how sensitive each pixel is on your CCD. And you want to know exactly how sensitive your pixels are on the CCD because they can vary across the CCD, and you don't want a star that's on the right side of your camera that is brighter. You want to be sure that it's not because the pixels over there are way more sensitive than the pixels on the left side of the camera. It's a way of helping to be sure that you are getting the actual brightness of your target, and you're not accidentally measuring something that is inherent to the camera itself. So these control these two lamps we use for flat fields. They're controlled here. We can focus our little guider telescope using an option here. And then there are just some little information for us down at the bottom, whether or not the dome lights are on. We can turn them on or off here. The remote observer, if you are working remotely, there is a little dead man switch. So making sure that if you fell asleep at your chair or if your internet cut out, the telescope doesn't just sit open and potentially being damaged by weather. So after about 20 minutes, if you haven't hit the little button, it'll just immediately kind of shut off, close the dome, close the mirror. So we're not remote, so it's currently inactive, but that is there as well.
Okay, I think I can zoom in for that. It's gonna maybe take a second, so we're gonna lose that screen. And then we will, whoop, that's fine. Add this screen, maybe. So this we'll be able to, during most of the night, we'll zoom in and give you try to give you a decent view of things close up.
Yeah. You got a hello from Mary Corrigan.
Hi, Mary.
All right. Phil Wise says this is better than Netflix. Thank you, Phil. I appreciate it. I'm glad everybody who is watching this, rather than, I don't know, something scripted and maybe a little more exciting. Thank you. We appreciate you tuning in. We appreciate your interest. This is something we've been excited to do for a few weeks, ever since well, I guess even longer than that, ever since we first put in the proposal to operate this telescope. This has been something we've been planning and getting more and more excited about. So a lot of fun.
I think this will work, but it takes quite, I don't know.
You were sharing the wrong screen last time, apparently.
I don't really understand what that means because I don't really have too many options. I just want to click present. Sorry, this is not interesting to anyone. Share screen.
It's kind of, I mean, it's interesting to me watching you flail.
Well, tell me if I'm doing this wrong. Okay. Share screen. It's just that my computer is basically melting a hole into the earth right now with all the things I'm asking it to do. So I'm gonna have to try to reimagine how we do this. I think so. Let's do it this way. Let's undo this. Remove, and I'll put this one back. Can you add the nickel telescope again to stage?
Nickel telescope. Yeah. Do it. Okay.
Okay. And then from up here, we will just share these screens individually. I think this is the way to go. So we're going to stop sharing that and then restart sharing VNC3.
So we have Karen Baisley says that we have a question from a middle schooler asking these questions. Do you think you could find new moons or maybe the hypothetical planet 9 with this telescope? And if so, how would we feel? New moons or planet 9? I would struggle to think that we could do that with this telescope. Because I think bigger telescopes, maybe not better, bigger telescopes have tried to find planet 9. I don't know if I think planet 9 is an interesting idea. I don't know if I think it actually exists, but I would be thrilled to be proven wrong. I think it would be very, very cool to see that. Finding new moons, I think that would be, at this point, I think at this point we've found a lot of the moons for planets in our solar system. I don't think there's a whole lot else to be discovered on that front. We would have to be moving very, very far out in the solar system, probably out in the Kuiper Belt or something out there, maybe a dwarf planet that has a moon. In which case, yeah, we could probably see something like that, I think. We just have to know where to look.
Yep. And so, are you able to click on one of the other views to get it to actually, add that to stage? There we go. Okay. Better. So this was what we were trying to show about, I don't know, an hour ago now. No, it was a few minutes ago. This was the screen that Ryan was trying to walk you through more fully. We'll also have more time to look at this later. But on the left there, in this window that's now highlighted pink, that was all of the dome controls, the mirror cover control, the flat lamps, and a lot of the status for the physical stuff on the telescope. Okay. As for I think you answered the Planet 9 question. But we would be excited, yes. And then let's see if we can switch to sharing a different screen. We'll show what the calibrations will do. Can you add that to stage, please?
Add this one, yes.
Okay, good. So this will actually let us take our calibration data, which we should get to before it gets too late. So, Ryan, did you describe this VNC yet?
No, not yet.
All right. So just a quick run through of what we're looking at here on this screen. When we take an image, it will appear in this center panel. This is the last image that was taken. It was a bias frame, which means that there was no light on the telescope or no light on the camera when the image was taken, so it was completely dark. And we're actually going to start with those first. There's some other controls here. This sets the filter that we're looking through. So again, which wavelengths of light we're letting through to our camera. This one here, if I can click through to it, is the control for this image view. So it lets us change the scaling and the zoom and stuff like that. On the left, this is actually the camera control. So, oh, did we lose? No, it's just me. Let us know in chat if you lost the view of the telescope control that I'm showing, but I think it's still there. Yep. So this camera control here on the left gives you things like the status of the current image. So in this case, the readout complete means that the image was finished. There's the time of the exposure. So the way we take images is the camera has a shutter. It's an iris, basically. So the shutter, when closed, blocks all light from hitting the camera. Then when it opens, light gets through to the camera. And basically at that point, you start exposing. You're letting photons, light, you're letting light hit your camera and get collected. We call that exposing or exposures. And the amount of time you do that for will show up here in the elapsed number. And then the amount of time that you want to keep going in that exposure will be the remaining number. You'll see how that works. There's a bunch of buttons to start taking a new image, to pause an image, to stop an image and save it, and then to just give up and abort the image that you're taking. You can set the exposure time here. This is in seconds. You can set how much of the camera's light-sensitive chip that we use to collect data with. We want to use the whole thing, so it's on whole CCD right now. The control is to open and close the shutter, again, to let light through or not let light through to the camera. Binning, we don't have to worry about that. It just combines pixels into groups. Readout speed, so this is how quickly we translate the information in the camera sensor into data, basically. Slower gives us less noise, so we like slow. The observation number, so that's kind of what number we're starting with. Let's actually just keep it at 1083. We won't be taking 1,000 images tonight, probably, but it's nice to have 4 digits just in case we do take 1,000 or more. And then whether you record the image or not, so whether we actually save the image to a file that we can then open later and do analysis on and stuff. And then you can name the object you're observing down here. And then the very bottom is sounds. So you'll hear, hopefully, that there are sounds that the telescope will make as it's taking its images to keep us updated as to what's happening. They're kind of fun. Okay. All right, so Ryan, we should probably start taking our bias frames.
Yep.
let's see. So I think this is pretty straightforward. The very first thing we want to do for calibrations, I'm just going to start them and then we'll explain them. So what we do is we want 0 exposure time. We actually don't want to let any light hit our camera. So this means that the shutter will never open. We'll keep the shutter closed. And we will name the object bias. And this all looks correct. We are recording the image, so we will start 1 exposure. I don't know if that sound came through, but it's a little bit of a...
Never gets better.
Oh, I like it.
Oh, I don't.
So I might turn this down a little bit. There's some fun Star Trek sound effects and other things that tell you when you start an exposure, and then when the exposure has ended, and then you have to still wait for the sensor to be read out, basically, to get the information from the light out of the sensor to an image file. Okay, so we can, crossing the streams here. Don't worry about that. All right, so we can actually use this panel down here. This is just a standard, on the bottom here, this is just a standard command line terminal window. We can run this. It's really probably impossible to see. This command here called iGetNick, and then a number. And iGetNick is basically I get an image with the nickel. And we want to take 9 more of these bias frames. So we run that, and it will now take 9 in a row. We don't have to keep clicking the start exposure button. All right, so Ryan, do you want to explain the biases and what we do take?
Sure, yeah. So like the idea of flat fields, where pixels have variations in how sensitive they are. Biases we take because reading out the CCD, reading out the image, that is also not a perfect process. When you think about a camera like this, you're reading out electric charge and trying to determine how much was in each pixel. There's a computer doing that, and that computer will sometimes add its own charge to it. And so you don't want, in order to get really precise data, you don't want the actual computer that's reading out the image at the end to add its own bias to the image. So what we do here in order to take that out is the way that we get around that is we take exposure times that essentially have no light in them, so that everything that we get is only what the computer is adding on its own as it's reading out the image. It's actually important sometimes that the computer does add some of its own little charge because you don't ever want charge to possibly be negative. If the computer somehow makes any kind of a mistake and you get a negative value, that could really screw up the computer, could screw up your data. So it's actually a good thing that bias gets added, but it's something that we definitely want to take out before we start using any of our data that we're collecting for actual science. So that's why we take these at the beginning of the night, is to get an idea of, okay, what is this CCD doing? What is the computer on this CCD actually adding to the images, and so that we can take it out later, because no piece of hardware is ever going to be the same. Even two exact same computers with the exact same specs, there's always going to be some little minute differences that come from small variations in how they were produced, small variations in the machine. So this just lets us get rid of all of that kind of messiness without having to worry about it when we want to come to some conclusions about stars or asteroids or whatever it is that we're looking at that night. So we usually take 10 or so. It's up to you whenever you are on the telescope. But you take 10, you average it out, and at the end of the night, that lets you when you're actually looking at the data, be sure that you are looking at the data and not looking at what the computer on the CCD has added to your data.
Yep, exactly. And so let's see. We can look at. I changed the color stretch here on this image. If I zoom out again, instead of it being just totally black, you can see that it's some features here, even though there's no light reaching the camera. And so the different colors of the different colors in this image are related to how bright that pixel is. So each of these little points is a pixel. If I zoom in enough, maybe you can see
individual.
It's tiny, but you can see individual pixels here, and they have different colors, which means they have different amounts of voltage, like Ryan was saying, different amounts of charge, which is essentially, you can consider it different amounts of light
that it's collected.
Even though there's no light coming in, charge and light are basically indistinguishable here. And so if we zoom back out a little bit, let's zoom out over here. You can see there's one very bright line across the entire image here. There's something wrong with this one column of pixels. Their voltage is way too high. And so when we process our data later, these biases will let us remove this bit of noise here. There's also on the right side, if I zoom in a bit and then click over here, you can see the image gets darker and darker, lower and lower intensity. The purple color towards the edge of the chip. This is known as the edge effect. It's a physical effect that you get with these silicone CCDs. And so that's something that subtracting the bias frame from those science images will compensate for, and we won't have this gradient to worry about affecting our images. And then on the very far right side, these columns of the image are never used for collecting light. They just tell you what this bias level is in each row. And so it's kind of like a calibration built into every single image that we can use later for our analysis. All right, so that sound effect meant that we are done with our 10 images, and we can now move on to the next set of calibrations, which will be flat field images. So let's see, to do that, we need to move the telescope first and point it at the correct place in the dome. So the dome is still closed, but we're going to point the telescope at a specific part of the dome that has a screen, or basically a screen. That we'll shine a light on, and then we will use that to take flat field. So we want to point at our angle 4. Oh, let me
switch to.
I don't think I'm going to switch back, but we're just going to move the telescope. We'll see plenty of this later, I promise. Okay, so I think we don't want the dome to move, right?
We do. It's in the. So it's in the. We had a little thing
here.
Observing hints.
Okay. Sorry. We haven't done this much before now. Yeah. So.
Not the flats, flat field screen.
Flat field screen.
Okay. And the windscreen is gone, so that's what we want. Yeah, 38 hour angle 4.
Right, but I mean, do we want dome hold or dome? We just want dome hold, right? We keep it where it is. Yeah, parked. We want to keep it parked and tracking off.
Right.
Yeah. Okay. So we will move to target.
And then we need to move the dome to, so hit functions.
What?
And then go down to
manual dome.
Yep. Because we need the dome to be at azimuth 328. So we have the little screen that is on the dome. So right now we're moving the telescope so that it is pointed at a very specific position, but we also need to move the dome because there is some light that comes in through that slit in the dome. You probably saw it while we were looking. It's not perfectly blocking out everything. So we want to move the dome so that we minimize the amount of light that is leaking in from the outside while we're doing this, because the idea of the flat field is that you want just the light, the lamp that you're projecting, to make a nice little even distribution of light. And if you have anything coming in, light from the outside, reflections from somewhere, that can disrupt your flat field. So it makes some portions of the image brighter than others, and you can no longer tell whether or not a brighter portion of your image for your flat field is because the pixels are more sensitive, or if it's because that was where some stray light showed up. So we're moving the dome as well to make sure that we are pointing it away from the sun, pointing it away from the sunset, and minimize the amount of extra light that's coming in. In the meantime, while we wait on it to move, what about dark frames? So we have somebody asking about dark frames. Dark frames for this telescope, we don't have to take. Dark frames in general are an underlying current in the CCD, usually from the CCD being warm. So when the CCD is warm, you can get some extra of that voltage at the pixels. That doesn't come from the computer that's reading out the image, and it doesn't come from light itself. It's just from electrons being happy to be there and having some energy from being warm. So if you are using kind of your own camera, or if you are using a smaller telescope or one that isn't cooled, dark current can be something that you have to worry about. And the way that you fix that is you keep the shutter closed like we did for biases, but rather than having a 0 exposure time, you expose, so you keep the shutter closed, but you still you tell the camera, okay, we're collecting light for X amount of time, where X is however long you're planning on making your exposures for your target. And so if you take a bunch of those, that will let you get rid of the dark current. But like Tom said earlier, our CCD is being cooled by liquid nitrogen. It is currently at like minus 100 Celsius. So thankfully, we don't really have to worry about that tonight. So we are not actually going to take dark frames.
Cool. Okay.
Yeah. But that was a great question. That is something that a lot of people will have to do. If you are we also work for Unistellar, or I work with Unistellar data. That is something that we ask people to do because those are smaller personal telescopes. And you want to make sure that if you're living in a warm environment, you are taking out that extra signal that isn't necessarily representing anything.
Okay, so I think the telescope's in place, the dome is in place. I turned on the lights, the lamps that let us illuminate the field to take our flats. Ryan, I think we need to initialize and set the spectrograph right first for the filter. So we're going to choose to start in the B-band filter. So this is basically looking at blue light. And the first thing you have to do is the filters are in a wheel, and they're either square. I think in this case they're square filters. So basically little pieces of some sort of transparent material like glass, though they're usually not just glass. They might be circular instead, but basically they're in a wheel. So you rotate the wheel to put the right one in your light path so that the light passes through that filter. And that initializing that button sets it to be in the right place. So we open the shutter. We're not gonna record this first one just because I want to make sure we did everything right. 30 seconds for B-band, and I think we're going to start taking it. And we change the object name here to flat dome so that later on we know what this image number 1092 was an image of. And now we will wait. You'll see now that we're actually taking an image with exposure time, you can see it's counting up in seconds elapsed and counting down in seconds remaining. It tells us the exposure is in progress. And then when this seconds remaining hits 0, you'll notice maybe already, it actually takes another 20 or 21 seconds to finish. And that means that what it's doing right now is it's kind of shuffling the voltage in each pixel down every single column in the chip, in the CCD sensor, and passing it into electronics that measure how much voltage there was and then turn it into a number called a count that we can actually make sense of in terms of human terms. All right, so I think this came out pretty good. This is what a flat field should look like. We're getting, you see here in this right-hand value number, We're getting about 38,000, 39,000 counts in the center of the image. That's good. We'll explain about that later. And we're just going to keep taking, what do you do, 5 of them total?
Yeah.
Right. So we'll do 4 more. Ah, shoot. I didn't record that one.
Got him.
So we will abort that. Had to turn on record. That's not the last time that'll happen tonight.
You did record the biases, right?
The biases were recorded, I believe, yes. We'll find out. I can check that later. Okay, so we need to take 5 of them because I didn't record the first one. This is not done exposing, so I didn't abort it in time, so we got to wait for this image to finish. Oops. And it will then get thrown away.
I wasn't listening. Did you talk about the gradient on the image?
Not yet. I was trying to get this going, and then we'll talk about it.
All right.
I just want to make sure that this image is. So, first mistake of the night. Hopefully the last, but probably not. When we're actually doing science, I will probably never hit the don't record button because we don't want to waste time when we're on Sky. So that's done. We're gonna try this again. Okay. We're now recording the images. Everything should be good. All right, now do you want to talk about that?
Yeah, so like I was saying earlier about the pixel sensitivity, this is a very good example of how CCDs and cameras are not perfect. We have right here in the very center, the pixels are brighter. They're more yellow, which means that they caught more light. There are some pixels that look like they have dust on them. So that's what those little like donuts are. So all of that is something that if you don't take care of, if you aren't aware of when you are looking at your science data, that could really screw up what conclusions you come to. So this is a good example of why we do this, why we flat field, because the CCDs, the variations, can be quite large. If the experience you have with cameras is like a photography camera or a phone camera even, it might not be something that you ever really have experienced or have to deal with, but for astronomical data, it's very important that we take care of this and we make sure that we are accurately representing what we are imaging at any given time. So
yeah, and so the dust, any sort of dust particles or any sort of dirt that is on one of the surfaces of the telescope, so either the primary mirror or the secondary mirror, or there is a little, usually some sort of a glass plate that covers the entrance to the camera to keep it sensor clean. Any sort of particle there will be out of focus as far as the telescope is concerned. And that's why you get these donut shapes. That's the shape you get. In this case, it's a shadow. But we'll see later, we're going to focus the telescope once we get on Sky. We'll see that stars will have this donut shape if they're out of focus as well.
Yep.
So that's where the donuts come from. And every single science image we take will have that donut in it. But when we divide the image by this flat field, the donut essentially gets wiped away or flattened out. Hence the flat field is that we take all this variation, this gradient in the donuts, and make all of this a uniform flat color, flat intensity. Okay, so these take a little bit of time. The B band is, the lamps are not super bright in these short blue wavelengths. So we need 30 seconds of exposure for every one, and then we need another 20 seconds to read out the sensor. So it's about 1 minute per image. We took 5 images, so we're going to take about 5 minutes. 2 more images, 2 more minutes to finish this round. Then we'll move on to the V band, which is basically greenish, yellowish, greenish color. That will be quicker. And then I think we'll just do R and not do I. We could do I.
Yeah, it's fine. I mean, R and I are very quick, so.
Okay, yeah, we'll see. We may do R band, which is reddish, and then I, which is redder than red.
Yeah.
I does not stand for indigo. I don't know if it actually stands for infrared, but it's towards the infrared end of the light spectrum. Astronomy filter names, some of them sort of make sense. A lot of them don't. For example, Z and G, well, G sort of, but yeah, Y and Z and others. Yeah. And these are what we call broadband filters. So they let through a lot of light. There are much narrower filters that only let through a very specific color of light. For example, if you want to look at only light emitted by hydrogen atoms at with a certain energy, then you can do that with a filter.
Yeah. So I do want to get through, we have a couple of comments from way early when the stream started, so I'm very sorry that we didn't get to these questions early on. Was hoping we could catch a little bit of a break in between then, but we can take some time now since we're waiting on the B-band stuff. So John Ray asks, do you ever take a break during night session to go outside and simply stargaze? I did this last night, actually. I was, I'm not in the screen. So I was going out to my car to get a generator that we have so that we can power one of our eVscopes last night and make sure that its battery was still charged. And I didn't come back for like 10 minutes because first I tripped when I went down the stairs and I did a nice little Mission Impossible roll. But then after, once I was out there, I sat on my trunk for a minute and kind of looked at the star. It's very nice because San Jose is visible as well. So you get the city. Not really nice when you want a dark sky, but thankfully it doesn't get in the way too bad for us. But yeah, stargazing, it's one of the things of being in an observatory, like literally being on the mountain, is that it's a dark place and you see so much more of the sky than you're ever really used to. And I think it's very easy to forget how much is in the sky and how nice it is to just kind of meditate on what's out there.
Yeah, I mean, I do the same.
So say follow that up.
Yeah, I mean, I really couldn't even try, but yeah, it's a lot of the time, given where we live these days, we live in bright places. So we really don't see the sky, the night sky, at all like it actually looks. And so it's nice to be up on a mountain and see the stars, how many there are actually up there. If you get somewhere really remote, like a mountaintop in Hawaii or Chile or something, the Milky Way comes out. It's a little tougher from here. I didn't see it last night.
Yeah, I didn't see the Milky Way last night.
We do still have a lot of light pollution here from San Jose and the surrounding cities. Let's see. That image looked good.
Yep.
42,000 counts. So, and we are recording this time. So 4 more of those. We're doing the V-band filter now, flat fields. Yeah, but. Yeah. Basically, that's the deal, and it's also just quiet. It's nice to be out there.
Yeah, something you don't really get when you're living in or even a suburban area. It's just, I'm certain if you live out in the country, that's something you're probably very used to, is just the peace and quiet, the lack of noise all the time. But yeah, it's very interesting. It's isolating, but it's a good kind of isolating where you can go back to society at any time, and you just kind of use it to recharge. Phil Y asked what the weather forecast is tonight. Pretty sure cloud-wise we're okay. We're expecting a good night on that front. The question is going to be particles in the air. So we talked a little bit about this before. There was a wildfire in Napa Valley. It looks like it's largely been contained, but that is throwing up particles in the air, and there is a limit that of how saturated the air can be with these particles because they can damage the mirror. So it's a lot harder to predict what that is going to do. It fluctuated a lot last night. We got maybe an hour of actual time where we could use the telescope. Because it fluctuates so much, when the dome closes and the mirror closes, when it hits that limit, it waits essentially for 20 minutes to make sure that the particle count has gone back down. So that may be one of the things we run into tonight, where the particle count just like skyrockets for a little bit, and now we're locked out of the telescope for like 20, 30 minutes. So we'll see. Ideally, fingers crossed, we're going to have a very good night, and that is what we were hoping for. Weather-wise, it looks good. Particle-wise, we'll see.
Touch and go.
Yeah.
It's exciting, chat. Stay around. Who knows what'll happen?
What is the coolest thing about living or being at the observatory? I feel like we actually just kind of answered this. Phillips, this was at 5:17, so that's why I'm getting through these. These were like an hour ago. I'm very sorry. Yeah, I really like the kind of being away from everything. Observatories, by their nature, tend to be isolated places. It's very quiet. It's very kind of a chance to meditate and think without having a lot of like your everyday life worries getting in the way. You? Anything different?
Yeah, I mean, I think
You actually stayed here last night.
Yeah, so I actually slept here in one of the dormitories last night. I've done kind of 6-night runs, are kind of the longest that I've had in a row. Sorry, let me do some things here. I'll come back to this.
Yeah.
I need to change the lamps, so we're going to turn off one set of flat field lamps and turn on another set. We're going to switch to the R band filter and set it. And
well, this, yeah. So while you're doing that,
I'll come back to that.
So Jet Fusion asked, and answering this one because this one I think was directed at me. This asked from SETI at home project data. So I think that was in response to me saying that I really like data mining. So for those who have just come back in, that was part of what my research was in grad school. Data mining in general is all about taking data that's already been collected from someone else for another project and finding another use for it. I like it because it's very efficient. I think it feels like a waste to take data for a single project and then never use it again. So yeah, the SETI at home project is a great example of that. Citizen science, being able to kind of use your computers to work with data. But in general, a lot of astronomers just on their own are sitting on lots and lots of data from years of having telescope time for specific projects. And then a lot of the time they'll have another idea for the data, but they won't have time to get to it, or they won't have time to write the proposal to get the money to actually do the project. So just finding people to work with. If you go up and talk to an astronomer who has been in the game for a while, if they are an observational astronomer, they probably have some set of data that they have lying around that they haven't used. And then there's, tons of free data. So there's Gaia data, there is Hubble data. There's lots and lots of data that's been collected from NASA telescopes that is out there and free to use. So as long as you have a project idea, that's always the hardest part, is coming up with, okay, I have all of these data. What can I find out with these? But yeah, so that's the general idea. The SETI at home project data, that is a good example.
And I'll just note that the NASA data is public after a certain amount of time, small amount of time, usually somewhere between 6 months and a year from when it's taken. It's automatically public and free of use by law, because NASA was this was actually written into law a while ago, many years ago, when NASA started.
That one.
What?
You're looking at this.
Oh, I am.
I do it too.
I know. I was learning from you. So that's kind of a cool thing about NASA data. It may also be true for ESA, the European Space Agency. I'm not as familiar, but I think they have some, and other space agencies that launch space telescopes as well. Ryan, can you do the I-band when we get to it, so I can answer that other question?
Absolutely.
It'll be 4 seconds exposures.
All right.
We didn't have to wait for this to be green, right? The lamp, lamp.
Not this one. Wait, why is this one on?
That's the R band. Should be.
Oh, I thought you. Okay, sure.
That's what I wrote down last night.
Yeah, that's fine. That's what we'll do then.
The counts are good. So to answer the previous question, what do I like about the observatory? It's just kind of a different world that I think a lot of people don't get to see. So I feel like I try to take advantage of that privilege and just, get the behind the scenes look at what these amazing telescopes that we have, what they're like, how they work, what seeing all the machinery and the electronics and the hardware and stuff, all the behind the scenes of what the telescope operators do. Most large telescopes, this telescope is small enough that we can operate it ourselves. We can move the telescope, we can control the camera, do everything ourselves. Telescopes that are basically 2-3 meters and larger, usually you have a professional telescope operator who is their job to point that telescope, to run the telescope, to make sure it's operating safely and correctly. And so you don't get to do the things like push the button to move the telescope. You do get to control the camera, so you get to control the science side of things. You can tell when to take an image, what exposure time to set, what filter to use, but a lot of the other stuff is out of your control. So I kind of like being able to see the telescope operator when you're actually at the telescope do what they do. And yeah, just sometimes the food's really good, sometimes it's not. Over the observatory, depends on the observatory.
I will die on this hill that the cafeteria at Kitt Peak in Arizona is amazing. I have never had better food in the middle of nowhere on a mountain. Fantastic. Would recommend.
Yeah, others not so much. I won't name them, but not so much.
This is a shout out to the Kitt Peak cafeteria staff. I see you. I love you. You do great work.
We got that.
Yeah, okay, council, get on that one.
Okay, I'm just checking that we actually recorded those bias frames. We'll find out in a few minutes.
Okay, good.
Now we can always do them later. So we'll also usually do calibrations in the morning, when we're done with all the signs. But that is 12 hours away, so that'll be for other folks to watch probably. So it's almost 7 p.m. here. Sunset's at 7:33. Mm-hmm. And we're essentially done with calibrations for now. We will do one more set of calibrations right after sunset, when we will point at the twilight sky with the dome open, and then just actually take images of the sunlight that gets scattered by the Earth's atmosphere. That will actually uniformly illuminate our camera better than these dome flat images will. So those are probably the ones we'll use for our calibrations in the long run. But it's good to have both just in case something happens where the twilight flats don't work out, or they're not good.
Jet Fusion has answered that the ESA image data sets are available through the Copernicus Sentinel project browser. Cool. So yeah, cool. Thank you. I didn't know that either. So that's awesome. All right. So yes, I guess we can answer some more stuff. So Stephen Schreier asked a little while ago about how camera images are recorded and stored. So the Lick Observatory has its own archive, right? That it basically writes all this data to that we can access. Right.
Yeah. Yeah, so it's part of the University of California Observatories operate Lick Observatory. And so, yes, they have online archives that basically, as soon as we take an image here, it gets written to a local hard drive. I think within an hour, no, within a few minutes.
Yeah, you said it was like a few minutes.
Within a few minutes, it's copied from there to an online archive that we can access right away. And it doesn't become public right away. But as the observers, we get first crack at the data, which is, I think it's fair. There is a push, there is a movement in astronomy to make data public. I think there's strengths to that and also weaknesses. All right, that was the end of our dome flats. So we can answer more questions. I think I'm going to start setting up an eVscope.
Yeah.
If you want to answer questions, I'll go out and do that.
Sure. I guess before that, do you know what kind of computer? So I know hardware-wise, or do you know what kind of hardware we're using for this? Software, this is all like in-house made software that was written. Basically, astronomers like to just throw software together. So this was a question from Paul Hawkins. What kind of computer hardware and software do we use up at this observatory? All of this software is specifically made for the nickel and the telescopes up here. So astronomers, we love to just kind of throw things together. That's why I'm not in case to support astronomers or anybody who is at this. I'm not knocking the software. I think it's amazing that all of this works, but that's why it looks the way it does, because a lot of it was written in like the 80s.
And by many different people, because it was written over time. It's kind of a hodgepodge of different authors. It's most of the control. So most of the computer systems are running Linux operating systems. They are the most. They're kind of the cleanest operating systems. They are something that you can have a lot of customizability over. They're very lightweight to control stuff without needing a really powerful computer. This computer that's running the DNCs is like a little mini box. It's sitting here on the desk. But there's a computer that's, I actually don't know where it is. It's either bolted to the telescope underneath the bottom of it, next to the camera. That's probably where the computer controlling the camera is probably bolted to the telescope or just off to the side of it.
Yeah.
And then, like I said, there's more servers and stuff running in the back here that do other things.
Yeah.
Okay. So.
Yeah, you go set up stuff.
Yeah. Can we? We're just going to close the mirror cover because the next thing we're going to do is open the dome up later.
Yep.
I think everything else is probably, you can turn the dome lamps off and you're in charge of the rest.
Okay.
I will go set up a telescope.
And so we're just waiting right now on Twilight Flats, right? That's essentially it.
Yes, and we'll have actually one of the support astronomers will come in to help us with that. Paul will help us because we could not do this last night because we could not open because of the particle count. So because it's been 10 years since I last used this telescope, Ryan's never used it. We don't know exactly, we think we know how that Twilight Sky process works, but we have a support astronomer help us out and make sure we get it right. And that's their job. So yes, I will be out for a bit and I will come back.
Okay.
I probably won't connect and show it. We'll see, but probably not.
Okay. We'll talk smack.
Sounds good.
All right.
Tell me what he says, chat. When I get back.
Don't. It'll be our little secret. So I've seen a few people asking about satellites and contrails. This is actually, I don't know why I moved the computer in front of me. It's not like this is the one that people are looking at. Here we go. Okay. So, Prince Planet, how do you manage satellite photo bombing? For this one, we don't. We largely just hope that we don't get unlucky enough. Satellites are, I'm about to get on my soapbox. So satellites are an increasing problem for astronomy. And while I think they have a lot of good that comes with them, internet, being able to kind of see around the world and knowing what's happening and communicating, they do have a problem with astronomy where they're very bright. When they're at the right angle, you have the sunlight that's reflecting off of the satellite, and then it just streaks through the night sky. At any point, you can probably, in the middle of the night, look up and find a satellite. They move not too fast. Depends on what their orbit is like. But they book it about as fast as an airplane, but they don't blink, and they move at a very steady rate, and they don't like wiggle around in the sky. And then if you see it, a little light trail, it almost looks like a star moving that fades away. That was a satellite. So satellites in general are tough for astronomy when you are working with large fields of view or when you are taking very, very long exposures. In both cases, you are basically inviting a satellite to, you're upping the probability that a satellite will come through and hit your image and streak through your image. So this is going to be something that we have to worry about a lot more in the future. There were, several years ago, there was maybe about 4,000 satellites that were in low Earth orbit. And now, in the low Earth orbit satellites are the ones that are very bright. So those are like your Starlink satellites. Those are your telecommunication satellites. The Over the past few years, that number has jumped. I'm trying to remember. I think it's around 10,000 now. That may be an overestimate. But there are plans, proposals, hopes from different companies to get as many as like 400,000, depending on how you want to count it. Satellites, I just threw my pen around. Satellites up in the atmosphere. And if that many won't actually make it into the sky. But I mean, if that happens, it's going to be very hard to take any kind of data without several satellites streaking through your image. So observatories, big observatories, are working on ways to mitigate that. One of the ways that you can do it is predict when a satellite train, which is when a group of satellites essentially are going to pass through your field of view. And big observatories are working on determining when that's going to happen and then having the shutter of the image close really fast. And then wait until those satellites have passed by and then open up again. So the nice thing about the satellites is that even though they're really bright, they're moving very fast. You don't have to close the shutter for very long. That's a solution that I think is probably what's going to end up happening until there are so many that that's just not even feasible anymore. And I think that would be a much longer time before we can't just close the shutter and open it back up almost immediately. For this telescope in particular, we have a very small field of view. Around 6 arc minutes, I think was what it was told. This is where I wish Tom knows the technical specs. All of that stuff just bleeds out of my ear whenever I hear it. But yeah, so we have a very small field of view that we're working with. In general, satellite could pass through. Satellites tend to be lower on the horizon. When they're brightest, you'll see them closer to the horizon. And shortly after sunset or shortly before sunrise, those are the times where it is easiest to catch a satellite, a very bright satellite in the field. So we're just kind of hoping tonight that we don't get any. If we do, we'll have time, hopefully, to get more data, and that will be a very unlucky experience. But that's something that I think is something that astronomy is going to have to reckon with, that we're already starting to think about and make calls for, is keeping our sky clear while still allowing progress to happen in terms of making lives better, making it easier to call people on the other side of the world and stay connected. I think all of those are very, very much worth it. But we don't want to lose our night sky as well. Even without astronomy, we were talking about, Tom and I, being at observatories, the kind of meditative, isolation out here, the fact that the sky is so much more vivid, more brilliant. You can see so much fainter objects, things that I forget are even visible when I'm back in the city. And it would be a shame, I think, to, especially astrophotography, it'd be a shame to lose that ability to really appreciate the night sky without having to see, trails of starling satellites flying through. But yeah, so it's a tough problem, and I think that's something that people smarter than me are working on. So hopefully we will find an answer that can please people. Let's see. Gary Allen Smith, you asked a similar question at around 6:05. Does the increased number of artificial satellites impact your observing? Mine specifically, no. It does. So I largely work with the eVscope, which is a digital personal telescope that Unistellar makes. And as working with SETI, I take the planetary defense data that the users of those telescopes catch and upload. And you'll occasionally get a satellite passing through, but thankfully it doesn't happen all that often, unless you're working with really, really large fields of view or really long exposure times. It doesn't get in the way all that often just yet. And then Paul Hawkins, do jet contrails interfere with observations? That's a similar situation where not all that often. Planes are very small. Contrails in general are very small. They're not something that I think you have to worry about all that often. You would be incredibly unlucky. I'd actually be more impressed that I managed to catch a contrail than I would be mad, I think, if I got something like that in my image. Let's see. So Anthony Miller, you asked this around 6:14. What type of telescope would you suggest for home observation for a fourth grader? I am not good with telescope brands. I don't want to give you a telescope brand on stream and make it seem like I'm trying to sell something. So what I would suggest, and this is what I always suggest for photography, for astronomy, for any kind of interest or hobby that is really expensive to get into, I would start small. Especially, a fourth grader. They're kind of at the range where some of the planets, nebula, some of the brighter objects in the sky that a smaller telescope can still see would be really interesting. And those are some of the most beautiful objects in the sky. So I'm sorry I can't give you a full answer. Maybe I'll ask Tom when he comes back in if he has something that he can suggest. I would say anything that is more than a couple $100 might be. Maybe that's too high level. I think you can get a lot with $100 to $200 telescope just to start, and see how your fourth grader likes it. See if that is something for them. I think that is a great way to start. I really like photography. I have now hit the problem where when I moved out here, my camera lens broke, either because it was stored badly when I was living back at home, or because it ended up getting broken on the move. And it's just so hard to get back into that kind of hobby because lenses are ridiculous. So I would say definitely start with something small. Figure out if you like it, and then you can always, if it's something that you've decided or your fourth grade decides seems like they're really interested in, save up and see what some of the bigger purchases are that you might like. Again, I don't know anything about brands. I'm sorry. I will have to ask Tom when he gets back. So, Paul Hawkins, do you guys? I'm just going through all of the list of questions that we have. So if you have any more questions, please let me know. Oh yeah, Rich. Plus, can you use a cell phone on the telescopes with a cheap holder and get great images of planets? Absolutely. I am a firm believer that a lot of the really expensive tech is probably not super necessary for good, nice images, good, nice observations. If you're just trying to do some backyard astronomy and see some really cool things, you can do a lot with a little. What was I going to say? Local seismic data. Yeah, so do you guys keep an eye on local seismic data? We don't specifically, but Mount Hamilton does. So they actually have a seismometer. We'll probably see it later when we do a little tour of the building. They have a seismometer that they have just out in the hallway that is used to check whether or not we're having an earthquake out here in California. So yeah, we don't have to really specifically worry about the seismic data, but that is a big part of the observatory itself. That's one of the things that they have been doing for decades, if not 100 years or so, something like that. They've been around for a while, and they've been cataloging that data. So hopefully we'll get a chance to look at that soon. So let's see, what else do we have? What kind of technology compensates for atmospheric disturbances? So atmospheric disturbances. We talked a little bit about this earlier. Somebody asked about AO on the telescopes here at the Lick Observatory. So atmospheric disturbances, what does that mean? So you've all probably heard about stars twinkling and have seen it likely if you've gone outside on a windy day or a windy night. You can see the stars kind of twinkling in the sky. But have you ever thought about why that is? Why do stars twinkle? And then if you look at like Jupiter or Mars or Saturn, planets, they don't really twinkle unless it's a particularly bad day. That is because when the light is passing through the atmosphere jostles it around, essentially. Planets are close enough that we get enough light that it's hard to see that light being jostled as it's coming through the atmosphere. If the atmosphere is particularly turbulent, like I said, it can even affect planets.
But the idea is that the light passing through from stars is so little that we're getting such little light that any kind of movement through the atmosphere will cause it to look like that star is kind of wiggling in place, wiggling on where it is. And that's purely because passing through the atmosphere itself distorts the light, distorts the path, and makes it look like the star is somewhere else in the sky for just a little bit. So how do you deal with that? That is adaptive optics. That is an entire field of science on how you deal with that. At the minimum, things that you can do, you can have a little mirror that takes the light and basically just tips and tilts. So the light gets shifted a little bit. You try and shift it back with a mirror that adjusts itself as the night goes on based on what the weather is doing. So I don't think we have anything like that here. We certainly don't have it on the nickel. And there are some adaptive optics in the Shane telescope on the mountain. But that is one of the ways that you can do it. That's at the most simple. If you get to a little more high level, you are taking light, and before it goes to the CCD, you're splitting some of it off, and you run it through a computer, and that computer calculates, okay, I know what a star should look like. Why does it look like this? And what do I need to do to change the light back into looking like a star? And the computer essentially decides, how do we fix this? How do we fix the way that this light has been distorted? And you can have a little flexible mirror that the computer then basically tells, okay, I need this part to push out. I need this part to push in. I need this part to angle a little bit. And when you get the light in, the mirror is basically shaped in such a way that the waveform, the light that was distorted by the atmosphere, gets put back into the way that we would expect a star to look. That is much more complicated, much more prone to problems, but it's also potentially a way that you can get really pristine images as if you were out in space. So we don't have anything like that here. But I think in some of the newer observatories, that's tech that is implemented that you could use. Paul Shields asked earlier if we could snap a pic of JWST. I don't know if we can do that with the nickel. That might be feasible. I'll have to see where JWST is. But we have tried that with some of our personal telescopes, so we could maybe look at that as well with the eVscope. Right now, JWST is out at Lagrange point 2. It's very faint, so it's hard to see with a small personal telescope. So it might be interesting to see what it looks like with a big telescope. I'll have to check what our agenda is to see if we'll have some time for that, but I think we will. Especially later at the night or earlier in the morning, we might be able to swing to that and see what we can see. It's probably just like a little dot. What is the limiting magnitude? Prince Planet, you're killing me. So limiting magnitude, I don't know what that is specifically for the nickel. It's got to be mid-20s, I would think. So for a 1 meter telescope, I would expect something along the lines of 24th or 25th magnitude. Our guider, like our little small guider camera, is able to see down to 18th magnitude on its own. So we can get pretty deep into the field on this one. But I don't know the exact. My estimate is probably somewhere around 24 or 25. Yeah, no worries. The nickel telescope. How is the 36-inch Lick refractor being used? So I don't think it's being used for research, but one of the nice things about this observatory is that it has many public nights. It's a pain to drive up here. It's about an hour from San Jose, and you're having to cross through and climb a mountain. But when you're up here, the views are spectacular. So that was actually one of the things we were doing last night when we were shut down and unable to observe using the nickel. They were having a public night where they opened the 36-inch refractor up
to be just looked through. They were just pointing it at things. The Dumbbell Nebula, and I don't remember what was the other thing we looked at. Globular cluster.
M15.
Yeah, M15. So I think largely it's being used as kind of an outreach event, which, if you're in the area, 100% I would suggest. It is a magnificent telescope. This huge. So for refractor, for people in chat who maybe don't know, that's the type of telescope that uses a lens. Yeah.
Well, we need to open the dome.
Oh, okay.
So, do we want to go in there, or should we just do it? I think we should just open it.
Yeah, we should just open it. All right. So
We're going to open the dome to the nickel, folks.
Yep.
Mirror is closed. We're good.
Okay. So yes, refractor telescopes have big lenses rather than mirrors. The downside of that is that your telescope has to be quite long. You have to give the light time to actually focus when it passes through the lens. So the 36-inch refractor, that's pretty much at the limit of how big a refractor could be, and this thing is massive. Do you have any idea how long it is? Like,
oh, sorry, that was a question for me.
Can't believe.
No idea.
Yeah. I mean, it's 10 meters?
School bus sized. Longer than a
I
school.
don't think it's longer than
A school bus.
Yeah, school bus. 57 feet. Thank you. All right. Yeah. So, quite long. They're 57 feet. It's big, but the thing is beautiful to behold. The floor is this big wooden floor that don't know if they'll still raise it up, but when it was being used for research, one of the ways, because it's so big, when you have to observe something that's closer to the horizon, the bottom end of the telescope is just going to fly up, and you either need a ladder or you need to raise the floor to stay level with it. So the floor itself was motorized so that it could rise and lower, and it's so cool to see. It was my first time seeing it in person last night, and I would heartily recommend anyone who can make it out here. If you have any kind of interest in astronomy or historical telescopes, that is one that I would definitely recommend. Must see.
All right, the sunset's really pretty out there. I don't know if you want to try to go see it,
Yeah.
or not. You want to poke your laptop is the best bet, unfortunately. So
Do we have a Wi-Fi extender out there, or?
I know, not for the internet Wi-Fi.
Okay. I'm gonna switch to.
You can also just look. Try looking out the window.
All right, so yeah, this is it, chat. This is what you came here for. The sunset views through a window, through somebody else's computer when he hasn't even made it the full screen yet. Yes. Now, this is our view. Gorgeous area. I absolutely love this part of California. It's so pretty. But yeah, we can't really see the sun out here.
Yeah, it's to the west. I took pictures, but I don't know where I'll be able to show them. Okay, sorry to interrupt you. I think we're so sunset's in about 10 minutes, a little less. About 10 minutes after that or so, we can actually start recording Twilight Flats, I think. Probably a few minutes before that, we'll have Paul, support astronomer Paul, will help explain and guide us through the situation.
Cool.
The two eVscopes are set up. When you were pointing out the window, you might have seen it, maybe not. One of them.
Did we?
Yeah, it's around that corner. You can't really see
I was say I don't think we did.
but they won't be doing anything until it gets dark. So they're just chilling. And yeah, I'll see if I can post pictures of the sunset, but may not happen. Right,
Yeah, no worries.
continue. Sorry.
Well, that was it. I just kind of walked through the questions. So somebody has asked if we could look at JWST. So I figure, if we have some time at the end, that could be one of the targets, maybe, depending on where it is.
With the eVscopes.
Yeah.
Not with the nickel. But,
Yeah.
I don't know where it is.
Yeah, I don't either. I'll have to look that up.
Unistellar ephemeris will tell us.
Okay. And then let's see, what are some of the others? Will you be able to find neat stars and exoplanets with this telescope? So this telescope could definitely find So one of the ways you find exoplanets is by staring at a star and watching the light dip down. Sorry, this was Karen Baisley. So this was the middle schooler. I'm sorry. I should have answered this way long. I hope you're still in chat. Yeah, one of the ways that you can find exoplanets is by looking at a star and just waiting for its light to dip. That is because the sun basically passes in front of the star. I don't know why I'm answering this. You're the exoplanet guy.
I was just going to see how far you got. Yeah.
Go for it. I'm getting my chips.
I'm wearing the shirt.
I know.
Yes. The answer is yes. The nickel can definitely detect detect exoplanets. The eVscopes can detect exoplanets. But just like Ryan was describing, we watched that planet that's orbiting its host star, hundreds or thousands of light years away. We watched that planet pass between us and that star. So it essentially creates a little mini eclipse. It dims the star. The ones that we can detect with the eVscopes dims them by 1%. So we see that star, its brightness decreases by about 1% for a few hours or several hours as the planet moves across the face of the star. That limit of that depth, so 1%, that's usually like a Jupiter-sized planet. So the biggest planet in our solar system is Jupiter. You could fit 10 planet Earths across the face of Jupiter. That's how much wider that planet is. A 1% dimming of the star is like a Jupiter orbiting a sun. It's the equivalent. So that's what we can see with those little 4.5-inch eVscopes. The nickel, you can see much smaller planets. So the bigger your telescope, the more sensitive it is to those dips in the star's brightness. You could probably see more like Neptune-sized planets, maybe even smaller. I don't know exactly what the nickel's performance is, but if they didn't take so long, we would do one tonight. But these planets, unfortunately, often take well over an hour, or usually multiple hours to see, and you don't see anything visually while watching. That 1% dimming is not enough to tell by the naked eye. So you have to do all the analysis, and so the next morning you could tell, but not in real time. Kind of a bummer.
Yeah.
And then there's also, if we could do spectroscopy, we can measure detect planets in other ways. If we had different cameras that blocked the starlight more effectively, we could actually take images of the planets directly. That's what I do actually with my work at UC Berkeley. So there are other ways to detect planets, but I think this transit method is the one that we would use for the nickel.
Yeah. Yeah, and so Joseph ended up, I'll show his comment on screen, talking about the 36-inch Lick refractor. He gave us some fantastic information there. Floor does not, or still raises, but we don't do it for the public. So I think it's very cool. Still, even if the floor doesn't raise, 100% people should come out here, support Lick Observatory. It is a beautiful area. It is a beautiful observatory, and there's a lot of history to it. So hopefully we'll be able to kind of go through and show some of Lick Observatory later on in the evening as well. Phil Y asked, when we submit an observation, what metadata goes with it? So Phil, I'm going to assume you're talking about the eVscope. So going back to, we are also astronomers who look at data that citizen scientists have collected using their digital telescopes, the eVscope, which is a digital telescope made by Unistellar. So that part of the deal with SETI is that we work with Unistellar on that front. Data that gets submitted, we use for science. So I do planetary defense. Tom does exoplanets, like we said. So the metadata, what metadata goes with that? So in general, some of the things that we get, most of the things that we get are the location of the observer. So this is why we can't really ever make that data public without scrubbing some information like that. So the location of the observer, the time of the observation, when was the time of the observation, what the eVscope serial number is, so the identifier for the eVscope, what the target is supposed to be, where the telescope was pointed in terms of right ascension and declination, exposure time, the gain, some of the basic parameters to get an idea, so that you need to know in order to work with the data itself. So yeah, the gain, the exposure time, CCD information. Largely, I think that's the important stuff that we use. The big ones are being sure that we know where an observation was taken, and being sure that we know what the target was, what the target is meant to be, because we don't want to send a planetary defense observation through exoplanets. Doesn't really make sense to have an asteroid being sent through an exoplanet pipeline. We're not going to see much in that case. Katie Hoya on Twitch asked, do they have a gift shop? They do have a gift shop on the observatory, although I haven't seen it open today.
They do indeed, and Katie Hoya has socks from that gift shop.
Oh
yes, so thank you for the question. Yes, they do have a gift shop, and yes, I have socks that I have given to various people.
I have something, I guess, to look forward to. My birthday is coming up.
I think they have more than just socks, but the socks are really nice.
You know, I need socks.
That's true. You do need more socks.
So you can tell when we're starting to struggle for content. Tom had a bet about how long it would be before we brought this up. 2 hours. 2.5. Mm-hmm.
That's not bad.
Not bad. Okay. So
I had the under 30 minutes, so that's not bad.
I have a chronic hatred of buying clothes. So I need all of my socks. Oh God, Frank's here. Ryan's eating already. Yeah, that's me. Look, all right, it's carbo loading. This is going to be an intense night. All right, you got to keep the energy up. But yeah, I despise buying clothes. I despise buying things as long as they're still useful. So all of my socks have holes in the toes. And recently now my shoes have also developed a hole in the toe. They're only a year old, so I don't know why. But so my toe goes through my socks and my shoe at this point. It's not great. So that was the bet. How long would it be before that came up? So Frank says, oh yeah, the gift shop you can order from UCO Lick. That wasn't Frank, that was Joseph. So yeah, you can order there. If you would like to buy your own Lick Observatory socks, as Tom said, I'm sure they have other things. But that is a fantastic Christmas idea.
It is indeed.
The holidays are coming up.
Or birthday. Okay, we just passed. It is sunset officially, I think. And so yeah, we've got a few minutes. I'm setting up the telescope here. The dome is open. We're letting things cool off in there because you want the telescope and the air around it to be near the same temperature as the outside air. It keeps turbulence from that air down a little bit. So the light from the stars and things that you're looking at doesn't have to pass through air that's all wavy and disrupting the light.
We had to talk about adaptive optics.
Sorry.
No, by all means, please. No, I don't know what I'm talking about half the time.
I won't go over it again.
That's why I feel all my friends here.
And then, yeah, we're setting some other things up.
Thank you, Joseph. I appreciate it. Make sure to give me a pair of socks.
Yes. You need socks that don't have holes in them.
No. It's greatly overrated. Right, so I think we are getting set up right now. Just waiting on support astronomer to show up so that we can do our twilight flats, and then once that is done, we will be good to start the night. We might have to wait for it to get a little bit darker before we actually start seeing scientific data. So for those that don't know, twilight, sunset is not just sunset. You have many different stages if you're an astronomer. I guess it's technically twilight, but whatever. That you have to go through before you hit the point where you can hit astronomical twilight and start taking data. So there is the civil twilight, which is the sunset that we're kind of used to, where the sky is still relatively bright, but the sun is below the horizon. Then you have nautical twilight, when the sun is what, like 8 degrees below the horizon?
Wait, nautical is 12.
Nautical is 12.
Civil is 6.
Civil is 6. Okay. Yeah. So that is where I think it's where ships can't like make out the ocean horizon. No, I don't.
Sounds like you're making this up.
I am. I don't know. Yeah, I don't know. I'm sorry.
It's
Look,
nautical for a reason. So it has something to do with that. But
because I used to know this, and I used to be really proud that I knew it.
So
No,
you can see the horizon itself at the same time.
bless. So you can see the stars and the horizon at the same time. Yes. Okay. Excellent. All right. So yes, you can see the stars and the horizon at the same time.
true astronomer.
I'm so bad at my job. Yeah, and then astronomical twilight is when it is dark enough that we can actually start taking observational data. We're not going to get any kind of sun interference.
The sun is 18 degrees
Mhm.
below the horizon. Cool. Yeah, we're just waiting for it a little darker. I guess we can.
I'm gonna get some coffee.
A few minutes we can start taking test exposures. Let's see, what are we sharing right now? I'm not really sharing anything, but stop sharing that and share the view in the dome. Wow. Can you let bring it into the studio thing?
Yep.
For some reason my computer is super slow on that. So okay, yeah. So you can see now the 2 cameras here on the bottom right. We see sunlight, a little bit of leftover sunlight coming in through the dome slit. Telescope is looking out that slit, and you can see the side view pointed in the right direction. It looks like the control software tells us that the telescope is clear of the dome, so the dome's not blocking part of our view. Let's see, we should probably point to a specific direction here.
Wouldn't hurt.
Oh boy. So we will see that. East or west? That's pointed north at the moment, so we might want to point east or west. Is there a particular direction we should point, Paul?
Just keep on working.
Okay, so I should point at 0 hour angle then, right? Okay, wrong computer.
All right. So for those of us just joining, we should probably be more vigilant about that for those who are coming in. I am Ryan, and this is Tom, and we are here with Paul, a support astronomer. We are currently about to take twilight flats. So those are when we point at the sky while it's still relatively bright, so that we can get some measurement of how sensitive our pixels are on the CCD.
And then, so then everything here is good. We can do I'm just gonna record everything. I'll throw it away later if I need to. What recommended exposure time do you suggest?
So let's start with 3 seconds as a test.
3 seconds. B filter. I think everything is good here. The telescope's still moving. We'll wait for it.
Okay, so the telescope appears to be pointed straight up. So we need to go to a depth, probably 20.
Okay. Yeah, we were doing the dome flats since the last, or whatever we were doing. Yeah. Dome flats.
And then hit move to target. Because pointed straight up is partially occulted.
Yeah.
Got it. Yeah, now it is.
The deadman timer is making the noise, I think. We probably need to hit the deadman timer every day.
There.
Back here. I thought that was disabled.
I will disable it.
Okay.
Okay.
That's good that you knew what that sound was. I would have noticed.
Yeah, I didn't realize that's what that was.
Most parts of the telescope involuntarily. Okay.
Okay, we're on target. So let's unrecord. Do not record.
Okay, you want to
3 second test exposure.
Okay.
I'm expecting this to
Go
saturate.
and visit
Okay.
Lick. So Inga Stevenson, yes, locals can go and visit Lick. There are tours. I would suggest checking the website out to see when the tours are. The drive up here is beautiful. The mountains are beautiful, and I would definitely recommend finding out when you have time when a tour is happening. Like last
Not
night.
saturated. See the council.
Last night they had a tour of the observatory, of the building, the main building up here, and especially the big 30 refractor, which is a very huge historical telescope. So yeah, absolutely, I would suggest checking out the website, see when the tours happen, and get out here when you can, because it's definitely a very, very cool place.
So the first image we took was good, but rapidly getting darker.
Phil, yes, we did take dome flats. This is
41, still good.
This is also just a test. So there are reasons that you want to take sky flats versus dome flats. The colors of the sky are a little bit more natural. So sometimes with the white light, you're not going to get the same exact color spread as you would an evening sky. Another thing is that it's really hard to get perfect dome flats. The lamps sometimes will cast shadows because they're just mounted onto the telescope. And the little sheet that we have up there that we could use to take flats, that's slightly curved, and that slight curvature can cause a gradient in the brightness on your flats, which, if you have nothing else, it's not bad enough that you can't use them. But this is more of a precaution than anything else. You'd rather be able to say that you have the different kinds of flats, different kinds of observational kind of ways to fix your observations, and have too much than to not have enough. So this is a bit of a precaution more than anything else, because you only have so much time on a telescope and you can't come back. So it's always better to just do as much as you can. And right now, this is a point in time where we wouldn't even be able to really use the telescope for an actual astronomical observation. So it's not like we're losing anything by doing it.
You want to take them. You want to take your calibrations close in time to your science observations.
Yes.
Not everything is perfectly constant on the telescope. The thermal,
Stuff changes.
the camera sensor is a different temperature one day to the next, slightly, but enough. Things move on the dust particles and stuff. Okay, so that's done with V band. We can switch to V. Spectrograph.
Recorded. It's not recorded the first one at 3 seconds.
Okay. Done, and go. So all of those were bright enough that we just took, even though the sky is fading. So we went down. I say the brightness of our images decreased by about 40% from one image to the last in the V band, but it'll look brighter.
Let's go to 6 seconds and do another again. Record.
Yep.
Record.
Hello, Meg from Malaysia. Wow.
I think I may know Meg through a mutual acquaintance.
Oh, cool.
So, hello.
You also probably know Andrew Brown, because they specifically said, "Hi, Tom, we couldn't agree on a movie, so we're here for you to wow us."
Hey, Andrew. Shout out to the Star Pigs and the Flying Pigs, my soccer team. Soccer teams. Alameda Athletic, I'll throw that in there too. Shout out. All right, how are we doing here? We're 40,000 counts. That's great. Hopefully it stays high enough.
Just get into the game.
Ryan, one of us should be logging these. I'll try to
Right.
catch up on the observing log.
Okay, I can say log after that.
post a particle and then it will still.
Yeah, it's turning up.
You won't need to do the deadline timer anymore. So if you get shut down, it's for the environment.
All right.
Got it. Yeah. Cool. Well, this is better than it was last night. So.
Yeah.
13,000.
So the last one. One more should be out there, I think, right?
That was for this.
Yeah, this should be fine. Okay. So then what? 6 seconds also for the R band, or do we go?
Yeah, we'll start. That'll be our starting guess.
Right.
What were the numbers for the biases? 1083. That sounds right. And we took 10 of those?
Yes. Yes.
Okay. So, currently, what we should have been, we're bad astronomers. What we should have been doing, we were distracted, is keeping a log of everything that we have, all of the observations and of the correction images we have taken. So we are updating that now. We want to make sure that we know which images we took were the biases, which ones were the flat fields, the dome flats, twilight flats. Catching up on that currently. So we took flat field.
Yeah, we can also go back and do this later.
Yeah, that was 5, right? For
yeah, 29,000. So 9 seconds.
Start giving us 29,000 now.
Yeah.
Yeah, okay, we can go in 9 seconds. It's going to start fading quite quickly.
Yep. So one of the things about twilight flats, sky flats, is that twilight doesn't last for very long. You've gotta be quick. So this is one of those times where it is really, you're racing against the clock to try and beat, yeah, to try and beat the sky.
Well, you always want to be taking data if you can with a telescope.
Yep.
Always
Maximize your time.
My PhD advisor used to say, "Always be exposing." Like, is that Glenn Ross?
Yeah, but I don't know if I would use that phrase.
Well, in the right context. Up to 35. I did 2 here just in case it gets really faint. Can change it again. Probably go up to 11 seconds. Yeah, that's at 30,000. So maybe bump it up. You say 11. Yeah. Probably be 12.
Okay. Tom's dad has been endlessly plugging this event for the whole week. We are all here, and we got you on big speakers in the backyard, so the whole neighborhood is listening.
Wow, that's a little more pressure than I expected.
I didn't even tell my family.
Well,
I was like, I don't want them here.
This is what happens when you're an only child. So thank you, everyone, for watching. Appreciate it. We'll hopefully make this entertaining for you. We will eventually look at something more than just
the sky,
the blank sky, I think, weather allowing.
What did I say? Yeah, you really jinxed us on that one.
The eVscopes for sure. I mean, it is clear.
Yeah.
As I was outside, there wasn't a cloud in the sky. That's definitely jinxing us.
Yeah.
But you know, as for the eVscopes, will definitely show us some cool stuff starting pretty soon. 8:15 is our first target. 30,000 counts seems okay. Yeah, 8:15 is supposed to be our first target. I think we'll probably just describe the eVscopes instead of go visiting them. It's just a little tough to get a good stream connection from outside.
Yep.
But we're done with this. I will go down. Let's see, we've got one more filter to do. Right. I will go down and turn them on and start calibrating them.
Yeah.
They're much quicker. We don't do flats. We do take darks, but we will do that after the science observations. And
Keep it the same.
okay. So even though the sky is fading, the filters we're looking at are getting redder, looking at redder and redder light, and the sky is staying a little brighter in the long wavelength. So you normally go from shortest wavelengths to longest wavelengths when you do this Twilight Sky process, because the sky gets darker in blue colors faster than it does in red colors.
Andrew Brown asked, is AI-based tooling changing how you work? Not yet, for me at least. I don't think for you either. That's something that probably will in the future. AI, basically machine learning algorithms to reduce your data. So that's definitely something that I think is on the horizon for us. But at the moment, we haven't implemented anything directly into our pipelines. But that is something, working on a pipeline to observe satellites. And that's something that I think we could probably do there. Having an algorithm that can determine whether or not there is a streak on your image is a very good way out of like 400 images. It seems like a perfect method for machine learning. I think that would definitely be something that we could do. Can you describe some of the methods that you use to analyze raw data? From Paul Hawkins. So we will talk a bit about photometry, I think, in a little bit, and how that works. That was actually one of the questions that I had prepped for when we have a Q&A later. But yeah, the basic idea is that you have an image of some amount of light, and not all of it is the light of what you want. So you have to decide, how do I get rid of all of the bad parts of this image that are polluting the light that I want, that I actually want to know about. So we talked a lot already about biases and flat fields, and even talked about dark current and dark frames. Those are all instances of how we go about removing noise, essentially, from an image. Noise being light that doesn't necessarily represent the actual reality of the sky of what we were looking at. So a lot of the methods basically are about trying to quantify how that noise works. So taking bias images to determine how your CCD is reading out, what kind of voltage it's adding to its measurements. The flat fields determining how sensitive each pixel is, so that you can correct for that. But then once you've done all of that, assuming you have pulled all of that noise out, what do you do with the actual image? And it really depends on what you're looking for. So if we wanted to find how bright a target was compared to some other stars, we would simply put like a circle down around the asteroid or the star that we want to look at. Make sure that that circle captures everything, all of the light from that asteroid. And you can measure, okay, well, you know that it has this much, we have this many counts. So pixels, the CCD basically counts things in terms of the charge, and we convert that to counts. It gets a little confusing, but basically you say, I have this many counts, this much light from my asteroid, and then you can compare it to a star in the field in that same image, and you can say, okay, well, I'm going to sit down and get this much light for this star. But then the way that you make that comparison is a lot of stars out there already have known brightnesses or magnitudes.
All right, let me interrupt you, Ryan.
Oh, yep, sorry.
All right, so we're done with flats. Turn tracking on, Paul. Is that what you're saying? TV's going to turn off on us. All right, so we're going to start tracking this. Let the telescope start tracking the sky.
Yep.
And yeah, we're done with calibrations. And so just Paul, before you head off, do we need to wait until it gets darker to do the pointing and centering, or can we just find a star and go?
Yeah, you can find a bright star and go for it.
Okay.
All right. As soon as you can see the star against the background, you should be able to point it.
All right.
Excellent.
Do that.
Thanks so
Great,
much.
Thank you very much.
It's cool. You've got a problem.
Yeah.
Got it. Yes. All right. Cool. Yeah, sorry to interrupt you, but
Yeah,
we'll
it's fine.
move on because it is getting dark.
Yeah. So, Paul, we will get back to your question later. I think that how do we go about actually getting information out of the data that we've taken is very important. It's not something that gets talked about a lot for how astronomers do their jobs. So we will get back to that.
Yeah. All right. So let's see. Where are we? We're at RNA 17 right now.
Mm-hmm.
So we can.
It's a focusing star.
That is a focusing star. Thank you.
Yep. So right now we're currently in one of the other VNC screens. If you were here earlier, you may remember when we were talking about the screen that controls the nickel telescope and the dome. There's a little list of stars that we can point at later on. This is now later on. We are looking for a star that we can point the telescope to that's going to be very bright. Not so we can take data of it, but so that we can line up the telescope accurately. So the telescope's already pretty close. Whenever we want to send it somewhere, it's going to do a pretty good job of pointing in the part of the sky that we want to point it at. But we want it to be very, very precise. We want to try and make sure that whatever we're pointing at is going to end up in the middle of the screen rather than kind of off in the corner. So the way we do that is by going to a pointing star, which is a very bright star where you know where the RA index is. And you know, usually it's in a field that it's the brightest thing around and there's not a whole lot else. So you can't mistake it for another star. So that's what we're going to do now is we're picking out a pointing star.
Why don't you do this?
Okay.
We'll follow along in the notes.
What?
The morning.
Oh, okay. We're just going to move to the target.
Yeah, we moved already.
Oh, we already moved?
Yes.
Oh.
I don't know. It might be that bright star to the top right.
Uh,
No, the right. Top right.
top right. Oh, yeah.
Maybe.
Well, I'm going to say don't record and just see what we see. But I'm going to
take a 3-second exposure.
Yeah, I'm moving to V. So, okay, yeah. So what we're going to do is we've already moved the telescope to a star in the field. I'm looking at the wrong screen all the time. In the field. And now we're going to take just a short exposure to see where it is, see if we can even see it. So this one, we don't really care about what the exposure is going to be named because it doesn't matter. We're not saving this. This is just so that we can kind of figure out where the telescope is pointed. And then we want to do offset telescope. Okay, so right now it's reading out. We're gonna see in a minute if we're in the, hey, look at that bad boy, beautiful, and it even looks like it's pretty close to the center, so we don't even have to do a whole lot.
Yeah.
Ooh,
So
look at that.
Can you mouse and see or change the stretch a little bit?
I could. I don't know if I will.
There you go. Just so you can see the center. That's good enough. That's good enough. Just
Okay.
zoom in.
Okay. All right, so the way that we actually go about doing this, we try and get to as close to the center as we can on this star. Ooh, wow, I'm really messing with the stretch. You determine, get pretty close to the center of the star, and then we look at this row and column value in this window right here. That's telling us where our mouse currently is. And so what we want to do is get this into the center of the screen. And so the way that,
Do you want to even adjust this?
I don't know, it's actually pretty close. So the way that we see if it's in the center of the screen is we see that row and column. We know earlier we talked about the imaging camera on the nickel. It is a 2048 by 2048 CCD. So it's got 2048 pixels on each side. So we know that this star, which should be in the middle, is at pixel 994 and column 974. How much would we even have to nudge that?
So I wouldn't worry about the rho, which is the y-axis direction. If we want to nudge it in x, that would be a 9 arcsecond nudge. So we could move it 9 arcsecond. Well, before you do anything, which way is up and which way is down? So just mouse around. So left is higher value, and so we want to move the star to the left, which means we move the telescope to the right.
Yep, to the west.
Yeah, so we're gonna.
You said 9?
9 arcseconds.
Okay.
It's 50 pixels, so 0.18 arcseconds per pixel.
So
then,
Tom has already done the math on this. The way that we go about it is, determining how many pixels away is it, and then we know how much of the sky that translates to. So
this is a very tiny nudge of the telescope.
all right. So I think the telescope has
moved.
Yeah, telescope's already moved. Now set. So we're just going to take another very quick exposure.
And we're close enough in the y direction that we didn't even really need to nudge it. Hopefully, see now if we moved in the right direction or if we got it backwards.
Haha. Ooh.
It's fine. It's resetting.
Yeah.
We got that right. Check.
Hey.
Just wait until it's finished.
Yeah.
Okay. Nope.
Whoop. I did
You're
it.
killing me, Smalls.
And I'm gonna continue to do it. You're stuck with me all night.
Oh my god. Try clicking linear and log, just redo it. Or go back to log again. All right, color control, other.
I did it.
All right, let's just see where it is. I think it's good.
All right,
we're good.
Yes.
So
all right.
We didn't move all the way there, but we got pretty close.
Yeah. So we don't have to be perfect. We just have to be good. Close enough.
Okay. So now we need a focusing star.
Mm-hmm.
We will do. So we want to pick a star close to where the telescope is now.
Yep.
At the meridian.
This one looks pretty good. Yeah. Send that to Foco. Then we will move to the target.
You can do in the cores box. Can you hit send object name as well? All right. There. We record these, right?
No.
We don't record.
No.
But we just expose and.
Yeah.
Okay.
This is just to make sure that everything is working.
Yeah, so now we need to make sure the telescope's focused. We know that when we point to a target, it'll put it in the center of the image. Now we need to make sure that that image will be focused. So we're going to point to another bright star, one that's not quite as bright as this one, because this one was so bright that we fully saturated the image, meaning that we couldn't actually see the brightest pixels because they maxed out.
Mm-hmm.
You can think of a pixel like a bucket that's collecting rain. And so at a certain point, the rain fills up the bucket. Did you already explain this?
No.
The bucket, and any more water that falls in just overflows. And so that's what saturation is. The pixels can't take any more photons without overflowing. So now we will...
I'm just checking to see that the star is in the field.
Yeah. And what we'll do is we'll intentionally, we know what you can pull up the focus control while we're waiting. We know what the kind of typical focus setting is. And so we'll intentionally defocus the telescope from there.
Mm-hmm.
And then progressively change the telescope focus a little bit at a time and record the star at each focus level. And basically what we're doing is we're moving the secondary mirror of the telescope first, either away from the primary and then towards it. Yeah, let's just say that. We move the secondary mirror away from the primary mirror, and then we slowly move it closer and closer and closer until that secondary mirror is just the right distance to keep the stars in focus. Okay, I think are we good? Are we saturated here?
Let's see. No.
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 So we
Excellent.
could stick with that. We can even
Up it a little bit.
up it. So I think last time we did 110 seconds total.
That was total,
And
yeah.
we
But
paused
10
it.
second, 10-second exposures each. All right, and that seems reasonable. Okay.
Wait, 110.
Oh, you're right. All right. We got 10 minutes to do this.
Yep.
Okay. All right. So walk me through again how we did
Yes.
this last time.
I will find the notes. Okay, so we set a long exposure. We defocus by -15. So you would go to, yep, so 353. And then hit go. And then we'll start an exposure and pause it after 10 seconds.
Mm-hmm.
Then we will
Nudge. First one by 10. Or no, the first one
it's
by.
the shift, yeah.
Yeah.
So the first one will be by 30 arc seconds, and then we do 20 after that.
Okay. All right.
And we want to make sure there's no nearby stars, so any direction we go is probably good.
Yep.
Okay.
All right.
So
So
we're good. So start and then pause in 10 seconds. So we'll see how close Ryan can get to 10 seconds and pause the image.
right on time.
It doesn't really matter. It's
I missed it last night. I tried. I got so close.
just fun to see. If anyone remembers a very old commercial with Jerry Seinfeld and the perfect pump at a gas station. Okay. All right. So that's the first
So we
exposure.
go.
So now we will need to increment. Oh, you did already.
I did.
Increment the focus.
I know what I'm about.
We move the telescope. We nudge it a tiny bit.
Mm-hmm. Once it's settled, we start again.
And so what we're doing in the next 10 seconds of exposure is we'll put the star farther down on our image by about.
So close.
You're doing great.
Thanks.
Increment the focus. Good.
Yep.
Wait.
I'm not clicking it yet. I know what I'm about.
You got it. So we'll do this a bunch of times. We're going to go through what we assume is the best focus and kind of out the other side. So we'll intentionally defocus in the other direction. And what we'll see is the star will start out kind of wide and blurry, and then it'll get sharper and smaller, and then it will get wider and blurrier again. And we have some built-in software here that will measure just how wide that star is in every single one of those recordings, basically, and it'll fit a model. So it'll do some math and figure out, okay, based on these 9 measurements, what's the approximate best focus level? And then that's one we'll go with for the rest of the night. We don't really expect the focus to change throughout the night significantly. It can, as the mirrors change temperature, or if something goes wrong, but
In general, you don't expect it to be a very large change.
yeah, usually do it once and you're good.
Socks for both of us.
And then we don't even need to do the guiding because the comet's
Yeah, it's gonna move. So.
cool. I should probably look up the ephemeris.
We got there. I'm a winner.
Highlight of the night so far.
You're buying my breakfast tomorrow morning.
All right, that's fair.
Yes. Means I don't have to pay for it. It's my favorite thing in the world. All right. We only did like 8, right? 8 exposures last
Yeah,
night.
so we went to plus 20. So you're probably one more. We were at 368 to begin with, so maybe do one more after this, and then we're good.
All right.
Did you click that while you were exposing?
No.
Oh, it's paused. Okay,
Mhm.
sorry.
Yeah, I did that just to screw everything up.
Multitasking and not paying attention. All right, so while Ryan's doing this, I'm going to look up the location of our first target, which is a comet, Comet E1. And we're running a little bit behind.
You said 2 more? Is that right? Or 3 more?
This should be the. Are we at 389 right now? Yeah, we're good.
Okay.
This should be the last one. So now you got to do the
Stop
whole.
and read out.
Yeah, all right. So let's stop and read
All
out.
right. Yes, and while we go, Neil Yablonsky, you asked for unistellar telescopes. Would it help if we took twilight flats? In general, it's not necessary, I don't think. We
Okay. All right.
we don't expect that it basically the precision that we're working at isn't going to be enough that the twilight flats are 100% necessary. And it's really more we just don't have the pipeline set up yet to do something like twilight flats.
All right. Control GUI. We got to open that ITV
Yes.
window.
So this is what we just took what we spent all that time making was this beautiful performance art.
It might be more if you click to center that in the middle one.
What?
Click here, center there. I think there are more dots. Yeah. So we started off
Quite
pretty
donut-y.
pretty off focus, I think, or pretty close. I mean, no, yeah, we started off pretty off focus, but we'll see. Okay, so now we do
Pixstellar.
erase focus data,
Oh, right.
and then we do Pixstellar stat loc. Click on the center of the first star, so the top one or the bottom one, whatever. Bottom one.
Do stats.
Do stats.
Add to focus.
Move that out of the way.
Scooch.
Yeah, add focus data, and that one should have been it's 368 minus 15, so
353.
So make sure to get this right, and do not hit enter. 353.
Yeah, last night.
Wait. That's 354.
I'm working on it. The last night when we were doing this, we got through 7 out of the 8 stars, the data taken to do this. We got 7 out of the 8 done. And then I accidentally pressed on the keyboard enter rather than specifically pressing the OK button with my mouse. Oh, and it did not enjoy that. It was a very upset little piece of software. This was 358. So we ended up having to redo the whole thing, which was actually quite funny. Because even then, it still was so upset that it didn't really work. All right, that was 358. This is 363. So you can see over here in the corner, this little stat window. This is how we're fitting. It's basically taking the information that we're giving it about the stars and the focus that we were at when we got that. We took the image of that star, and it's fitting the data, and it's going to spit out at the end of this what focus is the best. And it will, because it's doing a fit, it's not like we had to be on that particular focus. We didn't have to be on the specific number. It's just going to figure out, okay, based on these 8 points, here is the best one. Here's the best number to pick for your focus. And so just because we are not doing this as often as we should, for those who are joining us, just to update you, thank you for joining us. My name is Ryan, and this is Tom. We are astronomers with the SETI Institute and Unistellar, and Tom with Berkeley. And this is just kind of a hangout stream, just to show you we're working on we have a big telescope tonight, the nickel telescope, the 1 meter at Lick Observatory. And this is really just a night to kind of show you what it's like to be an astronomer and to do what we are doing. And what a typical night like for us is. So 1, 2, 3, 4, 5. I nearly lost count of which star I was on because I was doing the greeting. but it was worth it. So 378. No! This is the other thing, is the mouse has to be on the window. We were going to put a little counter to see how many times my mouse slipped off of the window as I was trying to type something in.
I've lost track.
Yeah, I've already lost track as well.
Assuming this goes well, that's okay.
I was just double checking what our last one was, which was 389. So, or 388. Yeah, it went to
We
388.
get off by one somewhere. You must have. We were doing increments of 5, so it must
Yeah.
have, moved a little farther on its own. I think it's okay.
Yeah.
All right, and then
All right. So we have that.
let's see. We should see the plot. Oh, looks pretty close.
Yeah, I'm thinking it's this again, what we decided.
So 385.
Yeah.
Right, because so the last one was 389. The one before was 383.
Mhm.
And so 384, 385 seems about right.
Yep.
All right, let's do 385.
Cool. And we will change. Whoops, we will not change. We will go. And then we will change.
Yeah. Okay. Okay, so we have the Comet info. Do you want this in here, or do you want to pull it up yourself? Comet info.
Common info?
I have it. If you
Okay,
want it, just
yeah, I don't
use
have
this. I don't know. Make sure those are all the columns.
There. What the heck?
I checked some other ones, so you might want to scroll up and change them.
You got a parent? Oh, you got a parent. Okay, fine. Whatever. A parent works. Parent's good.
I figured that is more relevant.
It is more relevant. I don't need to.
Ariel is here.
Who?
Our guest.
Never heard of
So
it.
let me. You may need to. Let's.
What am I looking for? That's great. What comment is this?
C2023 E1.
Ah, yes. Rolls right off the tongue. So we are getting ready. Our first target is going to be C2023 E1. It is a comet. We are getting this at the behest of our friend and colleague. What time is it? It's 15. Okay. Yeah, I bet you are. Your poor computer is just so stressed. It's so put upon. 08, 40. So right now we have the coordinates pulled up on another computer. I am inputting them into the interface, which we're not sharing. We're sharing the other one. So I'm putting them, basically giving them to the telescope and saying, hey, please move here. And then what we're going to do is, because this is a comet, so one of the nice things about like stars and galaxies, things that are far away, is they move with the sky. They don't actually, they are moving, but they're so far away that you can pretty much just say they're not moving. At least for like a single night observation, you don't have to worry about it. That becomes much harder to do when you're looking at stuff that's in the solar system. Because it does move, often quite fast. So usually you can just have the telescope turn on tracking and match the sky for some of those distant objects. But one of the things we have to do when we are picking targets in the solar system is tell the telescope, hey, don't match the sky. Don't move with the sky. This thing actually is moving a bit faster. So instead, we would prefer it if you would move at this certain speed. And so we have to input how fast the object is moving.
All right, I'm going to go to the eVscopes. Are you good here on your own, or do you need
Sure. Are we bringing someone in, or?
So Ariel's here
Yeah.
waiting. I think once we get
set up,
on target, then
Okay,
I'll wait.
whenever you want. I'll just wait for you to come back because
I'm gonna be a few minutes, so
Oh, okay.
whenever you're ready.
I don't
You're
know.
on your own.
I don't know what I'm doing. Oh,
I have our notes that are back.
you have notes?
in the-
You got notes?
Nick tab is our notes from last night.
I didn't get notes. All right, so we are moving to our target now. We need to dismiss this window, close this window, and that window can stay. We're moving to our target now. Our guiders, gross. We out of focus, but that's fine. We don't need the guider. So I'm just going to take a quick little test exposure. Let's see if we can see something. It'll be neat. And if we can't, it's because comets are bad. All right. So while we're waiting on that to show up, and actually I don't know how faint this might, we might need a larger exposure time. We'll see. Well, that's something. Oh, never mind. That's not. All right. Well, this is. How bright is this look at? Supposed to be? Oh, this is supposed to be like 16th magnitude. Okay, yeah. So. Is this actually? Am I picking the right time? I feel like I'm not. I moved to a part of the sky that doesn't make any sense. Thomas, friends of Thomas. He vexes me. He vexes me greatly. Tell him I said that. Thank you. 3:22 is what the time is in UTC. Yeah, that's why we're not seeing anything. I put in the absolute worst coordinates imaginable. So that is also part of being an astronomer, is doing stupid things like this, where you're like, why can't I see the target? And then you check and you're like, oh, because I'm not pointing at the target. That'll do it. 22, 07, 32.73, 03. 0334.53. Yeah, we're just a few arc minutes off. So we're not that far away, but we're also not close. Oh, thank you, Katie. And let's set target tracking back on once the telescope stops moving. Telescope shouldn't have had to move that far. Why are you moving that far? Just don't move that far. It's not hard. Ow. All right, so we are now at the target again. I'm going to try just a quick. We'll try 20-second exposure because I think comets are not great. And just so people are aware, I am joking when I say comets are not great. I'm purely saying that to get the goat of my friend who likes comets a lot. Also, comets aren't great. See, right. It's like 13.5 14th magnitude. Well, Ariel, it can't be 13.5 or 14th magnitude because JPL is saying 16. So, seems bad. Seems incorrect. JPL lies. JPL has never lied. They will destroy you for saying such things. Hey, that's a goober. Why are we so wildly out of focus? We just did this. Hmm. I see. All right, so clearly whatever we did for focusing did not work. Sorry, Ariel. I tried. Change script. So why didn't that work? What do we do? What do we do? What do we do? So yeah, this is again part of being an astronomer, is being vexed by the telescope doing silly things. Yeah. So I'm just gonna try something. We're gonna see what happens. So I'm also kind of cheating when I try and do this because I can see on another screen the guider, the guiding telescope. I think what happened was we got it backwards on which star we were looking at was which focus count, focus number. I think we accidentally measured it the other way around. And it turns out we were going from reasonably focused to very much not focused. So let's test. Let's just test this. Let's see what happens. Let's see what happens. So what are the major differences between optical and radio astronomy? And can you set up very large optical arrays like radio telescopes? It is a good question. So radio, there's a lot that goes into radio astronomy that you can't really do for optical. I'm not the best radio astronomer. Radio astronomy is more like magic to me, because yeah, you have these giant discs, these giant dishes. Yeah, I think that's it, but it's surprising that we're so very far off. Who is messaging me? Probably won't fit the launch. Oh yeah. Okay, so what was I saying? Yes, so radio astronomy in general, radio waves pass through a lot more stuff. So you have to make your dishes really big, and you have to really make some very specific kinds of detectors for radio astronomy. So like your CCD cameras, when Tom was talking earlier, for those who were here, he mentioned that if you want to try and catch infrared light, which is a longer wavelength than optical, that if you don't build your CCD with the right materials or make it right, the infrared light will just pass right through your CCD, and you won't ever know, it won't ever count any of the photons there that it saw. So radio astronomy is the same way. You have to very specifically build a detector for radio astronomy. And a lot of that is the same way as like radio antenna. A lot of the detectors are similar, where they're just like very well-designed radio antenna for different wavelengths of radio waves. One of the cool things about radio astronomy is that you can set up, you can set up different radio observatories, different dishes. And if you know precisely how far apart they are, you can do what's called interferometry, which lets you basically act like those two radio dishes working together. Oscilloscope versus an oscilloscope. So yeah, those two dishes are working together, and the combined effect of having those two dishes observing at the same spot or observing the same thing, when you know their distance apart, you get a really, really improved image, almost like you had an observatory dish, a telescope dish that was the size of the distance between the two dishes that you're using. So it massive. If you have two radio telescopes on either side of the planet and you know very precisely how far apart they are, you could have technically a radio dish the size of the planet to observe with. The problem with interferometry, and I only say problem because I guess it's really like the difficulty with it, is you have to know that the preciseness that you have to know the distance between your two observatories scales with the wavelength or the frequency. So radio waves are very, very long wavelength, very low frequency light. And so you need to know how far apart the two dishes are in on the order of like a meter, something around that area. The longer the wavelength, the more imprecise you can be. 10 meters, kilometer, something like that. But to do optical interferometry is truly difficult. There's a lot of things that you'd have to like pull apart, but one very big one is that you'd have to know precisely how far apart the two observatories are on the order of like a micrometer, which you're not going to be able to get those observatories very far apart if you're able to accurately get the distance that well. So in practice, you can't do you can't do a lot of the same stuff that you do for radio astronomy with optical astronomy. It's tough. It would be very tough. People have tried, and I think it's just there's a lot of dragons. It's doable, but there's a lot of dragons you got to slay to get there. So what I am trying to do and failing to do at the moment, because I'm being pulled on many different directions, is determine if that is our comet. So actually, what I can do is, I guess I could just bring in Ariel. That would be fun. So what I can do is to take some of the heat off me so I can think a little bit. Tectonic shift will be enough to really screw up your optical interferometry. Any kind of earthquake, and suddenly you're like, crap, we got to redo this. So what I think we're going to do is I'm going to bring in a guest, assuming that she's okay with that. So some say that she is the Ice Queen of DC. Others say that I was supposed to come up with some bit for this. I actually didn't. I'm sorry. I just didn't have time. Others say that ice on comets don't even exist, and she beat that person. And this is a kid's stream. This is still for family in Hacky Sack. She absolutely devastated them. Please give it up for Ariel Grakowski, the Comet Extraordinaire.
Hello.
Hello. So our focusing didn't work.
Why?
I'm thinking we went the wrong direction because I put us at 380 and we were like donuts. So I did this just to get it a little bit better. But hi, Ariel.
Hi, Ariel.
I was supposed to come up with a Top Gun-like intro, and I forgot.
Top Gun. Top Gear.
Top Gear. Yeah, that's what I meant. So right now I'm trying to figure out, is that a comet or is that not? Wait, why is Ariel gone again? Ariel's gone again. No. I kicked her. I did, but I kicked her off because your computer is so far behind. Hi, Ariel. I'm sorry.
Hi.
eVscope, I think, has it. So Yeah.
eVscope has it. Yeah, I can't tell from here if we're on it or not.
You are here.
Oh,
All right. I'm muted. I'm done.
Talk again, Ariel.
hello.
Yes, we can hear you.
Yeah.
Okay.
So, is it true? Did you meet that guy who was telling you that there is no ice on comets?
I beat him in hacky sack. Yes.
Devastating loss for any person of culture. Yeah, we did lose our guy. Thanks, Cider. We did. We lost Ariel for a minute. I would say that's definitely technical issues and not astronomer incompetence. I promise.
Yeah, I think so.
Okay. So while Tom is getting set up and while I am desperately trying to figure out what we're seeing,
Mhm.
I'm going to try and go back and fix our focus. Can you tell us a little bit about what a comet is? Just a quick summary. Oh.
Yeah, sure. So I am a postdoctoral fellow at the SETI Institute, and I work with Unistellar on their Comet program. So I'm the Comet expert at Unistellar. And so basically, I'm interested in comets because they are these leftovers from when our solar system first formed. They're these small rocky bodies and icy bodies, kind of like asteroids, but with more ice. And they come from much farther away places than asteroids do. The asteroids occupy the asteroid belt, which is between Mars and Jupiter. But the comets come from places much farther, like the Kuiper belt, which is beyond all the planets, and the Oort cloud, which is even farther away. And so sometimes these objects get perturbed, they collide with each other, or they have some sort of interaction, and they get gravitationally perturbed and their orbits changed. And that's why they'll become elliptical in their orbit, and they'll come to the inner solar system. And that's when we can see them. So they really aren't anything special until they do come into the inner solar system, until they start getting closer to the sun. When they heat up, those ices turn into gas through a process called sublimation. And that's when we see something called a coma or a tail, which the classic comet, if you're thinking about a comet, any picture you've seen of a comet, you see kind of these massive tails that go across the sky. That's all this water ice gas. So yeah, that's pretty much what a comet is in a nutshell. Very icy.
So this comet that we're presumably looking at that we haven't started yet, so I'm off the screen. What is there anything that makes it special, or is it just like another comet?
Yeah, it's kind of a typical comet, to be honest. Okay. But the thing about this one is its classification. It's a Halley type comet, which is also not rare or anything. But I do think it's interesting to note the type of comets. In general, in my head, I divide comets into short period comets and long period comets. And in the comet world, that's arbitrarily defined as if its period is less than 200 years or more than 200 years. And then in my head, I just kind of say, okay, if it's a short period comet, it originated from the Kuiper belt. And if it's a long period comet, it originated from the Oort cloud. So E1 is kind of a weird one in the sense that its orbital period is 85 years. So it's a short period comet, but it doesn't come from the Kuiper belt. It actually comes from the Oort cloud. So it comes from much farther away, where it can have these ices that are much more volatile for a much longer period of time in its life. So it's kind of cool when we get Halley type comets. They tend to be bright. I mean, you might think of Comet Halley, right? Because they have all these ices and they get on these highly elliptical orbits. So they brighten fast because they are approaching the sun pretty quickly, and they are heating up quicker than other comets might. And so they might be hyperactive. They might lose those gases really fast and become really bright. And so when this comet was first discovered in March of this year, people were excited because they were thinking this could brighten quick and something could happen, like maybe it could outburst, or maybe it'll become super volatile, but then lose all its gases and then kind of peter out. So that's why everyone wanted to watch this early on.
Excellent. That's very cool. We have a question from Absorbing Underwear on Twitch. How long do comets last until they've ejected all of their matter?
That's a really good question. Yeah, no, it's like millions of years, and if you just consider that they lose their mass via sublimation. So every time they get close to the sun, they sublimate, they make coma in the tail. They are losing mass when they're doing that. But they're losing actually a really small percentage of their mass. So it takes thousands to millions of years for a comet to just disintegrate because of that alone.
Oh,
But
yeah.
in the recent like years, decades, people have found that comets are actually disappearing for more catastrophic reasons, like they outburst or they fragment. And it's kind of same thing. So they're sublimating, they have all this pressure going on, this gas pressure buildup that can cause them to outburst. They might be spinning too fast and break apart. And that causes them to lose mass a lot faster than sublimation alone. So it's a good question because we actually don't really know the answer. And that's what comet scientists are looking to answer right now, is how much this outburst effect affects the lifetime of a comet. It's definitely going to be shorter than we thought before. But yeah, sublimation alone is just kind of a little bit.
Interesting. And so these comets are really, like you were saying, are very primordial objects. They were forming when the solar system itself was formed. It almost sounds a little sad, honestly. They formed these ancient things, and then they come in, and a lot of times they just get destroyed.
Yeah.
But that I can see how that would be a very good window into the early solar system, being able to understand comets. Is that right?
Yeah, totally. When the sublimation starts happening, I think there's a lot of comet astronomers that are really excited to get the spectra of the comet. They want to know exactly what ices and elements are in there, because some of those ices, for some of these comets, it's going to be their first time they've ever visited the inner solar system. In the case of E1, it's been here before. And so we probably have had chances to see what those ices are. But in the case of some comets, it'll be our first time ever to see what's inside the comet. And then if something like an outburst happens, then we kind of get even a deeper peek into the interior of the comet, or at least deeper into the mantle of that comet.
Oh, very cool. So we have another question from Paul Hawkins. He asked if comas are always the product of ice sublimation. Are there any other effects that might cause a coma?
Yeah, good question. So when the ice sublimates, it's not just the gas that you're seeing. That gas drags dust with it. So comets are also rocky, and they have these small bits of dust or pebbles on their surface as well. And that sublimation drags that dust off. And so actually what you're probably seeing most of the time, the brightness of a comet is due to that dust, because dust particles are bigger than gas particles. They reflect sunlight a lot easier. So when a comet gets really bright, that's really what's driving it, is that dust, that rock. But when you're seeing like the colors of a comet, sometimes you see pictures of like E1, for example, there's pictures online of it being very green. That's the gas affecting that color, different types of carbon gases.
So if I were to look at some of these comets, is that green? So I know, sometimes we like to see what's out in the sky, and you can spice things up with false color. Are these comets actually green? If you were to see them with your naked eye, would they look green?
Yeah, they're actually green. So these elements are vibrating at a wavelength that is green. So there's the most commonly attributed to the green is C2, or diatomic carbon, so 2 carbon atoms. The way they interact with the sun and reflects to us, into our telescopes, into our eyes, if we were able to have eyes large enough to capture that amount of light, would be green. And there's also CN, carbon nitrogen, which kind of leans more blue. So you kind of get these bluish colors. It's also sodium, which leans more yellow. And that is just how it vibrates and how your eye sees it. So we should be able to see the colors if our eyes were as big as these telescopes. Or if it's bright enough for us to see.
I was saying, I'm glad we do not have telescope-sized eyes. I feel like that would be
I don't know.
in most part.
I think I'd like that.
Broken Symmetry has asked on Twitch if the comets that swing back out, if they swing back out to the Oort cloud, so the ones that survive, do they go all the way back up to the Oort cloud, or are they now bound closer into the inner parts of the solar system?
Yeah, typically the ones that come from the Oort cloud and stay in the solar system are bound much closer than the Oort cloud. A lot of the times, the long period comets end up on hyperbolic orbits. So they interact with the planets, usually Jupiter the most, and the sun. And they come in and then they go out forever. It's hard to get them back in if they're going to go that far.
Mm-hmm.
But yeah, that's a good question. But there are some. There are
Yeah.
some.
All right. Well, we have a question from Raw still that I think we can answer as well. It's not necessarily comet related. Raw asks on YouTube if there are any green stars. I see your comment, Phil. We'll get back to you in just a second. Are there any green stars? So I know the answer to this as well. If you don't want to comment on it.
Yeah, you go for it.
Okay.
I know there are different color stars.
Technically, our sun is green. There are green stars. But the way that humans evolved, we evolved to detect light at the optical wavelength because that is what our sun puts out a lot of. And actually our sun peaks in the green. So the way we have evolved is that basically the black body radiation, when you have light of the different colors around the green, where it peaks in the green, we see that as white. So there are green stars in that sense, but because of the way that humans have evolved and the way that we have evolved our eyes to detect light, because of the way that stars put out light in this very predictable way, they don't ever just put out light at a single wavelength, but this broad spectrum, green stars look white to us for the most part. You also have some instances where there are really big stars that are putting out a lot of light and that look white as well. That's a different case. But stars like our sun in general are the green stars. So Phil Y, also on YouTube, moving back to comets, has asked, what is the impetus for a comet from the Kuiper Belt or the Oort cloud to enter the inner solar system? Could there be different things that cause that? Is it always the same kind of instance?
There can be different things. I think one of the most obvious things is a collision. However, in the early solar system, collisions were a lot more common because there's a lot more little stuff before it all coalesced and kind of became more stable. And there's less collisions in general now, but still happening a lot, especially in the belts like the Kuiper Belt and the Oort cloud. So a collision can just knock something off into a different orbit. Also, just gravitational interactions. So there could be a sort of three-body interaction of some large Kuiper Belt objects that's just perturb the one of the objects just a little bit, and one gets sent in and one gets sent out. That's typically how it goes. There's also for the Oort cloud, which is much farther away. It's about, we could kind of think of it as kind of halfway to the next solar system is how far it is. And so there's thoughts of when we pass by other systems, their Oort cloud can kind of perturb ours a little bit and give little nudges in that sense. So that's another way too. But yeah, there has to be some sort of gravitational interaction with something where one body gets sent one way and one gets sent another way.
Very interesting. That's really impressive to think about when giving the idea of how big the Oort cloud actually is. That our Oort cloud is interacting with the Oort cloud of other stars, of other objects out there. And I mean, we know the nearest stars are light years away, so that gives you an idea of just how far out these comets can be, and everything out there. So that's very, very cool. So I guess that probably makes sense on why we don't really ever see comets out in the Oort cloud, right? Because I imagine they're very far away. They probably don't get that bright.
Yeah, totally. So we've never observed anything in the Oort cloud. Mm-hmm. It's too far. So that would be like the coolest thing ever to me if we could ever directly observe something in the Oort cloud. That'd be the next great step for astronomy in my mind. But yeah, it's way too far away. Things are just not going to be bright enough to see. Yeah.
Wow, that's very cool. Let's see. So we are still working right now. Tom,
We have the Comet with the eVscope. I can
That's good.
hold it up to the camera,
Oh, yeah.
but I cannot get my computer to do anything. It's in there. You can't see it right here.
I believe.
Tom is so mad. It's
My
great.
computer is absolutely useless. So I'm trying to share and show that to everyone, but not going well. I might need to do a full restart here.
That would be a bummer.
What does it look like?
It's here. I am going to have to just restart my computer. So let's see if we can
Poor computer.
do this.
Oh yeah, no, I can see.
The beautiful reflections.
Yeah,
on
the
screen.
reflection is the problem. Let's see. There we go. So it's out of focus. It's that blurry blob right there.
Yeah.
So you can see the core, the nucleus is moving. So that's the line. It's the streak that's moving. I don't know, this way. It's hard to do upside down. So yeah, it's not a lot of color here yet. We've been looking for this is about 15 minutes of staring at the comet with one of the eVscopes. Part of the problem is it's very low down on the sky. And so it's still was getting a little bit dark when I started. But yeah, so I'm trying right now to find a better way to share this with everybody. But it's been a struggle.
That is life.
So I'm gonna just shut down my computer.
That's observing.
Yeah. I am currently trying to check to see if our pointing was somehow got messed up, because yeah, I still can't see this comet on the nickel, which it would be very surprising to me if we could see it. So I apologize if I look distracted as well. I promise I am listening to you.
Yeah, no, it's not the brightest comet out there right now, but it's bright enough that the nickel should be able to see it. So hopefully we can catch it.
Yeah, I feel like this one is definitely a user error situation more than on the nickel.
Can you zoom out so you can see this whole image? I can try to help while this
Oh,
is
we're not on the whole image. That makes sense. That makes sense.
1/2. Boop. All right. So
while we're working on that, so Prince Planet asks, how can citizen scientists contribute to cometary astronomy now, perhaps in the near future? I think we talked a little bit about eVscopes, so I guess that's one thing. But yeah, if you have any other ideas as well as that.
Yeah, I mean, I could talk about what we do in the Comet program specifically.
Yeah.
Our goal is basically I'll choose a few comets that are of interest at the moment, and I ask citizen scientists to monitor them over time. And what I want to do is see how that brightness is changing over time. Especially in the beginning is really interesting for me. When we first have discovered a comet and it's still approaching the sun before it passes perihelion, so that I can start monitoring how much brighter it's getting every day and model how bright it will be in the future. So I can guess how bright it will be at its peak and beyond, and then we can continue to make these models even after it passes perihelion. It's good to have the solid model to say, hey, whenever we observe a Halley type comet, this is the general shape. We can expect this kind of activity from a Halley type comet, and so on. And so in general, what we do in the program is we monitor comets over time. And sometimes this is just a few months. So for E1, it's probably just going to be a few months long. But some of the comets we can observe for over a year.
That long.
And so yeah, and it's kind of fun. And so every now and again, even when it's past perihelion and nobody's really taken an observation in a while, somebody will take one. I'll be, oh yeah, that comet's still going, and we add it to the light curve, and it helps with our measurement every time. But one of the more interesting things is we monitor this to look for anomalies as well, or something exciting or interesting, like an outburst, like I was talking about before. Like it's interesting when a comet outbursts because the comet will probably die faster than we thought it would. And so that's why we need to know when this happens and why. And so what we can do with the Citizen Astronomer network is try to catch these. So far, it's been really great for me. Whenever an outburst is reported by the comet community, I just tell the network, hey, can somebody look at this right now? And somebody with an eVscope does, and we can right away measure that brightening because they're very fast. And so I love that aspect of citizen science for comet astronomy. And then my near future goals for that in particular is to catch the outburst ourselves. I want to be the one to report it. You know, I want to say, hey, the Unistellar network is reporting an outburst of this comet. Everybody go look at it, you know? So that's our one of our big goals. And it's a really, citizen science is a really good tool for that. So yeah, I love doing the program.
So just to clarify for viewers, yeah, the way Ariel and Tom and I all work together, and the way that you can get involved with citizen science is doing just your own backyard astronomy is with an eVscope. So Unistellar is a company that makes a digital telescope, a personal telescope that works fine on its own in terms of it. You can see a lot of things. It's a beautiful telescope designed to work even in cities. But the real kicker, and the part that I love because we get to be involved in it, is that you can do science campaigns with it. You can participate in science campaigns every month. We will, each of us lead a different campaign. I do planetary defense, so looking at near-Earth asteroids. Ariel looks at comets. So spoilers, Ariel and I do know each other. Tom knows her too. We tried to build you up as some big celebrity, and while you were in Nature, I think, right?
So were you.
So one of the benefits of that is we focus on our own specific science campaign, and we try and determine. So 2011 MD5, the asteroid we're going to look at tonight, that's a campaign that I picked. The Comet 2023 E1, that's a comet that Ariel picked out. So that's one of the ways that you can get involved in citizen science. I would also recommend other citizen science opportunities if I knew them. This is where I was like, man, I really don't want to just make it seem like I'm selling it, but it's an option. So that's one of the opportunities if you want to participate in citizen science. SETI Institute works with Unistellar to look at eVscope data.
Yeah, there's a lot of others. So NASA sponsors and supports and funds a lot of citizen science programs. So you're going to go to just basically Google NASA citizen science. There's probably a couple dozen projects on there. They're not all astronomy. Some of them are climate related, nature related. There are some really good ones that we collaborate with, like Exoplanet Watch. They do the exoplanet transit observations we mentioned a while ago in the stream, where they actually observe and detect and time, basically, measure the timing of exoplanets orbiting their stars. And you can do this with any telescope that has a camera attached, a telescope of a decent size, basically 4 or 5 inches or bigger. And they will support you on how to do that, teach you how to do it. So Exoplanet Watch, I highly recommend. There's a bunch of others that come to mind, but check out NASA Citizen Science and find one that suits you.
Yeah. Awesome. Thank you for saving me on that, because I really would have felt bad if I was just like, yeah, that's the one. So yeah, there are a lot of options out there. But cool, very cool. So we have a question from Claire Johnson, who, going back to the idea of not having ever observed anything in the Oort cloud, why can't we use JWST, or can we use JWST to look at the Oort cloud if none of our telescopes on Earth can see them?
Yeah. I mean, so it just is still too faint. These objects are small and they're not active, and they're not going to be active until they come close to the sun. Mm-hmm. And so these small inactive objects are just so faint. JWST isn't going to see them.
Yeah,
it just comes down to that.
Moving it to asteroids. I mean, there are still asteroids that are near Earth that we can't see because they're just really small. I think that's one thing is it's very easy to think that everything in space is very big, and forget that there are a lot of what we're dealing with are not. They're very small. And so when they're that far out, you've got a very small surface area. It's like trying to look at a penny from a mile away and catch the. It's tough. You can maybe do it if you had some really big binoculars, but
yeah,
hey.
it's also cool.
We finally got there, folks.
Yeah.
Hope this was worth the wait.
Whoa.
I'm sorry to just barge in there, but when in doubt, turn it off and turn it on again.
Yep.
So yeah, there's this is the full wide field view of the eVscope, one of the eVscopes. I think if I turn it this way, it'll get stretched out in the other direction. That's a little better. So you see lots and lots of stars around here. I don't really want that in the way. Whoa. Okay, whatever, we'll deal with that. And then, yeah, this blurry thing here is the comet. So there's the fuzzy coma around it, and then the nucleus is this. That is this line right here. So we'll keep monitoring that. This is 18 minutes this telescope has been exposing or adding images as we look. And so at least we can follow the comet for a little bit with one telescope while we get the big one sorted out. Sorry for the wait. But thank you for sticking around, everyone. All right, Ariel.
Next is
Go back to what you were saying.
I think I was just going to add one more thing about the James Webb thing. It's kind of weird to think about how James Webb is advertised to see really far away, the farthest we've ever seen. And the Oort cloud is closer than these galaxies that it's seeing. And so it's a good lesson to remember. It's not necessarily about distance when you're talking about telescopes and astronomy. It's about brightness.
Yeah.
So yeah, that's the only thing I wanted to add.
Oh yeah, I think that's fair. So I'm trying to find a nice little segue back into the DART mission. So are comets all right, look, you're going to have to work with me on this, Ariel. Are comets the only things that can beat comets? Okay, so
that's a good question. Asteroids can be comets too, actually.
Really?
Yeah, there's a whole population of asteroids called active asteroids, and they're actually also called main belt comets by some people. They look like comets, but they're in the main belt asteroids. But there was a lot of people in the community who didn't like that name because it was confusing, because they're not comets, they're asteroids. So we have these asteroids that are active, which means they have this coma, and some have these tails, just like comets do, but they don't have the same orbits as comets, and they don't come from the same source region. They come from much closer, and they stay much closer at all times. And so kind of similarly to comets, they can become active for a lot of reasons. They can heat up eventually enough that enough gas pressure built up and it broke through the mantle, and now it's sublimating. The ice is exposed to the space and to the heat of the sun, and it's sublimating. Collisions could have revealed ice to space. Various things like this. And another one is it can spin too fast once again, and if it spins fast enough, things might fly off of it, revealing it's underneath ice to space and to the sun, and then it sublimates. And you'll also see dust dragging off with it, especially in a collision, you'll see a lot of dust. And that is kind of one of the connections to the DART mission. If you all remember NASA's DART mission last year, they basically sent an impactor into an asteroid to see if they could alter its orbit in the name of planetary defense, right? If an asteroid was ever on an orbit to Earth, we want to know if we can hit it enough to change its orbit just so it misses Earth instead. That was the goal. And they actually accomplished this really well. It was a really exciting mission. But for me, it was more exciting because when they hit this asteroid, they activated it, essentially. They hit this asteroid and it became really bright and fuzzy, and we saw this dust moving away from the asteroid, and we were able to kind of treat it like a comet, the activity of a comet, to estimate how much stuff came off using the same methods we do when we look at activity in comets and outbursts in comets. And so asteroids have ices too, and that's been kind of the big revelation of the last decade or so, is there's more ices in our solar system than we think, and that's interesting in the name of water and life in general. But yeah,
I think it is always very interesting to me how it seems there is a pattern where we really love categorizing things and trying to fit neat little boxes, and then the more you look into stuff, the more you realize it's like, oh well, it's kind of like a sliding scale. Like, it's not, you got a little bit of asteroid and a little bit of comet. So
yeah,
it's very hard. It's very hard to ever neatly categorize and say something is exactly this. So I think that's very cool. That's very cool. I do not think that, I don't think I ever would have, before this year, I didn't even know active asteroids existed. And then you were the one that actually told me about them. So
yeah, active asteroids are awesome. But yeah, the naming thing is always weird because you want a name for something so you can talk about it and everybody can know what you're talking about. But then, yeah, you end up on this scale of it's somewhere in the middle and it's kind of like this, kind of like that. I mean, we could get into the whole Pluto debacle, but...
Oh, people have in the comments. Yeah, I mean, Pluto is an excellent example of planet was a very poorly defined term way back when, and it is it's tough if you want to include things like Pluto as planets. Then you start having to give kids like 100 different objects to memorize. Like, these are the planets of the solar system.
Yeah, because all of a sudden there's a lot more things like Pluto out there.
Yeah.
I've also heard Pluto be called a comet before by a niche group of people. But I loved it because it has like this hazy atmosphere that seems to be potentially active. And, you know, people describe that as its coma. And they're like, oh my gosh, Pluto's actually a comet from the Kuiper Belt, not a planet at all. And I always thought that was funny, but what's in a name?
I mean, that sounds like a hot take that...
it's a hot take.
That would definitely start some fist fights in the astronomy convention.
Oh, yeah.
So we have confirmed, just to update everybody, we have confirmed that the nickel is in the right field. We think we just weren't exposing for long enough. I was a bit ambitious, expecting the comet to show up as soon as in as short an exposure time as I did. So we should see it in a few minutes to see if we gave it a 5-minute exposure, and if that works, then we'll share this screen too, and hopefully we'll all be able to see what the nickel sees. Ooh, I don't know if can you hear that? The beep beep, the ding ding.
I can.
Okay, good, because it's very loud over here. If you see Tom or I jump, that's it. That's why.
It's necessary though. You'll need it at 3 a.m.
Yeah, I mean, it's definitely, it keeps you honest, keeps you awake. Yeah. So we see some stars trailed. I think that's it in the center.
No, it's a streak like the stars.
Yeah, you're right.
The stretch is terrible.
Look, all right, I'm doing my best.
I know.
So it does non-sidereally track?
Yes. So let's see. Can we share? Where is it again? There.
Trying to get the eVscope back.
I know. So while Tom works on that, we can at least show what we're seeing. So.
Oh, you want to share that?
Yeah. So this is the 5-minute exposure. You can see these little doodads here, these little globbies. These are actually stars. So because we are tracking on the comet rather than tracking on the sky, the stars end up looking pretty streaked out. And so at least we know that the telescope is doing what it's supposed to. But the downside is that not seeing the comet. So we might need an even longer exposure time.
That doesn't make any sense. It should be really quite
bright. I would think so.
Right. This telescope is like 10 times larger than the eVscope. It should be able to see something. This is the kind of thing that we would have tested last night. We planned to.
Yeah.
And we never opened the big telescope. So
thank you all for coming.
Kind of why we're
That's a great time to explain for any new viewers in chat. Welcome to our little live stream. This is a cozy corner with us. You're here with Ryan and Tom and Ariel, our guest speaker. This is not really planned. We have a big agenda, but largely we got telescope time, and we thought it would be fun to give people an idea of what it's like to be an astronomer at a large telescope. So that's what this is. And right now we're hitting like every good astronomer does on a large telescope. Crap. So yeah. Okay, so we need to figure that out. Why are we not seeing it? So we double checked that it was in the right field. And we did see a lot of the same stars. So it is a little bizarre that we aren't seeing anything at all. We got a question from Paul Hawkins about the possibility of Planet 9, wanting to speculate on that. Tom and I gave kind of our opinions on that early on. We can reiterate that as well, though. But do you have any particular feelings or thoughts on the subject?
Yeah, I have a little bit.
Not necessarily your wheelhouse, but
yeah,
it's not mine either.
Right. Yeah. Right. So this isn't my field of research or anything, but I do know a bit about it here and there. And my understanding for Planet 9 or Planet X, this is another one where people debate about what it should be called because, yeah. But anyway, my feeling is that the evidence has become more and more against it. There's never been very good evidence for Planet 9 being there. And when there was better evidence, when there was evidence that seemed not so against it, a search was done and nothing was found. And then more and more, we found basically these objects that basically told us, okay, there's these weird objects over here, so Planet 9 might be over here. But now these weird objects are kind of everywhere, so Planet 9 must not be anywhere. That's kind of the gist of what I've gotten from the research. So more evidence against it, and we haven't found it yet. And my feeling is that we won't. If we did, I'd be stoked. That'd be the best. But my feeling is that the evidence points against.
Yeah, I think I agree. So I mean, I mostly work outside the solar system, but it's hard enough. Yeah, I think the original evidence was based on kind of a specific way of looking at statistics, right? If I remember correctly, and yeah, when you looked at things other ways, the orbits of objects out in the Kuiper Belt, then maybe the evidence for Planet 9 wasn't quite as strong.
Yeah,
and just the amount that it's been searched for so far does reduce the chances that it's still out there, I think. So it is really, really hard to detect. It's so if it's out there, it'd be small and dark.
Yep. And just my feelings are the same, but just to clarify, we said this was a bit of a repeat, but this is a stream that is very long, and we are 100% expecting people to come and go. Do not ever feel bad about asking a question. We are expecting that the question is new to somebody, and we're expecting to give some repeat answers. It's not a big deal. Don't worry about it. But yeah, I'm largely in the same camp. From what little I know, it's like I would be super thrilled if it turned out that there was a Planet 9 or a Planet X and we could find it. I think that would be cool as all get out. But I think it's unlikely. But that doesn't rule it out entirely. So it's one of those things where I like to dream about it. I like to think about it. Yeah, Phil says the search for Planet X is like the search for Bigfoot.
Yeah.
Yeah, I mean it's one of those where it's like, gosh, it would be so cool. It would be so cool.
And every now and again, somebody dresses up as Planet 9, and somebody gets a weird
photo of it.
Right now, it's kind of like the search for this comet.
Yeah, this comet, I'm not convinced is real. Ariel, you've sent us on a goose chase.
We saw it.
The eVscopes use it.
Saw it with our little telescope. Where is it with the big one?
Yeah, it might be worth looking at something else just to see if you see some.
I was
Yeah,
gonna suggest
Pointing is right.
one of the pointing stars.
that's what I was looking. There was not a whole lot.
But I mean, well, that's not
nearby,
true.
but-
We confirmed we were definitely at the right coordinates. That I matched the
Oh.
stars to
Yeah.
a known field of view, so we were definitely in the right spot, and we were where the telescope thought it was, and we were where JPL thought the comet was, and I could check. I'm pretty sure that's accurate because it's the same coordinates I use for the eVscope. What I was trying to do was match the eVscope field of view to the nickel field of view. So maybe we can actually do that. Ryan, I'm going to put the eVscope view back.
Yep.
By
all means, I'm just playing with the stretch.
Yeah, so actually, scratch that. I'm gonna readjust a little bit here. So,
how long have you done one exposure for the nickel for this comet?
Yeah, well, we've taken. While I've been talking to you, I've also been like frantically trying. Frantically taking some observations. Yeah, the filter we're in right now is V. But yeah, I've tried a couple minutes, and then we tried the 5 minute just to see if we can get it. So I haven't been recording, but.
So here we can at least have these two side by side.
Okay. Right.
Okay.
Matching game.
Yeah, there we go.
So
what's the field of view of the nickel?
It's like 6 arc minutes.
6 arc minutes on a side, but we have a guider cam that we're not showing right now on stream that has I think an 18 by 18 arc minute field of view. But before I was able to match, I was able to match the nickel field of view to a survey image. And so if I try to do it also with the eVscope, how can I do that here? eVscope, if I zoom in.
Flip?
Ryan, can we re-stretch this to show more stars? I think we got to bring the bottom down. It'd be nice to have a button we can type, a thing we can type into here. That's fine. What if you click find? What happens? It stretches it out. So yeah, drag this end over to here. Ooh. Okay, and then drag this end up a little bit. Mouse around here. What's the background value? 1900. So drag this up to like 19. Okay. Let's see what that looks like first. Whoa. Here. Okay, keep going. Drag it up to like 1800. So a lot, surprising amount of astronomy is knowing exactly how to look at your images. So this is obviously not flat fielded. You can see all the garbage in the image. What is the, so
this has to be it, right?
That, or is that just a bright spot? So if we try to match, I think the eVscope image tends to be flipped vertically. It's mirrored, like in around the vertical axis, the horizontal axis, compared to what we see with the nickel, which makes this a little bit tougher. No, that won't work. Can we bring?
Oh, it's dust.
Yeah, bring the top end down. Yeah. Keep going. Okay.
I'm not convinced this isn't it, in that because it's because it's trailing there. Yeah. Good point. Although it might be the tail.
It could be that in the middle there. Yeah. It would also be handy. Did we record any of these? We should record some. So can you hit record?
Hi, Daryl. Sorry. Yes, we are here. We're just currently we're on a big telescope at the moment, so we're trying desperately to take our data at the same time, and it's having issues. We'll get to your question in just a minute, though.
E1 should be pretty round. Like it doesn't have much of a tail.
And take let's just do, since we're not sure, let's just take data.
Sure.
Okay. We take a deeper one, but that's fine. I want to get an image so I can look at it on my computer.
Yep.
And subtract the flat, divide the flat out or
All
something. Yeah. So anyway, we have this is what the eVscope is for. It actually kind of demonstrates how easy it is to use
Compared to a big telescope.
Yeah, we would definitely, once we get all the data down and have time to massage it, then the nickel data would give us better results in the end. But yeah, I think I'm starting to think maybe that's what it is. That's it in the middle there. But I would have thought we saw a much brighter source. I mean, that seems like
And it shouldn't be streaked, right?
right.
Right.
Unless we have the
The
rates wrong.
could be.
So
So
that would definitely hurt. So times it right now. It's
sidereal rates are
because
wrong.
it doesn't matter.
They're old.
They're wrong.
Yep. So it's 27, 187, and I've got 30 and 188.
That's pretty close, right? Are these the numbers we actually want? Is this what we used last time?
Arc seconds per hour.
It's what, 4 o'clock? Now it's 26.8 minus 186. Can we
change it?
All right, the next one.
Yeah.
Right.
Okay. So
All right. Well,
and minus 187.
minus 187. 7.
Yep. Okay.
So this says, let's see, TMAG. What's TMAG? T is
Total mag.
what is it? Total mag. Okay, so it
Yeah.
says total magnitude is 16.2.
And it should be brighter than that.
Yeah.
Yeah,
little bit.
JPL's often a little bit off
Should be brighter
on their estimate.
Yeah.
So the
I've been getting like 14.
So the current time is what? It's 04:15 UTC.
Yes.
So-
0422, but yeah.
Yeah. So the target should be at 22 hours, 8 minutes, 48 seconds.
22
So
hours, 7 minutes.
Pretty close.
34.
And then minus 3 degrees, 38 arc minutes, 0. Yeah. So
Should be there.
smack dab in the middle.
Yep.
Our pointing centering was pretty good. Yeah, maybe I don't know. We could try a different filter. Would this be Ariel? Would this be brighter in other wavelengths?
I would try red.
Yeah.
So
Okay.
we'll try when this is done exposing. We'll try R band.
So I don't know if we want to open this can of worms right now. David Grush and the testimony. We had a question about that. What are our thoughts about David Grush's testimony? And a follow-up to that, do we believe that the government would stonewall us if they do have evidence of extraterrestrial life visiting us?
Can you guys talk about that?
Yeah.
And give context about what the testimony was before you do that?
I didn't actually watch the testimony, I'll be honest.
I didn't either. So
So my general rule of thumb is that unless you can provide some evidence for aliens, there have been lots of instances like this where a supposed whistleblower has said something and not been able to follow it up with proof. I do understand the idea that you could very easily discredit somebody who is telling the truth by making them sound insane or making them sound like they're crackpot. I don't know if that's what's happening here. I 100% think the government would probably stonewall us on something like that. But in general, I I find that it's a rabbit hole that you go down if you aren't careful. So in general, I'm a wait and see. I do not particularly think that I think people have the best of intentions, and I think people genuinely believe that they know something, but I don't necessarily. I think you can be misled. I think people can be misled. I'm open to the idea. I have no idea if it's true. I also have very certain that we would not know the truth, at least for a little while. But I think conspiracies that big will unravel rather quickly. So I don't know. You have thoughts on it that are different?
Yeah. No, I'm pretty much exactly the same. But I do totally get the intention of, like, you see something and you think, could this mean this? Without it actually being evidence for that. And I mean, we see that all the time in science with scientists with good intentions. Like, even with our Planet 9 discussion, there's all this research being done that could mean Planet 9, but there is no direct evidence of it, right? That's kind of
Right.
how I saw this too. Like, he presented these things that weren't direct evidence of aliens, but he went through the thought process of how could this be aliens, and so in that respect, I think it's kind of interesting, and I like hearing about those kind of things. But for me, in the end, there's no evidence. So that's kind of just where it ends for me. But I think it's interesting all the time, nonetheless.
Yeah, I don't ever want to like shut somebody down for what they believe. So
Yeah.
What channels / spectrum is SETI monitoring for alien signals? I actually do not know that one off the top of my
Yeah.
head.
Me neither. It's broad though.
Yeah.
It's like a really.
Go ahead. Sorry.
It's a long wavelengths, but a lot of them, and they're looking at a bunch of different wavelengths. I guess typically they say radio, right? But I think it actually spans a lot more than that.
Yeah, my understanding is that they're pretty much searching as many as they can find, or as many as they can justify, for that exact reason of you never really know which band. But yeah, neither of us, Tom either, work specifically on that project. That's actually SETI was founded with the goal of searching for extraterrestrial intelligence, but it is more generally an astronomy nonprofit. So it does help. It helps with a lot of different projects. Some citizen science, some focused on searching for extraterrestrial intelligence. There's a lot at SETI, so we're not the best people, unfortunately, to answer that question. Although it's a good question. I just don't know. I'm sorry.
Yeah. I like to think, like, in general, and I think you guys were kind of talking about radio wavelengths earlier anyway, in contrast to like visual wavelengths, them being longer, and because they're longer, they travel farther. So I think like we use radio wavelengths for our radios to broadcast far music and all that kind of stuff. And so we can kind of assume that we should be looking for these longer wavelengths from other places as well. So in the longer wavelength zone, that's a broad range of wavelengths though.
Yeah. All right. So we are moving to, I still don't see it in this. So we're moving to the red filter, which hopefully will be more aligned with the light that's getting reflected off of this comet. And let's see, we're going to try a deeper exposure. Let's try something like 10 minutes. You think you can vamp with me for 10 minutes, Ariel? I know you don't ever really talk in general. I don't.
I can do it. I hope we see it.
The effects of ELF. So I don't actually know. ELF is that's gone over my head a little bit. Do you know what the implications of ELF or what ELF is, Ariel?
I know that I've heard this.
Okay.
Okay. Is it upper atmosphere lightning?
So
I'm
yes,
Googling.
the questions from Paul. Sorry, Paul, this isn't. I just don't know much about this topic. Implications of ELF as it affects our atmosphere and ionosphere. I have no idea.
Me too.
Sorry. Yeah, I'm not. I've never been very good with atmospheric physics. I largely my experience with the atmosphere begins and ends with turbulence and how it affects seeing. And I've recently started gaining a little bit more knowledge, having to learn about low Earth orbit satellites. Yeah. Has there ever been a follow-up on the WOW signal? I don't think there has been. I think that was that's actually part of the reason people justify it not being the existence of message or anything, is that there hasn't really been any follow-up as far as I know.
Yeah, I mean, we've looked, like people have looked there again to try to find the WOW
Right.
signal again, but it hasn't repeated. So
it reminds me, as much as I hope it's not the case, it reminds me of that one, what was it, Green Bank in Virginia, the radio observatory, that it's like they couldn't figure out for the longest time. They would keep getting random radio signals, and they're like, what's happening? And then they realized it was like, it's a radio quiet town. No like cell signal, no reason for there to be interference. And they were like, what is doing this? We do not understand. There was no rhyme or reason when the signal would show up, and they realized it was like a poorly shielded microwave that was going off every time somebody used it in like the employee like lounge or the lunchroom.
no,
Whenever somebody would heat up their lunch, they'd be like, what?
that seems dangerous for the employees.
Well, that's what we had yesterday. So the microwave we have in here, we had the support astronomer he was a very nice guy, John. When we were shut down so much of last night, he sat with us so that when we got any point where we could maybe get on the sky, he could help us get trained on the telescope and we'd be done. And at some point, Tom had heated up dinner in the microwave, and he was like, my internet just cut out. The second the microwave started, the internet got cut out.
Oh,
so,
yikes.
Tom and I might have problems when we come back. We don't know.
Yikes.
Neil Blonsky says that for someone who grew up knowing that Pluto was a planet, Planet 9 specifically, hearing us talk about Planet 9 confuses him.
Yeah, that's exactly what I was kind of hinting at earlier when we were talking about it, is some people don't like us to say Planet 9 because that's Pluto. And they're like, how dare you? Pluto's Planet 9. We have to call it Planet X, So yeah, that's another thing. It's all in the name. People call it what they want, and it's confusing, and it's hard to pick something that everybody can agree on.
Yeah, I mean, that's the dangers again of, we talked about naming, is when you decide that your name, your category for a thing doesn't fit anymore, it becomes very confusing when you get in that transition period of, well, we used to call it this, but now it's not. So
now it's not. Yeah.
Sorry. Well, so how long, I forget if you said this already, how long do you think this comet in particular will be visible? Obviously for us right now, on the nickel, it's not visible at all. We'll see.
Yeah.
But in general, for others who are not cursed at the moment, how long do you think this will be visible?
I think we have another month or two, if I'm remembering correctly.
Okay.
Yeah. So a little while, but yeah, other comets have lasted longer, but other comets have lasted shorter.
Yeah. Is it gonna, do you know when it's gonna be at perihelion?
It's past perihelion. So it went to perihelion already in in July, because July is when we did the super image, mid-July. And then in August, it got its close approach to Earth. So it already reached its brightest point for us. And now it's leaving. It's going away. It'll be back though in 85 years.
quick question. What is a super image for the people at home?
Oh, yeah. So a super image is an event that we like to hold sometimes with Unistellar eVscope users. Basically, in general, when we're looking at individual observations of a target, like E1, people will take images over 20 minutes of time, a bunch of short images, and I'll stack them on top of each other in order to make it brighter and make the error and noise go away, or at least go down. And so we kind of do this on a massive scale, and it's more of a fun event than anything, where basically instead of just taking one person's observations and stacking them, I take a bunch of people's observations all taken around the same time and stack them. And the idea is that if we all had, if we put our telescopes together and had a telescope that big, this is what we would be able to see. And that's what we get with stacking. And so, yeah, we have as many people participate as we can, and we stack all their images together into one big super image that comes from a bunch of different people. I can share one if there's still time.
Yeah. Tom and I we don't have any. This is you're here as long as you want to be, honestly, Ariel. I'm okay with that.
Okay.
So yeah, you will have to let me move this so that it's not in the way anymore. Okay, so yeah, if you have one, by all means, please pull it up.
Let's see. Will it let me share a window or full screen? I'll find out.
It should let you share a window. I think you can pick one.
Oh yeah, okay, I see. Okay, I think I'm sharing.
You have to, let me see. Yeah, add it to the stage. There we go.
Ah, cool.
Boom.
Okay,
So
awesome.
That's a super image.
This is a super image. This one in particular, I just kind of picked randomly, but it was from about 15 people in Europe on July 15th. So
that's a single day. That's crazy.
Yeah, single day, and we try to get the same time, so that way the stars, there aren't too many I don't know, weird shifting of stars in the background. So same day, same-ish time. Yeah.
That's very neat. I do like that you can see the stars. I mean, it kind of looks like what we were seeing with the nickel, the stars kind of blurring. Gives you a sense of the movement of that comet without the comet itself being blurred out.
Yeah, and you can see the roundness of this guy. It doesn't have much of a tail at all. He had a really faint, thin tail that you could see with bigger telescopes at this time when it was at perihelion, but we weren't able to catch that quite. It was really thin, but we still got this, which was cool. So hopefully we could see something like that in the nickel. But yeah, you can see in the images from the eVscope that Tom was showing earlier, it kind of looks like this, except the comet is streaked instead of the stars. So the eVscope doesn't follow the comet the way the nickel is going to. So it's cool that it does this. And then, so when I stack the images, I do this part manually. I ship them together. Yeah.
So do you have to open the images individually and like just say, okay, the comet's here. And then
that's one way to do it, and that is how I did it the first time I ever tried back in grad school. For sure, it was horrible. But basically, I can get its location from its ephemeris on like JPL Horizons, which I know you guys are using, and say I know it should be here. Put that in the center. Essentially, have it do that consecutively with all of the images.
Clearly, it works to do it that way. Cool. So is there something, so what kind of science, can you get any science out of this, or is it purely a very cool kind of image, really a way of kind of visualizing the comet from the different options?
It's a good question. For the super image events in particular, they're more of like a social event and getting everyone to go look at it rather than scientific. And the reason for that is everybody observes in slightly different conditions. Even if we try to get people as close together as possible, somebody's telescope might be out of focus where someone else's isn't. And it's just hard to get an accurate measurement at that point when you combine them that way. It's more accurate to look at their observations individually so you can see what's going on in each of them. So it is doing something like this is more for fun, and it does bring out the actual color of it so people can see that clearly. And but yeah, more for fun than anything.
I see. Okay. Well, I'm going to share real quick again because our image just got done. And spoilers, it doesn't look great. So we want the direct imager. I got to find which one is correct. There we go. Allow. And then we got to add it to stage. So it seems our comet has changed directions a little bit. We are now, or at least the telescope has changed its orientation a little bit. So the stars are streaked straight down. Unfortunately, I still don't see a comet. I'm actually very tempted. I think what I'm going to try and do now is we can try and recenter on where we know the comet is supposed to be, and turn the non-sidereal motion, so tracking on the asteroid, we can turn, or on the comet, we can turn that off and maybe see if that is causing issues. I don't really know.
I vote we give up on the comet.
Yeah.
Because it's time to look at our asteroid.
Oh, well, okay.
All right.
Fine. Asteroids are cooler anyway.
We've kept Ariel long enough.
Thank you, Ariel.
Whatever.
I appreciate
You're welcome.
you vamping with me for as long as you did.
Yeah, it was fun.
Yeah. And genuinely, thank you so much for answering questions for everybody here. There were a lot of great questions in chat, and I appreciate you taking the time to talk with everybody and kind of showing off what you do.
Yeah.
Thank you, Ariel.
Thank you for having me.
Yeah, anytime. All right.
Anytime.
Goodbye.
Okay.
Bye.
Goodbye. Clear skies.
Thank you.
Thank you. Oh, all right. So, comet, unfortunate. This is why I don't like comets.
Well, it was a challenge, and
We
weren't up to the task with the nickel.
I mean, we got something.
But so what I was doing is eVscope number 1 is still looking at our comet. I think it's still showing a live view. It's been looking for 69 minutes. It's been tracking without a hiccup. eVscope number 2 is set up and looking at our asteroid. It's already collecting science data on asteroid 2011 MD5. And so it's going to do that basically as long as it can. It's very low in the east right now, something around 20 degrees above the horizon, which is very low for people who aren't used to thinking about these things. 90 degrees is directly overhead. 20 is problematic because you're looking through a lot of the Earth's atmosphere. You look through more air. The lower down on the sky you look towards the horizon, than when you look straight up or higher up in the sky. There's actually less air particles above you. But anyway, yeah, the eVscope should have no problem detecting the asteroid right now. And when we tested it last night, it could track probably until about 2 a.m.
Yep.
At least, at which point the building may get in the way, and then we can just, might be okay. At which point we just move the eVscope to the other side of the building.
Violates the elevation limit. What's the elevation?
We might be right at the limit for the nickel.
Whoop. Well, okay.
So we can just wait a little bit.
Yep.
Was that the hard limit? That was the soft limit, I guess. So what is it? It says, does it say what the limit is?
No.
So there's a way you can pull up the limit again. What was it? It was we click on something, and it tells us what the pointing limits are. I have that written down.
Okay.
Can you
figure that out? How do I get it to not move anymore?
The telescope?
Yeah.
Just let it move.
Okay.
I don't want to go interrupting slews.
Yep.
Did you explain what a slew is yet?
Oh, thank you, Paul. Appreciate you stopping in. You have a good night.
Good night. Let's see. So anyway, this is our main science target of night. This is actually the reason we're here. Everything else is a bonus. But this asteroid is the main reason that we're here. What was the thing I was going to look up, Ryan? The limits?
The limits. So there is, to keep people like us from being stupid and breaking multi-million-dollar equipment, there are some limits on how far the telescope will move before it just says, and apparently we've hit that, trying to move to this asteroid. So,
we knew that right at this time it was going to be very low down, and so we were thinking this was the earliest we could possibly point to it. And yeah, so this is telling us towards the east. All right, so our angle is not a problem.
No.
It says we're clear.
Yeah, on all of these.
On all of these. So
I mean, it still went. So
yeah, it may have just been warning us.
Oh wait, this was for. That was for the Comet. No,
It wasn't near anyone.
No, that doesn't make sense.
This was at 9:43, so that was just 2 minutes ago.
Yeah, I don't know.
All right, what's the RA deck we should be at? Check
I think that's it. It's 144.5.
Check that that's right.
Yeah, 144.5, 5 degrees, 12 arc minutes, 38 arc seconds, 39 arc seconds. Yeah, we're there.
All right, then we reset the sidereal rates.
Yeah, we need to do that.
And so this we did observe last night, chat. So we know we can see this asteroid. We know it's bright, and we should recognize it when we see it. So no more of this silliness. And this is what the nickel will look at for quite some time.
Yes.
So we're going to look at it for a little bit, or we'll be showing it on stream for a little bit. At this point, probably, we'll take a 20, 25 minutes. We'll talk about what we're doing again. We'll talk about this asteroid, and Ryan can talk about planetary defense and everything that he loves about it.
Oh boy.
And then we'll go on a bit of a cosmic tour, hopping through some of the really pretty targets that the eVscope can see while we continue to do science with our other 2 telescopes. And so that's why we have all 3 of them out there. I think we've got some good stuff lined up for you. That's in the schedule.
I'm going to initialize the filter just to be sure that it's not anything like that. So just initialize it again. So it'll take a little longer, but not that long.
Sure. We're going to look at this in the V band. So again, kind of that greenish, yellowish color, I guess.
What did we? It was 150 last night, right? Oops. Yes, it was 150. Okay, I remember. So thankfully, because this was a target, we'll just record. Because this is a target we actually got to look at last night. We know what we're looking for. We know what time to set for our exposure time. So hopefully this one should go off without a hitch. We'll see.
Indeed.
This morning, Nishimura is tough logistically, but had quite a bit of viewing from Southern California even this morning. Yeah, I mean, we can check to see what the elevation will be like, but I don't think we're far enough south still.
Unfortunately, I did check this out in advance. Comet Nishimura is rising very close to sunrise.
So we won't even have time.
Yeah, it's above the horizon, but again, it's these pointing limits. So it hits about 20 degrees altitude above the horizon, right at like 10 minutes before sunrise. We absolutely cannot point to the east that close to sunrise. You do not want the sun getting anywhere near your telescope. So very occasionally, if you have the agreement of the telescope operator and everyone, you can point towards the west close to dawn because the sun is not in the west.
Yep.
It's in the east. But you only do that with infrared telescopes because the sky hasn't gotten that bright in the infrared yet. And it's really not something they encourage.
Yeah, the smell of burning CCD, not great.
Not my favorite aroma.
No.
No.
And that is because the telescopes are designed to focus a very small amount of light onto the CCD. Having a very large amount of light like the sun instantly obliterates your camera, and you do not want that.
Yeah, I think it would damage a lot of things. It would damage a lot of the. It might even damage the mirrors, even though they are so reflective.
Yeah.
You just don't. You don't do it because you.
It's a good way to make sure you never get time on the telescope.
Exactly. So I'm gonna swap.
It smells like sadness, Lauren. Lauren asked, "What does a burning CCD smell like?" It smells like sadness. It smells
a little bit like tears.
It smells like a ruined career. Is what it smells like.
It's a smoking ruin of a career. That's right. That's right. Yeah, I don't know what the unemployment line smells like, but that would be it. Okay, so I have the eVscope view. I can share it. Frankly, there isn't much to see here of the asteroid, but so we're gonna swap off the comet. I'll leave the comet going with that eVscope for a little bit, but put it in the background. So where are we here? We want to. Did I stop sharing? Did you stop sharing for me?
Stop sharing what? No, I
From my
think
laptop?
I think it did that itself.
Oh, weird. Okay, well, so you weren't watching the comic for a while. That's okay.
Sorry.
I'm gonna show it real quick before we
Move off.
move off, so we can see where we ended up. Apologies, my computer might have gone to sleep while we were while I was away. And hide. So this is where Comet E1 left off. You can see here it's become quite elongated as it moved through space relative to the background stars. I'm gonna try to adjust the brightness a little bit. Let's see what happens. I don't like it too much.
Oh, now you're getting on Asteroid.
Maybe not. That's probably good. Let's adjust that. And meanwhile, Ryan is looking for the asteroid.
Yeah.
There in the middle. Is it?
That's yeah. No, there's no way. That's no.
Okay. It shouldn't be.
Yeah, it should be elongated unless the rates. I have to wonder if this target tracking is maybe not working like it should.
Using that and show a whole.
Good.
Or it could be right behind that star.
Yeah. You can check the eVscope too. See what it sees.
It didn't look like it was near a bright star.
Oh, well, bummer.
Okay, but anyway, so last view. Oh, there we go. Finally caught up. That was maybe I stretched it a little too hard, but you can kind of see if I zoom in. There's the comet, and I got a lot of extra noise there as I was playing with the settings. I'll turn that back to the way it should have been. Oof.
Oh, bye, Lauren.
Hi, Lauren. In the meantime, I don't want to leave on that note for this comment, so I want to let it
Sit for a second.
Yeah.
What'd you do to it?
I was messing with the enhanced vision background and brightness settings, so I was making it do things I shouldn't be.
All right, I'm going to turn target tracking off and just see if we can see it. See if that changes things or not.
This is our limited Wi-Fi connection is what's slowing down the update. I'm just gonna pull the plug on the Comet. Say goodbye to Comet E1. And we're gonna swap to the asteroid here while Ryan sorts out the nickel, and then I can help with the nickel.
Okay. Well, I've got it exposing right now, and I know it's bedtime, but I do have to use the restroom. So,
Yeah.
okay. I will be back momentarily, chat.
And we will bring up the asteroid view. A minute now. There we go. So this may be a little hard to see. I'm gonna try though. All right. So, can you zoom in here? Okay. All right. So this is the view that we get from the asteroid. Sorry, not the asteroid. The view from the asteroid would be pretty interesting. But this is the view from our second eVscope looking at asteroid 2011 MD5. And what we're seeing, most of these points of light are stars. We have the camera settings of the eVscope set so that the asteroid is not saturated on our eVscope camera, which means that in this view here, it actually looks quite dark because we're just looking at the single frame that the camera is recording. But I can zoom in and maybe we can see it. The asteroid is there. Wow. That's it. Ooh, impressive. It's that tiny little point of light, but we can actually see it moving. I think. Let's see. Huh? I had a rough image there. Or either that was the asteroid moving or that was a little bit of wind shake on the telescope. There is a little bit of wind out there today. All right. So anyway, pretty sure still that's our asteroid there, that tiny little point of light. Not very impressive, which is why we're not going to stare at it. We're not really going to look at this view for too long tonight. But it's the start of our science operations, so we're going to. Yes, Katie and Cozy MZ. I think you had the right idea. They're all really far away. Some asteroids with a bigger telescope, you can actually resolve them, and they don't look like a tiny little point of light. You can actually see that they're a potato-shaped or dumbbell-shaped asteroid. But others, and with smaller telescopes, they're so far away and so small, they just look like tiny little pinpoints of light. Okay, so Ryan's image ended with the nickel. And let's see, we see stars. He turned off target tracking, so the stars look okay. The telescope's not guiding, so they're going to be a little bit smeared, which that's fine. If we zoom in, do we see our asteroid here somewhere? That was 150 seconds. No, our asteroid was very bright. So it could actually be, let's see, with any of these points. But I would think it would be somewhere near the center of this image. I'm pretty sure it's not one of these two stars here. If we zoom out with the eVscope, we try to match the pattern of stars the eVscope sees to what the nickel sees. And so the best way for me to do that is here. So When you're trying to match patterns of stars, pairs are really handy. Two stars close together. So I think, for example, I have a little bit of better view with my direct view on the laptop here. But there's two stars very close together, right where I'm circling with the little cursor in the eVscope image. I think I thought those might be these two stars here in the nickel image, but now I'm not so sure. We have 1, 2. Yeah. Look at the guider image instead. So 1, 2, 3, 4. Yeah, that's not really helping. This really was not a lot more smoothly last night. So let's look at the next thing. Typically, if we can't find a target, we will pull up a catalog image of what that region of sky should look like. And so it'll show stars, which are always there. And indeed, the nickel is spot on target. It's pointed exactly where it says it is, and that's exactly where the asteroid should be. And this bright star here, which is 2 stars, if I zoom in, this pair, this is really a pair of stars. So that is not the asteroid, just happens to be next to a bright star. Which can happen, but not the case right now. So now the trick is, if I zoom out and try to compare with the known stars, do I see a point of light in our image that's not in the catalog image? So let's see. So these two are stars. This is a star. These two are stars. Star, star, star and star. Star, star, star. These all look to be stars. These 1, 2, 3, 4 stars. Or that up here. So we've got these in a line. This is a star. Move up a little bit. Yep, these are all stars up here too. So there is, no, that's not right. That's a star. Double check our coordinates again. I think they're okay, but can't hurt to check. And actually, while we're doing this, I am going to give up on the Comet E1. And what we can do with our second eVscope for it, I think we'll be able to do it. We'll see if it's too low down. Is we can do the same enhanced vision image stacking trick that we just did for the Comet. And like the Comet, the asteroid will make a streak in our image over time. So we're going to set it to do that for the next, I don't know, 15 minutes or so. And then we'll go look at some cooler stuff. I think the Pinwheel Galaxy is up first, starting around 10:20 Pacific time. So that's about 15 minutes, 17 minutes away. And while we
we're doing that, I will look up coordinates. 011, 5 hours. Yeah, yes indeed.
I'm back.
All right, so Ryan's back. I've determined so far that everything in this image is a star that I can see.
Yeah.
I matched it to
That's why I'm
other
on
stuff. But
convinced.
the coordinates that we pointed at with the eVscope are the same, and I'm pretty sure that we have the asteroid in there.
So what the heck?
That is the question.
How do you get what's a big telescope? You want to catch this? We caught it last time.
Yeah, so we could do one of two things. I just got to think of what those two things are. So what I want to do first is I want to point the other eVscope to the asteroid.
Okay.
And that one's closer. This one.
I'm helping by keeping us fueled.
Thank you.
Oh, these are soft cookies.
All right, so we're going to swap that. Plug in the. I wish we had a good way to show all three telescopes at once, but unfortunately, technologically, that is.
These cookies are a bit too soft.
They are. I do like our soft cookie though.
How does this affect Mercury in retrograde? I do know Mercury is in retrograde right now.
How does this affect Mercury?
Oh no, Mercury will be in retrograde at the end of the month.
So does that mean it's in prograde now?
Oh, it looks like some kind of planetary scientist.
Indeed. So the eVscope view we see on the left now, that's the first eVscope that was looking at the comet. It's now pointing towards the asteroid. It's just finishing up its move. It's done, so it should be on target. I don't want to do science recording though. I'm going to back out of this. Instead, I want to go to the live view, which I don't want either. But I'm going to start the enhanced vision. So I want to see that the asteroid is really there. It's interesting that this field of view is not nickel, is it? What is that binary pair? I'm wondering if we have like what?
Nothing. You keep thinking. I'm talking to chat.
Oh, give me my cookie.
What? What?
Don't take all the cookies.
Look, all right. If you want cookies, you gotta be quick, right?
All right, talk to chat.
Okay. You can't listen. Okay.
Earmuffs.
And specifically for people in chat that apparently know you. Tom's the smart one. I'm just here to keep people. Yeah. Thank you. Thank you, Cozy MZ.
She knows what she's talking about. Check out Cozy MZ's Cozy game streams on Twitch.
Is that where you came up with the name for this? The Cozy Cosmic Night?
A little bit.
Hey.
I was inspired. Also, people like.
I regret having this camera on now. Oh.
Oh, is that what you were trying to do to me?
No, I put that camera on because I keep looking at it. But
can you switch us to the one that puts us in the corner? The one just to the right.
Boop. Anyway, what I was going to say with Tom's earmuff was while I was being stupid and eating my cookie, and he was thinking of solutions. That's kind of our dynamic.
Yeah.
He's the smart one.
What we do.
I just talk a lot.
Don't sell yourself short. You don't really talk that much.
Thank you. Wait.
So, what are you saying? Or do you have a story, or you...
No, there was no point to it.
Okay,
I was killing time.
gotcha, gotcha.
While you figure things out, because I'm a little stumped about the nickel at the moment. I don't quite understand what it's doing.
Yeah, I agree. So here's the eVscope Enhanced Vision view just popped in. We got a lot of devices here.
Yeah.
So I pointed a little bit slightly different from where the nickel was, but I'm pretty sure when I look at this, if I zoom back out again. Let's see. There are a couple of pairs of stars here. So again, this eVscope image is flipped around, but I'm somewhat confident. Right, is this? I think that's that. Are these two that? And that means that this and this are this and this. So are these two these two?
Then what's
Yeah, exactly. That would have to be.
So this is the next part of
Oh, it must be these.
yeah. This is the next part of astronomy. So we are off.
Well, so I moved. This is the 1025 field, so it's 15 minutes from now. But there's this pair. Could be this pair. They're really bright, and then that could be this. This.
So a big part of astronomy is matching star patterns. That's just to see if you were in the right spot. Oh, you already explained?
A
Dang
little
it.
bit, just a little bit.
Okay.
But it's still relevant.
Yeah.
Let me zoom out here. So this is 19 arc minutes. And what was my, there should be a galaxy in here if the eVscope field of view is right. But it might be just off the edge.
That feels like that's the asteroid.
It is right here.
Looks a little elongated.
Could be. Yeah, it's possible.
I think that's it. Which means that.
Let's keep an eye on this streak here.
Yeah. Oh well, there you go. Just saw it move.
Okay, so all right. So the eVscope is dead on. That's the asteroid there. So
Yeah.
It's starting to move. Good eyes. That's a true asteroid expert.
So we are. Where the heck are we then?
Oh, wait. No, you can't see that. Yeah. So this would be. Yeah, I'm pretty sure then we were right. So this here.
Flip it.
It's like flipped and flipped. And then can we do that in nickel? No.
Wait. What about?
We should probably just be taking data.
Yeah. What about if it's so rotate 90 degrees? Rotate 180 degrees. No, 90 degrees. Yeah. This, there, that. No, that doesn't make sense.
I'm having trouble finding these stars.
Yeah, that's what I'm. It does. I don't think we're in the right field.
Well, sorry. Remember though. So the nickel field of view
It is only 6 arc minutes.
is something like this, I think.
I guess the stars are going to be much brighter in the nickel. Oh, hello, Cassidy.
Hi, Cassidy. I know her.
Oh.
Yeah, so let's see. So in the finder, here's the finder chart. These are the coordinates that eVscopes pointed at. No,
Yeah.
these are the coordinates the nickel's pointed at.
Which
They're
they're
definitely
there.
right.
Yeah.
So now though, if I point to what the, if I go to what the, nope. That's not at all what I want to do. I want the deep link. Fortunately, the deep link is in degrees.
Yay! We can do the math.
Well, 11 degrees.
Here, there's a.
0.11.
We can get a converter. Oh, okay.
I don't know if this will work. It worked.
Yay.
Okay, so 508248. Oh no, I typed in the wrong ones though. So 506.
Do you want me to read it?
294. 7044. Okay. Let's see if I believe it. So does this match that? eVscope. Maybe if I can zoom out more. Yeah, the eVscope needs to be. And zoom out to. So the eVscope field of view, I don't know if we mentioned this, it's about, whoopsie daisy, 45 arc minutes by 38 arc minutes, no, 37 arc minutes, something like that on the side. So you can just about fit the full moon or the full sun in the eVscope field of view. So let's see. We've got 2 bright stars. Could be these here.
2 little close
Or
coopers.
these here.
Yeah, and then that little guy. Those 2 little close coopers. No?
Oh yeah, these.
Yeah.
These
Yeah.
Okay, and they in a line point almost straight to the asteroid, which is about right.
Yeah.
Okay, so we need to make the nickel field of view look like the eVscope field of view. How do we do this?
So what are the coordinates of the
I can
eVscope? Because it's got to be what.
I
So
can read them to you. It's it's 1 minute, 37.02.
uh-huh.
We're gonna move the telescope, folks.
Yeah.
And then it's plus 501.
Plus
Yeah,
501.
It's off by 10.
Yeah, that's why. It's like I knew we weren't in the right field. It didn't make
Well,
sense.
we were
Oh, and then we
half
weren't
an hour
tracking.
ago.
Yeah.
And then 01.6.
Okay. Let's move.
And then let's get ready to take a quick exposure.
No, still, I don't think it's actually mad at us.
Oh,
It's
that's-
just saying what we've done.
Oh yeah, we can close that. It'll pop up again. Right?
Probably, yeah. We can suppress it. Yeah. Okay.
Okay.
On target.
We're
Track.
still on V-band.
Yep. Tracking is off.
I would do.
Too late. We did 150 last night. Yeah. So Rich asked if there was any way we could cheat with a plate solver. I think it's just a case of we weren't. Well, I don't know. We'll find out. In general, the telescope knows where it is. It is correct.
Yeah, we verified that.
I'm not convinced that we went to the right field, which might have been that I flubbed the number that we were going into. Hello, Facebook. So I think I might have flubbed the field that we were going to rather than where we were supposed to be. I'm not sure. I'm pretty sure we were close, but maybe not spot on. We'll have to see. From Argentina.
Yeah, buenas noches.
But yes, so feels like
So look, we're a little bit on the struggle bus.
yeah, we have been cursed
We're gonna
tonight
get there.
with it's been a good time at the very least.
Really, we're not that far behind schedule. The Comet was a little disappointing. I'm not gonna lie, but
Well,
we did see it.
Ariel doesn't need data.
Yeah, we saw it with the eVscope.
She's fine.
No, the Comet was just a bonus. Like I said, that was because there was something that was up in the beginning part of the night that we thought we could.
See,
Yeah, that we thought we could kind of challenge ourselves with.
we challenged ourselves for sure. We were quite challenged.
Okay, so now here's the next challenge.
Yeah.
I'm going to screenshot this eVscope field of view on my computer because we need to take this telescope that's looking at the asteroid right now, which again, for new folks, this wiggly streak is asteroid 2011 MD5, orbiting out near Mars, right? So it's orbiting out near Mars and
Well, no,
moving-
it's orbiting near us. It's in between us and
Oh, that's right. It's a near-Earth asteroid.
Mm-hmm.
Why am I saying that?
Oh.
Yeah, it's a near-Earth asteroid. That's why we're looking at it. But it's moving across the star field. And so our eVscope, as it adds the images up, it keeps the stars fixed in place, which means that the asteroid appears to make a little streak across the image. But we are now currently going to telescope to the Pinwheel Galaxy instead, and make that image go away.
No. So, John Gleason from Facebook asked why we aren't looking at some nice bright objects. We intend to. We're about to do that now.
That's literally what we're doing right now.
This is just a mix of, we have the big telescope on this asteroid. We want to see if we can see it with the eVscope as well. We have confirmed we can see it with the eVscope as well.
So we're still on the stars, not guiding.
So let's see. How does that match with the eVscope field? That, there's two right there. No.
It's flipped, remember?
Yeah.
So wait. You work on that.
Nah.
Or I'll help work on that, but I gotta tend to I also think I need this guy.
Uh-oh.
What?
Goodbye, eVscope. Oh, you moved it.
I undid the enhanced vision, yeah.
Yeah, I was comparing the field. That's okay. No, that's fine.
No, it's fine. I'll stop sharing for a second. And then I'll pull up this shot.
Oh, that's good. Thanks, bud.
And then put this back up. Oop. Don't need to see that or that. Hold on, almost there. Okay,
We
so
did
that's
it.
the field of view.
Yeah. Okay, so then what? Where the heck is this asteroid? Okay, let's first things first. I'm gonna set the target tracker down. I think we can say for sure it's not that.
We can also, if we're really struggling, we can ask Paul. But frankly,
I'm just
the
confused.
telescope's doing what we want it to do. We just don't see the asteroid.
Yeah, I'm just confused as to how we're not seeing it.
Yeah.
All right, so what time is it? It is 5:22 UTC. Okay, smack dab in the middle of.
How are we doing here? Is this right? Yeah. So this telescope's still good. All right, I'm re-upping the science eVscope for another 40 minutes of science. I think we need, I don't think we need
Let me look on this.
Science eVscope is going strong.
Yeah, I don't think we're supposed to be using the apparent. I don't
Maybe
think,
that's what's
I was
wrong.
gonna say I don't think that is. I never used that before.
All right, well, that's what I asked you earlier.
I don't remember that question, but I don't doubt it. Can't I grab this there? Yeah, I think that's the case. That's got to be the problem that we're running into, is that we're being goobers. Or I'm being a goober, and you didn't stop me from being a goober, which was literally like the one job that you have. When you signed up, Frank asked, he's like, so you're going to be Ryan's babysitter, right?
He did say that.
Mm-hmm. Thanks, Patrick. Yeah, have a good night. I just saw you were leaving.
Thanks, Pat. Have a good night. Sorry, we didn't have anything prettier for you.
One day.
I think we're there. Well, we're on the pinwheel, so we will.
Yeah, the apparent is not. I thought it was weird that it was so different.
But the
I'm working on it.
the coordinates were basically what was in the deep links for the eVscopes. No.
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 Well,
But that's what we just did. We moved to where the eVscope is.
there. No. No.
Yes.
Oh.
That was our last move. Was
Mhm.
I read you the coordinates and you typed in the eVscope coordinates.
I wonder if it looks better because it's it was in decimals. If it looks closer because of that, 298 maybe. Honestly, I don't know. Let's just see.
No, we'll try it.
Ooh.
Anytime. Oh, I don't think I actually did it go to you.
Classic.
Indeed.
Yeah. It's like,
Multitasking is hard, chat. All right. Now we will try this again. We will actually go to the Pinwheel Galaxy. So,
Pinwheel Galaxy. I'm going to keep these chips.
it's fine.
Got a carbo load.
You could actually eat dinner at some point.
Uh-huh.
I want to get this working first. Though.
Yeah, me too.
I'm also considering moving the
Oh, everybody's making the watch me die. I can't eat over this.
That's exposing for a minute. I'll be back in a second.
Mm. Yeah, there is something to be said. This has been difficult. I've had lots of observational nights where it's like, man, telescope just doesn't want to cooperate, but this one's been a struggle. Hopefully this fixes it though. We'll see. Hmm. 30 seconds. So I turned the movement rate back on. So the stars should be smeared out when we see them again. Also, I don't like this color. Ooh, I like that less. All right, so already seeing some stars that are smeared out. That's good. Please be in the field, little dude. Yes! Ha ha ha! We got there. All right, so let me zoom in. That is our asteroid. It was a journey, but thank you all for sticking with us. We got there. So I can tell it's the asteroid because it's the only thing in the field that isn't streaked out. Remember that the telescope right now is moving along at a roughly the same rate as the asteroid. So it should be the only thing. It's actually the exact opposite of of this image here, it should be the only thing in the field that isn't a streak. Because the eVscope, when we were imaging it, was tuned in on the stars, and the nickel telescope that we're on is tuned in on the asteroid. So, all right, we got there. So next steps, what do we do now? Let's check the counts. We want to make sure that we aren't underexposing it. And so that is this little value tag. You can't see the screen. Yeah, actually. Remove empty stage. Bam. Okay. So this little control panel over here has the rows and the column. The value here, that means how many counts, like how many light, how many photons did the machine think that it counted for each pixel here? That's what the value is, roughly. It's not literally 1-to-1, but it's good enough for a general idea of how it's working. So basically, the thing we really want to avoid is getting counts that are up in the 50,000s or down in the background. So let's see. Out here, we're getting values of about 1,400 counts. That's what we can expect when there is nothing on the sky. We're not getting any extra light from anything. So we expect about 1,400 counts. For this, we're getting 6,000 around the peak, which not bad. Oh, can't hear me. Why can't you hear me? Okay, so somebody can hear me. Some people can't. I wonder. Okay. Prince Planet. Is anybody else not able to hear me? Okay. Thank you, Yvonne. Let's see. Yeah. Might need to restart. Reload. We found the asteroid. Not us. We don't have to restart. But Prince Planet can't hear us, so
We did it.
might need to reload the page.
Reload the stream.
Yeah.
Not us, him.
Yeah.
Them.
Right. So, okay. For everybody that can't hear me, then hopefully Prince Planet's able to jump back in really quick. Thank you, Katie. In general, looks like we're hitting about 6,000 counts, and the background is about 14,000. So it's not bad. I think the stars themselves were getting their smeared out, and they're 1,800 across the entire thing. We could probably do with upping the exposure time a little more. You okay with trying 200 seconds?
Yeah, why wouldn't we? I guess, right. The only reason is if the stars are going to smear out too much.
Right.
And based on what we looked at last night, I think it's fine. Just go ahead.
Okay, cool. Let's give it a go. So we'll check this, and then if it looks okay, we will basically tell the telescope that, okay, cool. Let us know if it worked, Prince Planet. Hopefully you can hear us again. But yeah, so if this looks good, then we can basically start automating what the telescope is doing and say, hey, yes, these are the parameters. These are what we want to stick with. And we can just say, take 10 images at a time. And we have to do a little bit less clicking.
In the meantime, we have the Pinwheel Galaxy going
Aha!
on the left there. This is M101, Messier 101, the Pinwheel Galaxy. And so this is cool because this has been a target we've been a target we've been observing for the Cosmic Cataclysm Citizen Science Campaign with Unistellar citizen scientists since May, because there was a supernova in this galaxy back in
I think around May 19th, something like that. That was the closest supernova to us in about a decade. So supernova, they are stars that are ending their lives, typically just stars larger than the sun. They will, at the end of their lifetime, go through a couple of different phases. And at the end of those phases, essentially they explode. It's a lot more details than that, but that's the general idea. And that explosion is very, very bright. It's that explosion that is the supernova. And it puts out so much light that that one star, for days, weeks, or maybe even months, maybe not months, but days or weeks at least, it can outshine the entire galaxy that it's in. So these galaxies can have tens of billions or even hundreds of billions of stars in them. So you can imagine the type of extremely energetic explosion that has to happen to have one star outshine all of those other stars combined. Yeah, we caught it part of our plan, or sorry, part of our scheme, part of our science goal, I guess. Yeah. Part of our science goal.
You made everything sound incredibly sinister.
It did. It's very nefarious. Part of our science goals for this Cosmic Cataclysms program is to be some of the first, if not the first, to observe and take data on these supernovae when they happen. They're unpredictable. They basically happen at random as far as we're concerned. And so you never know where or when one will go off. But there's a lot of important information that gets transmitted in their light within the first minutes, hours of when those supernovae happen. And so that's why it's valuable to try to observe them as quickly as possible, even though you don't know when they're going to happen. We do this by we search and filter alerts. Yeah, asteroids looking good. For this Cosmic Cataclysms program, we monitor alerts from telescope, also in California, at Palomar Observatory, which is south of here, near San Diego, California. There's a telescope there, the Zwicky Transient Facility, which surveys the entire northern sky every 2 nights and basically looks for, all right, is there a point of light that is there in the sky tonight that wasn't there last night? Or is there a point of light that was there that isn't there anymore? And then there's some fancy computer algorithms, machine learning, AI, basically, that runs on the images every night. That's from a group called LRC, that then tries to flag, okay, this looks like it could be a supernova or another type of cosmic explosion. Somebody, here's the information, go look at it if you want. And then we look for those every minute, basically, during the night, filter out the ones to find the ones that we can actually observe, and then immediately send that information to our observers. So within about a minute of the discovery by that LRC classification system, we can have our citizen scientists pointing their telescopes at that supernova and collecting data. And for this Pinwheel Galaxy supernova, we were a little bit slow getting on it science-wise. I think we were on it the next day or so. But we actually, because this is such a popular galaxy to look at, and there are so many people with eVscopes, we had serendipitous data from almost all the way back to when the supernova happened. So we had observations from just before the supernova, and then just a few hours after the supernova. And we've been monitoring it, observing it ever since. And so we have now, since May, late May, what is it, September? June, July, August. So yeah, 4+ months of data on this supernova, which I should probably point out to you where it is as soon as I remind myself of where it is. It's visible in this image. It's out on one of the arms, but I get things flipped over in my head. It's either one of these points here or maybe one of these points here, but I'll actually look it up. Asteroid going well?
Yeah, so the little bit of extra exposure time doesn't seem to have washed out the stars, and it gave us a few extra 1,000 counts, which is good. So I think I have said it. So we're taking 10 images now in the middle of, since we've not been doing a great job with the log.
That's fine. We had higher priorities than the log.
Yeah, so working on that, getting that written out now.
So the log is useful for kind of quick reference during the actual observing night. You can look back and say, okay, we observed this long, or we've done these filters, and let's move to a different filter. But basically, all of that information is written in the images in the metadata. So it's kind of written underneath the images in the background, and we can always pull that information out. Though having a good log is always
better than not.
Yes, better than not. NASA, this picture was useless.
One report suggests that 2011 MD5 is a binary system. That is could. So the question is, this asteroid might be a binary, which means that there would be a little moon. And could the pooled citizen science light curve potentially show this? So basically, if we took a lot of light curves we have a lot of people on eVscopes that are observing this asteroid as well. Yeah, no problem, Rich. Feel free to pop in or out whenever you want. Thank you for stopping in. So yeah, basically, this is our target this month for the Unistellar citizen scientists. They are also taking lots of observations of this asteroid. Difficulty that tends to happen with determining if something, to finding binary asteroids, is if you don't have a light curve to compare it to, it's sometimes quite hard to pull out a binary. So I guess I should back up. What does it mean when the asteroid has a binary, and what's that do to its light curve? So the binary, it has a little moon orbiting around it, another smaller asteroid. Sometimes that little moon will be, as it's orbiting, in the right position, where it casts a shadow on the asteroid, and it causes that asteroid to look dimmer than normal. You can have the same thing happen if the moon is big enough, I guess, where it's on the other side, visible, but not completely blocked by the asteroid. You get a little bit of extra light reflected your way. I think that one's less common because the moons tend to be quite small. So yeah, one of the ways that you would be able to tell if an asteroid has a moon is the light curve of an asteroid as it rotates doesn't usually vary that much unless the asteroid itself is tumbling, which is where it's not just spinning like this, but actually like kind of being chaotic and doing its own thing. And tumbling is usually a bit of a slower process. So if you're taking a lot of images of an asteroid over a very close period of time, you can make a light curve, and that light curve will generally look similar to the light curve that someone takes at an asteroid, or you take at an asteroid in 2 or 3 weeks' time. So one of the ways that you can spot whether or not an asteroid has a moon orbiting around it is by taking a light curve of that asteroid and looking to see if there are bigger dips than normal. If there is a dip that doesn't normally appear. So like a dip in brightness that you wouldn't have expected based on that light curve. I think if we had enough data, that would be possible. The first thing we'd have to do is get what does the light curve look like when the asteroid is not being eclipsed, because you have to have that as a comparison. So that would be the first challenge, is we want to make sure that we are getting a light curve that doesn't have the companion affecting the asteroid, affecting the light curve. But I think that is doable. That's what we were planning on doing anyway. The next thing is going to be, are we lucky enough to have an observation occur at the same time where the companion is casting its shadow on 2011 MD5? That one involves a bit of luck if we don't know anything about the companion. And then probably the hardest part for us is going to be how big is the dip in brightness from that companion, because there's some inherent scatter in the photometry. As you're taking these measurements, there's always going to be some noise that gets in the way. And so the question is, would we be able to tell a companion eclipsing 2011 MD5? Will we be able to tell that dip apart from regular noise in the data? That one I think is tougher to say. It would depend on how big the dip is. If 0.3 magnitudes, that would be a pretty big companion.
Can I ask a question?
Yeah.
Can the companion be the same size as the main asteroid?
No. I want to say no. I don't think that is. I think that is
smaller.
I think that is unlikely. You would be able to tell if it was the same size. You'd be able to see it. I guess if it was like 2 450-meter asteroids, but they'd have to be if they were orbiting that close together. There would have been other ways to tell. So I don't think that's.
So probably a smaller movie.
Yeah. I'm working off of gut instinct on this one. I don't have a paper that I could cite. But in my experience with the other moonlets, and maybe Frump, that's a question we can give Frump to.
Yeah.
In my experience, moonlets, the moons around the companion asteroids are always much smaller. I do not think that system would be stable. I think they would either collide with each other or they would have been ripped apart by now.
Okay.
Yeah, so I think that's the tough part, is we'd have to get the uncertainties down. And right now, with the photometry pipeline, for an asteroid that's around 14th magnitude, we're consistently hitting uncertainties of about 0.05 to 0.1 magnitudes, which I think is probably too big to say that we could see the companion. However, I will say I'm a bit skeptical that our defense pipeline, the photometry, is as good as it could be. I find it hard to believe that a 0.1 magnitude is the best we can do. So I'm going to go in the coming time. I don't know. Whenever I have time, I want to go in and really dig into that code and see if I have a feeling that there's some kind of bug that maybe is making our scatter a little bit worse than it actually is.
Yeah, we're always looking to improve our methods.
Yep.
We're always looking to improve our methods. Basically, we go through a lot of data sets every day, and we want to process them automatically. And so doing that sometimes means compromising a little bit. You go for speed rather than accuracy. We're still accurate, but you sacrifice. There's always trade-offs.
Yeah, you can't always get in for problematic data sets and do it yourself. In that case.
Sometimes you can, but we have only so much time, and there's only so much you can do sometimes with poor data also. I want to interrupt though. So I did finally point out where figure out where that supernova is.
Isn't it down like there?
Yeah.
Oh.
Other side. So it is, if you look at other images of the supernova, it's down and to the left
Oh, but
of the center of the galaxy,
flips
but
it.
the eVscope has, the native image that it shows is often flipped on the sky, and that's just the way that the optics in the camera are oriented at the moment. It's this little point of light next to my cursor here is the supernova. It was much brighter in the past. It is fading over time. It's faded by a factor of, I don't know, it's faded by several magnitudes, so that's something like a factor of 100 or so, ish, probably more. And it'll continue fading until basically it fades away and we can't see it anymore. But we're continuing to measure it every day, essentially, and we're building up a light curve, kind of like we're doing for this asteroid, where we're seeing how the brightness of this supernova decreases over time. Well, first it increased, and then it turned over and started decreasing. So that's the Pinwheel. It's a cool galaxy, spiral galaxy. I didn't really talk about it much, but it's a spiral galaxy, just like the Milky Way that we live in. So it's always a galaxy. Yeah.
Oh,
Did you know that?
that's crazy.
Yeah. We live in a galaxy that looks probably somewhat like this. It's got the spiral arms with the stars in it. The new stars are generally born. Younger stars exist in the arms, and so they tend to be a little bit bluer in color. We can get to the why later. So the arms tend to be a little bit bluer or whiter, and then the older stars, after they're born in the arms, tend to drift into the space between the arms. And so you often see those stars are fainter, there's less light between the arms, and they also are redder, because those stars that hang out there tend to be older. So yeah, that's the Pinwheel Galaxy, and we're gonna move this eVscope on to something else.
Grab some water really quick. Would you like anything?
No,
You have a cup
thanks.
for me to eat the water up with.
No, I'm good for now.
Okay.
So we'll end that enhanced vision. We did about 20 minutes. That was the view after 20 minutes for the Pinwheel Galaxy. Next up on the list is a nebula, I think. Let me look. I want to say it's the Eagle Nebula. Yeah, it's the Eagle Nebula indeed. We're a little behind, but we'll still get it. No problem. So you can look through our little catalog here. This is how the eVscope finds things. And yep, M16. No, it's the Eagle Nebula cluster. That's not quite what I want. Did I go past it already? Easiest way to find it is just search Eagle. Okay. Go to. And you'll see some streaky stars. The telescope is now moving and pointing towards the Eagle Nebula instead. I don't know if we mentioned this earlier, but it's probably been long enough that I'm not repeating myself. But when we move a telescope, or when a telescope is moving, we call that slewing, S-L-E-W. It's just a technical term for moving, but it's kind of like, it's on a fixed pivot point, and then it swings around, and the swinging around and up and down is the slewing. So if you want to sound like a professional astronomer, tell people that you're slewing around when you're doing stuff, mopping the floor. I don't know, whatever you do, swinging baseball bats. And our asteroid observations are still chugging along. All right, probably. I have a sneaking suspicion that the Eagle Nebula is behind something like
a building, perhaps.
Yeah.
Mayhaps.
Let me go poke my head out. In the meantime, let's go to the next target, which is the Ring Nebula.
Yeah, that should be no problem. And I'll look back up. I'll look up again. No thanks.
Can I interest you in red berry French bread pepperoni slices?
Southwest. It might have been behind the building. No. Sure. I'll take one of those, please.
I'm trying to cook us dinner.
Yeah. Thank you.
No problem.
All right. So we're going to move to the Ring Nebula. I have a feeling the Eagle, with where the telescope is right now, the Eagle is behind the edge of the nickel dome. Actually, it was a little farther south than I thought it was. So instead, we will do the ring, which I know is a good one.
This still requires an oven.
Nah, just cook it in the microwave. Nothing really requires an oven. You can microwave just about anything.
You're a literal monster. Oh.
Yes, but I am always well fed.
Actually horrifying. I don't know how your wife deals with this.
I don't know either. All right. Let's see if I lost my Wi-Fi connection here. Or if the telescope has gotten where it's going. eVscope here will be back in a sec.
Oh boy! With so much chocolate and caffeine. I think my heart's gonna explode.
That'll be exciting.
That would definitely be good content. Which is what I'm here for.
Okay.
We should start a YouTube channel.
I think we did. Isn't that what we're doing?
It is part of it.
Isn't this the launch of our YouTube channel? All right, chat, we're back. So here is the live view of the Ring Nebula. This is what the camera sees from the eVscope, basically in real time. It doesn't look like much, but it is there. It's ring-shaped. It's this ghostly ring thing in the center here. But when we turn on the enhanced vision mode, that's when it'll actually start looking like something cool, and we'll see a lot of color popping out here. Any minute. What are you doing?
Take a picture.
All right. You know this whole thing's being recorded, right?
Yeah.
Okay. Just saying. So the way the enhanced vision works, I don't think we could explain it again if we have. And this lag here is not the telescope; it's my Wi-Fi connection to the telescope, which has been a little bit spottier than it was yesterday.
Well, I can see you playing Baldur's Gate 3 on Discord.
Let me check this real quick.
I appreciate you watching this in the background.
So the one challenge, well, not the one challenge is silly. One of the challenges for tonight is we need the telescopes to be far away from the building, the eVscopes, I mean, to be far away from the building so the building doesn't get in the way of them and they can actually see the sky. But we also need to be able to connect to their Wi-Fi signal, which is how our devices or tablets or phones connect to the telescope to control it and to see their view. Apparently, the walls in this observatory building are very thick. Either that or they're full of lead or something, which means that the Wi-Fi signal doesn't really get through very well. So
Superman either. Well, he can. He just can't see through it.
Yeah, he just can't see through it.
And so we have Wi-Fi extenders set up to boost the telescope signal to reach us. Because even though they reach pretty far on their own, we push them beyond what they're designed to do. There we go. Ta-da! So there is a much better view of the Ring Nebula. So all those points of light around it are stars. Thank you, sir. And then the ring is the colorful stuff in there. You can see, so I'll talk about a little bit what this is in a sec. I think I've basically finished my story about the eVscope connections. And so occasionally, if the image is lagging behind, the telescope is doing its thing, because once you tell it what to do, it just does it. It doesn't care if your phone's connected to it or not. But what that does affect is what we're seeing here. So sometimes it's just enough to disconnect and reconnect. Anyway, you can see here the little counter at the bottom. It says 3 minutes. So this is 3 minutes of images that the eVscope has added up. And what we're seeing is a planetary nebula. So what that means is, so a nebula in general is a giant cloud of gas and dust out in space. It usually is very large. So nebulae, at least the ones that we can see from here on Earth, are many, many solar systems across. You could fit hundreds, thousands, or more of our solar systems inside of a nebula. There are almost certainly smaller ones out there. They're just a little too small for us to see or to see well. The way that you get a planetary nebula like this has nothing to do with planets. It is completely a misnomer. One of those historical quirks happens quite a lot in astronomy.
Yeah, we don't like renaming things.
Yeah, it often comes because people would look at the sky, they would see something, and they would think, okay, maybe this thing comes from this other thing, or it's related somehow. And then it turns out, after more people study it, it has nothing to do with that first thing they thought it did. For example,
don't blame
galaxies.
Yeah.
Sorry, yes, galaxies, other galaxies outside of our own, were originally thought to be nebulae.
Yep.
People thought that these fuzzy blobs on the sky were just clouds of stuff. They didn't realize they were full of billions and billions of stars.
I mean, they weren't wrong.
There is stuff in galaxies.
They are clouds of stuff.
That's true, but the light we see for them is not the gas and the dust. At the most, at least,
right.
It's the stars.
Yep.
And so, I forget. Do you remember what was the original term they had for galaxies? It was, I'm such a bad astronomer. But there was a famous astronomy debate.
Yeah.
Over what are galaxies? Are they basically close to Earth and cloudy things like nebulae, or are they really, really far away and they're actually full of stars like the Milky Way?
They were known as spiral nebula.
Yeah, so they're right. There you go. Their early galaxies were called spiral nebulae. Because again, they looked like a nebula through those early telescopes that people had. And there's like the Shapley-Curtis debate. Is that, I think, what it was? Yeah, these two astronomers.
Shapley. Arlo Shapley.
Shapley and Curtis were the ones debating it. I forget who was who. But anyway, planetary nebula, long story short, nothing to do with planets. This is what you get when a lower mass star dies. So I talked earlier about supernovae. When you have a high mass star, a star bigger than the sun, when that dies, it explodes as a supernova. When a star like the sun or smaller dies, and by die I mean reaches the end of its natural cycle, where it produces light normally. So the sun is bright because it fuses or combines hydrogen atoms into other elements. Stars can only do that for so long before they run out of hydrogen. And so once that happens, we kind of consider the death of the star, the end of the star, even though they often go on to do other things, which is what happened in this case. So this star, possibly like the sun to begin with, reached the end of this lifetime. In the process, it swelled up quite a bit larger than it was originally, into what we call a red giant star. As it did this, the center of the star, the core, actually contracted and it got smaller. And this means that the gravity from the center of the star became weak on the outer fringes, and the star lost hold of that outer layer of gas that it used to be able to hold on to. And so that outer layer of gas, all the stuff that's basically not really gravitationally tied to the core, gets kind of drifts off into space, and actually the light from the remaining star helps push it away. And so that gas that is drifted away is what we see in the nebula. It gets lit up by the star that's left at the center, which ends up being a white dwarf star. It's in a late phase of stellar evolution basically it's small. The star becomes kind of the size of the Earth, and very hot, but because it's so small, it's not very bright. But it's bright enough that its light illuminates the gas, kind of like a neon lamp, or more like a neon lamp than a fluorescent lamp. But and the glowing gas is emitting these different colors, and so the different colors map to different elements. The red around the edge, which is a little bit tougher to see here. Maybe if I zoom out a little bit, yeah, that kind of helps. I wonder. Let's see. Let me drop out of here for 1 sec. Do I have night mode or something on? Just want to check. No, I don't. Okay. The red. Here's my mouse. Around the very outer edge is mostly from hydrogen gas. So it's the most abundant element in the universe. Stars are full of hydrogen. Even when they're older, they still generally have a lot of hydrogen left. And then there's the bluish stuff, I think is often oxygen carbon, some mix of those elements. And then there's some greenish in there, I think is helium. Or is that also,
I think that's also
oxygen. Maybe the greenish is oxygen, and the bluish is more carbon. But there is helium in here as well. These are things I should remember, but at 11 p.m. it's getting a little bit more complicated. And so this nebula, let's see, I can look up the stats. So if that's not what I meant to do. The eVscope app, Unistellar app, tells you information about this. So for example, these planetary nebulae don't live very long. They are created, and then within thousands or tens of thousands of years, they tend to expand so much that they just get really thin and fade away. And at least we can't see them very well from Earth. So this one is 6,000 to 8,000 years old, which in astronomical terms is like super young.
Yeah.
Our galaxy is 4.5 billion years old-ish, more.
No, the sun is 4.5 billion years.
Our solar system is 4.5 billion years old.
The galaxy's older.
Yeah, the universe is about 13-something billion years old. So 6,000 years is nothing. It's 2,290 light years from Earth, so that's actually also pretty close in terms of astronomy scales. Let's see, so that's 2,000 light years. Trying to get some scale here. So that's 100 parsecs. So it's less than a kiloparsec. Because the Milky Way is something like 8. We're like 8 kiloparsecs from the middle of the Milky Way, right? It's like generally 15 in radius.
Yes,
yeah.
Radius, yes.
Yeah,
right.
so let's say, this, the distance to this nebula is something like, I don't know, a 40th or a 50th of the width of our galaxy. Maybe not a very useful size scale after all. It started out better in my head. And the last note here is that it's expanding at a rate of 30 kilometers per second. So if you're used to the metric scale, it's fast. It's pretty fast. Yeah. So that shell of gas is expanding really, really rapidly. We don't see it happen in real time because it's so far away. You just don't see that expansion happening. Let's see, is there anything else of note here?
Someone angry react. That's something. It was several hours ago, but just seeing it now is very funny.
It's funny. So that's the Ring Nebula, planetary nebula. And one of the more well-known ones, the ones that gets observed the most. It's really quite tiny on the sky, though. You can see it when I zoom out. You know, compared to stars, it doesn't look that much bigger. Do you have a favorite nebula, Ryan?
Favorite nebula? I mean, I really like the Thor Nebula. But the Ring, the Cat's Eye, all of those are beautiful. Beautiful to look at. Trying to think. Actually, so when we were doing that event, the outreach event, where was that? I forget what that was called.
The Montalvo Art Center?
Yeah, that one. Sorry, it's too late. It's hard for me to remember names. When we were doing the outreach event there, I guess last month, I ended up going to a nebula I'd never heard of before called the Snow Globe, which admittedly, I'm willing to bet it probably is a rather famous one. I just hadn't really seen it, but that one looked really cool. Snow Globe Nebula. Nope, that's not the picture we want. Yeah, so looked kind of like that. Basically, it looks the Snow Globe Nebula just looks like a giant ball that's just kind of out in space. It's kind of like the Ring Nebula, but a little bit more red through the eVscope. But that one was very interesting. And this outreach event was primarily aimed at younger kids watching the Perseid meteor shower. So they loved that. Thought it was the coolest thing ever. Hello from Sicily.
Ciao. What time is it there? Is it morning?
I don't know.
Morning, right?
I don't know.
Yeah. Buongiorno.
Oh, jeez.
Buona mattina.
Oh, jeez.
Ryan, you've been studying Italian.
I did my Duolingo while I was in the bathroom so that I wouldn't lose my streak.
But have you been studying Sicilian?
No.
Okay. That's
8:11. This is early.
indeed. All right, so hi from the Czech Republic as well. I missed that one. I don't speak any Czech, I'm sorry. Though I believe it does have some similarities to the Romance languages. So we have the asteroid occultation coming up soon.
Oh, yeah.
We're nominally supposed to start heading to that in about 8 minutes, which we can do. I need to figure out, so the nickel's not going to look at that. That's going to be an easy, okay. Well, we can, but I didn't think we'd take away.
Yeah, it's probably better we focus on the asteroid. That is what we got time for. So
yeah. So the limit with the nickel is we have to do some adjustments to take short enough exposures.
Yeah.
The general short exposure time is 3 seconds, and this occultation I think would be over in 3 seconds. So we will look at it with the EV. I think we'll just do one. Do we need to do 2 eVscopes? The asteroid one is currently in between observations, so I wasn't going to
I don't think there's a benefit to do. If we catch it on one, then
okay,
that's good enough. Hi, hello from Bharat.
Where? I'm sorry, I don't know where Bharat is. What country is that? Ooh. Showing my international ignorance.
It's a name for India in various Indian languages, so it's India.
Right.
Hello, much love. Well, thank you for stopping in. It's very cool that we're getting people from all around the world. Just appreciate everybody who's stopping in. Which also, that reminds me, we were told that it was a good idea every 15 minutes to give a recap of who we are and what we're
15
doing.
minutes is a little often.
Yeah, Frank.
Redo it.
Take that.
Yeah.
Yeah. So thank you everybody who has stopped in, even if you have us on in the background. That's actually, we kind of like that. We had always envisioned this as being just a kind of fun hangout stream. I'm Ryan, and this is Tom. We are both astronomers, and we are currently hanging out at a professional telescope in the Lick Observatory in California, USA. And we both work for SETI, the SETI Institute. Hello, Paul. And so we got time on this telescope, and we kind of figured it'd be fun. Actually, this was your idea, so I don't want to steal credit for it. I think this was a really cool idea. But we figured it would be fun to share what it's like to be on a big professional telescope with everybody else. We have some plans, and we're just kind of hanging out. So if you have any questions, feel free to put them in chat. If not, we're just kind of hanging out, vamping, talking about what we find interesting. So we're happy to have you here. Thank you all so much for joining.
Yeah, and actually, it wasn't fully my idea either. It was kind of a joint idea with Joy Asensio, who was at the time was an intern working with Unistellar, visiting us in the United States, He helped actually created the planetary defense campaign at its inception. So we had this idea, and fortunately, that was kind of back in lockdown times. A lot of it, things were getting pretty complicated, and we never quite made it work while he was here. But Joey, if you're watching, we did it. Wish you were here to do it with us, but maybe next time. We're hopefully, if this ends up going well, maybe we'll do it again. No promises, but we will see. Okay, so I want to let's see if we can do this.
All right. So while you're doing that, I'll give a short explanation, I think, of occultations.
Yeah.
Missed a few hours earlier. I suppose those streaks on the right side are satellites. So actually, Paul, what we are looking at right now is an asteroid. Because the asteroid is moving faster than the sky is moving, we have the telescope following it so that it stays a nice circle. So those streaks aren't satellites. They're actually stars that are field. It's just that while we're taking a 200-second exposure, the asteroid's moving and the telescope's moving, so it causes the stars to kind of streak along rather than stay nice and circular. But yeah, so we've done some satellite observations, not on the nickel, but with personal telescopes. Okay. With personal telescopes, the eVscopes, we can get short enough exposure times to observe satellites, and they do. They look a lot like that, essentially. Maybe a little more stretched out, but very similar. So yeah, okay. Hello from Mexico. Thank you for stopping in. So occultations. What is that? What are asteroid occultations? I really think these are very cool events. An asteroid occultation happens when an asteroid passes in front of a star. And so from our point of view, the star looks like it blips out for a minute, just kind of disappears. You can only really do these on very bright stars because the asteroid is moving pretty fast and stars are not very big. So the asteroid's like in front of it and then back out away really quickly. So what is actually happening in that case is that the asteroid is casting a shadow, and that's what I think is so cool. We can actually see the shadow of asteroids on Earth, and they're only a few kilometers across, a couple of miles. So they're very, very small. They're very easy to miss, but we can see them. We can see the shadows that asteroids cast on Earth as they're passing in front of stars, which is just the neatest thing I think I have ever heard. That I did not know these existed until a few years ago, and I think it's neat. So what do you do with these? So the best thing you can do is you can get asteroid shapes. If you get one line. So let's say you're hello from the Netherlands. Nice to see you. Thank you for stopping in. So yeah, the nice thing about that you can do is if you have a telescope in the path of one of these occultations, you basically can measure how long does the star disappear for, and that gives you a pretty good idea of how big that asteroid is. If you know how fast the asteroid is moving, you know how long the star disappeared for. You know at least for that little length of time where you were, that portion of the shadow, you know how big that asteroid is. So one line on its own, one person getting an observation of an occultation is impressive, but not. It's useful, but not super useful, right? Like it gives you a really good idea. We know exactly where this asteroid was, confirm that we know exactly where this asteroid is in the sky. But the real power of occultation events, of catching these asteroid shadows, is if you have multiple people in the path, and even if they're outside of the path. So usually what happens is you have some predicted area where the shadow is going to fall. You have some general idea, okay, it's going to be somewhere in this 5-kilometer spread. And you want to send people out along in various intervals along that path, all the way across that 5-kilometer, here we go. Thank you. Oh,
Sorry.
how dare you?
What did you want to see?
I wanted to see that. So this is our path.
It's
loading in the map behind it.
No, it's not.
How dare you?
Yeah, hold on. I can get you what you want.
Anyway,
what you want. Wait.
the point being.
There you go.
Okay, so yeah. Chef's kiss. So the orange lines. What are the orange lines?
Start with the red line. The red line is the center of the shadow.
The red line is where it's most likely to be.
Right, and so the orange lines are some uncertainty over how wide that shadow will be. So I forget exactly what the uncertainty level is. I always forget.
That's why I asked you, because I didn't know.
Yeah, in about 2 hours, we can ask the occultation expert who works with us. If he's in chat right now, maybe we can put it in. But yeah, there's some uncertainty based on our knowledge of the asteroid's orbit, exactly where that shadow will fall on Earth.
I'm doing my explanation. I just wanted to know the thing. All right. Anyway, thank you.
Mm-hmm.
So anyway, yeah, what you want to do is send people at various points along this path, because yeah, you don't know exactly where the shadow is going to be. You don't know exactly what the shape of the asteroid is going to be, and so depending on who sees the star disappear and who doesn't, you can get a really accurate idea of how that asteroid is shaped. So not one occultation, you get an idea of how long the asteroid is along that one section that you were at. 10 different people spaced evenly across this path. Well, now you're cooking with gas, and you have 10 different parts of the asteroid where okay, so the star disappeared for a second from this leftmost region out over here. The star disappeared for 3 seconds in the center, and the star disappeared for 2 seconds out to the right. We know that it looks kind of like an oval now. So you can, if you get enough of these occultation observations together, figure out what the shape of the asteroid is, on top of figuring out exactly how big it is and where it is in the sky. There's very little that you can get a better estimate of where something is in the sky than when it passes in front of a star. So that's what we're hoping for. That's what we're going to try and find. These events are happening all the time. They are constantly, there's tons of asteroids and there's tons of stars. The real question is, are you in the path, and is the star bright enough for a telescope to see? Because this is happening so quickly, on the order of 1/10 of a second, 1/2 a second, you can't have very short, or you can't have very long observation times. We're exposing for this asteroid, we're opening the shutter on our camera for 200 seconds. We would need something like 1/10 of a second.
in order to catch an occultation event. So you need something bright where a 1/10 of a second is going to be bright enough to still see that star. So they're happening all the time, but they're also hard to find one that you can actually observe. But we found one, and we are now sending the eVscope out towards it. So what asteroid is this? This is
2005 TX14. So this is the Mars crossing asteroid that I was confused with earlier.
The name rolls off the tongue. You really like that.
So that means I guess it's near the asteroid, the main asteroid belt, if not in it. But it is crossing Mars's orbit, is what that means.
Yeah.
I don't know where that means it lives. If it just actually orbits near Mars, or
well, it means
if it lives most of its time past Mars and then occasionally swings in, or if it's the other way around.
Yeah, I'd have to look to see. I don't think it would. I think that would mean that it probably doesn't cross Earth's orbit ever. Very likely, it's basically if you took an Earth crossing orbit and you made it bigger so that it crossed Mars instead of Earth. Which means that it would be in between Earth and Mars.
Okay.
And in between Mars and Jupiter.
Sure. Yeah, there's a lot of that solar system jargon that
Yar. I don't know what kind of orbit that's called.
You pointed to the target here, I thought.
Mars crossing orbit.
Okay, so yeah, we're on target for the occultation. It should be one of the stars near the center of this field of view here. When the time comes, so that the actual predicted time of the asteroid passing in front of the star for us here in San Jose-ish at Mount Hamilton is about 35 minutes past the hour. So something like 9 minutes from now. We'll start recording science images before that, and then let the telescope just keep collecting data for a few minutes before the predicted time, then a few minutes after. I think the shadow has already passed the east coast of North America. It was supposed to start sometime around 13 minutes after the hour. But it takes something like, the prediction says it'll take about 20 minutes for the shadow to cross the continent. So this here is just a static image on the right, but this map extends all the way to the east coast. I think it ends up somewhere in southeastern Canada / far northeastern United States. So yeah, we're gonna wait a few more minutes. Occultations take very, very short exposures. Well, at least for us. So 300 milliseconds, 0.3 seconds per image, which means that it has to store a lot of images on the telescope. And because we're looking at a lot of things tonight, I don't want to record more images than we need to. So we will just kind of hang out for a little bit there. In the meantime, we can minimize this map a little bit and keep that other asteroid, not to be confused with the occultation asteroid, keep that in the background. So the nickel is still looking at our near-Earth asteroid, 2011 MD5. And that's this point of light here, Ryan mentioned earlier.
Mm-hmm.
So you can see here in the eVscope settings, get rid of this window.
Doing another series of 21 MD5 observations.
Is there a way I can make this go away?
Make what go away?
This little controller.
Oh yeah, I see. I don't know.
Anyway, you can see here in the eVscope, the Unistellar app window, we have camera control settings. 300 milliseconds for the exposure time, and then there's some electronic gain that we apply to the sensor in the eVscope camera, and that is a way to kind of boost signals from faint objects without taking longer exposures. Basically, it's an electronic way to multiply the signal you get from every photon. It does introduce some noise, so if you could always make it work, I think you'd prefer to do longer exposure times and lower gains. But like in this case, we need to take very short exposures because the occultation event itself doesn't last very long. It lasts a few seconds or even maybe a fraction of a second. You can't take a 10-second exposure because the occultation would just be kind of averaged out by the time when the star wasn't being occulted. So you need to take lots of short exposures instead, where you see the star is bright, 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 and then faint, 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 bright, 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 bright. Mm-hmm. So that's one of the technical challenges of occultations.
Hello, Elliot. Thank you for stopping in. Hello from Laser SETI, now as always observing from nearby Sonoma County. Glad you could stop in. Thank you for stopping by and saying hello.
Cool. Laser SETI. So I believe that's looking for laser signals from extraterrestrial intelligence, which is a very cool project. We've often thought that if we needed to communicate with someone over very long distances, you might do it with a laser.
Yeah.
Because you can pack a lot of information to a narrow little beam that keeps traveling through space. All right.
It's extra funny if it just hits somebody in the eye.
That too.
Goes through space and some poor guy's looking up and just like, boom!
That's one of the hazards of interstellar space plane travel. All right, I think maybe one more minute and then I'm going to hit go.
All right. What time is it supposed to occur exactly again?
Somewhere around 6:35.
Okay.
Ish. Sorry, yeah, 6:35 UTC, so 11:35 local Pacific time.
Oof.
And I'm just waiting. I guess I'll save those settings and then cue this up to start the recording. And I'm just going to hit go. And we are recording. And you can see the graininess of the image is because of the short exposures and the slightly higher gain. And it's a little bit more noise per image, but we get that short, what we call cadence, taking one image very often. Now, if I go back to live. Oh, no, I don't want to. I don't want to cancel. Keep going. If I turn this sideways, what happens? It's a little better. So bring. So, oh, you can. Yeah, but I don't know exactly which star it is, so I didn't want to zoom in too much.
Yeah, well, it doesn't say anyway. So
okay.
It fights.
So yeah, so chat. The trick here is keep your eye on the stars, and we will try to see if we can, by eye, see the occultation happen. So if we do, one of those points of light in this image will wink out for a second or so, and then it will come back. It might not wink out completely. It might just dim by a lot, but that'll be the trick. And so I think it should be one of the ones near the center. So I'm going to be looking at these two.
Yep.
But if anyone wants to pick a favorite star, we should have put money on this. Which star it is?
Yeah.
But we'll see if we can see it. And so that we're about 2 minutes away from the most likely occultation time.
So the way that I go about it is rather than focusing on any one star, just kind of looking at the center of the image and moving your eyes every now and then a little bit so that your brain doesn't get rid of the stars at the edge of your vision. But this is an astronomy trick. Your peripheral vision is much, much better at discerning differences in brightness. So as long as you are focusing on what your peripheral vision is seeing rather than the center of your vision, you could probably have a better chance of seeing the star wink out in theory.
It's called averted vision.
Yeah, sure.
It's because if there are any optometrists out there, shout out. But
love your work.
It's the two different kinds of cells in your eye, the rods and the cones. The cones are better at seeing color, but need high light intensity. They need bright light. The rods are better at low light seeing, but they don't give you the color. So that's why the stuff at the edges of your vision will often be less colorful, but you'll see fainter things there. And in astronomy, that definitely helps.
It helps us see some of the stuff through telescopes when you're looking through an eyepiece.
So it should be any second now if it's going to happen. I'm on the edge of my seat.
Well, don't fall.
And there is some.
Did that? No.
There is some lag because of the stream. So it's possible that we actually record it but do not see it live. We will process these data and actually get back to a real result.
Yeah, when we process the data, we'll know exactly which star it is that we're supposed to be. That is supposed to be. Oh, hello, Marianne from Malta. Oh, no worries, Russell. Thank you both for stopping in. Yeah, the focus problem. Focus problem for eVscope. Was there
the nickel?
Oh, the nickel. Yeah. Okay. That's why I was like, I don't remember a focus problem for the eVscope. Yeah, we got the focus problem fixed. It's been a journey tonight, Russell. Thank you for stopping back in. But we finally got there.
So I think the highest likelihood of occultation time has passed.
Yeah.
So I didn't see anything happen.
I didn't either.
Which could be one of two things. One of a few things. Let me finish eating here.
No, go ahead. Everybody wants to see. I feel bad. You have had that all the time. You haven't had a chance to eat.
It is nice and lukewarm now. So either we were not in the path of the shadow, very possible.
Still useful as well, because that lets you know the limit of the asteroid where it wasn't.
Right. Or we were in the path of the shadow and we just didn't either notice by eye that the star blinked away, or it didn't actually get transmitted over the stream video. Those are basically, I guess, the two possibilities. If we were in the path, the eVscope would have recorded it. So we will get back to you, I guess. Mm-hmm. We'll post it on our citizen science results at least.
How long were you? 24 minutes.
No, I'm gonna stop it.
Oh, okay.
We've done almost 6 minutes of recording.
Yeah.
I'm gonna let it go another 30 seconds or a minute. Yeah. So the entire event crossing North America was about 24 minutes.
Yeah, I see.
So that's why the recording duration was set for that. So we'll see what we get. Unfortunately, we won't have a chance to process it until we can bring this telescope in and upload the data from it. It's got more work to do tonight, so no rest for the weary telescope.
Did you hook the telescope up to the giant battery?
No,
Oh, okay. Okay.
you didn't need to.
All right. Okay.
They're fully charged, so they should last much of the night, if not the entire night.
Oh, all right.
Sick. We'll see. The occultations requires a lot of power because it's going to write something like, well, you can do the
That's
math.
probably several thousand images in that.
Not quite
What was the
that many.
what was the exposure?
300 milliseconds.
Oh, okay.
So I'm going to stop this observation. It warned me, that's fine. I'm not going to bother doing any calibrations for this observation because they are not used for occultations. And we're done with that. So asteroid occultation observed. Or not. We'll see.
Yeah, maybe. I mean, we observed something.
We did indeed. We observed, but maybe not detected.
No result is still a result. Don't let anybody tell you different.
All right, chat. What's next on the eVscopes watch list? Dumbbell Nebula coming up. We're right on schedule, baby. All right, so we will look at the dumbbell. This is a classic, chat. If you haven't seen the Dumbbell Nebula, you haven't lived. Yeah, we've been taking data on. I'm not doing a great job of staying on top of the other one. It's recording.
Okay.
But I'm missing the gaps, so we can either
That'll be
start
fine.
setting alarms, or we can just both try to pay attention.
Yeah, I'll pay attention to it. I forgot that this one was also running on the asteroid stuff.
Yeah. Actually, let's. Can you come back to the planetary defense ones? Is this gonna?
No.
Okay. We're almost on the dumbbell. See, the telescope will get close, and then it does one kind of final fine adjustment. It had to swing all the way around the sky to get here. It was pointed in the east. No, that's not. Yeah, it was pointed southeast-ish, and now it's pointing west. And we're there.
Oh, you saw my banner.
What?
Never mind.
Oh, I did see your banner. Sorry. So let's see if you can see it. So this is the live view. There is a fuzzy cloud in the live view that has a vague dumbbell or hourglass or bow tie shape to it. And I'm tracing with my cursor. That is the Dumbbell Nebula. And so if you were to look through a small or even a big telescope with the naked eye, that's about what you'd see.
Mm-hmm. We actually looked at that last night.
We did. We looked through that 36-inch refractor next door, and that's more or less what we saw.
Yeah.
It wasn't as grainy because you're looking through lenses with your eye, not a camera, but same cloudiness. But when we do the magic button.
In the meantime, Siders SJ on YouTube says that they think they might have seen the occultation. So,
Okay.
All right, yeah, upload that data. Let's see what happens.
Yeah,
It'd be very cool to have caught it.
I think that's Jennifer, one of our citizen scientists. We'll see what we get. Thank you for observing.
Yeah, appreciate it.
Yeah, that's Nebula. That dumbbell's starting to come out. That's
The colors.
8 seconds, 12 seconds of enhanced vision. It's really going to start shining soon here. This one's going to look pretty good. We looked at this one last night. And I think we had more citizen scientists observing that occultation as well. So hopefully at least one of us got it. Let's see, we've got the Hercules globular cluster is up next after this. And then the Andromeda Galaxy, that's a classic. Our big sister galaxy neighbor. Big sister neighbor galaxy. And
we'll continue looking at stuff with the eVscopes, but we'll talk about some citizen science highlights from the last year or two, I guess. And then we'll have our special guest talk more about asteroids and citizen science and whatever else comes up.
Yeah, that's what I was saying. I mean, we talked about pretty much anything and everything with Ariel, so.
Let me move this. We'll move this back. See the guy. It's kind of fun to see the exposure happening. So can I? Is there a way to? Let's see. Maybe if I can just move this on top a little bit. Is that acceptable for us? So, I like seeing the little countdown.
Yeah, the countdown is nice.
It proves we're actually doing something. I don't know if it proves it, but it
proves it.
It's
beyond the
strong
shadow of a
evidence. So, okay, I didn't talk about the Dumbbell Nebula. Again, this is another planetary nebula. So if you were here when we were looking at the Ring Nebula about 45 minutes ago or so, it's same phenomenon. So there is a star at the center of it that went through its full life cycle. Basically, it's now a white dwarf star, and it has expelled its gas into space. And just something about how probably the wind and the light pressure from that star pushed away that gas is what gave it this characteristic dumbbell shape. You can kind of determine where the pressure that is exerted by the star goes based on a bunch of different factors, which really I'm not an expert in, but I think oftentimes in astronomy, when we don't understand what's happening, we just say it's related to magnetic fields. So that's what I'm going to go with on this one. The sun has a very influential magnetic field. It's actually, I believe, the magnetic field on the surface of the sun is quite weak, weaker than a pretty standard magnet that we play with in our daily lives. But there's just so much of it that it has quite a strong influence, and the star would have something similar. So again, you can see all the different colors, and you can really see the red on the outer edges here, and the blues and the greens. I'm just looking something up, and I'll be.
Are you looking up the color?
I am. I want to get a little more detail on the elementals split on the colors. I don't want to be wrong again. So anyway, I'm trying to pull it up. You may, let's see, I don't know. At the end of the night, we might be looking at, we have more nebulae, which is the plural of nebula. We have more nebulae in our list for tonight. A bunch of them are planetary nebulas. That's just, they are particularly bright and colorful, the ones that we can see. But there are other kinds of nebulae. And so you might be thinking of some others that are kind of on the other end of the spectrum. So those are something like the Orion Nebula, which will be up at the end of the night, and I think we might try to get before sunrise. Or the Eagle Nebula, which we didn't quite get to before. Maybe I'll check if that's up in a little bit, or still up in a little bit. But these are
places where new stars are born. So these are what we call stellar nurseries. They are still giant clouds of gas and dust, but they don't come from the deaths of stars like this. They can include gases and dust that are created by dying stars, but I think more of their content comes from that raw material from kind of the early young days of the galaxy, where you just have these nebulae are even denser, and you have just clumps of hydrogen gas, hydrogen molecules that are getting pulled together by gravity, and then you pull enough gas together like that, and you make a new star. And so that's what's happening in something like the Orion Nebula. So at the other end of the stellar evolution spectrum.
Sophia, which actually I know Sophia is spelled like that, but I don't know if you're the Sophia I know. So hello, nice to see you. But we have a very enthusiastic call to look at the Eagle Nebula at some point. So we will get to that one.
I see. I mean, we can take a look at where it is, but I have a little bit of a worry that it's down low now. So the Eagle Nebula is a great, it's 18 degrees to the southwest. We can take a quick shot at it after this dumbbell here. Because that is, if you've seen the pictures, the Eagle Nebula is the host for the Pillars of Creation, which is an iconic image from the Hubble Space Telescope, among other things. They're just a very cool complex, what you would call a complex or a structure of dust and gas within this nebula, where the dust is casting a shadow, and you just see these giant pillars of material. They're very cool.
Yeah, it's always very interesting because space is dark in general. You never really know if you are looking at a cloud of dust or if you are looking at something where there is genuinely just not really anything to see. So I always love those nebula, like the Eagle Nebula, or is it Barnard's Cloud? Or I feel like I'm mixing that with Barnard's Star. It's basically a dark cloud of nebula, a dark cloud of gas that basically blocks out all the stars around it.
There's a nebula called like the hole in the nebula, which is that kind of thing.
Yeah. So I always think that is so cool because it is. I don't know. You look at space and it's one of those things where you just assume it's empty, and it's like, nope, maybe not. That might just be you can't see it. There might be a bunch of stuff there. It's kind of spooky to think about.
Yeah.
But it's very interesting.
Yeah, and so the dust, when we talk about dust, it literally is dust. It's tiny little particles of solid stuff. So, you wipe off your windowsill, right, and you get dust on your hands, it kicks up a cloud of dust, and the sunlight reflects off it, and you see sparkles in the light. It's essentially the same stuff that's in these nebulae. It's what we consider heavy elements. Think any element heavier than hydrogen or helium.
Metal. Everything is a metal.
Yeah, in astronomy, if it's not hydrogen or helium, it's basically just a metal.
The computer's about to die.
Yours?
Yours.
Mine?
Well, this
one. Oh, you can plug it in.
Where's the plug?
Right here.
All right, I helped.
Okay.
I got it.
Thank you. So anyway, yeah. So things like carbon will kind of condense out of a gas phase if it gets cold enough, and it will turn into a solid. And you get enough of those solid carbon atoms or carbon molecules stuck together, and you make a little dust particle. And these things are A lot of them are smaller than the width of a human hair. They're tiny. Some of them are bigger. Some of them are several hairs across, I guess. You can get definitely plenty of dust particles in space that are millimeters across. So something you can actually see with your eyes. But yeah, it's all just kind of out there in these nebulae. It's in young solar systems. It's plenty of it in our own solar system. If you've ever heard of the zodiacal cloud or zodiacal light, so it's something you can see from here on Earth. If you look, I think it's around sunset or usually around sunset, just after it. You can sometimes see a kind of a streak or a band of light in the sky above the horizon, and that's actually dust in our solar system that is reflecting sunlight towards us. Anyway, this is a very long way to get to my point, which is that that dust blocks optical light. So light in visible wavelengths, like we're looking at with our telescopes tonight, gets blocked by that dust. And so it blocks whatever light is behind it. But if you look at longer wavelengths, like infrared, the dust is transparent. And so you can actually use a telescope like the James Webb Space Telescope to look through those dust clouds and see what's behind them. So this is why we do things like build big, expensive space telescopes like James Webb. When we are like the Hubble Space Telescope, which observes in the infrared as well, but doesn't go to quite as long a wavelength. All right, how long have we been on the dumbbell? 13 minutes? We can spend a few more minutes.
Sure, maybe smooth 15. Nice round 15.
Tight.
Yeah, now that we have you all here, we're going to practice our type 5.
Type 5. What's the deal with net? That's my Jerry Feinstein. Jerry Seinfeld does astronomy.
You need to take that one back to the workshop.
No. Back to the drawing board.
We do have the fun game of yes or no, the fun game where I ask Tom questions and he can only say yes or no with no elaboration. But I feel like we're busy right now and it's not late enough in the night to pull that stupid thing out.
Why did that come up?
What?
Why did you think of that just now? Oh, okay.
I didn't have the type 5.
The type 5. I see.
We're hitting the point in the night where I'm a little bit tired and really leaning on some coffee. So
we're halfway there. We passed the halfway mark.
And cheers to you all for being here. Thank you so much. Oh yeah, you know what else we passed? Our 15-minute recap of who we are and what we're doing. So yes, thank you all for joining. If you are just joining us or have been just joining us in the past 30 minutes, hey, thank you for sitting past Tom's very long but very interesting talk about dust. I'm Ryan Lambert, and this is Tom Esposito. We are both astronomers, and we are here on Mount Hamilton at the Lick Observatory using a 1-meter class telescope, the nickel telescope. We wrote a proposal to see this asteroid, which we're currently observing, 2011 MD5. It's an asteroid that's not really got a lot known about it. And we figured while we were up here, it would be kind of fun to just do a live stream of the entire event. Not because we think that there's going to be something crazy to see, but because we figured this would be a fun chance to show off what it's like being an astronomer without any of the flair, the glitz, or the glamour. And also, you being here is entertaining for us, because if we weren't doing this, we would very likely be falling asleep.
I probably would be choking you. Right?
Yeah, that's true. I mean, you're already, you were already about to.
Intellectually.
Yeah, you're already keeping me down, man. But yeah, so thank you all for stopping in. If you have any questions, please feel free to put them in the chat. If you don't, you just like having us in the background, that is great too. We like the fact that people are viewing and listening to us be kind of silly. But yeah.
Yep, absolutely. I'm still finishing my dinner. I apologize for
Make me watch me eat on stream.
Oh, I mean, I already did that.
Yeah.
But you got to eat like me, where you just like hoover it down.
Just open your throat and pour it down.
Thanks, Will.
Yeah, we've got some more stuff on tap. We're going to keep looking at things with the eVscopes. Like I said, we're on the Dumbbell Nebula now. We'll head. I think we're going to take a quick detour to the Eagle Nebula, which we delayed earlier, and see if we can get to it right now.
Mm-hmm.
Still going to be dicey.
We'll give it a shot. We'll see what we see.
There's just so much good stuff to see.
Yeah, you're not even going to have time for your wheel of targets at the end of the night. You're going to have gone through all your targets.
Oh no, there's a lot more. I really had to thin out and pick the best ones to get on the written schedule. And there's about a dozen more cool things on the wheel of targets that we'll spin later, because that's the point where we'll have really lost our minds and won't be able to really think properly around 3:45 in the morning. It's always good to get your good science, the hard science done early.
Mm-hmm.
Either that or recruit more people to
work in shifts.
Yeah, sleep the first shift. I'm gonna grab more caffeine.
Okay. Yeah, the coffee is warm. Or you can go for Monsters.
We're gonna stick with energy drinks because
Coward.
I don't want to cover the phone.
Double coward. Leave them for the next astronomer. That's my favorite thing to do, is just leave inexplicable little gifts for whoever is next in the room.
Nice of you. So considerate.
Well, I mean, that's the part about them being inexplicable, is you want them to be a little bit upsetting.
Sure.
Not like not in a bad way, but just kind of in a like, why is this here?
Perplexing.
Yeah, like, why is this here?
I want to give someone pause.
Yeah.
Yeah, okay. Chat, this is Cosmic Peach. Can you see that? Cosmic Peach.
Oh my God. Yeah, who needs 3:45 when you're already one night of sleep gone and half a night now.
I'm always
After
like this. What are you talking about?
Oh no. That says more about you than you know.
That's not bad.
No,
It's acceptable.
I'm afraid of Monster Energy drinks. I'm pretty sure my heart will explode.
You're high strung enough.
Yeah, that's
You don't
true.
need any help.
Oh man, I had a terrible. Tom got to be smart.
Got to be.
Yeah, he got to stay on the mountain. I, like a dummy, have been driving back and forth between San Francisco and here. And man, I had a terrible morning this morning trying to get here.
Hold that story.
Yeah.
We're going to move on from the Dumbbell Nebula, everyone. So fix it in your mind and now. Take
Really?
a mental snapshot of what it looks like.
You'll never see it again.
Yeah.
Really zoom in.
Zoom
That's
in
great.
on it.
Great.
So
Yeah.
I don't know if this star at the center here is the white dwarf at the center of the nebula that created it. I don't know. It would be
Quite
convenient
bright.
if it were, but I agree. It seems rather bright for a white dwarf, either behind or embedded in a nebula. So it's convenient to think that, but I'm not sure that's actually true. Okay, that's all. We're gonna try the Eagle. Continue your story of your misery.
I don't remember anymore. So basically, because Tom is so needy. Oh my gosh, so needy. He was like, we need to have 2 eVscopes because we got to have one to do science and we got to have one to show people things. I went, do we really have to do that much for the audience? For chat? And he was like, yes. We have to do everything for chat. And I was like, fine. You're right. So I got up this morning and went to the office to go grab an extra eVscope.
Did somebody happen to recommend that you bring it yesterday? Did
Maybe
that happen?
that could be.
I'm not.
I don't remember such a thing occurring.
Yeah.
I would never make a mistake. And
I thought maybe you had 2 eVscopes up here already. Anyway, yeah, so I grabbed that and I decided, you know what? I need to pick up snacks for tonight because I ate all of Tom's snacks last night. And I need to get coffee because I will die without it in the morning. And then I need to, looks like it's doing something. And then I need to get something to eat because it's around like 12:30. So I go to the grocery store, get everything, get piping hot coffee, try and get onto the highway, and I missed the exit like 4 times because I'm halfway paying attention between driving and trying to cram a muffin down my mouth while I'm eating. And so I've got crumbs all over my car now. I'm embarrassed to have this car. I eventually get on the highway, and as soon as I get on the highway, I hit a pothole and my coffee explodes everywhere. I was like, this is the worst. I'm losing my mind. And then we finally got up here, and Tom, being the calm, meditative person that he is, immediately put me in a happy place and said that he was going to do all the talking. And I proceeded to do all the talking. And then you spent like 10 minutes talking about nebulae. So,
yeah, I just couldn't get a word in edgewise. I was happy to talk. You just didn't. You didn't breathe for 20 minutes. It was really impressive.
I actually
like a circular breathing. Is that how you do
it? I just don't breathe. Fun fact: you don't need to breathe.
You're like a sea lion. You can just hold your breath.
Don't believe big health's lies about big anatomy's lies about how breathing is necessary. You're good. It's fine.
It's true.
You just gotta keep going.
Yeah, I breathe with my stomach. It really helps. This is the Eagle Nebula. We are getting it. So,
hello, David. Hello from Sacramento.
I think things are looking a little redder. That's what it is.
Did you find it?
Okay. Yeah. So I had night shift on my laptop, which was sharing the screen of the iPad. Mm-hmm. And so we can see the beginnings of those pillars of creation.
Yeah, look at that.
Right here.
Yeah, so, Sophia, if you're still here.
Yeah, who was it? Who wanted it? So was it
Sophia?
Yeah, Sophia, if you're still around.
This one's for you.
Yeah, so these are those pillars of creation right here. 1, 2, another little chunk over here. The picture you might be used to is, might be used to is rotated about 90 degrees where the pillars are kind of pointing more up. But that's really just a matter of perspective. There's no up in space. And so the color's starting to come out. The Eagle Nebula is very red, a lot of pinks and reds in this one. And this is one of those stellar nurseries.
Mm-hmm.
So this is not a planetary nebula. It is a different phenomenon than the Dumbbell and the Ring Nebula we were looking at before. But there are new stars being actively born in this nebula as we watch.
Hidden in that each of those little fingers of creation, the pillars. Thousands, hundreds of little stars being born and hidden away because they're embedded in those gas clouds. So it looks like our observation of the asteroid finished. Why are they a different color here? Would it be because the color is saturated in the famous photo of the pillars? So I'm going to start this while you answer that.
I can answer that. So the colors we're seeing here are more or less what you would see with the naked eye. If you could get up into space and be close enough that you could see this nebula. The colors you would typically see in like a NASA press release or something from the Hubble Space Telescope, those are often false color images, for one thing, where they assign visible light colors that we can see with our eyes to other wavelengths of light, like infrared or ultraviolet. So that's one thing. The other thing is the Hubble telescope is just more sensitive. It's a 1.5 meter, no, 2.5 meter telescope in space. So it is much more sensitive and takes much longer images than
I'm pretty sure 2.5 is right.
I'm looking it up. I'm gonna fact check you. Actually, according to Wikipedia, it's 332 miles.
What?
That's how high
anyway,
it is.
what I'm trying to say is it will be detecting other parts of the nebula that we're not seeing here. So that's kind of the short answer. I think more often than not, it's the false color image. People have assigned colors to the different wavelengths of light that we're seeing.
Yeah, which it's not like you do that because it makes the images pop and it makes them look nicer, but also there is some general reasons why you would do that. For instance, certain elements, like we talked about with the planetary nebula, certain elements will emit at specific wavelengths. So if you wanted to make sure that those elements really stood out, you could assign them a brighter color, a higher saturation, to be sure that you see where those elements are in the image, and really emphasize them. So there are reasons to do false color beyond just making the image look nicer. But yeah, this is closer to what you would see if you were to get a big telescope and just look with your eye.
Yeah, and there is a third reason why this looks, I don't know, or third, we might 10th, but there's another reason this is going to look extra red right now. Is it is at about 15 degrees above the horizon and setting. So we are looking through more of Earth's atmosphere, and as we know, Earth's atmosphere tends to scatter or reflect blue light. That's why the sky is blue. And so it lets red light through more readily. No pun intended. So when you look at things low on the horizon, they tend to look redder. You've probably seen this with the moon. When the moon rises, it tends to be a little more orange or red. You'll get that blood moon effect. But when it's up higher in the sky, it's white. So that's another reason things are going to look a little redder even than usual for the Eagle Nebula right now.
Yeah. So it looks like our eVscope that's looking at the asteroid has about 6 more minutes to go.
Oh,
We'll start it again.
Glad you're paying attention.
One of us has to.
It does.
One of us has to keep it together.
What's your favorite animal, Ryan? Do you like animals?
I do like animals. I have a pet cat that I hate.
What's your cat's name?
Her name is Curie.
Named after?
Curie. Madam Curie.
Which one?
So yeah, stray cat I had that I found. My mom found, named Curie. Originally, I named her Bose because I thought that she was a boy, and then I took her to the vet, and I went, "Oh well, okay. I want to keep the scientist name, so Madam Curie instead." But she is a little jerk of a cat, not socialized very well. Hisses at everybody who isn't me. So every person that has tried to come in and watch her, we actually would have, Lauren, nobody else would, but one of our coworkers and friends, Lauren, while she was visiting San Francisco one week, I had to be out of town. So she ended up watching my cat, and she sent me a picture. She opened the door, and my cat, thinking it was me, ran up and then saw her and immediately back arched, went and ran away.
As cats do.
So I guess that's my favorite animal, specific animal that I know. Otherwise, I don't know. I'm really a big fan of birds. I like birds. I think those are just cool little dudes. I don't have a specific that's my favorite, but birds are neat. What about you?
I'm on the fence about birds. Pros and cons, for sure. So this is a little bit inside baseball here, but so our SETI group, Unistellar group, we have a meeting every week to update everyone on kind of what each person is doing. And our leader, Frank Marchi, who will join us a little bit later, likes to start things with a question.
His last name?
I don't know.
Okay.
Marchi.
Frank, if you're watching, we don't know how to say your last name apparently.
Sometimes I just say Smith. He likes to start with a question of the week that everyone can answer. I think though, 2 meetings ago, someone else came up with it. It might have been Ariel
It was Ariel.
Krakowski, who was on earlier as a guest.
It was Ariel, because then immediately after, Frog said, we're never letting her pick again.
That's right.
And then next week she picked
That's right.
the question of the,
So
the week.
her question was, I think it was just along the lines of parrot or sloth.
Would you? Yeah.
Would you rather have a parrot or a sloth? And so the parrots are great. They're smart birds. Some of them, something like African gray parrots, are terrifyingly intelligent. But
Very long-lived.
they're very long-lived. They don't. You really got to commit if you're going to have one as a pet. Some of them can live 80 years.
Yeah, enjoy. That's your kids have to commit, essentially.
Right, you're committing for your kids, or whoever you're leaving this parrot to in your will. And you know, there's other downsides, but I would go with the sloth. I think they're kind of cool. They're weird little creatures. They move so slow.
Mm-hmm.
I don't really have a strong preference, honestly, but the parrot seems like a lot of work. I don't know how much work a sloth is. I've never seen one.
I mean, I would take the sloth for cool factor. I'm going to be honest. Tom, can I be frank with you?
Please.
Wait, that was a terrible French accent.
I thought you were doing Italian.
No.
Right.
I like attention.
No.
I like standing out.
You do?
I do. I know. You never guess.
Huh.
I think being a sloth, that's a status. That's a status. Right
Being
there.
a sloth?
No, having a sloth.
Okay.
I'm sorry. Having a sloth, that's a symbol right there. Who else has a sloth?
Sure. I think it's illegal.
So,
Well, that's not true.
then you're a rebel. That's even cooler.
It probably depends on the state in the United States. Other places, I don't know. I imagine you could wear a sloth like a backpack. You get its arms
I don't know how
and
well
kind
that
of
would
put
work.
them around your neck. That's what I imagine.
It'd take a while for them to get off your back, at least.
That's right. Yeah. So mark it down. 12:16 is when we went off the rails.
We stopped having enough astronomy stuff to talk about. So if you would like us to talk about astronomy, by all means, please ask us questions.
We'll get back to it.
Otherwise, we'll just kind of, we'll meander, I think.
Yeah. We're at the 7-hour, 15-minute mark of when we started this stream. We have about another 6 hours to go.
I do want to say, have you ever streamed before? Have you ever done a stream?
This is actually my first time.
Yeah, we really went
Whole
feet
hog.
first.
Yeah.
All right, Will, that's not. William asks, why is dark energy? Okay, so we can give you an answer. We can give you an answer, Will. We can give you an answer. I don't know. In general, dark energy might be real, might not be. But in general, we don't know why the universe expansion is accelerating, and the only thing that can possibly do it is a thing we made up. It's a fudge factor.
Dark energy?
Yeah. Do you have anything to add to that? Because I really don't know a whole lot about dark energy beyond it's a goober. It's goofy.
Yeah, I don't know. Hola in Argentina.
Oh, hello.
Argentina. Welcome. Yeah, I don't know. Dark energy. I'm not a cosmologist. I stay far away from that. But I think why is dark energy is the correct question.
Yeah.
I don't have an answer.
Yeah. I mean, we don't know. We don't know. It would be it's a very bizarre concept. The idea that space propagates more space. I think I would be so interested in finding out a reason for why dark energy happens, or even if there's another explanation for what could be causing expansion of the universe, accelerating expansion. What's the official difference between astronomy and cosmology? Should probably be like showing these. I can't. Sad.
I think you do that. Oh, you're doing everything.
Yeah.
Cosmology is just a subfield of astronomy, as far as I'm concerned.
Yeah, I mean that's pretty much it. Is pretty much I think true. Yeah, cosmology just is the subfield that is focused on the very biggest portions of the universe itself, whereas astronomy, other subfields of astronomy, asteroids. Also, if there's so much, why use fudge factor instead of going back to the drawing board? So, okay, first, yeah, astronomy itself, full of subfields, exoplanets, asteroids. Cosmology is just another one of them, but specifically dealing with the largest stuff.
Big picture astronomy,
Yeah.
kind of like, you know, scale of the universe type stuff.
Yeah. So if there is so much, why use? If there's so much missing, why use a fudge factor instead of going back to the drawing board? I think it's largely. So I say fudge factor, but it's largely because everything so far has been well predicted, and it's mostly. I don't think anybody. What?
We don't have the dust cap.
Oh, whoops! Skip. Whoops!
I was trying to take dark frames with no
Look, all right.
darkness.
Do I need to redo?
You might want to redo. I got it. You answer the question.
Okay.
I'll do it.
Yeah. So the idea that it is a fudge factor, I think a lot of people would take issue with. I don't. I think that's probably me being a little disingenuous. It is an explanation for what we see. The explanation itself is nebulous on purpose because we don't have a particularly good explanation. I think a lot of ideas of what dark energy are still up in the air, and mostly because there's just not a lot of concrete evidence one way or the other. We do know that the universe, the acceleration of the universe is accelerating, the expansion of the universe. To answer Paul Shield's question that's related to this, we know this because we can measure the distances to galaxies using multiple methods. And we can see nebulas and nebulae. Yes, it is similar in that it is quite cloudy. But yeah, so if you go farther back in time, if you go to more and more distant galaxies, you can see that we expect them to be receding from us at a certain rate. But the farther back you go, the faster they are moving away from us. So the only real way that could be is if the expansion of the universe, it's not just expanding, it's accelerating. There's quibbles and caveats to all of that. When the universe was first, right after the Big Bang, when it was first expanding, there was like a big inflation. So a moment where it went really, really inflated and fast, really expanded quite fast, and then the expansion slowed down. But it is still accelerating now, based on what we see. So it's definitely a topic. Dark energy is tough. I think there's a lot of people who have dedicated their entire careers to really trying to understand what exactly that means, like what it is. In saying that dark energy, there's a lot. You get this saying that dark energy is like 89% of everything in the galaxy. That really has to do with the amount of energy involved. So the amount of energy it would take to continue the accelerating universe to accelerate at the rate that it is going would require like an 89% increase, or I forget the exact number, like an 80% increase in the total amount of energy in the universe. And that's basically an amount of energy that we didn't account for, that we don't know where it's coming from. That's why it's dark, is we don't know what the cause is. But yeah, it's a complicated topic. I wish I was more qualified to actually talk on it. So if you do talk to somebody, you can name drop me and they will be like, wow, he's an idiot. And I
probably won't disagree. But yeah, it's super cool. I wish I had studied it more in grad school, but nobody really studied it where I was. So even the professors were kind of like, meh.
Yeah, I mean, this is like still a very yeah, right. So the expansion was discovered recently in astronomy terms. I mean, even in terms of the field of astronomy. And there's been several missions in recent decades to try and better understand this problem, this question, doing things like measuring that expansion rate and trying to make all the puzzle pieces fit together into a cohesive answer that actually makes sense on all the different levels. There's a European mission, I believe. Is it Euclid? I'm gonna get the name of the telescope wrong. But there was a launch recently. I did get it. Yeah, Euclid, which is a European Space Agency mission, just launched this year, I believe. Yeah, July 1st. And that will do more investigating of this kind of dark universe, dark matter, dark energy. How much is there? Where is it? What is it? A lot more to learn, for sure. I mean, it'd be cool one day if we could figure out what dark matter is, for example, and how to manipulate it. Just think of the stuff you could do if you could create gravity, basically, without the need for matter. So you could make... that's the kind of stuff that science fiction is made of, I feel like.
As I say, I tell you what, I'd be a lot more than just a postdoc if I could do that.
Sure.
I'd be king.
Yeah.
I think that's when you start getting into whether you can do artificial gravity, anti-gravity, perhaps.
Yeah. Dr. Fritz Zwicky mentioned dark matter first. Dark is an unknown. Yeah. So dark matter in its own is a super interesting topic. Yeah, Zwicky first looked at a cluster of galaxies, and basically he looked at it and he was like, these are moving way too fast for to be like gravitationally bound to each other. This cluster can't possibly exist. What is happening? And yeah, the main thing he came away with was like, there has to be something else there adding to the gravity, keeping all of these galaxies together. And yeah, so that's, since then we've seen similar things like the Milky Way itself is spinning too fast. If there was no dark matter cloud essentially that it was embedded in, the outer portions of the Milky Way would be flung basically away, be flung out, and our galaxy would kind of rip itself apart. So yeah, dark matter is very cool. It's one of those things where I understand people that say MOND, because there are other possible explanations. MOND, or modified gravity, essentially. The idea that gravity, when you're far enough away from where we might be in some strange position, being so close to the center of the Milky Way, close being relative terms, that maybe the equations we have for gravity are incomplete. So there are other possibilities, but
it's happened before.
Yeah,
Newton thought he had the answer.
Yeah,
Einstein was like, hold my beer.
So yeah, the dark matter in general, I think, is also a very, very interesting topic. The fact that we still haven't been able to get really any evidence beyond the gravity, like we haven't had any way of detecting it, despite having tried for a couple decades now, is I really feel like that's tough. Like it's an interesting topic as well.
Yep. All right, time for another mental snapshot. We're gonna move on from the Eagle Nebula. It's been fun. Pillars of creation, creating the way. But we're gonna look at some other cool stuff. This is a good shot. This is one of the best
images I've seen of that I've ever taken of the Eagle Nebula. The sight up on the top of this mountain is just fantastic. All right, bye-bye. So someone brought up Fritz Zwicky. That connects back to the Zwicky Transient Facility, which is the telescope we use to find our cosmic cataclysms targets for Unistellar citizen science. And then also, I want to come back to that rotation, the Milky Way rotation thing in a second. Let's see. So we're going to go to number 2 on the recommended list. Number 1 in your hearts, the Hercules Globular Cluster. So the Hercules Globular Cluster is next, and we'll get to that, describing that in a second. But yeah, you're talking about the Milky Way rotation curve. So basically, the fact that the outer parts of the Milky Way are rotating faster than they should be. Was, I believe, the bulk of that evidence was discovered by a female astronomer, Vera Rubin.
Oh, yeah.
Vera Rubin
Absolutely.
Has a special place in my heart. She was an astronomer at Georgetown University, where I did my undergrad studies. Really the main astronomer of note to come out of that university, maybe the only one. No disrespect to the other astronomers who came out of Georgetown.
Or yourself, apparently.
Well, but as a astronomy PhD, they didn't have one when I was there. And she now has a brand new observatory named after her being constructed in Chile, a mountain called Cerro Pachon, which is the Vera C. Rubin Observatory, and that will begin a major survey now called the Legacy Survey of Space and Time, I believe is the current name, which will essentially look for all kinds of changes in the universe every few nights, and should lead to a lot of new discoveries. And that should come online next year, I believe. But anyways, I'm proud to have Vera Rubin come from my alma mater, and she worked in the 50s, I believe, 50s and 60s. It's good also, I think, to see female astronomers getting recognized more in the field for, especially historically, what they've contributed. Far too long they were overlooked and even intentionally ignored, or their accomplishments taken credit for by men in the field. So happy to see that. Also the Nancy Grace Roman telescope, another one which will launch soon. Sorry.
Well, I was going to say, so Marianne on Facebook says that she wished Vera Rubin had a Nobel Prize, and that reminded me of something one of my graduate studies professors had said. That Vera Rubin did a bunch of work on dark matter, and it's actually a real shame because she published so many different papers, but just didn't say dark matter at some point.
Yeah.
And so it was like she basically did the legwork on a whole bunch of it, published tons of papers, and just didn't put them all together. Not that she didn't understand, she definitely made all of those connections and said so, but it was just like one of those things where somebody else came along and was able to staple some stuff together. I guess I shouldn't talk smack about other people.
No, but a lot of times that happens in science. Really. It's a matter of sometimes it's just a matter of who markets themselves better, who markets their discovery better. Yeah. There's lots of examples of that, and I'm not going to give a good specific one now because I'm too tired. But a lot of things have, for example, been named after the person who just was louder in talking about it.
That's why I'm going to be famous.
Yeah, the Lambert effect will be well known. But we're starting to see, at least in astronomy, it's been a very slow change, and there's a lot more that needs to be done, I think. But occasionally now you'll see some of those terms, the so-and-so effect or whatever, won't just be that
first name anymore. It'll be hyphenated. You know, the so-and-so and so-and-so effect, because actually they discovered it independently together. It's just for one reason or another we recognize
The one.
the one.
Yeah. I also, purely, she did a bunch of great work. Did the spectral classification system, was able to basically put together the fact that star types exist through the different spectra. So looking at the different elements in stars. But she has the best name I've ever heard in my life, and that is Annie Jump Cannon. So wanted to shout her out as well for anyone who maybe hasn't heard of her. Annie Jump Cannon did a lot of cool work, and was the mother of the basically stellar studies in terms of spectroscopy, and really classifying stars on the order that they are, figuring out that they were related to temperature, and that was how the spectra changed, and that affected what elements would be visible, not necessarily that the elements weren't in the stars, but that at certain temperatures, elements would be excited and be much more visible in the spectra.
Yep, and so now the American Astronomical Society gives out an award every year, the Annie Jump Cannon Prize, to a female astronomer who has made significant contributions to the field. So yeah, good to see.
So what are we looking at here?
Yeah, indeed. So this is the Hercules Globular Cluster. It's one of the brighter, more impressive globular clusters out there. We were talking about globulars last night.
Yeah.
They're pretty interesting. They're just dense clumps of stars that all formed together out of the same giant molecular cloud of hydrogen gas. Often they're very old.
Yes.
On average. So I think if, for example, if I bring up the info on this real quick, let's see, well, say how old, yeah. So this says something about around 12 billion years old is the average age for the stars in this cluster. And there's about 300,000 stars in there. And so it's the brightest such cluster in the Northern Hemisphere, 22,000 light years from Earth. So still, it's getting out there. That's pretty far away. Often, because it's so old, there are new stars being born in these clusters, but pretty slowly. They tend to be made out of whatever's left over from the original and kind of whatever's spit out by the stars that died in the past.
Yeah.
But they tend to be redder, I think, because they tend to be older stars.
Yes. Yeah, in stars, there is a kind of a redundancy in terms of colors. You either have a star that's red because it's old, or red because it is made out of a lot of heavy elements that were made when another star died, essentially, and spit it out.
Sorry, and if I could just expand on the first part. The age, it's not so much that the star is red because it's old, it's red because it's cool.
Yeah.
The temperature of the star is literally lower than other stars. So a cool star would be about 4,000 Kelvin. That's, for roughly 4,000 Celsius. That star will look reddish orange. Because it is so cool, it burns through its hydrogen fuel much slower, which means that it lives longer. So those stars might live for 1 trillion years, these little red dwarf stars. Whereas a star like the sun might live for only 10 billion years, but burn much brighter. And there's blue stars that burn much hotter because they're much more massive. They only live maybe 10 million years, something like that.
Yeah, that's a good point. No, that's absolutely right. I took that for granted. So that's the globular clusters. One of the things I really like is that they are so intensely bound together that any gas, dust, material that gets blown out by a star supernovaing is not going to leave that globular cluster. It's immediately going to get pulled back in and eventually sink down towards the center. And the reason, so we were having this conversation, I guess yesterday, you asked why don't globular clusters tend to get ripped apart? So there are two different types of cluster of stars. There's a cluster, which usually has 10 to 100 stars. They're all kind of loosely bound. Those don't have very long lifetimes. Just passing by nearby other stars, passing by other large gravity wells, tends to rip off stars, rip them apart so that they are no longer orbiting around each other. Clusters you are not going to be able to do that because all of the stars that could have been ripped off early were. And every time you take one of those stars out of the globular cluster, all of the other stars in it are just more tightly bound together. So you really get this very intensely entangled ball of stars that are all orbiting around each other, and they will continue to do that. So one of my favorite things about globular clusters is that they kind of pulsate all together. You end up with stars that are orbiting, and then they'll kind of have these interactions, and they'll start to lose momentum, and they'll start to all sink towards the center, and then they'll bounce back out. But they'll never bounce out quite as far. It's like dropping a rubber ball, and it bounces pretty high, and then the next bounce, not so much, and the next bounce, maybe less than that, and then eventually it's just kind of like puttering out. So globular clusters are like that, but on a much slower scale. Lifetime of the universe, and we've seen only a few bounces. So it's very neat that they essentially have this like core rebound as they are orbiting each other, and eventually they'll all kind of bounce back out, but a little bit less than before. So it's interesting to think about what that will look like in the future if there are still stars alive at that stage in the globular cluster's lifetime. What'll happen when they are when there's not really a lot of energy for that core of the cluster to bounce back outwards?
I never heard that before. Or I mean, if I did, I forgot.
I only know that because my advisor was my dynamics professor, and I worked with globular clusters. I worked with globular cluster systems as part of my thesis. Yeah, and that one I thought was really cool. That was the one fact. I hated my dynamics class, but that was the one fact I really remembered.
I'll take dynamics any day over electromagnetism or anything like that. Yeah, you can kind of see if you zoom out, you can compare the density of how many stars are in that cluster compared to the stars around it, which are just other Milky Way stars that are, they could be much closer, or they could be actually farther away, but they aren't necessarily near this cluster. I don't know if we mentioned this, but sometimes we shouldn't take for granted that this is common knowledge, but every star we see in these images, where you can really see the individual star, is in our galaxy. So it's in the Milky Way. We see light in other galaxies from their stars, but they're so far away that you kind of just see the cumulative light. You can't see the individual stars there.
Yep.
We do have some very large telescopes that can see some of the very brightest stars in those distant galaxies. I think those giant stars, but that's only a select few of the nearest galaxies, I think. And, it's very rare. Do we have a long?
Yeah.
Is this a question here?
No, but it's a comment. Thank you, Barbara. Barbara, you want to read it?
No, you already started.
So Barbara on Facebook says, this is so interesting. Thank you for doing this live streaming. I've already learned a lot and translated some to my mom, who doesn't speak English. It's super convenient for me because it's 10:15 on a Sunday morning. So yeah, and have a wait. I can't say that town name. I'm sorry, but in Czechia. So
have a thought.
we need a translation. I'm sorry, but no, thank you. That is so nice. Like I said, we didn't actually know what to expect with this. I honestly was kind of worried that we'd get maybe like 1 or 2 people that kind of want to hang out and that'd be it. So the fact that we still have 7-8 hours into this, we still have 30 to 40 to 50 people listening to us ramble and asking us questions is very cool. So thank you for listening, and thank you for for translating to your mom, because I think astronomy is very neat, and I think it's something that a lot of people think is cool, but maybe just don't have a chance to learn about. And so we appreciate you asking us questions, and you being here as well.
Yeah, absolutely. And honestly, having done many long observing nights, these questions come up on their own quite a bit.
Yeah.
You know, you get to 12, 1, 2, 3 in the morning, you start discussing existential thoughts and big ideas about the universe. They come up more than you would maybe imagine. So we are absolutely happy to discuss them with you instead of just ourselves.
Yeah, it's kind of sad when it's just two guys in a room just talking about this, but it's much nicer when it's with 32 of your closest friends.
Yeah, no, you're sitting here like, yeah, dude, the universe is so big, dude. Yeah, that's it is good to have some other thoughts come in. Speaking of thoughts, take a mental snapshot of the Hercules globular cluster, because we're going to move on from this target and look at something else pretty cool. So say goodbye to these 300,000 stars in this glob, as we call them for short.
No, we don't. No one calls them that.
Somebody calls them globs.
It's deeply upsetting that they call them globs.
Is that like people saying like San Fran or Frisco?
I despise Frisco. I also don't really like San Fran. Sophia, is it true that if galaxies were to crash into each other, the stars of each galaxy wouldn't crash into each other? That is absolutely true. Statistically, it's unlikely that the stars would collide. It is very easy to imagine because every galaxy has billions and billions of stars. It's kind of hard to believe that you would crash in these billions and billions squared things into each other, that nothing would actually collide. But it is true. That's just the scale that galaxies work on. The Milky Way is largely empty space, gas, and dust. So the gas and dust would 100% collide. That would all collide. We have a beautiful starburst, lots of nebulas like the Eagle Nebula forming, but a star that has already been formed and is already fusing and has blown away the gas and dust around it, those are relatively small compared to the distance between stars. So yeah, it could happen where you get stars colliding, but it's unlikely. It'd be more likely that when the Andromeda Galaxy, which is the closest neighbor to the Milky Way, which
you're looking at right now.
Oh, is that where we're going to segue?
It's almost like Sophia.
No.
You need to start taking more nickel data.
I have confirmed that it is the Sophia I know, so I'll ask later.
All right, is she a plant? Because it's a very good segue.
I did not know. She did bribe me with a restaurant that I hadn't heard of. Get some kind of orange.
You a restaurant?
She told there was a food, and I went, "What's the recipe on that?" And she went, "It's a restaurant." And because we showed her the Eagle Nebula, she told me what the restaurant was.
Oh wow. Okay.
Is it permissible to nap yet? It is always permissible to nap. Not for us, but for you. We get in trouble if we nap.
I hate naps. I am not a napper. Drives my wife nuts, I think. Naps make me feel bad, so I don't take them.
Oh, wait, so I can finish my thought. The Andromeda Galaxy. Yes, so the Andromeda Galaxy, our closest large galaxy neighbor, is on a collision course with the Milky Way. It's going to be a spectacular view for whatever is alive at that time, because it's not going to be happening in our lifetime.
Several billion years from now.
It's going to be a hot minute. But it will be a spectacular view. Lots of stars will be born, but probably no stars will collide. That was all I had to say about it.
Yeah. There you go. And so, yes, when that question was asked, we were in the process of going to Andromeda. I don't know if we're there yet.
Are we?
There it is.
Oh, sweet.
Slight delay. So yeah, this is the live view of the Andromeda Galaxy. It's bright as far as galaxies go because it is our neighbor.
Mr. Rogers' galaxy. I will hit go, and we'll see what it really looks like. Yeah, so it's what, roughly twice the number of stars of the Milky Way, something like 200 billion stars in Andromeda.
I think so.
It's about 3 million light years away, something like that. About a megaparsec is the more common unit. And it's another spiral galaxy, but it's inclined kind of more edge on with respect to us, I think. So you don't really see the spiral arms as well. We'll start to see them as the eVscope keeps taking data. You start to see some of the dust lanes, at least, I think, in there. Yeah, it's a beast of a galaxy, and we will merge someday. So all are one. And it's Andromeda, so I haven't really been, I don't know if we've been observed any other targets, maybe the Hercules cluster, but they get their names from the constellation that they're in. So Andromeda Galaxy is in the constellation Andromeda, which is up this time of year.
How lucky.
In the northern hemisphere.
I was going to say, I'm glad it's up this time of year. Otherwise, it would be very hard to have slewed to.
Yeah, indeed. So hence vision just started getting going. Yeah, this is a good one to look at. It's really quite large on the sky. I think it's, if you could see the whole thing, I think it's a couple of full moons across, I want to say. Is that right? Am I wrong on that?
It's at least close. I don't know if it's a couple full moons. I think it's at least I think it is a full moon, but I'm not positive.
Pretty big as far as deep space objects go.
Angular diameter. Let's go. Let's see. 2.8 degrees. And the moon's what? A degree?
Half a degree.
Oh, yeah. So I guess you're right.
It's
about
it's
two.
Multiple full moons across. If you could see the whole thing, but the outer reaches are pretty faint.
Yep.
We will not. The eVscope, we won't see the whole thing.
Look at
It's
that.
looking pretty good, though.
That is beautiful.
So you can see the core. This bright part in the middle is called the core, where most of the stars are at the center of the galaxy, bunched together at least. Then there's a bulge, perhaps, that's around it. Our Milky Way has a bulge of stars.
That's about right.
Else to call it. It's literally called the bulge. And then, you see the parts, and there's this, I'm zooming on the wrong thing. This here is an actual dust lane. Again, it's those clouds of dust particles that are blocking the light from the stars behind them. You can see that it extends all the way out to the outer edge that we can see here. Let's zoom back to the other side. So actually, this is the edge of it takes up the full eVscope field of view.
Yeah, I was gonna say, we can't see the whole thing.
Yeah. Do it this way here.
Yeah. Andromeda was the first real deep sky object that I ever looked at with a reasonably big telescope and was just straight up floored by. That's in grad school, we had this old 12-inch refracting telescope in an observatory that was largely just used for outreach events and like public nights for people to come in. And it was the grad student's job to kind of run those every semester. And so we get to pick the targets we'd go to. And I think at one point we had this like list that we would largely stick with of good targets, like really cool things that were easy to see, that were easy to talk about, that people found interesting. And I realized, I was like, well, yeah, I've never actually seen Andromeda, and we don't have that on this list. I wonder what it looks like. And just going to it with this big telescope and then immediately being like, okay, well, where is it? Let me see. And then moving it a little bit, it's just in your field of view. I thought I was going to have to work to see it. But no, it's just like this giant amoeba in the sky when you're looking at it. I think that was the part where I was really, really floored by what I was seeing. And that was there's always times where you really, when you're in astronomy, when you're doing this, looking up at the sky, looking at these things, where it just really hits you. You're like, oh, that's actually out there. Like that's a real thing. Like I am seeing something that is too far away for me to even comprehend. And that was one of those moments. I really love those moments.
Yeah, that's a good story. Yeah, I think it's part of the reason I like what the eVscope does, where it lets you see these types of objects. Because looking up and seeing the stars is one thing. We see them, we're used to them to some degree.
Yeah.
Even if you live in a city where you don't see the stars very much. But they're just points of light. Then to see that there's more stuff up there, and so much more stuff like this, where it's this enormous thing. It's so big your mind can't even really comprehend how big it is in physical size. And yet it's just hanging up there, doing its thing.
Yeah.
is pretty wild. Hard to get your head around, for me at least.
No, I think
it's hard to get my head around sometimes. And this is what I do for a living.
Yeah.
So sometimes it verges into philosophy, I think, and maybe theology more than science. And I think Andromeda, it is a naked eye object. You have to be somewhere dark for sure, but you can see it as a fuzzy little smudge on the sky without a telescope or binoculars even. You gotta be somewhere dark though.
I'm realizing I forgot to write down the times when we started. I'm like 2 things behind. Do we want to, so I think,
Switch filters?
yeah, that's what I was about to ask, is so a lot of our observations of the asteroid 2011 MD5 are in the V filter, which is, I guess that's short for visual. I don't know if that's actually true.
It as visible, yeah.
Yeah. Which is fine. That's a very good filter. It's going to be analogous to a lot of the other data that people who are using the eVscopes are collecting that I'll be looking at later. It'll be similar, but we have access to all these other filters. So we requested them. I'm wondering if we want to use some of them just to see.
Yeah, we could. I would recommend R.
Yeah.
But
yeah, definitely. I think R 100% because we can get some colors.
Yeah. I don't know. Yeah, we can do B. We can do R. It's kind of a question of what do we want to get out of it. So
I figure
for actual color, just get a color.
Yeah, I figure we do just 10 images of each.
Yeah.
See what we get.
Do you want to kill the sequence and just start now?
Yeah, it's gonna be a while, so it's probably worth it.
Just kill the script.
Okay. And let it finish.
Yeah, let's let it finish this one.
So yeah, one of the questions that no one asked, but that I want to answer is why would you want to do that? Why would you want to go ahead and switch filters? And that's because that gives you information about the color of the object, and not necessarily the color like what it physically is, the hue of the object, but what wavelengths of light are more prevalent, are being reflected back, is actually useful information. It could tell us what the surface of the asteroid looks like what's on the surface of the asteroid, how reflective it is. And you really can only do that when you have multiple filters to work with. So that's what we're going to try next. The R filter. So the filters we're using are called Johnson filters. They are the B, V, R, and I. They roughly can be remembered as like a blue for the B, visual, which is largely like the green portions of the optical wavelengths. Red is R, and then I is like the extreme R, extreme red, towards infrared. So right now the asteroid looks like we're finishing up this last observation of the asteroid, and then we're going to switch the filters, and we're just going to see if it'll probably look
largely similar, but when we analyze this data later, we might be able to pull something interesting out of it. So part of this is you never know what you're going to find, and it's always worth it to try new things and see what you can get that's useful. That's part of the process. So we will switch to and of course. So while Tom is doing that, I'm going to pull this up, and I don't want to cover all of Andromeda, but we'll come back to Andromeda in just a second. So yeah, switching over to the R filter. The R filter tends to let in light, a little bit more light in general. I guess that's not quite true. The R filter, at least when we were using flat fields, is more light tends to be in the R for things that we look at. So we want to try a slightly shorter exposure time than 200 seconds, and we'll see how that works out. So just to remind myself of what we're looking at here, 14,000 counts. It's not too bad. So I want to try 150 seconds. That's 3 minutes. We'll see if that looks reasonable. And if it does, then we can take just a quick, couple of exposures, 10 exposures, and see how things look in the end. All right, so I'm double checking. Yep, the filter is ready. And let's start here. All right, and now I will move Andromeda back. We'll take a look again. Oh dear.
No, you're exposing me.
Oh dear. Hey man, look at that messy desktop. All right, so trying 150-second exposure. We'll see. We'll see how that goes. Yeah. I'm gonna assume.
Fine.
Yeah, I'm gonna assume that'll probably be all right. And then if that works, we'll just do 10 exposures of that. So,
yeah, we'll have to see what this does for the light curve. Did you just talk about this?
I talked about it in terms of colors and reflections, so it can let us know what the surface of the asteroid is like. May give us an idea of what's on the surface of the asteroid, how reflective it is, what kind of light it's reflecting back or absorbing.
Yeah, we'll have to see. We may have a short gap in the light curve because
that'll be fine.
It may be a little tough to kind of compare the V band and the R band parts of the rotation of the light curve.
Yeah,
we could deal with that.
I think, and we don't have to take a full 10 exposures. I think we take probably like 5, and then we're losing 15 minutes, which
that's fine.
Yeah.
So sometimes in a situation like this, you would set up some sort of a automatic computer script that would rotate the filter for you so say you would take 2 images in V band, and it quickly rotate to R band, and you take 2 images, and then quickly rotate to V band, take 2 images, and it would just repeat that cycle so that you have kind of equally spaced observations in every filter. It's less efficient because you're waiting for the filter to change every time or in between those sets, but the loss of efficiency is sometimes made up for by the more even sampling in the different wavelengths. But since we're only going to take a quick look, it doesn't really make sense here.
Oh yeah, and I forgot I'm recording this, so I guess we'll see. If this is good, then we can just take
all of this. Even if it's garbage, we'll just ignore it later. See how it looks. But we're a little bit into our time. We were supposed to be talking about citizen science. So
were we?
Switch to that. That's okay.
Okay.
Our schedule is flexible. We'll have Frank talk about some of that too, because he'll be on. We'll have our special guest.
All right.
Let's see if he's
Read out
here yet.
All right, so 12,000, 15,000, 18,000. Yeah, that's great. That looks awesome. So take 4, you think?
Yeah, at least.
Okay.
And that's just something definitely to make note of in the log. So
Yeah.
later on, I'm not wondering why this chunk of my light curve doesn't make any sense.
You're welcome. This is 171 through, or 1171 through. This will be 1175.
There's a message. We are having trouble streaming to Facebook. There may be an issue on Facebook's end.
Oh dear. Looks like we got.
Do we have anyone chat from Facebook right now? If yes, please give us a wave or a message.
Yeah, doesn't look like it. Looking at the looking at the live viewers, the amount of people in Twitch and SETI Institute, YouTube, and Facebook. We got nobody in Facebook, so it must have shut down.
Okay.
Facebook probably doesn't like it when you live stream for 8 hours straight, is my guess.
It's possible. I'll just double check that it actually isn't running. And then we can try to kickstart it, but I've never done that before.
I haven't either.
As we've established, this is my first time. Saved on the SETI Institute.
Yeah, all right. I'll leave that to you because I have absolutely no idea what I'm doing with StreamYard.
I am barely ahead of you.
Too bad. I called it first. Give me the deep links. Where are those deep links at?
Notes. Open up notes. Excuse me. Indeed, there does seem to be an 8-hour limit on a Facebook stream. So
who could have guessed?
I'm cut off at the 8-hour mark. I'm going to try to, let's see, it says remove this destination, then re-add it. Do we want to try that?
Sure.
Can't hurt, right?
Oh, I mean, it's already turned off on Facebook, so you might as well.
Remove. I don't know what to do here. Post was created on Facebook for this. Delete it. All right. First, we're going to do this. Stop doing that. Then we're going to this.
Validated and all right. We'll record, please. There we go. All right. Our eVscope is continuing to look at the asteroid as well. Oh dear.
Okay. I removed the old Facebook stream and added a new one.
Okay.
It now has a green check mark instead of a red X.
That to me means that things are happening. And yeah, so we'll see.
I seriously mean now that the one angry face.
Yeah.
That's pretty funny. Okay, yeah, we'll see if we get anyone back on Facebook. We apologize for the Facebook interruption. We now return to our regularly scheduled programming.
We have regularly scheduled for.
Just make something up.
Okay. 1174. No, 75. That's right. Gotta get these notes down so that we know what we're looking at.
Voila. We are back. In the meantime, I will check on our next guest.
Oof. All right, I had to do a lot of the heavy lifting for the Ariel interview.
Sure.
So I will help.
All right, that's okay. I will lead the way.
Hello. Hey, we got somebody back from Facebook. Hello, Eric. Hello from
Yay,
Norway.
From Norway.
So we're extra happy to see you, Eric, because apparently Facebook has an 8-hour limit for live streaming, and it shut us down there. So we weren't sure. The fact that you're back, you're here means that we are officially back there. So thank you for joining.
We figured it out. Take that, Mark Zuckerberg. We can do it too.
You and your stupid hospital.
The hospital's a good thing.
It is a good thing, but his name isn't.
Well, it's him and his wife, I believe, or partner.
Oh, okay.
I think they both have their name on the hospital. But anyway, that's not what we're here to talk about. We this time is nominally scheduled to talk about citizen science, and so we can use that as a lead-in to our next guest, who will be joining us shortly. We could probably reintroduce ourselves for the people who are joining. We are professional astronomers at the SETI Institute, Unistellar, and UC Berkeley. I'm Thomas Esposito.
I am Ryan Lambert.
And this is hour 8 of this live stream. We are currently looking at the Andromeda Galaxy with our eVscope. That's the main image that we're streaming right now. This is our Unistellar eVscope 2 that is just outside the building here, looking at this object for 20 minutes. Looking pretty good.
Yeah.
On the right-hand side here, just peeking out, we've got the asteroid 2011 MD5 that we're observing with the nickel telescope, which is what we're using here at Lick Observatory, which is where we're streaming from in sunny, when it's daytime, Mount Hamilton, California.
Mm-hmm.
And that's a 1 meter or 40-inch telescope that is just outside the door here in the dome. And so this is our main science target. We're observing this asteroid to measure its rotation period via its light curve, how its brightness is changing over time. And the eVscope views are kind of just for fun. We do have a second eVscope that is observing this 2011 MD5 asteroid as well simultaneously, because we can use the data from both for the citizen science campaign, the Planetary Defense Citizen Science campaign that Ryan here leads. And so that is a segue into our citizen science programs. We, through the SETI Institute, which partners with the telescope and astronomy company Unistellar, works with the users, owners of Unistellar telescopes, to do science with them, actual professional grade science. And so the idea is that they use their Unistellar eVscopes to collect data. Oh. No, sorry, I thought I saw a satellite. They use their eVscopes to collect data on astronomical events or targets. They basically take images and record images with their telescope based on the planned observations that we design as the astronomers. So we will say, hey, this asteroid's coming near the Earth. We want to observe it to see if it might be a potential threat to impact the Earth. Please take a look, collect some data. We'll analyze it, send you the results, and then we will either pass those results on to other astronomers in the community who can do more with it, or we will publish the results ourselves if it's something that we can do like that. Hello from Switzerland, Julian. Julian, it's good to see you. I
I feel like it's been a while since we talked, but Julian is one of our original OG citizen scientists from way back in 2020 when we started this. If I remember, particularly, he was observing a lot of exoplanet transits. That's one of our main campaigns. We have 2 NASA-funded programs for that actually running right now. We just got a nice 3-year grant from NASA to use eVscopes and citizen science data to observe newly discovered exoplanets, planets in other solar systems that were identified by the NASA TESS spacecraft. This is a space telescope orbiting Earth, but it identifies lots of potential exoplanets, and we need more observations from other telescopes to prove definitively whether they are planets or not. And so that's one of the campaigns we do. In particular, we look at exoplanets that take a long time to orbit their stars. A lot of the exoplanets discovered with this method, known as the transit method, where the planet is orbiting its host star and passes, its orbit is just aligned right with our point of view that we see it eclipse its star. That is called a transit. And so if we measure that transit, a lot of the planets that we see with that method, it's easier to detect them when they have short periods. So they orbit their star frequently, every few days, for example. We try to go after the planets that will take 20, 100, maybe even 1,000 to orbit their star, because it takes more telescope time to detect them. And with 10,000 plus citizen scientists in our eVscope Unistellar network around the world, we have that telescope time and the sky coverage to do it.
Yeah.
So that's what we're doing. One of the things we're doing with it. Do we want to switch filters?
Yeah. All right. What are we thinking? Back to V, or are we going to go to B? Or
let's try B.
Yeah. All right.
Unless you think I is better.
Nah, B. All right. Moving filter. This one is probably going to block out a fair amount of light.
Yeah, we may need to up the exposure time for B
Probably
band.
250. See what happens.
You weren't anywhere near saturating before, right?
Right now.
So let's just do 250. Let me
Yeah.
just record. Yeah, just take one.
Okay.
And so let's see. Where were we? Yeah, citizen science. So that's one of the campaigns that we do with this. And the idea is we can get more people involved in astronomy, right? You don't have to be a professional astronomer with a PhD to do this work, to contribute to our understanding of the universe. We actually need the help of more people. There are not enough astronomers or telescopes to go around and do all the science that that needs to be done.
Yep.
So
Space is big.
Yeah, space is big. And so we really do need and appreciate that help. Hi, Sovan from India. Welcome. Citizen scientist.
In good company.
Yeah, love to have you here. Yeah, and so that's part of what the Unistellar and SETI mission is to involve more people, get more people familiar with the science that we do and how it works. Particularly, we really want to try to involve younger people, students if we can. So we do have some programs involving in the US community college students that maybe don't have access to telescopes as much as other university students. And we're starting to get into high schools now as well. One of our group members, about to finish his PhD in astronomy, is teaching us high school science right now and is now using eVscopes with his students. Some of which I think observed tonight, either the occultation and or this 2011 MD5 asteroid.
Yes, I know because some of them were going to be watching the stream while they were observing.
Yeah, so we should have given you a shout out earlier. If you're still here.
Daniel was in here earlier.
Yeah, that's true.
But if you're still here, shout out to those students who are participating.
It's very late. I'm surprised you're still here. Thank you so much for being here. Also being here, hello Tim F, Vicky from Melbourne, Australia, and Rob from South Africa. Melbourne. Okay. All right.
I don't know. I'm sure I got it wrong.
I was about to say, don't mess with it. Yeah. So thank you all for showing up. Thank you for being here. I guess we are at the point as well where we should also re-describe who we are.
Did we just do that?
I don't know.
Yeah, we just had people sign on.
Yeah.
I'm Tom. He's Ryan.
Oh yeah, thanks.
We're astronomers at Lick Observatory, combining these Unistellar eVscopes, 4.5-inch consumer telescopes with. Can you reply back to him?
He's here.
Okay. Frank, our special guest is just connected. We'll get him in here in a minute. Where was I? I was saying we are here at Lick Observatory on Mount Hamilton in California, near San Jose and San Francisco. We're at hour 8 of this live stream.
Going strong.
And using the 1 meter or 40-inch telescope, nickel telescope, which is observing this asteroid here on the right as a planetary defense target to try and determine how it's rotating in its orbit.
Yep.
And also looking at some fun, pretty things like the Andromeda Galaxy here with our eVscope on the left. And an eVscope is also observing this asteroid for science as well, but we're not showing that too often. Okay. I think that's that. We can bring in our guest. So we are very fortunate to have our next guest, Dr. Frank Marchi. Did I get your pronunciation correct? No, that's wrong.
Marcus.
Frank Marcus. Some say asteroids orbit him.
God. That's right. That's how the top, the whatever it's called,
But
Top Gear intro is supposed to go.
Frank, can you hear us? Are you there?
Yes, I can hear you. Can you hear me?
Excellent. Thank you for connecting.
How are you? 8 hours live. Wow, what did I miss?
We found out that Facebook has a limit on how long they're willing to let you stream for. So we had to start it up again on Facebook. But yeah, and they told us that over at SETI, they were like, no one's going to stay if you guys are longer than an hour. We proved them wrong. There are people that are really bored out there who are willing to listen to us for 8 hours.
That's right. So Frank is a SETI Institute senior astronomer. He's also the chief scientific officer and co-founder of Unistellar, and an asteroid expert. So we have plenty of things we could ask you about, Frank. Is there anything you want to talk about in particular?
I want to talk about the occultation that was tonight.
Okay.
Yeah.
And and then we can talk about Unistellar or SETI or aliens or whatever you want to ask me. But let's start by the occultation tonight, so we have an idea of what happened. Yeah.
Yeah, absolutely. So for those who have joined in after the occultation happened, that was around 11 or so. An occultation is when an asteroid passes in front of a star and casts a shadow on Earth. One happened to be moving through California and a lot of North America. So, yeah, were you doing the observation, Frank? Did you get a chance? Or I know you are currently away right now. I don't think the path went through where you are, right?
What was the question? It was.
Were you able? I don't know how far the path went. Were you able to observe, or did you see anybody observing?
Yes, I cannot observe because I'm in Czechia right now in Europe, so that's not. I'm not on the path, and I don't have any eVscope either. And it was. So I just saw that Matthew Reno from Milwaukee Astronomical Society and 2 colleagues, student Drura Kalyani and Jericho Kuhl, sorry for the pronunciation, also from the Milwaukee Astronomical Society. They attempted to observe it as well. And there is one more person who mentioned they observe it is Mark Ziegler from Colorado. I met mark when we went to do to attempt to observe an occultation by Didymos 2 or 3 years ago. And he's always observing occultation on this one above his house. So apparently he observed this one as well. Right? So occultation has low chance of success. And this one specifically, because this is a 100-meter diameter Mars crosser asteroid. So it's a very small asteroid. And the smaller is the asteroid, the more uncertain is the orbit. So you need to have a lot of people along the potential path of the orbit to be able to potentially capture the occultation. It's kind of, it's playing lottery, but the chance of success for this one, if I remember, I think, Tom, we got this number together, but I think it's top 2% or something like this if you are on the path.
Oh, wow.
Yeah, it was quite low. We watched in real time. We did not see by eye an occultation. We thought there was one other citizen scientist, Jennifer Sidders, sorry for the pronunciation, I think on the East Coast, perhaps. I'm not sure where exactly they were, but might have seen it. So we'll see.
Okay. Well, I don't have yet the logs, so I don't know yet how many people observe it, but it's going to come pretty soon. And as usual, we are going to have this data processed by the pipeline and generate reports, which are typically videos where you can see the star frame per frame. So you will see the occultation on the video. A posteriori there is one. And then the report is generated after an analysis using a machine learning algorithm that look at the star and compare the flux and basically tell us whether or not there is an occultation. And when this is done, the reports of all observers with the location and whether or not they have detected or not the occultation will be generated. So this can take typically 48 hours to get the final result. We don't do this thing manually, as Tom knows. We try not to, because it's there is way too many occultations observed by our network.
Still, 48 hours for, I don't know, 10s, 20s, 30, sometimes 50 people observing. That's pretty quick. It's pretty quick turnaround. So,
yeah, it's, of course, this is the perfect fairy tale I'm giving you, because of complication, way more complication in this process. There is always some difficult data. People observe there is clouds, the telescope shaked. I don't know. It's astronomy. It's not a scientific. It's not like it's not a theory. Okay, it's observational astronomy. So you have to deal with conditions. You have to deal with light. You have to deal with weird behavior sometimes. So
if it worked perfectly every time, we wouldn't need us. So I'm happy with that. I'm glad we have a job.
Yeah. Because if everything was easy, we have done already this kind of analysis and replace everybody by machines, and it will be over, right?
Yeah.
That'll be coming soon. ChatGPT astronomy version. Yeah. We know you're heavy into ChatGPT, right, Frank? You're a big fan.
I'm a big fan of ChatGPT because I'm an English second language person, so it's kind of a great tool for editing all my documents and taking the time to ask information about, I don't know, sometimes last time I was talking I use Bard for this one. The new mission is going to be, has just been launched by the Japanese Space Agency to land on the moon. It's a very interesting mission because it's going to, not to land straight, it's going to land and then collapse. So that's the one of the cool part of this mission. It's called SLIM. SLIM. And everybody was wondering what this mission is going to be doing, and I could not find any information on the web. And I asked Bard, and Bard gave me a list of activity. I don't know where Bard found this, but they found the payload of this, what's going to happen, and the timeline. So,
wow, pretty good. Probably in somebody's email. Some personal email.
Yeah, Google's like, don't mind if we do, just yoink this information from you. Appreciate it.
That's possible now I think about it. I like when Tom don't sleep too much. He's getting more and more in French.
Paranoid.
He gets a little loosey goosey. It's great.
We're paranoid. Yeah.
No, not paranoid. Acerbe. Oh, man. How do you say that in French, in English? I will find the word.
ChatGPT.
Acerbic. Well, no, I never heard anybody saying that.
Perfect. Yeah.
Bitter or sharp. Yeah.
Yeah. I'll take acerbic.
It's always acerbic. It's just you're usually a little more quiet about it.
Yeah.
Normally, Tom is on his corner typing hysterically on his keyboard to make sure that we finish the code that he has to finish. But I'm glad to see that when you observe, you're different. Good.
That's
Good.
True. Yeah, go ahead.
It's telling you.
After you.
Oh my God.
Me?
I'm bored. You guys talk.
All right. So I was going to ask, I believe in a past life, you used to work on telescope instrumentation quite a bit, developing instruments and things. Can you give us an overview of what you used to do, like in adaptive optics, for example?
Yeah, I'm gonna be like the old man. So we started adaptive optics in 1990s.
Wow.
Yeah.
Quite a few questions about adaptive optics early on.
Yeah. So when I did my PhD, was just starting this technology, and that's a technology that allows to correct the atmospheric turbulences as if the telescope, providing images as if the telescope were in space. That's the way we sell this. And my job has been for a long time to use adaptive optic systems for solar system observations. So to observe bodies in our solar system. So for instance, we used the first adaptive optic system on the 3-meter class telescope, which was called Adonis. And this AO system was at La Silla in Chile on a 3.6 meter, as I mentioned. We observe Io, the satellite of Jupiter, and saw the volcanoes. And that was the first time we detected from the surface of our planet the volcanoes of Io, because we could see them using this technology, because we removed the blurring of the atmosphere, so we were able to pinpoint the location of the hot magma on the surface of Io, or Io, whatever you want to say it. So that was my PhD, and I did that for Uranus, Neptune. We detected the moons of Uranus and Neptune using AO, and then we observed Cleopatra. We detected the bilobed shape of Cleopatra, made of 2 lobes. We found out that asteroids are much more interesting than people will believe. They're not rocky, tiny dots in the sky. They have worlds around them. Sometimes moons. Sometimes they're 2 pairs. Sometimes they're a combination of that. The orbit of the moons change over time. There is some very complicated phenomena into the moon system because of the shape of the primary, because of the spin, etc. So we spend a lot of time trying to understand how moons of asteroid works, basically. And in 2005, we discovered the first triple asteroid system. So an asteroid system with 2 moons, around 87 Sylvia in the main belt. And the good thing of when we do this kind of discovery is that we can also name the moon. So I named them Romulus and Remus, because they are the son of Rhea Silvia, known for being the founders of Rome. So yeah, this is kind of work I've been doing for 10, 15 years. And then when I arrived in the US, we also developed new instruments, and I met Tom doing this. That's when we started working on the GPI, the Gemini Planet Imager, which is an instrument dedicated to observe not only the solar system, but more importantly, to look for exoplanets and to image exoplanets. So that's a project led by Bruce McIntosh, who is now the director of the UC Observatory. And So that was a very cool project, because I always remember the first meeting we had in 2003 with Bruce and 10 other people. And we had this kind of secret meeting where we talk about what we could do in adaptive optics to make a difference. And Bruce was convinced that we could develop an adaptive optics system that will be able to image exoplanets. And at the time, that was a crazy idea, frankly. Most people did not believe that it would be possible to do that. Bruce betting this on the evolution of technology, on the fact that adaptive optics system will get better because the electronics will get better, more deformable mirror, more actuators, faster. The computers will get better as well. That was really that was a vision at the time in 2003, and it took us 4 years, if I remember, to get the funding for NASA. From NSF, even more, 5 years. And then in 2009, we started the building of the instrument and put together the instrument, then brought it to Cerro Pachon in Chile. And 2014 was the first light. So the cool story here is that sometimes you can have crazy ideas in astronomy and they may work. You just need to be patient to make them work.
Yeah.
Yeah. I will say, I do think it's been very interesting with my trajectory in astronomy. When I was an undergrad, all of my professors were much more of the old guard, and they were all very staunch, like space telescopes are the only thing that's going to be the future. There's no way you'll ever beat space telescopes. And it's been very interesting over the years seeing how that opinion is now, like, actually, I mean, AO is good enough that ground-based telescopes are very viable. And because they're so much cheaper compared to sending a telescope up into space like that, it feels like it's kind of wrestled back towards ground-based telescopes being the continued future of astronomy. Space telescopes always have their place, but AO's really moved the game, I feel like, just from my perspective as I've gone through.
Yeah, the advantage of AO is also that we follow the advance of technology on Earth. I mean, one of the problems of space telescopes, and people probably will not like that, but would I say that? But JWST is a great machine, it's a great telescope, but the instruments on board JWST are not cutting-edge instruments in a way that they are not they are not basically instrument that's just been developed. They're based on technology from the 90s. Which is kind of weird when you think about it, because they have to take a decision in the 90s of what they're going to build, and then design the instruments starting from that. Maybe I exaggerate, maybe it's 2000, but it's not the technology from now. Yeah. Adaptive optics, there is a new type of detector, a new wavefront sensor, a new way to measure the phase of a wavelength. You install that, you test this on the ground-based telescopes, and then you implement it in AO. You can improve regularly your adaptive optics system. So, for instance, the Keck adaptive optics system that Tom and I use like for more than 15 years now has been evolving over time. I don't want to enter into the details, but we used to have an adaptive optics system that could observe object of magnitude 13 or 14 invisible, because they are the reference basically source. And now with the pyramidal wavefront sensor, they expect to reach a much fainter magnitude. So be able to observe more targets in the sky using AO system. With the new camera, they expect to reach now a contrast ratio 10 to the 8th, so be capable of detecting, imaging more exoplanets or more moons around asteroids. And this happened by changing instruments or some parts of the AO system that we have at the Keck telescope. When was the last time, Tom, you used the Keck AO system?
It was a couple of years ago, 2 or 3 years ago, I guess. I've actually been working more with Hubble data, but yeah. Last I used it, I used their new pyramid wavefront sensor to reach one of those fainter targets, and it worked quite well.
Yeah, And Tom and I, we are on this project with Ben Gerard, called, what's the name again? It's
Redwoods.
Redwoods, yes. So Ben has the idea of a way to improve AO system by taking short. I mean, I don't want to enter into much details, but we are part of this group of scientists who are helping Ben and his team to design the new type of technology AO system, and it will allow to get better correction in the visible, because that was something that we really wanted. I forgot to mention that after GPI, I started a project at the VLT. I betray GPI, but because I went to the very large telescope, because they had starting a new AO system in visible. And we observed with this AO system 48 asteroids, main belt asteroids mostly. And when you observe in visible, contrary to the infrared, you get a much better resolution, factor of 4. So you really have a telescope observing in a visible, like Hubble, but instead of being 2 meters like Hubble, you have 8-meter aperture. So you see significantly more details.
Yeah, and yeah, so the beginning of adaptive optics focused on the infrared wavelengths because the atmosphere doesn't affect those wavelengths quite as quickly and severely as it does the short wavelengths, where the turbulence in the air really wreaks havoc on those photons as they come through with all their energy. So yeah, visible light AO is really something that's going to be coming into its own soon.
Yeah, can I show something quickly?
Yes, let me stop sharing my screen. So yeah, you should be able to.
Yeah, so share your
Present.
screen and we will
Yeah.
put it on stage.
You click present, and then we will add it. So.
Oh, there he goes.
Yep.
You didn't have to do anything.
There you go. I added it.
Oh, okay.
So this is a project led by Pierre Vernassa from the Laboratoire d'Astrophysique de Marseille. So we observe, as I mentioned, 48 asteroids, large asteroids. And this is an image with an adaptive optic system, for instance. So you can see the shape of the asteroid. This is truly seeing the asteroid, right? I don't know how many. So the good thing, like we observe, for instance, Psyche, and we detected some area, bright and dark area on Psyche. Psyche is a M-type asteroid made of metals, essentially, and it's a target of the target of the Psyche mission of NASA that's going to be launched at the end of the year. So we've kind of prepared Psyche mission by providing the size, shape, surface composition, not surface composition, but surface variegation of Psyche. I don't know, there is no many pictures here. I wanted to show you Pallas. That's a cool, very cool image. Here it is. So that's Pallas. So Pallas is a very large asteroid, okay, and it's number 2 Pallas, so it's very known. The interesting part here is that we had no picture of Pallas until, yes, I consent everything, until 2020. So we had no idea what Pallas really looked like, and it's the largest. So using adaptive optics, we finally got pictures of Pallas, and the remarkable thing that you notice here, he has this very interesting shape surface, like a golf ball, like tiny craters. And that's because Pallas is part of what we call a collisional family. So is part of an asteroid family that's been basically is a result of fragmentation of a large asteroid and reaccretion, and there is still a lot of fragments around it, or there were a lot of fragments, and regularly it goes through this swarm of fragments. So that's the reason you have this craterization, intense craterization. And what also is cool, but of course they're gonna show it here, but you see it here, is that. And that's something that we don't know yet. There is this white, bright features on the surface of Pallas in a very specific area. We don't know where it is. We suspect it's salt, a little bit like what we see on Ceres. On Ceres. And the reason I want to have a better adaptive optic system in the future is to be able to characterize that, to take spectroscopic observation of this and get the nature of this white spot on the surface of Pallas.
Oh,
Nice.
that's interesting. I hadn't seen that.
This is one asteroid. As I mentioned, we have 48 of them, so I could give an entire lecture. I already did that, but I'm not going to do that here today, talking about the shape of asteroids and so on. But you can see, we see the craters. I mean, that's impressive. Those are real observation with the VLT adaptive optic system, Zimpole sphere Zimpole, that's the name.
Yeah, that is pretty great. So how large is Pallas?
1,000 kilometers or something like this, if I remember.
Yeah, so really...
yeah, it's a giant.
Yeah, it's big, but also small when you're trying to get that level of detail.
No, it's 545 kilometers. Yeah.
Okay.
It's the same.
Order of magnitude. Yeah, interesting. Oh, sorry, we're taking exposures here.
I can stop sharing. I'm going to do that now.
Yeah. Creepy clown that Google kept trying to show us, that creepy clown. Where was I? Let me get my screen back here. I was going to ask, actually, to switch gears, so you are the leader of the Unistellar SETI Science team. We had just started talking about citizen science before you connected.
Okay.
I was wondering if you had a favorite accomplishment of our citizen science group so far since 2020.
I'm not going to play this game. I always say, you all my babies, and I love you equally, all of you.
Yeah, my mom says that same thing, and I think we all know that's a lie. Like, oh my God.
No, well, I'm gonna tell you some of the things that I thought was the big achievement. I really recently, of course, I love the DART result, the DART mission result. You probably talk about this with Ariel.
Yeah, I forced her to talk about it.
So that was the project led by Ariel and Ryan. So kudos to both of them because they were new members of our team. And yeah, we did observe with the only group who published the observation of the DART impact live. And we did the analysis, assuming it was a comet, which was kind of, I think, a good idea. And get some scientific result that show that humanity can deflect an asteroid, 100-meter size asteroid by kinetic impactor. And we published this with 5 other papers in Nature. So that was a big deal, I think, this last year. I love the fact that we are doing more regularly transiting exoplanets. I mean, we are getting a very interesting results with this program supporting the NASA test mission and preparing to support the next mission will be Plato probably in the next in 2027. So we have so many exoplanets now that candidates, I would say, that it's necessary to have more telescope observing those transits to confirm that they're truly happening and the true nature of these transits. So I think Unistellar network find its spot in being contributing to space, to the understanding of space with this program. And this is not going to end, as I mentioned, because we have more missions going to be launched. We're going to discover more exoplanets. I think there was a prediction that after the Plato mission, we should have more than 100,000 exoplanets candidates. Whoa. So, I mean, we are going to have a lot of work in the next 5 years, 10 years.
Yeah, no, I'm out. I'm checking out before we get to 100,000. That's too many.
Yeah, you will do like me. You will hire a group, and then you will basically have the people doing it
That's right. That's right. That's what grad students are for.
And it's gonna be cool. I mean, imagine 100,000 exoplanets. You're gonna be able to do the good science we do with asteroids. Start classifying them, understanding how they form and they evolve, doing some study of their orbits. I mean, that's gonna be a golden age for exoplanet studies. And amateur astronomers, citizen astronomers will be able to observe them using this Unistellar telescope and other telescopes. You can imagine that in the future there will be even more sensitive telescopes or even more better instruments capable of detecting not only Jupiter-sized exoplanets in orbit around solar-type stars, but even smaller. I don't know. Maybe Unistellar will do a telescope that will be more sensitive. Maybe we will do a telescope that will allow you to detect super Earths around G-type stars. We don't know. So I'm kind of, I think this is a very cool project because we have scientific results. We are detecting a very long duration transit last year. It was Kepler 16e, I remember.
Kepler 167e.
167e, yeah. And we have more papers coming soon. But it's also a success because we also got funding. I mean, that's a very important part of what we do as a scientist. As you know, we need to pay people. We need to pay for the equipment and so on. And having the support of NASA is key for this kind of program. And we just can we mention that we got this new grant, Tom, or no?
Yeah, I mentioned it.
Cat's out of the bag now.
Yeah, I mentioned it.
Okay, Tom so got recently a significant grant from the Exoplanet program at NASA to continue this research for the next 3 years. So yeah, kudos.
Yeah.
So that's I really like this part because of that. I love the fact that we can now observe flybying asteroids regularly. I know that Ryan is working on this tool that will alert citizen astronomers when there is a new asteroid detected and is flying by Earth, and we need to have more data. So that's gonna make us. This is gonna put us into this what we call time domain astronomy, where basically you do science because something new happened. Okay, and we are going to use the fact that we have a network all around the planet, and there will be always someone observing, and there will be always someone capable of seeing these asteroids in the future. That's very important. If we see an asteroid, for instance, that could enter into as a high probability of impacting Earth, we may be the network capable of observing this and helping refining quickly the zone of the area of impact, for instance. We have done that in 2006, before Unistellar, with Peter Jeninsken at SETI. We observed there was an asteroid that impacted Sudan, an area in Sudan, and we basically did live the orbit calculation by adding more and more points collecting by telescopes around the world. And we realized that this is great, but it's difficult because most of the time that people take the data, but it takes a long time for them to send the observations and so on. So with Unistellar, what we're going to do, we are going to bypass this and provide almost shortly after the observation an astrometric position of the asteroid. That's the goal. That's what we would like to be able to do in 2 years, 3 years. And the reason we care about this is because if we have an asteroid impacting Earth, if it's a huge asteroid, we want to be able to at least warn the people that it's going to happen. But if it's not such a big asteroid and it explodes in the atmosphere, we would like to be able to quickly deploy a team on the area and look for a fresh, pristine fragment of asteroids. So instead of sending mission that costs billions of dollars to go to the asteroid, capture a fragment and bring it to us, like Hayabusa 2 and next the new one who's going to land soon, Osiris-Rex.
Osiris-Rex, yeah.
we are going to simply wait for the asteroid to come to us, calculate quickly its zone orbit, zone and impact, and go over there and pick up fresh fragment. And that's also something we did with Peter Jennings-Ken in 2006 in Sudan. He basically went there and hired 400 people, and they work in the desert over there, and they find pristine, fresh fragment of this asteroid. So that's a kind of a cool science we want to do in the future. I love comets, of course, as you know, because they're beautiful and they're fun, and they are always surprise us. And the last one, transients.
Leaving for last, the best for last, of course.
I always leave this one for last because it's the newest baby, I always say. So this one is gonna be this one is in the end of Tom, and I kind of happy about that because when LSST, the Very Rubin telescopes, will be on, we are going to get thousands of alerts every night. So we are going to be able to use the Unistellar eVscope to confirm the existence of this this flash in the sky, and hopefully understand better the true nature of those. The goal is to be able to get a coordinate and an observation 2 minutes after the detection of these features in the sky. So these features could be anything, could be a nova, supernova, could be some weird physics in the star that brighten it suddenly, could be aliens telling us that they are here by sending powerful laser light to us. It could be plenty of things, and we are going to involve the Unistellar network into this study by plugging basically the Unistellar network to the Vera Rubin and making sure that people can get alerts on the Colibri app and maybe later on our app. So when they're observing, they're doing something, and suddenly they get an alert on Colibri saying there is a bright flash in this area of the sky. You can observe it. You press a button, the telescope flew to the right location, take the data the way we predefined it, and send us the observation. So that's going to be very cool. That will be extreme time domain astronomy, and I think there will be a lot of discoveries coming from that, from this project. So
yeah, definitely, I agree, and I see Fabian from Astro Colibri in the chat. So thanks for joining. And we just partnered with the Astro Colibri group so that we could pass those real-time alerts directly through their app to our citizen scientists, and actually to everyone. It's public. Anyone can see the transient alerts that we flagged as the most interesting to go after. I think gamma ray bursts was maybe one you hadn't mentioned. The most energetic events in the universe that we know. And we have some ideas of what causes them, but we don't know everything. So that's one of our next goals, is to catch one of them. It's a challenge. So yeah.
And it's not over. I mean, we have ideas of new science we can implement in the telescope. I can give some kind of vision we have. We try multiple times with the Observatoire de Paris and the DLR to get funding from the EU, ERC, and others in the goal of observing occultation by satellites of planets. Europe, something very surprising. I know most people think that we know everything in space, but for instance, Europa Galilean satellites, well, their orbit is still kind of unknown, which is weird. I mean, we've been observing them for more than 400 years, right? Because that's the first thing that Galilei detected using his tiny telescope. But despite that, we still have an uncertainty on the position of this moon. This was confirmed to us because last year, I think it was last year, I flew to Namibia to observe an occultation by the asteroid Europa. We used multiple telescopes, including the Unistellar telescope, to observe that. And the data analysis we got from this observation is that Europa is shifted by 40 kilometers, 40, compared to ephemeris. We have no idea. We still did not publish because we still have no idea if this is real, is that an artifact? I don't know. We have still a lot of conversation about that, but we suspect that there is some perturbation in the Galilean system due to the fact that Jupiter is not a perfect sphere. There is some homogeneity inside Jupiter, and also the shape of Jupiter is not perfectly circular. So this affects the orbit of the Galilean moon and probably the other moons as well. The best way to observe the location of an object is to do occultations. So we would like to be able to use the Unistellar network and others to observe the location of the moons of Jupiter and Saturn by occultation. So that was a project we submitted second time this year. We get rejected recently, but one day or another we will get this funding, and that will be probably one of the next citizen science implemented into the Unistellar telescope.
Cool.
We will also do satellites.
Yeah.
So, did you talk about that already or no?
Not yet. Just while you were talking about moons of Jupiter, something I happened to look up about this observatory, that the telescope that used to be in the dome we're using now, the 12-inch refractor that used to be here, was used to discover the 5th, 6th, and 7th moons of Jupiter. Those were the first discoveries of a new moon since Galileo, which I thought was pretty cool. I hadn't known that until just recently.
That's sick.
Yeah, so that was done steps away in the same dome as the telescope we're using tonight. So yeah.
Amalthea was discovered at Lick Observatory. I didn't know that. See?
Yeah, exactly. Yeah, I think it was 1880 or 1890 something. It was a brand name astronomer. I'm gonna get it wrong, but yeah, it's pretty interesting. Okay. Oh, Barnard, who discovered Barnard's star, which is one of the fastest moving stars across the sky.
Yeah.
Which sort of connects to satellites, as you were starting to say, fast moving things.
Yeah, so satellites. I'm talking about artificial satellites. We have, as you know, there is a constellation of satellites being launched, 2 of them, in fact. It's the Starlinks and the OneWeb. And so those constellations will have thousands of satellites. And apparently there is new project from other countries to do that as well. So we can expect that in the next 5 years, we'll be probably increase the number of satellites by hundreds of thousands. So we're gonna reach probably 100,000, 200,000 satellites in orbit around Earth. So that's a problem for astronomy, as probably some of you know, because those satellites, they pass in front of the objects and they can be bright, especially at the beginning of the night and the end of the night. But also more importantly, these satellites also, there is a risk of them impacting each other and producing what we call a catastrophic collision, and then wiping out basically because of production of fragments that impact other satellites, wiping up an entire area of potential orbit around Earth. So we are relying on those companies to take care of the orbit of the satellites, but it would be also, I think, important to continue to have also independent study to pinpoint the location of the satellites regularly, to know where they are, to see some kind of activity if there is some issues and so on. So with the Unistellar telescope, you can observe Starlink satellites. We see them regularly in our field of view. With 100 milliseconds exposure time, you can see a satellite, a Starlink satellite. So, and derive the position, the location, and the brightness of the satellite. So Ryan is working on that. Because I'm the one who talk about it, but he's the one working on this. So Ryan, tell us a bit about what you're doing right now with the satellite program.
Yeah, so I got on my soapbox earlier in the evening, but we have a whole new audience now. So yeah, basically what you just said, satellites are going to become a larger and larger problem for astronomy. So it's probably something it would be good for us to know exactly what that effect is going to be. So that is one of the science campaigns that I am working on developing for the eVscope is letting people observe Starlink satellites so that we can derive their brightnesses and using some of the other information available, such as what the Starlink satellite is, where it is in its orbit, how high up it is. If we get a big enough sample, we can start to identify, what positions are really, really bad for Starlinks to be in. How high up do they need to be? What's the elevation above the horizon where they're just going to be blinding through our field? And that's something that's honestly not there's some studies, but it's very hard to do, and for the most part, it's a difficult problem to solve. So people haven't really tackled it all that much. So yeah, that is what we're going to do. We already have a few tools provided to people on the Unistellar network who use their eVscopes. They can we have a little ephemeris tool that you can put in your coordinates and the times you want to observe, and it'll tell you, yeah, okay, so there are these Starlink satellites coming through. One big benefit of these kinds of observations is Starlinks move really fast. Satellites move really fast, so it's 2 minutes of your time. You could observe 30 Starlinks in an evening and still have plenty of time to look at whatever else you want. But yeah, so that's essentially what our pipeline is going to be designed to do. We're giving people the tools to observe these satellites, and then once they have those observations, the question is, how do you go through 400 images and figure out this is the one? This particular one has the satellite in it. And then after that, you actually have to decide where in that image is the satellite. That's something that you and I can do very quickly and very easily. But it's a lot harder to get a computer to do it without human input. So those are two problems that I think we have recently solved. And so after that, we just have to figure out efficient ways to do actual photometry on the satellites. And so those are the next steps. And once I think we have that done, we'll have a good working prototype and start being able to make some definitive statements on Starlinks and see if we can get some correlations on the brightnesses and the positions and everything else. Also, I don't know if you actually mentioned this. Sorry, it's very late over here. So if you've mentioned this, I apologize. But it's great for determining what mitigation strategies that satellite companies are employing actually work. So Starlink has the dark sats that they've made, where they painted some of their Starlinks darker to try and lower the reflectivity. And there were a few studies done where it shows that it did work. It did help, but maybe not to the degree that they had hoped. So it's another great tool where we could work hand in hand to try and give advice to the satellite companies to actually try and keep the brightness of these satellites down.
Yeah, because the brightness could be an issue definitely for ground-based observations. Unfortunately, we will be affected. I mean, now the question is at which level, and shall we limit the development of this technology because of astronomers? So is there a way we can mitigate this? Is there a way we can, for instance, predict when one of the satellites will cross the field of view of sensitive instruments, so we don't have to, so we can just go around this problem? So that's one of the idea. And for that, we need a database of all these satellites, and they change. I mean, the satellites are not asteroids. They have some of them can be moved a different location. So the private company may decide to move them. They can move them for technical reasons, but also because they want to avoid an impact with another satellite. I mean, so we need to kind of always observe those regularly, and the Unistellar network could be a great tool to do regular observation of satellites. So
Yeah,
that's
I
the
agree.
goal.
And one of the things that maybe we didn't touch as much on is that the position, the angle of that you're observing. So the satellite is orbiting Earth, and depending on whether you're looking from the north or from the south, could affect how things are. So the fact that people are observing from all over the world could also give us some really good information about really specific causes for what we might even be able to narrow down. Like, okay, so this specific instrument at this angle is very reflective. Maybe you don't have to paint the whole thing dark. You just have to paint this one specific instrument that is on the satellite. So yeah, it's very neat. I like this project a lot. It's just it comes with a lot of difficult challenges that aren't immediately inherent. So it's a very fun project to work on to try and solve those.
Good to hear. All right, so you're using you're watching a nebula right now, the Iris Nebula. What is this?
This is the Cocoon Nebula. I was just trying to see how well it was coming through on the stream, because it's starting to come through on my laptop and the tablet, but I feel like maybe not as bright on the stream. You can zoom in a little bit. It's all. Let's see, where's my mouse? It's a red nebula right around here. But I feel like it might need a little more time to come through. We've only been here for about 2 minutes. We were on the Andromeda Galaxy for a long time, so I wanted to move on.
I think our
Yeah, so that can you show how we can pretend to be an astronomer and to know everything about the Cocoon Nebula using the app?
Yeah, I can do that. Yeah. So that's where's my mouse? Yeah, this button here at the top. If I tap that, it will show me a little bit of information. There isn't actually anything useful for the Cocoon Nebula. I was showing this before for some of the other objects.
Yeah, M15 was a good one. It had lots of information on it.
Yeah, but for example, you can see, I think it's in the constellation Cygnus, which is the Swan constellation. So here's the wings of the swan and the body and the neck, I mean. And that's where the Cocoon Nebula is relative to that. So let me go back and see if it's looking, come on. See if it's looking any better yet. Go down.
Wait.
Yeah, maybe, what?
I think we've gotten connected, wires crossed. I'm looking at the Cocoon Nebula on this one.
Huh. That's your problem. Not
Oh, okay, fine. You continue. I'll figure it out.
Just change the Wi-Fi network. Yeah, so we'll see. I'll give this a few more minutes to see if it comes through. Actually, it is quite a bit more clear on my laptop, which is interesting.
I can see it here.
Okay.
Yeah, but I typically stay on this one for like 15 minutes, something like that. So.
All right, I'm gonna go check the.
Yeah, it's a fainter one.
I think it's turned off. I'm not sure.
Okay.
Yeah, sorry, we're sorting out the science eVscope. Ryan's in charge.
Yes.
Yeah, our plan is for the next hour or so to hop around some new targets with the eVscope while we continue to observe this asteroid with the nickel.
Okay, you want me to leave? You let me know and be frank and direct if you want me to.
No? Yeah, and you're welcome to stay as long as you want. If you want to go do things, it's your Saturday afternoon. So if you want to go do something more interesting, go right ahead.
You've been live for 9 hours. Wow, I'm impressed. Okay. No, I can talk about the Unistellar network because there is some people who ask often where this is coming from. I didn't mention, so maybe.
Yeah.
In 2017, we basically started this project with a Kickstarter. So I met the other co-founders at the CES, the Consumer Electronics Show. And the reason I went there is because I quickly, at the time, I was trying to raise money for a private project, a space telescope to search for for habitable exoplanets around Alpha Centauri. And we had to talk to investors and to wealthy people in the Bay Area. And I realized that I didn't know how to speak to these people. So I decided to go to CES to learn how to pitch and how to kind of interact with people, investors. So when I arrived at CES, I went to the French pavilion, and someone told me, hey, there is this company who wants to do telescopes. Since you're an astronomer, you should check it out. Maybe you will be interested in what they're doing. And that's the way I met Antonin, Laurent, and Arnaud, who are the other co-founders. We quickly realized that we have been working together, Arnaud and I, for different reasons, because Arnaud used adaptive optic systems to study the brain. And he was basically at the time using mirrors that I've been developing with a company called Ariel. And I brought those mirrors to the lab where Arnaud was working, but I never met Arnaud because he was the head of the group and he was always traveling and so on. But I met his students and postdocs and so on. So we were connected. So we realized we have a similar interest, image quality. And Arnaud is an amateur astronomer. So he really wanted to build a telescope for everybody, a telescope easy to use. And I brought to the company the idea of community, citizen science, and what type of citizen science we could do in astronomy to help professional astronomer by doing cutting edge scientific studies, basically. They had the idea too, but I brought kind of realistic assumption on what we could do with this telescope. And we had a prototype very quickly that I show around in different places. People remember me for being the guy who bring this weird telescope that I was operating using a tiny keyboard at the time. It was not as fancy as Unistellar now. It was not as pretty as well, but he had the technology that we wanted to develop.
Mm-hmm.
And we did a Kickstarter in November 2017. That was a significant success. It took us a bit by surprise, to be honest. We were expecting this to sell like 100 or 200 telescopes, but we had more than 2,000. So we had to create a real company at the time. So quickly we became more entrepreneur than scientist. Almost everybody quit his job to as a scientist to basically work for Unistellar, Antonin, Arnaud. And I brought SETI Institute into the mix with an MOU that we signed between the non-profit and Unistellar. And SETI became in 2019 the official scientific partner of Unistellar, meaning that we have access to the data of the Unistellar network to do citizen science, and we can promote citizen science in astronomy using the Unistellar network. And I think that's at the time you started working with me, Tom, specifically on Unistellar.
Yep.
Yeah. And then we created a scientific education group in San Francisco, which lead the science and develop science education and outreach. So we have now 6 people working in this group, even more. It changes all the time, so I still can't count.
6 plus minus 1.
And so the separation is that in San Francisco, we do science education outreach, mostly. In Marseille, they basically develop the technology, the telescope, the software on board, the app. Okay, so the group in Marseille is significantly bigger. We have almost 50 people now in Marseille, to give an idea to this audience. So I'm in Europe right now because Monday I'm going to Marseille to meet the team, to discuss about the next projects and stuff. I mean, and see the team, because there is I think I've not been there for like more than 8 months, and there is 10 person that I've never met. So it'd be great to see them in person, so we know each other. And we delivered the first telescope in 2019. So it took us only less than 2 years to go from an idea, a Kickstarter campaign, to a telescope. And that was the eVscope 1 that most of you have seen. Then we released multiple other products, the Equinox, and then the eVscope 2, and then the Equinox 2. So all of these telescopes are more or less the same shape and size, 4.5-inch, same technology, but different type of camera on board, with or without eyepiece. But they are more or less the same capabilities in sensitivity. I mean, the eVscope 2 is probably the most sensitive one. We recently have a student, Sam, work with Ariel and us, and she derived that we can reach magnitude 17.5 or something like this with the eVscope 2, observing after I've forgotten 10 minutes of observation. I mean, this is something that we knew, but now we have some direct calculation of this. So it's a powerful telescope. And with this telescope, you can do great science and can enjoy observing objects like you're just doing right now. And it's also kind of a dream of an astronomer. I mean, we have a network of more than 10,000 telescopes around the world. And I often say there will be always a starry night in the Unistellar network. No matter what, there will be always someone observing and having a nice weather in this network. So, and if something happens in the sky, something crazy, for instance, Tom and I can basically send an alert to this 10,000 potential and more potential observers, and there will be someone who will observe this part of the sky. I mean, that's kind of cool.
We communicate with our citizen scientists mostly through the Slack workspace, which is like a direct messaging chat application, and there's just about at any moment, there's just about always somebody on sky with their telescope in some part of the world. And I'm looking at our chat here. We have people from Quebec. We have people from South Africa, a bunch of people recently from Australia. And so, yeah, they're not all part of the Unistellar network, but I know some of them are. So it's cool to have people all around the world working together.
Oh, here you go. Cool. Yeah.
I don't think it's recording. Did you start recording that?
No, it was already recording. It never stopped.
Okay.
It was just, it
just
didn't update.
switched to the other
Yeah.
telescope. Yeah. So, yeah, we've been, go ahead.
Yeah, so beyond the technology, beyond the fact that we can do citizen science and make great discoveries with people all around the planet, there is two parts that I really like in the network that motivate me every morning to work on this project. One is the fact that we have created a truly international network. It's a worldwide network. Okay, we are on every continent but Antarctica. We're concentrating in the Western world at the moment because that's where we started selling telescopes. So United States, Canada, Europe, and now Japan. But we're growing the network. We see more and more people. I mean, we have published a few maps that I show at APRAM conference showing how the network is growing over time. And you can see it's growing in number, but it's also growing in distribution on this planet. We have more observers in Africa, in South America, and in Asia now that we had over the past 2 years. So we are bringing this technology to other places in the world. We're still looking for distributors. So if someone here watch this and wants to be a distributor of a unistellar telescope living in a country in the world, let us know. We are open to having more distributors, more resellers in different places. So that's one thing. Like, I really like the fact that now when I talk on Slack to people, I can speak to people from all around the world. It's not only the Europe and United States. The second part that I really like with this network is the fact that we also changing the demographic of amateur astronomy. We have a large part of our observer who are women, people of color, young, old. It's extremely diverse, and you see that in the Slack, and you see that as well when we do star parties. Like we have a telescope that people use using a phone, and the young generation, I can see that with my own kids, they're always on their phone. It's kind of the interface that they have with the rest of the world. So it's natural for them that the phone is also the connection they have with space. With this telescope, we've been attracted young people to do astronomy, to discover the dark sky. The UConn project that you probably mentioned, the idea of having our telescopes in community colleges and train the instructors and have more students doing astronomy, learning about astronomy by doing astronomy is working as well because of that. Because we have a telescope that allows these young people to observe the dark sky, to quickly see things like you're just showing right now, and to appreciate what astronomy is all about. Okay.
Yeah.
Without having to bring a telescope, mount it, plug it, forget the cable, all of this. We don't have to do that. Something I always say is that professional astronomers are not doing this. So why? I mean, when I say this, we are not. When a professional astronomer comes to observe, most of the time in most observatory, the telescope is ready. You enter coordinate, you move the telescope, you take your data, and after a few minutes, you can see an image on the screen of your computer, right?
Mm-hmm.
Amateur astronomers did not have that. I mean, you buy a telescope, you have to learn how to point, you have to learn how to process the observation, etc., how to align the telescope, calibrate it, and so on. So a lot of people basically buy telescopes but never really use them because of this. There was this barrier, make it way more complex than it truly is. So with these telescopes, we remove that. So people can quickly enjoy the dark sky and learn by doing astronomy without having to basically build a telescope from scratch. So that's the reason we invented Unistellar, to democratize astronomy and to make astronomy fun for everybody.
Yeah, that's part of the reason I wanted to get involved or enjoy being part of this is spreading the joy.
Yeah.
Getting. I mean, I grew up somewhere that I really couldn't see the night sky at all, and somehow I wound up in astronomy anyway. But I think more people would be interested if they could see this stuff more easily, especially at a younger age.
Yeah. So Ryan, why did you join us?
Me?
Yeah.
Actually, so honestly, yeah, a lot of the same things. I really like the mission statement of opening astronomy up to people who don't need an astronomy degree. I think a lot of astronomy, you don't necessarily have to have all of the college level information to really enjoy the sky. So I think it's very neat that we kind of give the ability to do science to people who don't have like a ridiculous amount of training, because you don't need it a lot of the time. To analyze data, maybe, but to take data, to enjoy the sky, to marvel at what is out there, you just need equipment that is used and willing to work with you, so that you don't have to spend hours fiddling and getting set up and looking, trying to find where you are in the sky before finally getting to something interesting. So I really like that. But I didn't have a lot of experience with Unistellar before joining up. So I did some research when I saw the job application, and I liked what you said. And then I got to say, having been a part of the team now for about a year and a half, put your money where your mouth is. I think it's a good deal. I think it's true. The eVscope is very, very nice. It makes it so much easier to do astronomy for anyone who has it.
Yep.
Indeed. I'm trying to find a new target right now. A couple of the ones that I
see a question I can answer. Should I take that?
Yeah, absolutely.
Yeah.
So from absorbing underwear, people, come on.
They've been here for a while. We appreciate them sticking around.
Yeah, absolutely.
Yes, the EU Commission or the EU, yes, the EU Commission had this program called Horizon Europe. and they will have multiple. That's the call we apply for this project to observe, to determine the position of asteroids around Jupiter and Saturn, for instance. Not satellites around Jupiter and Saturn. So this is a call that will probably be regular. It will be every year or every 2 years. So you should have a look. Horizon Europe. I think it's something like in the order of the million or 2 million in terms of funding. And it's for scientific studies and also for technological development. I see that Patrice is here. Patrice Huet from l'île de la Réunion, Réunion Island. Hello.
Patrice is one of the observers who actually saw DART live, right?
Yeah, he did it live with us as in a program like Zoom. So Patrice is basically, if you want to do something crazy, you ask Patrice and he will say yes. He's one of those. So we did DART with him live. So we saw the brightening live during the impact. And I remember that we were all speechless. Nobody knew what to say because we were very surprised to see the cocoon formation, etc. It was seriously a nice moment. It was 2 a.m. And then once we also went to the La Résidence de France in Washington, D.C., and we wanted to show the stars there for the 60th anniversary of the CNES, the French Space Agency. There was everybody from the agencies of the world were there. And of course, the weather in Washington, D.C. was bad. It was raining. So we anticipated that, and we asked Patrice if he could be showing the sky of Réunion Island, and he did that. So we were at the French embassy, residence of the French ambassador, with like hundreds of people there, and we show basically live the beauty of the sky of Réunion Island, which is the southern hemisphere, and the southern hemisphere, a much nicer sky than the northern hemisphere. That's why people are nicer over there. So thank you, Patrice, for always being ready to do crazy project with us.
Yeah, we also got a comment from Jennifer Siders looking at Neptune and Triton with her eVscope right now. So there you go. You get some interesting data about Triton and Neptune.
Yeah, it's really cool. We probably won't be looking at Neptune, but tonight here, but you can really see its blue color with the eVscope. That's pretty neat. To be able to see some of these moons that you don't normally see, and the moons of Neptune, Saturn, Uranus, pretty neat. I tried to point to Saturn earlier. It's behind the building, and so we may wait and go back to it a little bit later when it sets in the west a little.
You're doing the veil right now?
Yeah, it's starting to come through a little bit. It's right in the middle here.
I have a story about the veil. So the first time I showed the telescopes prototype that I mentioned in the US was at Chabot Observatory, not too far away from here, Oakland. And there was a lot of amateur astronomers at the time over there because that's star party. It's a star party they have regularly on the Friday and Saturday. So one amateur astronomer kind of challenged me to with the veil. Said, try to see if we can see the veil with the new telescopes. And we pointed toward it, and we saw it. And the amateur astronomer was speechless because he could not believe that with such a small telescope, in less than 3 minutes, we could see the Veil Nebula. And especially from Oakland, I mean, it's not like the dark sky. So here you are at Lick Observatory, we can see it, but it's still impressive that you can see this faint nebula. I discovered that this thing is huge in the sky. It's the size of the moon, even slightly bigger. Okay, and that's a remain of a nova that exploded. I forgot when, but yeah. So it's a beautiful body, and now people are doing mosaic of it. So basically, take multiple observations over the week, and they combine them together to get the entire nebula in the sky.
Yeah, it's pretty cool. It's a little harder to see, I think, on the stream, but it goes all the way from here underneath these buttons all the way down this arc off the field of view down here. It's just
No, we see it well. Huh? I
Okay.
think we don't see it in your side, but we see it very well on this
Okay.
screen.
Great. Yeah, it's this wispy kind of ghostly, like a veil. I guess that's the name.
It's called Nebula. Wow. I didn't know that.
I don't know how they came
Wondered,
up with that. Yeah. I wasn't actually sure how this would look. I've never looked at it before with an eVscope, but it is pretty impressive. We'll stay here a little bit and then probably look at a galaxy next. Yeah.
All right.
Yeah.
Well, I'm going to go then. It's 11:30 here, so almost time to think about lunch.
Yeah. Go take a nice long 2.
How many more hours you going to stay alive?
We're at 9.5. We got to get to 13.5. So we got 4 more hours.
All right. 4 more
We're
hours.
in the stretch now. We got another, let's see. We'll look with the eVscope. Well, really from now until the end. We'll answer some questions in a little bit, Brian and I, and then we'll spin the wheel of targets. We'll randomly pick some new targets and wrap up for the night.
Yeah.
Which eVscope are you using here? eVscope 2?
Yeah, we have 2 eVscope 2s.
Okay. Have you been using the Wi-Fi extender?
Yeah.
Yes. Yeah. We just need it to get through these walls. The walls here are thick, but yeah, it's worked pretty well.
It works well.
Yep.
Well, thank you for doing this. I know we are all watching you. So if you have any questions, I'm connected today, I'm gonna be working because it's Saturday.
Saturday. What else? What else would you do?
Yeah, clearly.
Saturday.
Yeah, I'll look forward to your Slack messages later.
You will get some messages. I will look at the occultation we have been processing over the past few days. So you're probably gonna get some questions from me. All right. Take care, everybody.
Thank you for joining, Frank. Thank you.
Frank.
Bye bye. See ya.
So this is an interesting.
Thank God he's gone.
Oh, geez, who was that guy?
I don't know.
So we have an interesting question from Absorbing Underwear. If our solar system was in the middle of a nebula like the Veil Nebula, or even something like Orion, would we notice? Would we even recognize that we were in a nebula looking outward?
This is one of those questions that I don't really know the answer to. I suspect you would see something. I mean, I think you would see at night, at least. I think you would see some of that nebulosity.
You would definitely see the reflection off of the gas and dust that we're seeing here. So I think it would take up a very large portion of the sky. But I don't know, because surface brightness in general is a weird thing where the closer you get to an object, the surface brightness, the fainter it looks to you. So I could see an argument where you might not recognize that you're in a nebula, but I do think you would know that you've got a big gas and dust cloud around you, because you would basically have an entire section of the sky that is dark.
Yeah, it is tricky. I think science fiction. You see things on TV where they're on an alien planet and look up and you see all this crazy stuff in the sky. But I think indeed you might not necessarily see something too fantastic. I think it's kind of a more interesting thing. What if our planet had rings? What if we had a ring system around Earth, for example? I think that would look pretty spectacular. I'm pretty sure we've seen when we send spacecraft to somewhere like Saturn, you see those rings. As long as the sun is hitting them the right way, on the right angle. I think that would give a pretty spectacular sight. But yeah, you would need a pretty thick
cloud of gas that was emitting light at just the right wavelengths to see something, perhaps. I don't know. I'm not really qualified maybe to answer that.
Too bad. You're answering it.
Let's see what else.
I'm setting up the
Paul is
eVscope.
saying the gas and dust in our solar system is visible. Yeah, I mean, we can see the dust essentially as it reflects sunlight. That's kind of what I was getting at with the rings. I'm not sure. You know, we see gas in the solar system. I think mostly comets is what I think of the most. They're pretty localized. So again, if you have enough gas in a small enough space, yeah, you might see something. But yeah, I could be wrong. Let's see. We got another recent. I'm going to scroll up a little. Sure. Let's see if I can find the mouse.
Nope, it's fine.
Scroll up a little bit to some questions that I might have missed earlier. Hello to folks from Baja, Mexico, Italy, Portugal. Welcome. I see a question. There was a question from Bruno. I don't know if you're still online, but asking about Planet 9. Yeah, we had talked about this earlier on the stream, but it's been a while, so I don't know exactly what your question was in reference to anymore. But
I was talking with Frank about something.
Okay, yeah, I lost track of that thread. Sorry, but we had talked about this with Ariel when she was on, and the evidence for Planet 9 is looking weaker, kind of all the time. So I don't think it's something we'll go after with our eVscopes and citizen scientists. It's kind of outside of our capability. Let's see, Sydney, would you support a campaign to have national dark skies on solstices and equinoxes in cities? That's an interesting idea. I think I would support, having a kind of a regular holiday, so to speak, where people turn off their lights and just enjoy some time. There is I think it's International Dark Hour.
Yeah, something like that.
Which is, I forget what time of year that is, but throughout every time zone, there's a kind of global movement to just turn off your lights for 1 hour. And it's always at 10 p.m. or 9 p.m. local time. I've seen that. It looks pretty cool. I think I've seen pictures from the International Space Station, for example, that show how much darker the Earth gets. And I think it's something we should maybe put a little more importance on. We are spending a lot of time
in the light.
In bright nights, and we miss a lot. We get disconnected from the night sky, and that's an important part of our natural world. I think, as human beings, we grew up, most of our evolution, we've been under dark skies, and it's only recently that we've taken that away from ourselves. So I think I would support it.
Yeah, I wouldn't. I think logistically it would be tough to do something like make it mandatory, but I think a gentle encouragement of something like the International Dark Sky Hour, like that, but for a night where you say, hey, this is the benefit, this is what we think you can get, and getting a mass movement like that to try and redarken the skies would be very cool. At the very least, I would love the idea of everybody working together to do that.
Yeah. Hi, Linda from Scotland. Thanks for joining. I guess what Sydney was getting at was having it kind of 4 times a year. So on every solstice and equinox, you see different parts of the sky, which I think is also important because, the sky's not the same all the time. It changes with the seasons. So I think that is an interesting aspect that I hadn't thought of before. There are movements, there are things you can push for in your local community to kind of combat light pollution and reduce it. You can
push for street lights that point downward more than upward, so they don't just shine their light into the sky where it's wasted.
Something where it's covered.
Yeah.
Sorry, I gotta check the rates are odd.
Okay. Yeah. And things like that. Having your local businesses, big corporate, commercial office buildings, for example, having them turn their lights off at night. Little things like that might make a big difference. Interesting. In Belgium, highway lights turn off at 1 a.m.
Oh.
I did not know that.
I didn't either. That's interesting.
Never
That's
been
cool.
to Belgium. And yeah, you would definitely save money for sure. Save on electricity. It would reduce climate impact. Light pollution in Scotland is horrible. I've been to Scotland recently. I would say it's not as bad as the U.S. Depends where you are, obviously. Big city like Edinburgh. You got a lot of light pollution. It's definitely very regional. Depends where you are. Let's see. We've been on the Veil Nebula here for 15 minutes. This I didn't get to talk about it. This is one of those stellar nurseries. So again, this is what they call either an emission or a reflectance nebula, where that gas is either reflecting light from the stars inside or absorbing that light and then re-emitting it at specific wavelengths, and that's where the colors come from. Hello, Julia from Germany. Linda near Glasgow. Yeah, another big city for sure. Let's see. So we're still going, Ryan, on the other eVscopes, still looking at the asteroid.
Yep.
Very nice.
So that's what, like 4 or 5 hours, you think, of this eVscope going?
Yeah, I started it around 9:30 p.m. And it is 2:45 a.m. So 5 hours at least.
Nice.
Yeah, more or less uninterrupted. Occasionally we weren't paying attention, but
to keep everybody in the loop, part of this this live stream, we're professional astronomers. This live stream was kind of a idea just because we have time on this big telescope, and it was a fun way to give people a look into what being a professional astronomer is like. So if you have any questions, feel free to put them in the chat. Let us know. We have been just kind of answering things all night as people ask them. But yeah, so the goal, the reason we have this telescope time is there is an asteroid, 2011 MD5. It's a near-Earth asteroid that's currently relatively bright, and not a whole lot is known about it besides basically the orbit. So what we're doing is observing it for pretty much the entire night to see if we can see how the brightness changes as the asteroid rotates. So as assuming the asteroid is like a phone, when you have lots of surface area, light gets reflected back and you get a very bright looking asteroid. And when the asteroid is something like this in its rotation, you don't get nearly as much light reflected back, and the asteroid looks pretty dim. So if you continue to observe an asteroid over a reasonably long period of time, and you check to see how that light is changing, you can get an idea of how fast it's rotating. And once you know that, you can also start building other information about it. So with enough light curves, enough observations over time, you can even start to get an idea of what the asteroid's shape is without ever having to resolve it, without ever having to, without it ever looking more than like a point source here. We can still figure out what its shape is. So that's the goal for tonight, and that's why I was asking earlier. Is we have an eVscope outside that's also observing this as a secondary project. We're going to see how it compares, how the data compares to this 1 meter class telescope we're using.
Yeah, indeed. And we're fortunate to have this opportunity.
Absolutely.
Yeah, UC University of California Observatories, which operates Lick Observatory. Fortunately, they put a lot of emphasis for this 1 meter nickel telescope on education.
And so it is still a science-grade instrument, but they also recognize and promote the value of education, using their telescopes to bring astronomy to the public and to folks who wouldn't otherwise have access to it. So that's part of the reason we have this time. Let's see, a couple of other questions. Sydney, what's the job interview like for a professional astronomer? Do they ask you if you started out as a paparazzi?
Because you're taking images of
I
the
get
sky,
it.
yeah.
I get it. That one went over my head. Thank you, Ryan. I see a question for Frank. Frank's is shorter, so let me answer him. The detector here is it's a CCD. So CCD stands for Charge Coupled Device. I know Frank knows that, but yeah. So it's a simple.
Kind of like the detector in your phone, the way a camera works.
Similar, yeah. The sensor in your phone is actually much more similar to the eVscope sensor, but yeah, the general idea is the same. Let me reshare this screen, and it's a 2,000 pixel by 2,000 pixel, so it's a 4 megapixel camera. If you think about megapixels, let's put this back. So to go back to Sydney's question, what's the job interview like for a professional astronomer? Well, it is. I haven't really applied for other jobs, so I don't have a whole lot of comparisons for context. But generally, so I'd say in the research world, you go to graduate school, you do your PhD, right? And when you're about to finish your PhD, usually in the spring or summer of some year, or maybe the year before that. So the year before you're going to finish with your degree, you apply to postdoctoral positions most often. These are kind of early career, short-term jobs at a university or with a research group or an observatory maybe that has funding for 1, 2, or 3 years for you to research a specific field or question. And to do that, for that application, you would generally send in your curriculum vitae, your resume with the papers that you've published, the projects that you've worked on. Maybe these days you would point to computer code that you've written to do analysis. And then you probably write some sort of a research statement saying, here's what I have researched in the past, here's what I plan to research as part of this job, here's how I plan to do it and how I'm going to back it up. Then you would submit that, probably compete with dozens or hundreds of other people for that one position, all of whom are very qualified and very eager to get that job.
It's one of my questions for the Q&A later.
Okay, and then you would, if you're selected to get through the first round, you would talk to the person who's doing the hiring. So usually a more senior astronomer, and the person typically who holds the purse strings, the one who has the funding or leads the research group, and they would interview you and ask you about your qualifications, try to assess your knowledge level, see if you really can do what you said you can do, see if you're a good fit. There's also logistical stuff. Where in the world is this job? Are you willing to move there? Are you willing to work those hours? Maybe if it's at an observatory, are you willing to work nights? There's salary considerations, as always. What am I missing? You went through this more recently than I did.
Yeah, I mean, the main thing I remember is you, which I don't even think you did, was critiquing my code. Isn't astronomy mostly remote work now? Yeah, I mean, a fair amount of astronomy. So it is a bit, depending on the observatory that you're going to, it is a bit odd to not be remote. Some observatories will require you to be in person. We had the option to observe remotely from the nickel, but obviously we wanted to do it here in the building so that we could show off the telescope and everything. But yeah, so there is, if you are observing, there's a lot of options now for working remote. Otherwise, I think it really just depends on, are you a professor? Are you at a college university, or are you somewhere else, nonprofit like SETI? And I think in that case, yeah, it's really just depending on, because you could do your research pretty much anywhere once you have the data. So yeah, I think it just depends on how flexible the job itself is. Going back to the idea of the job, I think, yeah, looking at your ability to write code, because a lot of the problems that we work with now is like developing software to reduce data, since we just have so much of it, and developing pipelines that take data in and reduce it and analyze it for us, so that we can then look at those results and come to some conclusions. I think the ability to do that quickly and efficiently, and to solve problems that aren't obvious, are pretty much the things that are looked for. I know with some of the jobs that I was looking into when I was looking before I got the job here, that was a lot of it. Is being a scientist is all about being a problem solver. You look at a project and you say, okay, I need to get to this solution. How do I get there from where I am now? Any use of Wolfram's Mathematica or Wolfram Alpha? I used Wolfram Alpha religiously in undergrad and grad school, but I haven't had to use it since, thankfully.
Yeah, well, Mathematica was the very first coding I did as an undergraduate in like, I don't know, maybe my sophomore year. And I struggled with it. I remember finding the language a little bit clumsy. Yeah, not to knock it. It is powerful.
Mm-hmm.
These days in astronomy, the preferred language, I think, is Python.
Yeah.
It's a more powerful, some would consider it a scripting language more than a pure coding language, but it really lets you do just about anything you need to. If you're optimizing for speed, you'd probably write something in C.
Yeah. I will say, since William on YouTube has brought this up, I'll see. I can't show it. Dang it! I got to be on the other computer. William asks, have we considered hiring front-end engineers to update the GUIs? Clearly, William has paid attention to the screens that we were showing earlier with these clearly like 1980s level computer graphic GUIs. Astronomers in general suffer from software rot a lot, because software rot is when you basically have written a software 20 years ago, and instead of updating it by going in and making things more efficient, you just start throwing patches onto it based on what you need. We do that a lot in astronomy. That's not great. Part of it is that I think astronomy education, while it focuses a lot on coding now, you're not required in a lot of places to take like computer science classes to learn best coding practices. So a lot of astronomers know how to do something in a quick and dirty and maybe not necessarily pretty manner. The other reason is it costs money to hire engineers to update the GUIs, and we're not paid that much. You're already like, I hope I get this proposal so I can work on this project I want, and if I don't know what I'll do, but it'll be all right. I'll figure it out. And so once you're already at that point, you're just like, I don't care what it looks like. I'll know what it does. I can figure it out.
Yeah, and I mean, for something like this, the controls for a telescope like this, there's kind of the general rule: if it ain't broke, don't fix it. These GUIs pretty much do their job. Sometimes they could be improved, but this telescope, and I'm thinking for larger telescopes, where time is in higher demand, they need to work every night. You can't take 2 weeks to shut the telescope down because you need to update the software and debug it. You would have to spend quite a lot of extra time working on that in the background, and then really make sure that it's ready to go when you actually implement it on the telescope. So I think that's part of it. But yeah, also all of the reasons that Brian just went through.
I really do think that astronomy education would greatly benefit from requiring some basic level computer science, basic level, like, here's the best way to code. Please learn PEP8, learn some like general good practices.
Yeah, it's something that the field is moving towards. It's when I went through grad school, there was no requirement to take any coding classes whatsoever. Now, you have to take at least 1 or 2. And yeah, you know, the work we do now with SETI Unistellar, we are developing full-blown data reduction pipelines. We now have to do things like we know how to use Git and GitHub for version control of our software. We have to, and do it properly, you know, not pushing changes to branches that are being actively used, and things that I have to constantly remind people not to do. Yeah.
Look, I will push some broken code domain, and no one's going to stop me except for the French side of Unistellar. They will get mad.
Yeah, kind of thinking a little more on the software engineering side when you are working in a collaborative space. My own code, I will hack that apart as much as I need to. But yeah, when you're working in a group, it's something that it's just kind of a necessity these days. You know, 30 years ago, this wasn't as much of an issue, but now it's a necessity. Let's see. Sounds like sounds like running an open source automatic trade bot on a Raspberry Pi, updating Fixburg yourself. Yeah, exactly. A lot of debugging these days in our jobs. Kind of manual fixed dependencies seems important. Yeah, I mean, there's definitely, you know, this software on the telescope, if something breaks, we don't touch it. We call for help.
There are people that are trained in every aspect of this telescope and its software far more than we are. So yeah, we do our best, and then the second we run into a wall, we call them up. They tell us that. They're like, no, this is what we're here for.
Yep, absolutely. But yeah, everything else is kind of fair game.
Yep. Just be careful. That was my favorite part of the introduction to the telescope and the software yesterday was the inconsistency in the windows and how you close them. So you can tell that all of this was patched together by different people based on what they needed at the time, because how you exit a window varies greatly. Sometimes it's in the drop-down menu. Sometimes there's a little button off to the side. Sometimes there's a giant button labeled quit that is very clear and obvious. And sometimes it just doesn't exist and you're expected to exit out. But if you just exit out on the wrong window, you crash everything. So you got to spend at least a few minutes looking. If you don't know, you've got to spend at least a few minutes looking to make sure there is no quit button on this.
Yeah, no, I will say all of that said, the software is actually pretty good here for the nickel.
It's been very robust.
Yeah, I've been at other observatories with much larger telescopes, and not all of that works as well. There's definitely some of those. There are buttons you can push that will silently break everything, and recovering from it is a 10 to 15 minute task that requires rebooting a lot of software, and you lose a lot of time if you are new to it or just accidentally click the wrong button, or maybe you're very tired, it's very late, and you click something you shouldn't. So it is certainly not specific to any observatory. Yeah, I think it's just a matter of it takes a lot of time to write up all of this software that controls stuff, and every instrument is different. Every instrument has different requirements. Some things are common, but
and instruments will get switched out. And every time an instrument gets switched out, you have to either update your software or write a new bit of software and latch it onto everything. So yeah, I was not knocking the nickel. I think the software, I've been shocked, been very impressed at how well it has worked. Because I'm used to pressing buttons and them not doing what I thought they were supposed to do, and silently breaking a bunch of stuff. And this is everything is done what it said on the tin. I've not been surprised whenever I press something.
Yeah, absolutely. Let's see. So we're almost done. I think we're almost going to move on from the Veil Nebula here. Eastern Veil Nebula. I have no idea what the Western Veil Nebula looks like, but I assume it's something like this.
It's just reflected. That's really brightened up.
Yeah, I just increased the brightness a little bit. The thing that amazes me about this is there are so many stars in this field of view. It really is a dense, what we would call a crowded field. Trying to do analysis on images like this would be tough. You'd always have stars that are blended or touching other stars. Yeah, glad I don't have to do any sort of science with this nebula. You can really see some of the color here. Where's my mouse? Yeah, the blues and greens in this little stretch. If I zoom in, yeah, the blues and the greens right here, pretty amazing. You can see the different colored stars as well, some more bluish stars. These are probably younger, higher mass, hotter stars. You can see all the red and the pinks here as well. Really pretty spectacular. There's, even more blues and greens. Let's see. Do you have access to adaptive optics on this telescope? No, we do not. The nickel does not have adaptive optics. They do test adaptive optics systems on this telescope, but it does not have them running. The 3-meter Shane telescope on the other side of the mountain does have an adaptive optics system. A pretty good one too. Let's see, which is closer, the Circinus Galaxy or Andromeda? I have no idea. I don't know where the Circinus Galaxy is. I'd have to look that up. Circinus or Circinus?
I've
never heard. Brian will look that up for you.
Yeah.
Does the terminal give you valid readouts of what individual software is doing as debug? Yeah, there is a lot of diagnostic information in the backgrounds of these GUIs that we're just not showing. It's something that we kind of can monitor, but we'll only often look at if something goes wrong. There is definitely more. There are about 1 million more windows we could open here. That we just they will clutter things. There's also so we have 4 windows that we're showing on our main screen. It's been a while, actually. We should. I'm gonna show. So we're gonna move on from the Veil. So say goodbye. Take that mental snapshot of the Veil Nebula. That's become my catchphrase, I guess. We're gonna disconnect, and while we're moving targets, we're gonna head to the Triangulum Galaxy next. While we're moving targets, stop. I'm gonna switch and just show you what. You're showing anything we shouldn't be showing here? No. I'm going to show you what this control computer is showing. I don't want to show that though. Let's see. I want to show all of them. So that was just one screen. Let's show the entire thing.
Andromeda is closer than Circinus.
Okay. Apparently, Ryan says Andromeda is the closer galaxy. Andromeda is the closest major galaxy to the Milky Way.
Yes, the closest big galaxy.
So anything closer would have to be quite a bit smaller.
A dwarf.
Yes, what is actually
Dwarf galaxy.
Technically known as a dwarf galaxy, indeed. Or a satellite galaxy. The Milky Way, you're not on cam. The Milky Way actually has little galaxies orbiting it, like moons, sort of, so-called satellite galaxies. So this screen now is showing
Let me hide this so we're not inceptioning ourselves. The 4 windows that we're looking at continuously as we observe with the nickel. So there, this top left is the telescope guider, which we're not using right now because normally that would lock onto a star in our field of view and keep the telescope tracking that star so it stays fixed on our camera. We are observing an asteroid which is moving too quickly. Something went wrong.
Oh, fine. I just gotta reload.
Okay. I don't know if we're still sharing that screen. I also lost it.
Oh.
All right, hold on. Technical difficulties. Let's see if we're still online. Okay. I think we're still online here.
Yep.
Yeah, but yeah, we're not guiding at the moment. We have window here in the bottom left. We've kind of been showing this one throughout. Shows our latest image, the camera controls with the exposure settings, how much time has passed in our current image exposure, how much time is left in seconds. This is the number of seconds we commanded the camera to expose for, whether the shutter of the camera is open or closed, how we are reading out the electronics of that camera to get the image out of the sensor, whether we're actually saving the image to a file or not, and then the name of the object for some later reference. Controls how to look at the image that just was taken. We can change the scaling and yeah.
What have you done to my beautiful
Definitely
image?
different uses. I'll go back to it for how you want to investigate your image, for example. Sound effects to let us know how things are going.
Yeah, you've been unable to hear them, but we have been getting like ding and bells and whistles happening on our end. So if you see us randomly jump, it's because every now and then when the exposure is done, when the telescope is finished, what it's doing, it makes a very loud like cowbell noise. Yeah. So.
Yeah, indeed. Let's see, and then in the bottom, yeah, then the more instrument control, we can change the filter that the telescope is sending its light through to narrow down the wavelengths that we're measuring. And then the bottom right is the telescope control itself. So this main panel is the POCO, the pointing control.
Yes.
Pointing control user interface. Yeah, so tells you our right ascension and declination coordinates of the telescope. That is like latitude and longitude, or sorry, RA is like longitude, declination is like latitude on the sky. Hour angle is another reference point on where we're pointed on the sky. It's kind of how far east or west you're looking, basically. The meridian is a line that passes due north through south, essentially, at 0 hour angle. So an hour angle of +1 hour is about 15 degrees towards the west. Is that right? Yeah. Past the meridian.
Yes, because it follows RA.
Yeah. An hour angle of -1 hour would be about 15 degrees towards the east. And then air mass tells you essentially how high or low in the sky you're looking. An air mass of 1.0 is looking directly up at zenith, straight overhead. You're looking through the minimum amount of Earth's atmosphere, or the mass of air that you're looking through. As you point farther down on the sky towards the horizon, that air mass increases. Once you get to air mass of about 2,
life becomes hard.
Yeah, your image quality starts degrading. You're looking through more atmosphere, which is distorting the light from your object in space before it gets to your telescope. And so that is what adaptive optics corrects for. but it not only distorts the light, it also scatters and absorbs the light, so targets are fainter.
Mm-hmm.
There's a lot of reasons you don't want to point at targets when they're low on the horizon. Let's see. I'm going to actually point at triangulum while we're doing this. Here, M33, beautiful. M33 is at 83 degrees altitude. It's almost straight overhead, so that should be a good one.
Oh.
And then, yeah, so we can point to new targets with the telescope from here. We can control the dome and how it's moving, and control how the telescope is tracking. Here we can have a list of targets. We only really have 2, so we haven't bothered to make a list. But a couple of cameras that are looking inside the dome. Right now the lights are off, so they're dark. Some controls, again, for how the telescope is moving. We're having it track the asteroid rather than the stars.
Mm-hmm.
That's a little bit unusual. You only do that for asteroids and comets, basically. Focus control from when we focused the telescope earlier. I could probably close this, actually.
Yeah.
Is there? So now here we go. Is there a quit button, or should we just close this?
No, it's just quit. Yeah.
And then this is another one we can close, I think.
Mm-hmm. Yeah, everything under Poco is you can pull the.
Gotcha.
It's just a close.
And then yeah, and then more controls, opening and closing the dome, so we can see out of it. Opening and closing the cover that covers the telescope mirror, that keeps it protected. Turning on the lamps that we used for calibrating the telescope earlier at the beginning of the night. Let's see, we're almost on triangulum with the eVscope. We'll come back to that in a second. And then, yeah, those are kind of the main things we've been looking at here. And then up here, we were looking at weather.
Mm-hmm.
Yeah, there's some weather stats here. And kind of, we scroll up. If all the numbers in this box are green, that's good. This is the particle count we were keeping an eye on because of the smoke from wildfires.
Yep, it's not just enough to not have clouds or humidity or I don't know, whatever else. You can't have stuff in the air in general.
Yeah, so the telescope will automatically close and park itself. We don't have a choice if it crosses these safety thresholds, but so far we've been good.
Mm-hmm.
There are also humidity and wind speed limits, and of course, if there's any precipitation, we will close automatically. Yeah, I think that's the quick summary.
Mm-hmm. So
let's look at.
We got a question from Sydney about how we feel about Starlink light pollution. So I understand the benefits of satellites and telecommunications. I 100% am for making it easier for people to access internet, making it easier for people to communicate. I think that is amazing and great. I also get really annoyed with Starlink. Selfishly, I do not particularly enjoy having satellites as a threat to like cross through my field. I don't know. It's not a hill that I'm willing to die on just yet, but I am generally on the side of I would like more to be done to mitigate the effects that satellites are going to have in the coming years, because at the rate that we're sending them up into orbit, we're going to get swarmed. Like right now, it's fine. I like being able to look up in the sky and I'll see something moving and be like, oh, that's a satellite. That's nice. But knowing that I'm going to have 7, 10, 15, 30 visible satellites at any given time, probably even more than that, kind of fills me with anxiety. Especially like I'm not affected you're not as affected. They still show up in your images, but something like the Vera Rubin Observatory, which is going to have a very wide field of view and is going to be taking very deep images with relatively long exposures. or even something that's just going to cover the night sky as much as it can, that becomes very hard to do if you know that your sky is going to have a million little satellites buzzing through at any given time. And it's going to be even worse if you don't have any way to mitigate that. So right now, I think more can be done to minimize the impact that satellites will have on space. And I hope some steps are being taken. Starlink has tried to, they've made efforts to lower the brightness of their satellites. So I think that's a step in the right direction. It shows that they're at least willing to give it a shot rather than just ignore us entirely. So I'm hopeful at the very least that something can be done. But it will take some concerted effort. I think we've already lost the war on getting tens of thousands of satellites into orbit. I think that's already going to happen. But we can still do something about whether or not it will irreparably change our sky.
Yeah, it's definitely been a important topic of conversation in professional astronomy for several years now. Definitely a lot of people working on it on the policy level, talking with private companies, talking with governments. You know, it's, if you're doing astronomy like us tonight, where you're, oh, we should take some nickel. We're not exposing. Are we just continuing here?
Yeah, sure.
If you're taking short exposures like we're doing here, and a satellite passes through one, or a satellite train passes through one of them, fine, you throw it away, 1 out of 100. But there are plenty of science cases where you take a 30, 60, or 90-minute exposure. If you have a satellite passing through that one, it won't be a whopping bright signal, maybe because you've been exposing for a long time, but it will pollutes your data.
Yeah.
And that's annoying. It's frustrating. I get it. So stay tuned. You know, who knows?
Yeah, I mean, it's one of those things that we just have to see where things go.
It is, and the satellites, a lot of the satellites are providing useful information. They're not just space junk up there. Mm-hmm. You know, a lot of them, there are companies that are observing Earth and monitoring climate change. Super important. There are satellites up there that are doing astronomy. You know, they are kind of paradoxically, or I don't know, oxymoronically, they are contributing to the problem of astronomy, but also doing astronomy in the meantime. So, yeah, it's complicated, as with most problems.
Yeah.
We're getting a pretty good picture of the Triangulum Galaxy here, starting to come through. Another spiral galaxy. This one's a little fluffy. I wonder if you would call this a flocculent galaxy. This is one of my favorite astronomy words. Flocculent. It's a fancy word for fluffy. Yeah. It's a spiral galaxy close to the Milky Way, 60,000 light years across. That is Milky Way size-ish, I believe. 3 million light years away, so it's about 3 times farther than Andromeda, which is our nearest major galaxy neighbor. It's got about 50 billion stars, so it's about half the size of the Milky Way-ish in terms of stars. We got a little bit more of a description here. Anything worth noting in the description? The distance isn't very well known, apparently.
Too fluffy.
Yeah, maybe too fluffy. Triangular diameter 70 arc minutes. So that's about a little over a full degree on the sky. So that's about 2 full moons with 2 full moons worth across on the sky. Apparently has many nebulae observable by large telescopes. One of which is brighter than all nebulae known in the Milky Way. That I did not know. You learn something every day. Says Triangulum Messier 33. Let's see, another question, a new question from, I think I might have missed one earlier. Maybe
No.
not. No. So another new question from Sydney. Do you guys have automated filters that alert to supernova or gamma ray burst events? Funny you should ask. So I lead the transient events or cosmic cataclysms campaign for our citizen science group with Unistellar Network. And we automatically filter through alerts from the Zwicky transient facility at Palomar Observatory in San Diego. So that's I think it's something like a 3-meter telescope that scans the entire northern hemisphere sky every 2 nights for new transient events, things that have appeared or disappeared from one night to the next. And we grab every 1 minute while the data are being processed from that telescope, we look for new discoveries, new classifications of things like supernovae, gamma ray bursts, that this machine learning algorithm named ALR-C has identified. So our goal is to identify those new possible supernovae, for example, or gamma ray bursts, and then within a minute, tell our observers, literally within 1 minute. We post that information on our website publicly. We send a message on our Slack workspace to our citizen scientists, and we send an alert through an app named Astro Calibri about everything they need to know to observe that target, and to do it within, again, about another minute. So that's something that we're actively doing. And the identification of those objects these days, the first pass is usually by machine learning, AI code. Then there's often still a human that looks at the more interesting ones, because that code is still not at the level where it can recognize a real supernova, for example, versus an artifact in the data 100% correctly every time. So if there's something that looks interesting, it almost always goes to a human for vetting or approval first. CME ejections, I don't know, that would be solar telescopes, and I don't know as much about them. I imagine the CME, they look at particle counts first, so probably neutrino detectors and or cosmic ray detectors. Telescopes, for example, look at things like muons. I imagine something like that might be the first indicator of a CME. I don't know. Maybe they're just looking at the optical telescopes that observe the sun, or the UV telescopes, for example. I should probably look that up. Yeah, that's basically that. All right, what time is it? It's 3:30. We have some Q&A time. Ryan, do we have Q&A questions that we should get through? Anything that's been burning a hole in your list you want to ask?
So, I do like the idea of, well, we'll start with something else.
Do the yes or no game.
No, that's all right.
I'm happy to do it.
I know. So, favorite telescope you've used or observatory you've visited?
So I can run through the major ones I've used on one hand, basically. I've used.
Oh, mine's not going to be major. I'll just let you know that now.
Okay. Well, so I've used the Unistellar eVscopes, one. I'll go from smallest to largest. The Lick Nickel, 1 meter. The Shane, 3 meter down the road. The Gemini South, 8 meter. The Keck 2, 10 meter. Those are the ground ones. I don't count using Hubble because you don't use it. You just get the data.
Yeah, that's fair.
But that's a 2.5 meter space telescope. Favorite to use, probably Gemini South. It's the one I've used the most. Again, you don't control the telescope there, but I operated the instrument, the Gemini Planet Imager. I was one of the lucky ones who was allowed to be trained by the group that created the instrument and ran an important exoplanet survey with it, trained to operate its adaptive optics system, which was cutting edge, kind of best in the world, and operate the camera in this very complicated spectrograph, imaging spectrograph. So Gemini South probably holds the most memories for me. I don't know. What do you think?
Nice. So before I start answering, I realized that this would actually.
Yeah, I know.
Okay. That does actually also be a good idea to. I came with the idea that we would do a Q&A for ourselves. You all could ask questions about us. But I'm actually a little interested in chat. What brought you here? So obviously you have some enjoyment of astronomy. Where'd that come from? What did you come because you were bored? Did you come? How'd you find out about us, about this happening? Basically, I'm interested in put your stories for why you are so interested in astronomy. What got you started on it? What you find interesting enough to watch two guys talk about astronomy for 10 and a half hours. For me, my favorite telescope to use was, I've already talked about this one tonight, I think. I went to graduate school at Indiana University, and they have this 12-inch refractor called the Kirkwood telescope. It's this telescope that was made in the early 1900s. It's like over 100 years old. The dome itself is this beautiful wooden dome that constantly seizes up whenever you try and move it. It's a mess, but it is a fun mess to play with. That was basically the grad students. One of the first things you do when you get there, you get taught how to use it because you're expected to operate it for outreach nights. You're probably going to have to use it as a TA for certain classes. For some of the upper level astronomy classes, they have the students use it to take observations. It has no research potential. It's literally in the middle of a campus that is lit up like the day. But it is just such a beautiful instrument, and it's this old piece of history. They still have the original captain's chair that the rope, I'm pretty sure I broke it sitting on it. You could have a little rope and you could pull on it and the chair would move up the ladder so you could move up.
That's fun.
Yeah, my big butt destroyed it. So don't tell them there. I don't think they figured out that was me. But I love that telescope. It was so fun. I would sometimes, not even nights where I had anything to any reason to be there, I would go and I would hang out and I'd just look at stuff. So yeah, that is my favorite. Otherwise, I haven't really used any big telescopes. I have been on Kip Peak out in Arizona. I helped with a class that was basically I helped a group of the level astronomy undergrads got lucked out and got a year where there was some random funding to send everybody out to Kip Peak. So they got to use the 0.9 meter that was out there. And we happened to go on the same night that was a donor party for the WIN telescope, which is this big 3-meter telescope. So what they did was they put the eyepiece on that. So you got to look through the eyepiece of this big 3-meter class telescope, which is very fun. But other than operating the 0.9 meter at some points, I operated a 32-inch telescope in undergrad, and I think an 18-inch telescope also in undergrad, because we had 2 of them on campus. One was directly on campus, and that was the teaching telescope, and then there was one that was built in the mountains some an hour away. Hardly ever actually got to get used because turns out the mountains of North Carolina quite cloudy all the time. Mm-hmm. So you were lucky if you got a clear night. But there were a lot of times where I'd go out to Dark Sky Observatory, was what it was called, and I'd get to hang out there, which was very cool.
Nice.
Yeah.
Yeah, I mean, I'm going to adjust this a little bit. I would be remiss and pretty spoiled if I didn't just throw Keck up there as a tie, because to have the privilege to use basically the largest ground-based telescope in the world with the most cutting-edge instruments, yeah, absolutely spoiled. It's a world-class facility with world-class staff and instruments, and yeah, just getting the chance to use it is very, very cool. And yeah, to have the opportunity to use the telescopes that are on the sacred mountain of Mauna Kea, sacred to the Hawaiian people, is also a privilege as well.
Yep, that's fair.
Yeah.
And I realized in the list that I forgot to mention nickel. So I've now added this to the list of telescopes I've operated, which is very nice. And this is my first time up at Lick Observatory, and it is beautiful up here. I really, really like this observatory. I know I was saying at the beginning of the night, if you are in the area, 100% I would recommend seeing if they have a tour available, because we got to see last night the 36-inch refractor, which is the largest refracting telescope in the world. For those who don't know, refractors they're basically an old type of telescope that uses glass lenses rather than the mirrors that we use now. Because glass lenses can only go so big before they start to sag in the middle. 36 inches is about as big across of a refracting telescope as you can get. And so this is a very old historical telescope. We got to see it last night during a tour, and it was gorgeous. Beautiful telescope. Very cool to see it being used, and the dome that it's in is huge. It's awesome. So if you were in the area, definitely go check out Lick. Tours, they do. They have a gift shop. They're cool, essentially, and they're criminally underfunded. So
yeah.
I think
I was just gonna say that we won't see a penny of this.
Yeah.
But I will say you can donate to Lick Observatory to help support it and keep it open. To primarily, I think, to support the things like the 36-inch refractor tours, the public education, but also to support the basic operation of the observatory. It's harder to keep these things running than it might seem. So that's all I'll say.
Yeah.
If you can donate.
Hashtag not sponsored. We just really like the observatory. So letting you know.
Literally will not see a penny. Also, you can also donate to the SETI Institute. We won't see a dime of that either, but
yeah,
it's an option as well. I think there's a button probably that we can put up there. But that's all we'll say about that. G'day from Melbourne. Sorry, I won't do the accent.
God.
Hi, Noel. Cosmos series inspired you. That's cool. Yeah. The original Cosmos, hosted by Carl Sagan, was, I think, formative for a lot of people. If you're unfamiliar, it was a television series that really, I think, brought the kind of wonder and impact of space and astronomy to a lot of people.
The Pale Blue Dot prologue,
Yeah.
Absolutely, that was a lot.
The Mortal Kombat reference, Liu Kang. Thank you, dude. Yeah, thank you, Noel. We will try to keep up the work as much as we can.
Yeah. Carl Sagan's a big inspiration.
For the novel about Voyager too. Interesting. It boggles my mind where astronomy in general does not get more state funding. Yeah, I think the sciences in general are underfunded right now. There's, yeah, right. The defunding of Arecibo would be one example. The telescope literally fell apart because they couldn't maintain it.
Yeah. I mean, it's a thing of priorities. And yeah, no problem, dude. That was, we laughed. That was pretty good.
We're hyped for MK1, don't worry. We haven't even talked about video games tonight, which is kind of amazing.
Yeah, we were expecting that we were going to get questions like that, or that we were gonna talk about that. But yeah, I think in general, it's one of the it's this is like an echo chamber. You all actually care about astronomy. We don't have to convince you that it's cool and that it's worth doing. It is a tough sell, though, on a lot of people, considering that astronomy doesn't have a direct effect on everyday life. No one's life is being meaningfully impacted by knowing how a star that is, 400 light years away works. And so I think just that removal of it is why it's so hard to convince people that astronomy deserves funding, and why these really beautiful big telescopes and big observatories deserve the funding that they need to maintain themselves. I will say, so I taught a class in grad school, and I kind of said it as a joke, but I also mean it, in that astronomy stopped mattering as much to people's everyday lives when we actually separate it from astrology, because at that point it was like it's one of those sciences that's a bit removed. But I also think that this is I will also die on this hill. Astronomy has none of the baggage that other sciences have, where you talk to a kid in middle school or high school and they're like, oh, I don't like science because I can't do it. There is none of that problem with astronomy. You don't get the, I can't do math, I'm not going to do it, I'm not going to try. You talk to people about astronomy, you just talk to them about the concepts of stars, of galaxies, of the solar system, and they're hooked. They want to talk, they want to know more. And it's very easy to get people interested. I think astronomy, that is the real benefit of it, is not only just learning about things, but we're the gateway drug to science.
I was just going to say gateway science, but gateway drug to science is more descriptive.
I debated about reeling it in. But yeah, I think that is the true power of astronomy, is that you get the people that don't think they can do science, and you trick them into it. You trick them into liking it and recognizing, like, oh yeah, I actually understand how that works. That's not that hard to grasp. Maybe I can do it. And then suddenly you like, haha, you like math now, nerd. And people get into it. So I think that's the big benefit of astronomy. But this was a long tangent for funding.
Yeah, well, yes. I mean, I think I agree with everything you said. So we have a graduate student, soon to be a doctor, who's worked with our group, Daniel Peluso, who specifically focused his PhD thesis on education in astronomy, or astronomy education. And one of the things he likes to point out is that astronomy used to be basically part of the core curriculum for science back in the earlier in the 1900s, for example. And then at a certain point, a small group of people, I let you decide what you think their demographic might have been, but it was the one you could probably imagine. They decided that we're going to redefine the things that every student should learn, specifically for science. And they said, we're going to learn biology, chemistry, and physics, in that order, basically. And astronomy got cut out. And ever since, it hasn't really been taught in the schools, in the US at least. I'm mostly talking about the United States.
We are US centric, unfortunately.
Yes,
we grew up here. That's what we know.
But I don't know. I don't know. Let me know in the chat if this is different in other countries. From people I've met, I would say it's not all that different. But yeah, so it really is kind of almost an arbitrary choice as to why astronomy is not taught formally in education more often here in the US, even though it is, I would hazard a guess, the most motivational and inspirational to the general public, to non-astronomers.
Yeah.
So it's a weird, isn't it, a paradox. Jennifer, thank you for uploading your data. We will crunch that, or our bots will crunch that as soon as possible. Yeah, Sydney, I don't know what would happen if you made those radio telescopes reflective. I would think they probably don't focus properly. Their shapes seem all wrong for like an optical telescope. But yeah,
probably melt a hole in whatever you were trying to use to collect the light.
It would be a lot of light.
Yeah.
Yeah, you would need. Yeah, it's almost like those power generation plants where they heat the water in the tower, the center of all the mirrors, and like a
tritium
James Bond villain.
Yeah. Jennifer brought up a good point. It is also one of the easiest sciences to get into. You genuinely don't need anything but a pair of working eyes. That's it. Like you go outside. So as part of the satellite pipeline that I'm putting together, I'm involved a little bit with the IAU CBS, which bonus points if you can guess what that stands for right off the bat, because I know you can't. It's the International Astronomical Union Center for the Protection of Dark and Quiet Skies. Yeah. I don't know where all those extra letters went.
The first three totally check out. Those last three.
But they're a group of astronomers who want to be aware of satellites and make people aware of the effect that satellites have on the sky. And part of that is doing satellite surveys, getting photometry of satellites, estimates of how bright they are. And one of the most active members on there, he just goes out with binoculars and he looks, and that's one of the old ways that you could get brightnesses is just by comparing whatever it is you're looking at to a nearby star, and kind of just figuring out what the brightness of that star is and what the brightness of another star is, and then saying, oh, it's in between those two. It's probably roughly this. It's not super accurate, but it's good enough in a lot of cases to give you a general idea. But yeah, so it is. It's one of those where you really you can jump in with absolutely no equipment or not. Oh, looks like Sydney is heading out. Thank you for stopping in, Sydney. Appreciate all your questions and everything. This has been great.
Absolutely. Have a good day or night wherever you are.
Yeah.
Okay, we're going to move on from triangulum. So open that shutter in your mind. Let your brain expose, and then close that shutter and write that mental image of what this galaxy looks like, because it's going away. So we are going to stop integrating on triangulum. We got a good 28 minutes there. I think it looked pretty good. We're going to move to the Great Orion Nebula. Let's see if it's up high enough. This one is spectacular. 23 degrees east-southeast. I think we'll get it. Let's see.
While you work on that, I'm going to get some water because I have had nothing but coffee for the past few hours and potato chips.
He's actually shrunk in volume by about 30%. Orion is shriveled.
I'm looking a little raised.
He'll puff back up with some water. And yeah, just back on the getting involved with astronomy. Whoa, did somebody just? What just happened here? I think we either our telescope looked at a light, or someone might have driven by with their headlights on. We saw some very bright light on our telescope all of a sudden. I think we're okay. Yeah, getting back on the how to get involved with astronomy. Yeah, there are quite a bunch of citizen science programs right now. NASA supports quite a few. You can just Google NASA Citizen Science. Our exoplanet program for Unistellar is on there now, for example. NASA Exoplanet Watch is another great program. They'll teach you how to observe exoplanets with your telescope, your small telescope and a camera. Really will help you learn and understand what you're doing and what you're learning. A lot of other interesting programs on there. One that comes to mind called Aurorasaurus. They observe auroras in the night sky. There's Orion. Yeah, and a lot of stuff you don't need a telescope for. Like Ryan was saying, you can also just use available public data. For example, sifting through Hubble Space Telescope data or NASA TESS data to look for exoplanets that have been hidden in the data and can be only really well identified by humans who can recognize patterns better than computers still. All right, there's the Orion Nebula. Let's get going on this. It's super bright. I hope it won't be too saturated in the core. We'll see. It's quite large though. So yeah, if you're really interested, and if you're here, I imagine you probably are, and you're not involved yet, I'd say check it out. You know, I know we're all short on time, so no hard feelings if you don't. Yeah, it looks like EU does subsidize projects. Yeah, that's great. Europe does seem to do a better job than the United States in subsidizing science, at least in what I've seen, my limited experience. Let's see, Copernicus Sentinel project. Hadn't heard of that, but yeah, that's interesting. Do swell. Long story short, grew up listening to Art Bell and George Norrie interview all the best ufologists, etc. Contact is a top tier movie. Wow, look at that Orion Nebula already coming through, looking real nice through the eVscope. Yeah, Contact. Quick sound bite about that. It's based on the main character played by Jodie Foster, based on a SETI Institute astronomer, basically one of the co-founders of SETI, Jill Tarter, Dr. Jill Tarter, real astronomer who was instrumental in the beginning of the search for extraterrestrial intelligence, and a lot of other great science as well. She's still part of the SETI Institute, and yeah, Contact, I guess, was based on her. Every time my laptop screensaver comes on, it stops screen sharing, and it drives me nuts. I could just turn it off, but I have failed to do that. There we go. So anyway, Contact is a good one. Star Wars, sure. Star Trek is my personal favorite, but I also enjoy Star Wars. Yeah, access to open source data, definitely important, especially for bringing in new people. I think, you know, a lot of kids these days are so tech savvy, computer savvy, giving them a chance to just play with real data and learn on their own is really handy. But also giving people the tools to do that with economic support and social support is important. Oh shoot, yeah, sorry, I stopped paying attention.
No, it wasn't me.
I have a little clock on when the last one was written out. Not really. Charlotte, North Carolina, East Coast, tuning back in at 6:50 a.m. Thanks, Tony. Glad to have you here.
Yeah.
I was wondering when those people would start rolling in. I hope you're doing something fun so early on a Saturday. I mean, this is fun. I get that. Something else as well. Yeah, we're looking at the Orion Nebula here. This is in the constellation Orion. If you can find Orion's belt, the 3 bright stars in Orion, this nebula is just below the belt. Often you see the constellation Orion drawn as the hunter, or the guy with the sword in a scabbard on their belt, and this is kind of at the tip of that sword usually.
Is that the 3 bright?
No. No, eVscope. There's a small possibility we lost the telescope. Let's see.
The telescope itself got carried away by the squirrels on the mountain.
Could be.
They do like to do that.
All right, I'm going to disconnect and reconnect in a sec. Let me stop screen sharing. I'll just go back to us.
So good news is, even if we're disconnected, the eVscope is just going to continue to do what it was last told to do. So it will continue to collect data on the Orion, unless it got carried away by squirrels, in which case then it's going to do, we don't know.
Or after 10 hours of observations,
It died.
Finally ran out of battery. It's possible. We were pushing the limit on how much it can observe continuously. Yeah, we can just we can remedy that pretty quick.
Yeah.
Yeah. Do you mind just going? It's right down there.
Where's the
chargers are in a wall over here. Yeah, I suspect that one may have finally ran out of battery. It really was a valiant effort. I think we observed, let's see, we started at about 8 p.m. local time. It's now almost 4. So that's almost 8 straight hours.
Yeah. Slewing and observing and also.
Yeah, and that's not just being on, that's actually taking data and showing images. That's not bad. So we'll just check on that. It's also just possible that I lost my Wi-Fi in here. What was I saying? I don't remember. I was talking about Orion, where to find it. So when we do reconnect, yeah, you can actually see the Orion Nebula with the naked eye from most places that aren't absurdly bright. The middle of a big city, the middle of a big city would be tough, but you can see it. It's a smudgy cloud just below the belt there. And Ryan was asking, do you see the belt stars in the image of Orion, the Orion Nebula that we see through the eVscope? And the answer is no. Those belt stars are much farther apart on the sky than the field of view of the telescope. So any stars you see in our eVscope image of the Orion Nebula are not in Orion's belts. Let's see. I'm reading through chat here. Let's see. That's a long. I'm getting through Noel's here. Quantum mechanics looks to the field of the essence of existence. Astronomy is the study of everything beyond Earth's atmosphere. Now James Webb allows us to gaze further back in space-time, further than ever before. Then there's the field of astrobiology and the possibility of extraterrestrial life. Increasingly, our work and leisure are more based in cyberspace, and now AI is coming to the fore. I know you're astronomers and not astrologers, but what's the next step? Yeah, I mean, I think we have a lot to learn still. You know, every new telescope we launch, like James Webb, it gives us access to new parts of the universe, and we just will find more things to study and more questions to ask. So I'm not worried. I don't know that things will change drastically from what we've seen in the past. AI is an interesting new development, I guess. Certainly will help in terms of data analysis and getting through large amounts of data more quickly. But why the artist formerly known as Dad? I don't know whose dad you are. One of ours, I assume. So thank you for joining. I will pass that on to Ryan. Get some sleep. Yeah, what's next? I think the extraterrestrial life is an interesting avenue. Was it a power issue?
Yep.
Okay.
Its dying breath, it said, "I'm going home," and it just stood straight up in the park.
Is it back online?
Yep.
Okay. Is it oriented, or what did we do with it? What did you do?
I just turned it on.
Just turned it on. Okay.
Yeah, it parked itself.
Okay. Yes, it will park when it runs out of battery to protect itself with its dying breath. Yeah, I think we're going to start to see more information about extraterrestrial life, I think. We haven't even broached the subject really amazingly tonight. But
we had 2 or 3 questions early on.
But, you know, we're basically in the field of exoplanets, which is what I work in a lot, as you might be able to tell. We are getting closer and closer to studying potentially habitable exoplanets in detail, in depth, learning what their atmospheres are made of, learning what their surfaces are like, if they're cloudy, if they have ocean versus land coverage. That's actually a thing we can do soon. And learning, what elements are in their atmospheres, are there so-called biomarkers, things like, for example, methane is a gas that life produces on Earth, at least. You can definitely get methane from things other than life. We've detected methane. I've been part of groups that have detected methane on other planets, things that are nothing like Earth. But we're getting closer to where we can detect carbon dioxide in atmospheres and atmospheres. So I think we're going to start getting a pretty long list of potentially habitable planets in the next 5, 10, 20 years. And then it's going to be quite a long time before we have any strong evidence, I think, of actual life in other places outside the solar system. I think inside the solar system, one of the more interesting developments is going to be these robotic missions to moons like Enceladus in Europa, these icy moons where there might be subsurface oceans, which would be really, really interesting places for life. That's kind of some of the stuff I'm most interested in seeing what happens. I would love to see some of these robotic worm-like robots they're sending to these moons. And to drill down below the ice and see what's down there. So kind of cool. What else we got?
Did you answer databases already?
No.
Okay. What databases do we use? I know for Unistellar and eVscopes, we use Amazon Warehouse Services for our databases. Here, though, I don't know what they do.
Well, yeah, I wonder if the question is also about what kind of public astronomy databases do we access?
Oh, yeah, that would
maybe. I'm not sure. But so like I access the NASA Exoplanet Archive that has a lot of information about all known and confirmed and suspected exoplanets. That's probably the one I access the most. There's the Gaia catalog. So the Gaia Space Telescope has cataloged essentially every visible star with a space telescope. It's cataloged its precise position and motion and brightness. Super useful for a lot of stuff. It's more of that's a big database. I don't know how many stars are in Gaia to you, but it's like
too many.
Billions.
Too many.
Millions, I guess. Many millions of stars. I should know the answer, but
I don't remember either. It's a lot.
What were we looking at? Orion.
Yes, right? The Orion Nebula. But yeah, well, for the other part of that, not for astronomical data, but for the eVscopes, we store everything on Amazon Warehouse servers just because that's simpler.
Amazon Web Servers.
Web servers, whatever. They're in warehouses. That's basically the same.
Amazon's watching. We don't want them to get mad.
Jeff Bezos, if you're watching, come.
I thought you were going to do something else on your hand.
No, I'm coming for you. But yeah, that's what we use. Just one of the cloud services. But yeah, in terms of astronomical data, Gaia is the one where it's like every time I want to use their data, I can't actually get it. I keep trying to get it, and they won't let me. And it's annoying because they have a lot of good data that I need.
Sounds like a skill issue.
It is a skill issue. I'm not skilled.
All right, we are back on the great Orion Nebula.
The artist formerly known as Dad has gone to sleep.
I don't know which dad.
Not mine.
Okay, so yeah, that's probably mine, I guess.
Somebody's dad.
Somebody's dad.
Good night. Why? If you're still here, which you probably aren't.
If it was him, he stayed up until 7 a.m. his local time, so that would be. No, what are the risks of accidentally seeding planets, moons, and other space? Yeah, so so when we send probes to other bodies in the solar system, they could be contaminated with Earth bacteria, Earth life, and bring it to those planets. And this is actually a concern. I'm trying to think of what. There is a name, a very fun, cool name for this. It's not planetary defense.
Say again what it is.
Basically, making sure that we don't bring microbes to other planets and bring microbes from other planets back to Earth. There's a very fun name for it.
Anti-cross pollination.
No. What is the name of it? I guess maybe it's just, it might just be planetary protection. That might be the name of it. But yeah.
Sounds similar to planetary defense.
Yeah.
I can see that being.
Yeah, it might be planetary protection. But yeah, there are definitely people at NASA and ESA and these other space agencies that put a lot of thought and effort into this. They do things like baking space hardware in ultraviolet rays and things.
NASA, if you're watching, I'll do it for half the price. I'll just spray Lysol on everything. Just nope, done. We're good.
Yeah, lots of thought. I don't know much about it really, but it's a thing.
Yeah, it turns out like a lot of things will kill the 99.9% of germs. That 0.1% is hardy.
Yeah.
And it becomes very tough to make sure you have gotten all of that gone. Yeah, I could definitely see that being an entire science on its own.
Yeah, I mean, like they know that tardigrades, these little water bear micro creatures, will survive in the vacuum of space.
Yeah, they'll just hibernate.
Yeah, which is pretty crazy. Like we can't, so they could totally hitch a ride. But then again, maybe that's where life on Earth came from. So,
yeah, absorbing underwear. Yeah, the biggest problem, immune system. That is definitely an issue. I think it also. I mean, probably we're fine here, but it is something to think about as well. I've seen people talk about the idea of how we kind of think about space from like a colonizing perspective. We'd have to be very careful as well if there was something on another planet that we wouldn't. I do not think we would want to risk them either. So it would be very. That would be a challenge that I guess we'd have to cross when we got to it. That would be hard to do. It would be hard to deal with.
Yeah, this nebula is pretty fantastic. All this just the stuff down here. Get this out of here.
One's X factor in the immune system.
These features in this nebula here, these sharp, crisp edges. This thing is huge. It's many solar systems across. Just the physics of what's happening here to separate this gas and this dust is pretty cool. And this is all stars in here. That's why it's so bright.
Yep.
There's a group of stars in here called the trapezium. 4 stars that make a trapezoidal shape, but they're so bright that the way we're looking at it right now, they're all saturated. I think this here is a tiny little nebula. It has its own name. I think this is Demaren's Nebula. Probably pronouncing that wrong.
Yeah, 100%.
Thanks for the support.
You're welcome.
Yeah, pretty good view of Orion tonight. All right, where are we? What time is it? Where are we?
It's 4:07 our time. It is.
I haven't spun the wheel of targets. So Orion was the last one in our list, so I'm gonna try to develop the wheel of targets. Let's see.
Had conversations through private message with Natalie Cabral, who is a high up at SETI, very important scientist, planetary scientist. Met John Dobson. He used to save portholes from scuttled ships, grind them, and make telescopes, and created street astronomy clubs. That's really cool. I've never thought about that before. That's a really neat idea of grinding up old ship windows essentially and being able to use them as lenses. Neat.
Let me see if I can do it here.
The issue is coming up in a few weeks in Utah. Asteroid material recovery. Yeah, so that is something that we have to be careful of. The OSIRIS-REx mission is coming in for a little flyby. It ended up, was it Hayabusa or was it Ryu? What was the asteroid it grabbed from? I forget the name.
Hayabusa?
I don't remember.
That was yeah.
I'll have to look that up because that is very bad of me not to remember.
OSIRIS-REx was the sample return, right?
Yes. So it is dropping off. It sampled an asteroid, and it's a
Bennu.
Bennu. Oh, duh. Yeah, it's Bennu. So it's dropping that sample return capsule off before flying off for a second part of its mission. It's like going off towards Jupiter. But yeah, that is, so it's in the sample return capsule. NASA is going to grab that as soon as it drops down. I've already tried. They won't let me near the site. But it's going to be in this like little vacuum sealed capsule that is going to be completely cut off from the Earth's atmosphere and from us. And that's part of it is when they actually open the stuff up to examine it, they're going to have to get it in a clean room. And that clean room is going to have to keep humans out of it as well. So they'll have to be examining it from behind a screen to get some information about the asteroid material.
Yeah, and so we should note that having the sample land fully sealed is the ideal scenario. We have there has been sample returns in the past. I forget the name of which one, but it landed hard, crash landed effectively when it was supposed to land softly and opened, at least potentially opened. They weren't sure if it was exposed to the Earth's atmosphere or not. So fingers crossed that it lands successfully.
All right. Thanks, Tony. Appreciate you stopping in and letting us know about that. That's actually really, really cool. That's a little fun fact that I had never heard before. So very neat. Yeah, that is a downside, absorbing underwear. We can't smell. We don't get to smell what the asteroids smell like. Maybe one day.
They smell like gunpowder. Wasn't that a?
I don't know. I've never.
Nickel.
Oh, jeez.
The moon smells like gunpowder, I believe.
Skill issue.
Yeah, because they brought back moon samples, of course. And it's something about what the dust is made out of. Though I haven't smelled it myself, I don't think. I don't know if that's true or not. I have actually touched part of the moon.
I don't know if it's true whether. Interesting. All right.
I think that's true.
All right. I'm over here writing down the log because I realize I have not been keeping track and I should be doing that.
I'm not helping at all in that respect.
I know.
I'm busy making the wheel of targets. All right. One more. All of them. Yeah. Here we go.
Any thoughts on the Chandra lander from India? Anything interesting? I actually don't know much about that mission. I know that it happened. Chandra lander. Chandrayaan 3. Yeah, launched on July. So when is that? Does that already come down? Am I an extra bad astronomer? Oh, it comes down on the 22nd.
Is this the second lander?
No. No, on the 3rd, it hopped and repositioned itself from the landing site. Yeah, so I remember seeing that, and hearing about it and being really excited. But I haven't really been following the mission that much. I was kind of figuring I would, once results started coming in, I would tune in a little more. But the fact that it landed and it's going to wake back up soon is exciting. I'm excited to see where it goes. Didn't Buzz Aldrin or Neil Armstrong have a moon rock on the attic that had to be returned to NASA a few years ago? They've been smelling it for decades. Yeah, I mean that's one of those things where I guess if you're part of the first crew to touch down, you get away with stealing moon rocks and smelling them. But a dry land life detector. Ooh. Yeah, Rich says, one astronaut says gunpowder, but if you can imagine what a capsule smells like after a few days, you wonder.
All right. Here is our wheel of targets. So let's spin and see what we end up with as our next target. So exciting. Services. The Pleiades cluster / Subaru, which is the Japanese name for the Pleiades cluster. All right, we can do that one. Got some interesting things. I'm going to spend a few more minutes on the Orion Nebula, and then we'll head over to the Pleiades / Subaru.
Oh yeah.
I have not been paying attention to your conversation, so
I know.
We've got it covered. I'll be back.
All right.
Research break.
I'm still writing down in this log. Crap, I was supposed to look at the time and I forgot. We'll say that we started this newest observation around 200 seconds ago, which would be roughly 3 minutes ago, so 11:12. So yeah, astronomy logs in general are, you fudge them. I mean, you don't fudge them, but the time itself, like Tom was saying earlier, all this information's in the header of the images. It's just meant to give us an idea. So I'm not doing a great job of actually keeping track of when we took specific images. So let's see. Yeah, I think not leaving your samples to just kind of hang out for a few decades, probably not the best scientific strategy. That's at that point, I think your sample is adjusted to Earth. It's probably just an Earth sample. All right, so let's take a look at our asteroid real quick, because I've just been kind of going on autopilot for this. Want to make sure we're still getting enough counts. Oops. Yeah, so I am excited. Haven't seen any big change in how the asteroid looks, which I wouldn't really expect from just a general observation like we're doing. I doubt that the rotation of the asteroid is actually going to cause a big enough dip in the light we receive that we'd be able to notice it just right away. But it is nice that we've gotten probably around 5 hours of this asteroid, and a good chunk of the asteroids that we've worked on in the past have rotation rates that are around 2 to 4 hours. So fingers crossed, this will be enough. but we'll see. And then if it isn't, we have all of the data that our citizen scientists with their eVscopes are taking. And ideally, with all of that done, we'll be able to pull something out. Let's see. Wonder if. We're good.
Okay. As much as Orion is looking just prime, A+++, nebula image here. I think we're gonna move on. Look at something different.
Don't say it.
Explore more of the universe.
Don't say it.
It's that time again, Chad.
I hate you.
Let the photons through your eyes to your memory centers. Feed the neurons. They're hungry.
It's getting worse every time.
Soak it into the gray matter. And remember what this nebula looks like. Because we're moving on. Ryan, is it time we introduced ourselves again? Has it been long enough?
I think it has been far more than 15 minutes.
Okay. I'm Ryan.
That's not true.
No. I'm Tom. He's Ryan.
I am Ryan.
We are astronomers doing astronomy. It's
11 hours and 18 minutes into our observation.
Yeah.
So we're a little loopy at the moment.
A little bit.
Thank you for tuning in and sticking with us.
Yeah, so we are astronomers. I'm at the SETI Institute, Unistellar, and University of California, Berkeley. Ryan is at the SETI Institute with me. We are here at Lick Observatory on Mount Hamilton, California, east of San Jose, California. We are operating the nickel 1-meter telescope. That's the image here in the background, looking at this asteroid, 2011 MD5, a near-Earth asteroid that we're our main science case. We're trying to measure the change in brightness over several hours, and then from that get its rotation period. See how this asteroid is rotating or tumbling in space. And while we're doing that, we have an Unistellar eVscope, a 4.5-inch consumer telescope that is also looking at that asteroid simultaneously from just next door, and then another eVscope that is looking at fun, pretty things like the Orion Nebula that we just finished. So we're now going to look at what the Wheel O Targets instructed us to look at, which is the Pleiades cluster. We're going to hope that it's in the right place. I think I picked targets that we would be able to see at this time of night.
I was about to ask.
I didn't just pick them willy-nilly. There was a method to the madness. Indeed, we're good to go.
Amazing.
So we'll repoint our eVscope. And yeah, we're at, like Ryan said, this is hour 11 of the live stream. It started at 5 p.m. local time. It is now 4:20 a.m. local time. Is this the witching hour? We passed the witching hour. That's midnight.
I don't know. I do know that between 2 and 4 in the morning is when most people die.
Well, we're safe. We made it.
Yeah, we're fine.
We made it. We're good.
I mean, I think, yeah.
Until tomorrow night.
Yeah, and then it swings back around again.
Yeah.
Bruno's back.
Yeah, I can put the web link for the Wheel of Targets. Sure. I'll write it in chat. If I can find the right mouse. We have so many computers here. I'm not in chat there. Let's see if I can do this.
Issue. See, I'm trying to get cool.
Join chat? No, let's not do that. I'll do it here.
Send me the link.
Okay, we'll do that. I will send you the link. How do I do that?
Over Slack or something. Email it.
I'll Slack it.
Oh no.
We have all of this technology at our disposal, and it's shockingly hard for me to send a message 2 feet from my computer to Ryan's computer without putting it on stream and all kinds of things. Okay, we are at the Pleiades. I'll start imaging. I think we're at the Pleiades.
Right now.
Yeah. So the Pleiades looks a little weird through the eVscope because it's such a big group of stars. I don't even know if we get them all. The Pleiades, also known as the Seven Sisters, is 6 or 7 bright stars in a really recognizable pattern. It's something called an asterism. It's not a constellation. A constellation has to be on the official list of, say, 88.
Yeah, it's 88.
Official International Astronomical Union recognized constellations. And the Pleiades is kind of too small and didn't make the cut. Pleiades is the Greek name, recognized in ancient times. Subaru, which I may not be pronouncing correctly, is the Japanese name. Also, if you own a Subaru car or have seen the hood ornament of one, the logo, it is the
Pleiades.
Bright stars of the Pleiades cluster. So it's a stellar cluster. It's an open cluster, not like the globular cluster we looked at way at the beginning of the night. This is a group of stars that were born together out of the same cloud of hydrogen gas, but have drifted apart since then. And so we can look up exactly how old this thing is, maybe. But these clusters tend to be younger than those globular clusters. Anywhere from, let's see, it's only 440 light years from Earth, which is right next door in astronomical terms. It's about 4 times the diameter of the full moon, if you were to look at the whole thing. So that's why we can only look at about 1/4 of it with our eVscope at a time, at least.
Oh, Paul says that YouTube will only save 12 hours of the stream.
Yep, that is correct. Yes, we knew that.
Oh, I didn't know that.
So yeah, we would have to end the stream and start a new one. I don't know yet what I want to do about that. Sorry, Paul, if you have experience with it, if we were to end the YouTube stream only and restart it, would that like boot everyone out of the stream and they'd have to reconnect? If you know, let us know in the chat.
We never answered Noel's question either.
What was Noel's question about the polar?
Polar radio telescopes.
Do you know anything about that?
No, not particularly.
I suspect one of the reasons to put a telescope in Antarctica is when it's dark time, you can, radio can be dark, so you can observe day or night. You just can see the same sky continuously, so the stars never rise or set, or they don't rise or set as much as they do elsewhere.
I imagine you have very little radio interference as well down in Antarctica.
Yeah,
so.
Indeed. Definitely radio quiet. If you were at the true South Pole of the Earth, the stars would never rise or set. They would just spin in circles, big or small, in the sky. So I think that's part of it. It's for other telescopes, optical telescopes, it's actually quite dry in Antarctica, so you don't have a lot of absorption in the atmosphere by water vapor. It's kind of counterintuitive. But I don't know. I think that does have some effect on radio. You do want dry sites, depending on which radio wavelengths you're looking at. That's why, for example, there's big millimeter wave dishes in the high desert in Chile, the Atacama Desert, like the Atacama Large Millimeter Array. They do want dry air because water vapor absorbs or re-emits light at some long wavelengths. Anyway, that's about all I know, unfortunately, on the polar radio telescopes.
Yeah, I don't know much more. I'm basically just able to guess at what the benefits would be. China seems like 2 set up. Yeah, I think it's just the inconvenience of having to build and maintain some infrastructure in Antarctica. It's probably enough or not enough to deter based on the benefits of having a target up the entire time and not having to deal with random radio interference from, I don't know, having to either quarantine your area so that there is no radio interference, which can be very tricky to do, or worry about dealing with radio interference.
I sent you the Wheel of Targets link.
I saw that.
In chat. We got the Wheel of Targets link coming, folks. Okay, people would have to join the stream.
Yeah.
We can see how many people were actually in the YouTube stream before we do this. Yeah, I considered doing kind of a pseudo sign off at the 12-hour mark, and then just keeping going unrecorded for the last hour and a half. Maybe we'll do that, and then also reboot the YouTube stream so we get the recording.
Yeah.
I don't know.
Okay, so we have currently I think 8 or 9 people on the YouTube stream. So
okay.
It's not like, I mean, if people that are listening passively may have to move windows and come back, but otherwise it's not like we are trying to migrate 100 people over to a new one.
Yeah, it's a good thing we scared everyone away.
Yeah.
SETI Institute special on I'll get a notification for the new stream. Okay, that's handy to know. Thank you, Paul. Very helpful.
I would feel bad about that.
Satellite in space easier than Antarctica? Could be. Hard to do radio in space. You need multiple antennas. Putting a radio telescope on the moon, on the other hand, definitely could be useful. And it's been discussed for a long time now, especially on the far side of the moon where you don't have any interference from Earth, really. Obviously, logistical issues, but I think we're getting close to something like that.
Well, that very loud cowbell noise that goes off never.
It's terrifying.
Yeah. How long? When does this set again? I want to make sure we don't run the telescope in the ground.
It'll stop itself.
Yeah, I know.
Just keep going.
All right.
It's up until twilight. So
okay, cool.
We have until, believe it or not, we did some preparation for this. I know it doesn't seem like a chat, but we sort of prepared.
Does that say Fight Club, and we take bets?
Yeah.
Did you write that, or did I write
You
that?
absolutely wrote that.
Oh, okay. That makes sense. I don't remember doing that.
Yeah. I wrote down, Ryan and Tom will also need to have some fun talking points planned in advance to fill airtime. And Ryan wrote, in bold capital letters, Fight Club, and we take bets. This wasn't recently. This was weeks ago.
I love Pass Ryan. He's such a goober. Yes.
So this asteroid.
Yeah, no problem, Noel.
This asteroid will be at 26 degrees altitude at 5:45 a.m. So we have an hour at least. With a nickel.
3D Prima, have you been doing any GeoBio field work? I have not. That is, I think in general, both of us are pretty narrowly in astronomy, observational astronomy. So getting out and doing field work, I think the closest I have done to field work is being given a week's notice that I'm being flown to Oman to try and catch an occultation. That was harrowing. Oman was great. Being given it a week's notice was harrowing. Frank, if Frank's still on the stream, I want him to know. But yeah, so not really, not particularly our field of expertise, but it is interesting. So if you have any experience with it, let us know in chat. I'd be happy to hear, read about what your thoughts are. Hello, Rebecca from Houston. Let's see, what are these bright stars? So these are the Pleiades. This is an open cluster of stars, and it's a reflection nebula too, right?
Yeah. There is some nebulosity, but I don't see much of it here. I think most of the looks like nebula is just kind of overflow from the stars. Yeah. They're wicked bright.
Yep. So the Pleiades are a cluster of stars that are kind of bound together gravitationally. And if you live in the northern hemisphere, they are stars that you can see with the naked eye. You could actually look up. They almost look like a very tiny version of the Big Dipper. And you can tell that they're the Pleiades because if you don't look directly at them, they'll look a little bit blurry because there is essentially a lot of gas and dust around them that is reflecting blue light. And so it kind of looks like a little cloud. Yeah.
Indeed. Mm-hmm. Yeah. Soak them in for a bit because I'm about to spin the wheel of targets again and see where we go next. But before we do that, open up those mental floodgates. Let yourself roll around in the tide of the Pleiades and write down this mental image of what they look like because they're about to go away. So say goodbye to Subaru. Because I do love stars, but stars are stars. And we'll go see what else we can see.
Yeah,
so,
what do we got now?
Wheel of targets, round and round it goes. Where it'll stop, nobody knows.
It's going to be Pleiades again.
I should remove the Pleiades. Ooh, the Horsehead Nebula.
That's a good one.
That is a good one. Challenging.
Yeah, that one's actually very tough.
It is very tough. We're going to give it a shot. The Horsehead is part of the Flame Nebula complex.
So Lawson has asked where the moon is. Also asked if
it's over there.
If we want to kill them, which we want to go on record saying no. We love you, chat.
Yeah, we don't.
We really deeply appreciate everyone here. Hi, it's now time to reintroduce ourselves. I'm Ryan Lambert. This is Tom Esposito. We're professional astronomers, and our 11 and a half of our observation on the Nickel telescope, which is a 1 meter class telescope on the Lick Observatory in Mount Hamilton, California. This is just a fun hangout for us, essentially. We figured this would be a good chance to show people what it's like to be a professional astronomer, take observations. So if you have any questions, let us know. And if you just want to hang out, that is awesome. We like just vamping and talking with everybody. So thank you and welcome to those who have joined us. So yeah, sorry, what were you saying about the moon? I wasn't listening to what you were saying, Tom. I'm sorry.
Oh no, the moon's over there. It's rising in the east.
Yeah, I don't think it's high enough yet. Or maybe it is.
Actually, look out the window and see. Oh yeah, it's up there.
Oh,
it's in a crescent phase. I think it's a waning crescent, but I could be wrong. First, yeah, it's definitely pretty high in the east. I wasn't gonna. I can put it on the wheel of targets. I wasn't planning to look at the moon because we can all see the moon just about all the time. But if we run out of things to look at, we could take a peek.
And yeah, so Will has chimed in about the YouTube saying that he is willing to refresh or do whatever. Show me the moon right now. I will call Trump. Okay. I would actually call that bluff. I think that would be a very interesting bluff.
Yeah.
C Nakamura. That's the comet, right?
Maybe Nishimura.
Nishimura.
Yeah, which is the hot new comet right now.
Mm-hmm.
Unfortunately, we will not. It rises above our pointing limits right before sunrise, and so we absolutely cannot look at it. I wish we could. It's a very pretty comet. But like we were saying earlier, you absolutely do not point professional telescopes or telescopes of any kind towards the east anywhere near sunrise, because you do not want the sun getting anywhere near your telescope.
It's a very good way to fry your electronics very quickly.
Yes, and quickly become unemployed as a result. I can always see Jupiter when I run. Can you see it? Yeah, Jupiter's up. I probably could have looked at that earlier. I tried to look at Saturn, and it was behind a building, and I could have looked at Jupiter, and I probably should have, but my bad. Serenity Base on the moon. We'll see. We'll see. All right. Let's see. Horsehead. Oh, I see a horsehead.
Oh,
It's coming. I won't see it from here, but it'll take a few minutes.
yeah. This so this one is pretty dark. It's going to take a little bit for it to show up.
I'm not going to help it along here.
And in the meantime, we should probably decide. We got 2 minutes and 30 seconds before YouTube.
It's 12 hours, right?
Oh yeah, never mind. We got sorry, I meant to say we got 22 minutes and 30 seconds to decide.
I think we will end the YouTube stream and then restart it because we'll do that in about 20 minutes because it will indeed stop recording and archiving our stream, and then we'll just restart. So you can either hop over to Facebook or Twitch if you don't want to be interrupted, or just wait, I would guess, 30 seconds or a minute for the new YouTube link to pop up and reconnect.
So one question from 3D Prima, where would you look at Nishimura with other robotic observatories? So anything in the southern hemisphere, I think, would be good. A large part of the problem right now is that we are very far north as well. But it's also just near the sun, so it's very tough to do.
Yeah, when it's that close to the sun, I don't think there's much you can do. You wait for the comet to move, which it will. But yeah, if it's near the sun, it's near the sun for everybody. Doesn't matter what time zone you're in.
Yeah, best you can do is have something that tries to block out the sun, but that's iffy. And I personally, I wouldn't risk it with I don't think any large telescope would risk that.
Yeah. We're starting to get the horse head here, so you can see there's all this red nebulosity here. And then there's this dark shadow. It's in the shape of a horse head. It's going to come out more. You see the nose and the ears and the head and the neck. That's going to get better and better, so we'll keep an eye on it. Maybe I'll jack up the brightness a little bit more. Oh, yeah. Oh, there it is. There it is. Let's see. Where can we observe from the lunar south pole and the Chandrayaan lunar observations? What can they help us with? Yeah, I mean, there is a lot you can observe from the moon. And the South Pole, we've actually looked into this, and I'm afraid I don't remember the details. But there are plenty of interesting science targets that you can observe from the South Pole of the moon. I know part of the reason they landed there is it hasn't really been explored before by humans. And so it's an interesting place to look for, I think, water ice and other potentially useful materials for if you were to build a long-term base on the moon or use it as a stopping point for missions farther out in the solar system. But I know you can do things like asteroid observations from the moon. You can definitely do exoplanet transit observations. things like that. Basically, anything you can observe from Earth, you can observe from the Moon, I think. And the lunar south pole would just give you a particular vantage point. Can you find the Exoplanet Studies T-shirt? As far as I knew, you used to only be able to get it from SETI headquarters. You might be able to find SETI merch online. I can try to look it up, and if I find a link, I'll put it online or on chat. Let's see, there are some additional questions that I missed here. They're coming fast and furious now.
Yeah, so 3D Prima asked about space-based, if that was a way of getting around the fact that the comet is very close to the sun. And no, so it would be very tough. The problem is, even if a telescope is space-based, it's unlikely that it's going to be far enough away from the Earth to really have a different vantage point. You probably need to be like in between the sun and the comet to really make that work. So unlikely to do that. There are space-based telescopes that can block out the sun that are designed to do that. So there could be some observations there. But I don't know how faint those telescopes can go. So I'm not sure. They'd probably be able to see it, I guess, I would think. But I'm not positive.
Yeah, I'm not sure. I think, yeah, I mean, there are telescopes that, for example, are in the same orbit as the Earth, but they trail Earth in its orbit. So they are, say, like 1/4 of Earth's orbit behind. And so they might have a different angle where they can look away from the sun and see the comet still.
Cool.
But you know that still won't be for long, because the comet's moving at this point in its orbit. It's probably moving pretty fast, because it moves fastest. Usually it's probably on some long elliptical orbit, which means it's moving fastest as it's close to the sun.
Yep.
And so it's going to be moving into a different part of the sky pretty quick. Sarah D'Amato, how do you tell apart the Horsehead Nebula from the Flame Nebula? Any tips for viewing the nebula for amateur astronomers? I tell it apart because the eVscope, the Unistellar app, lists it separately.
Mm-hmm.
It is part of the Flame Nebula. That is true. I think it's, I have to look this up again. I think it's in the southwest part of the...
I just looked.
Okay.
So yeah, Flame Nebula up there, Horsehead Nebula right there.
Yeah. I would say I would look for, depends what kind of telescope you're using and how big your field of view is, but I would look for, I would Google basically an image of the wider nebula and look for star patterns like these bright stars here, for example, 4 or 5 bright stars, and try to match that pattern of stars to what you see with your telescope, and then from there kind of triangulate where the Horsehead is in relationship to those. That's kind of the general, I think, approach, is you find something that you can recognize, and then you
start building from there.
Yeah, you either star hop or kind of estimate from there. That would be my best suggestion. How do we perceive depth in deep space observations?
It's the neat part. You don't.
Yeah.
For the most part.
Yeah.
So distances have been historically a very, very tricky question for astronomy. I actually really love that question, because it's like saying it's something that we in our everyday lives don't have to really deal with. As long as you don't have a problem with depth perception, you generally have a good idea of how far away something is. But it's like standing when you're looking out in space, it's like standing completely in the dark and seeing a little bright light far away. You have no idea if that is a candle that is, maybe a few feet away, or if that is a floodlight that is miles away. It is very tough to tell. So yeah, astronomy, we've developed some very cool relationships. One of which is we found a certain star that pulses and the speed at which it pulses directly correlates with how bright that star is. Or no, the speed at which it pulses directly correlates with the star's mass, which we use to understand how bright it is, which we can then turn into a distance. There are a lot of little tricks like that. Type 1a supernovae, so a white dwarf that has collected enough material to explode. Because a white dwarf always explodes at the same mass limit, theoretically, those types of supernovas were always going to be the same brightness, and you can get distances that way. So you have to, in deep space images, really work hard to get an understanding of how far away things actually are. That is a very, very tough question in astronomy. Even today, that is something that can be debated. No, when I was a kid, I could see the Pleiades with the naked eye. Now, with the amount of light pollution in the city, there's no chance. Yeah, I mean, that is unfortunate. I've noticed that too, living in San Francisco. It's much harder now for me to see the Pleiades than when I lived in a relatively small town, Indiana, or in North Carolina. So yeah, your mileage will vary depending on where you are. It is unfortunate. But it makes coming out to these dark sites even more impressive when you actually get to see the night sky in its full grandeur. But yeah, there's country of Victoria where all street lights have to point down to prevent light pollution. Yeah, that's excellent. I think that's one of the easiest ways that we could cut down on light pollution is just there's so much stray light from not really thinking our designs through. Managing where all of the extra light is going for street lights and things like that would go a long way. All right. Wow, man, I'm way behind on comments. Sorry, I am long-winded.
There were a lot of them.
So, what do Lagrangian points offer observatory possibilities? So, the nice thing about Lagrangian points is that they are not stable, but they are relatively stable. So you can send a telescope out to one of those points, and it becomes reasonably fuel efficient to try and keep it there. You can focus all of your fuel on moving the telescope and pointing it to your different targets. Problem with something like Hubble, when Hubble was up and operational,
Still is.
oh, it's still operational? I always think Hubble's gone.
Hubble Space Telescope?
Yeah, I always think it's gone.
Absolutely still working.
I don't know, man. Look, some of us don't get Hubble time, all right? So it's dead to me. Is that it's in low Earth orbit or relatively low Earth orbit. You're constantly going to have to be using up fuel to boost it back up into a higher orbit. So Lagrangian points kind of get you away from that. You also have less debris to dodge in terms of space-based telescopes. After that, I think it's just you also get a stable point, a reference point. If you are sending something to like Jupiter, you're constantly having to recalculate where the targets that you want to look at are going to be in the sky. Because if you think about it, RA and DEC, what we use to describe where stars are in the sky, are very dependent on where Earth is. And if you get a significant distance away from Earth, you start having, it's not a huge effect, but you start having to take that into account.
Yeah, it's actually also, so sorry if you already said this, but the Earth is bright, so you can't point space telescopes towards the Earth because it's shiny and warm in the infrared. So if you put the telescope at the L2 Lagrangian point, the Earth and the Sun are in the same direction. So you have a smaller, just a single part of the sky that you can't point at. And also you want to shield the telescope from light to keep it cold. And so again, you can point your heat shield in one direction, and it'll block light from the Earth and the Sun. more efficient.
So Lars, you asked a question, but I've lost the context on it. Would you be able to detect amino acids that far away? Can you re-up that? Let me know what the context on that question was, because I lost the thread on when you asked that. How can we use different observations to cross-validate deep space observations and astrodynamics of celestial objects and space situational awareness? How can we use different observations to cross-validate deep space observations? So on that, I assume the first part of this question is having to do with the distances again. A lot of that is you have to find different distance methods and see if using multiple methods to calculate a distance match up. They won't ever really match up exactly, but ideally they get pretty close to each other. And that's been done on lots of different targets, which is a good sanity check that our distance methods at least work as well. But there's always room for improvement on that front. Celestial objects and space situational awareness. So use different observations to cross-validate astrodynamics of celestial objects and space situational awareness. I'm having trouble understanding this last part, which is probably on me. We have been doing this for about 12 hours, so I apologize. I think my brain is starting to turn into mush.
Yeah, no, mine too.
Okay.
Small words, chat. Small words, please.
Oh no, you're an aerospace engineer. That makes sense. Okay, so yes, we are kind of stupid at the moment. I apologize.
Let's see. Wait, hold still.
No.
Scroll down.
Is it possible to compensate with other satellite data from the sun, like SOHO, for filtering other research data and make it more accurate? Satellite data from the sun. Is this probably about the comet, or just in general? Something like SOHO.
9 minutes ago feels like a million years ago.
Yeah.
Yeah, I'm not sure. SOHO kind of is limited to looking at the sun, so you probably can do some. Might be able to combine some information, but yeah.
Lawson says they can't hear us. So we've had this problem before. Let me
try reloading the stream if you haven't yet. Just reload your web page. If no one else can hear us,
let us know.
I guess, yeah. If someone in chat can hear us, please just say in chat that you can hear us. Otherwise, we'll adjust something on our side. We are going to refresh the YouTube. Okay, Rajas can hear us. All right, so yes, other people can hear us. Lawson, I would recommend you, thank you, chat, we got it. I recommend you just refresh your stream. In a couple of minutes here, we're going to end the YouTube stream and restart it. So you will get booted, and then just have to rejoin quickly. And that's just so we can keep the recording going on the YouTube archive, which stops at 12 hours.
Okay. So yeah, Lars said, will we be able to detect amino acids that far away in like the Horsehead Nebula or the Pleiades stars?